ForAllX Calgary. P.D. Magnus et al. Audio by Paper2Audio. ForAllX Calgary, An Introduction to Formal Logic. By P.D. Magnus, Tim Button, with additions by J. Robert Lofties, Robert Truman, remixed and revised by Aaron Thomas Bolduc, Richard Zach, Fall 2020. This book is based on ForAllX. Cambridge, by Tim Button, University College London. Used under a CC by 4 license, which is based in turn on ForAllX, by P.D. Magnus, University at Albany, State University of New York. Used under a CC by 4 license, and was remixed, revised, and expanded by Aaron Thomas Bolduc and Richard Zach, University of Calgary. It includes additional material from ForAllX by P.D. Magnus and Meta Theory by Tim Button, used under a CC by 4 license from ForAllX. Lorain County Remix by Cathal Woods and J. Robert Lofties, and from a Modal Logic Primer by Robert Truman, used with permission. This work is licensed under a Creative Commons Attribution 4 license. You are free to copy and redistribute the material in any medium or format, and remix, transform, and build upon the material for any purpose, even commercially, under the following terms. Play button. You must give appropriate credit, provide a link to the license, and indicate if changes were made. You may do so in any reasonable manner, but not in any way that suggests the licensor endorses you or your use. Play button. You may not apply legal terms or technological measures that legally restrict others from doing anything the license permits. The IATEX source for this book is available on GitHub and at ForAllX, OpenLogic Project. Org. This version is revision DC1 EOG 2021-0421. The preparation of this textbook was made possible by a grant from the Taylor Institute for Teaching and Learning. University of Calgary. Contents. Preface. Preface. As the title indicates, this is a textbook on formal logic. Formal logic concerns the study of a certain kind of language which, like any language, can serve to express states of affairs. It is a formal language, that is, its expressions, such as sentences, are defined formally. This makes it a very useful language for being very precise about the states of affairs its sentences describe. In particular, in formal logic, it is impossible to be ambiguous. The study of these languages centers on the relationship of entailment between sentences, that is, which sentences follow from which other sentences. Entailment is central because by understanding it better we can tell when some states of affairs must obtain provided some other states of affairs obtain. But entailment is not the only important notion. We will also consider the relationship of being satisfiable, that is, of not being mutually contradictory. These notions can be defined semantically, using precise definitions of entailment based on interpretations of the language, or proof theoretically, using formal systems of deduction. Formal logic is, of course, a central subdiscipline of philosophy, where the logical relationship of assumptions to conclusions reached from them is important. Philosophers investigate the consequences of definitions and assumptions, and evaluate these definitions and assumptions on the basis of their consequences. It is also important in mathematics and computer science. In mathematics, formal languages are used to describe not everyday states of affairs, but mathematical states of affairs. Mathematicians are also interested in the consequences of definitions and assumptions, and for them it is equally important to establish these consequences, which they call theorems, using completely precise and rigorous methods. Formal logic provides such methods. In computer science, formal logic is applied to describe the state and behaviors of computational systems. For example, circuits, programs, databases, etc. Methods of formal logic can likewise be used to establish consequences of such descriptions, such as whether a circuit is error-free, whether a program does what it's intended to do, whether a database is consistent, or if something is true of the data in it. The book is divided into 9 parts. Part 1 introduces the topic and notions of logic in an informal way without introducing a formal language yet. Parts 2, IV concern truth-functional languages. In it, sentences are formed from basic sentences using a number of connectives, or and, not, if, then, which just combine sentences into more complicated ones. We discuss logical notions such as entailment in 2 ways, semantically using the method of truth tables in Part 3 and proof theoretically using a system of formal derivations in Part 4. Parts 5, VII deal with a more complicated language, that of first-order logic. It includes, in addition to the connectives of truth-functional logic, also names, predicates, identity, and the so-called quantifiers. These additional elements of the language make it much more expressive than the truth-functional language, and we'll spend a fair amount of time investigating just how much one can express in it. Again, logical notions for the language of first-order logic are defined semantically, using interpretations and proof theoretically, using a more complex version of the formal derivation system introduced in Part 4. Part 8 discusses the extension of TFL by non-truth functional operators for possibility and necessity, modal logic. Part 9 covers two advanced topics, that of conjunctive and disjunctive normal forms and the functional completeness of the truth functional connectives and the soundness of natural deduction for TFL. In the appendices, you'll find a discussion of alternative notations for the languages we discuss in this text, of alternative derivation systems, and a quick reference listing most of the important rules and definitions. The central terms are listed in a glossary at the very end. This book is based on a text originally written by P.D. Magnus and the version revised and expanded by Tim Button. It also includes some material, mainly exercises, by J. Robert Lofties. The material in Part 8 is based on notes by Robert Truman, and the material in Part 9 on 2 chapters from Tim Button's Open Text Metatheory ***. Aaron Thomas Bolduc and Richard Zach have combined elements of these texts into the present version, changed some of the terminology and examples, rewritten some sections, and added material of their own. The resulting text is licensed under a Creative Commons Attribution 4 license. Part 1. Key Notions of Logic. Chapter 1. Arguments. Logic is the business of evaluating arguments, sorting the good from the bad. In everyday language, we sometimes use the word argument to talk about belligerent shouting matches. If you and a friend have an argument in this sense, things are not going well between the two of you. Logic is not concerned with such teeth gnashing and hair pulling. They are not arguments in our sense, they are just disagreements. An argument, as we will understand it, is something more like this. Either the butler or the gardener did it. The butler didn't do it, the gardener did it. We here have a series of sentences. The 3 dots on the third line of the argument are red therefore. They indicate that the final sentence expresses the conclusion of the argument. The 2 sentences before that are the premises of the argument. If you believe the premises and you think the conclusion follows from the premises that the argument, as we will say, is valid, then this perhaps provides you with a reason to believe the conclusion. This is the sort of thing that logicians are interested in. We will say that an argument is any collection of premises together with a conclusion. This part discusses some basic logical notions that apply to arguments in a natural language like English. It is important to begin with a clear understanding of what arguments are and of what it means for an argument to be valid. Later, we will translate arguments from English into formal language. We want formal validity, as defined in the formal language, to have at least some of the important features of natural language validity. In the example just given, we used individual sentences to express both of the argument's premises, and we used a third sentence to express the argument's conclusion. Many arguments are expressed in this way, but a single sentence can contain a complete argument. Consider. The butler has an alibi, so they cannot have done it. This argument has one premise followed by a conclusion. Many arguments start with premises and end with a conclusion, but not all of them. The argument with which this section began might equally have been presented with the conclusion at the beginning, like so. The gardener did it. After all, it was either the butler or the gardener, and the butler didn't do it. Equally, it might have been presented with the conclusion in the middle. The butler didn't do it, accordingly it was the gardener, given that it was either the gardener or the butler. When approaching an argument, we want to know whether or not the conclusion follows from the premises. So the first thing to do is to separate out the conclusion from the premises. As a guide, these words are often used to indicate an argument's conclusion. So therefore, hence, thus, accordingly, consequently, for this reason, they are sometimes called conclusion indicator words. By contrast, these expressions are premise indicator words, as they often indicate that we are dealing with a premise rather than a conclusion. Because, given that, but in analyzing an argument, there is no substitute for a good nose. 1.1 sentences. To be perfectly general, we can define an argument as a series of sentences. The sentences at the beginning of the series are premises. The final sentence in the series is the conclusion. If the premises are true and the argument is a good one, then you have a reason to accept the conclusion. In logic, we are only interested in sentences that can figure as a premise or conclusion of an argument, that is, sentences that can be true or false. So we will restrict ourselves to sentences of this sort and define a sentence as a sentence that can be true or false. You should not confuse the idea of a sentence that can be true or false with the difference between fact and opinion. Often, sentences in logic will express things that would count as facts, such as Kierkegaard was a hunchback or Kierkegaard liked almonds. They can also express things that you might think of as matters of opinion, such as almonds are tasty. In other words, a sentence is not disqualified from being part of an argument because we don't know if it is true or false, or because its truth or falsity is a matter of opinion. If it is the kind of sentence that could be true or false, it can play the role of premise or conclusion. Also, there are things that would count as sentences in a linguistics or grammar course that we will not count as sentences in logic. Questions in a grammar class, "Are you sleepy yet?" would count as an interrogative sentence. Although you might be sleepy or you might be alert, the question itself is neither true nor false. For this reason, questions will not count as sentences in logic. Suppose you answer the question, "I am not sleepy." This is either true or false, and so it is a sentence in the logical sense. Generally, questions will not count as sentences, but answers will. "What is this course about?" is not a sentence in our sense. "No one knows what this course is about" is a sentence. Imperatives commands are often phrased as imperatives like wake up, sit up straight, and so on. In a grammar class, these would count as imperative sentences. Although it might be good for you to sit up straight or it might not, the command is neither true nor false. Note, however, that commands are not always phrased as imperatives. "You will respect my authority" is either true or false, either you will or you will not, and so it counts as a sentence in the logical sense. Exclamations, "Ouch," is sometimes called an exclamatory sentence, but it is neither true nor false. We will treat "ouch, I hurt my toe" as meaning the same thing as "I hurt my toe." The ouch does not add anything that could be true or false. Practice exercises. At the end of some chapters, there are exercises that review and explore the material covered in the chapter. There is no substitute for actually working through some problems, because learning logic is more about developing a way of thinking than it is about memorizing facts. So here's the first exercise. Highlight the phrase which expresses the conclusion of each of these arguments. 1. It is sunny, so I should take my sunglasses. 2. It must have been sunny. I did wear my sunglasses after all. 3. No one but you has had their hands in the cookie jar, and the scene of the crime is littered with cookie crumbs. You're the culprit. 4. Miss Scarlet and Professor Plum were in the study at the time of the murder. Reverend Green had the candlestick in the ballroom, and we know that there is no blood on his hands. Hence, Colonel Mustard did it in the kitchen with the lead pipe. Recall, after all, that the gun had not been fired. Chapter 2. The scope of logic. 2.1 Consequence and validity. In Section 1, we talked about arguments, that is, a collection of sentences, the premises, followed by a single sentence, the conclusion. We said that some words, such as therefore, indicate which sentence in is supposed to be the conclusion. Therefore, of course, suggests that there is a connection between the premises and the conclusion, namely that the conclusion follows from, or is a consequence of, the premises. This notion of consequence is one of the primary things logic is concerned with. One might even say that logic is the science of what follows from what. Logic develops theories and tools that tell us when a sentence follows from some others. What about the main argument discussed in Section 1? Either the butler or the gardener did it. The butler didn't do it, the gardener did it. We don't have any context for what the sentences in this argument refer to. Perhaps you suspect that "did it" here means was the perpetrator of some unspecified crime. You might imagine that the argument occurs in a mystery novel or TV show, perhaps spoken by a detective working through the evidence. But even without having any of this information, you probably agree that the argument is a good one in the sense that whatever the premises refer to, if they are both true, the conclusion cannot but be true as well. If the first premise is true, that is, it's true that the butler did it or the gardener did it, then at least one of them did it, whatever that means. And if the second premise is true, then the butler did not do it. That leaves only one option. The gardener did it must be true. Here the conclusion follows from the premises. We call arguments that have this property valid. By way of contrast, consider the following argument. If the driver did it, the maid didn't do it. The maid didn't do it, the driver did it. We still have no idea what is being talked about here. But again, you probably agree that this argument is different from the previous one in an important respect. If the premises are true, it is not guaranteed that the conclusion is also true. The premises of this argument do not rule out by themselves that someone other than the maid or the driver did it. So there is a case where both premises are true, and yet the driver didn't do it, that is, the conclusion is not true. In this second argument, the conclusion does not follow from the premises. If, like in this argument, the conclusion does not follow from the premises, we say it is invalid. 2.2 Cases and types of validity. How do we determine that the second argument is invalid? We pointed to a case in which the premises are true and in which the conclusion is not. This was the scenario where neither the driver nor the maid did it, but some third person did. Let's call such a case a counterexample to the argument. If there is a counterexample to an argument, the conclusion cannot be a consequence of the premises. For the conclusion to be a consequence of the premises, the truth of the premises must guarantee the truth of the conclusion. If there is a counterexample, the truth of the premises does not guarantee the truth of the conclusion. As logicians, we want to be able to determine when the conclusion of an argument follows from the premises, and the conclusion is a consequence of the premises if there is no counterexample, no case where the premises are all true but the conclusion is not. This motivates a definition. A sentence A is a consequence of sentences B sub 1 through B sub n if and only if there is no case where B sub 1 through B sub n are all true and it is not true. We then also say that a follows from B sub 1 through B sub n or that B sub 1 through B sub n entail A. This definition is incomplete. It does not tell us what a case is or what it means to be true in a case. So far we've only seen an example, a hypothetical scenario involving 3 people. Of the 3 people in the scenario, a driver, a maid, and some third person, the driver and maid didn't do it, but the third person did. In this scenario, as described, the driver didn't do it, and so it is a case in which the sentence, the driver did it, is not true. The premises of our second argument are true, but the conclusion is not true. The scenario is a counterexample. We said that arguments where the conclusion is a consequence of the premises are called valid, and those where the conclusion isn't a consequence of the premises are invalid. Since we now have at least a first stab at a definition of consequence, we'll record this. An argument is valid if, and only if the conclusion is a consequence of the premises. An argument is invalid if and only if it is not valid, that is, it has a counterexample. Logicians are in the business of making the notion of case more precise, and investigating which arguments are valid when case is made precise in one way or another. If we take case to mean hypothetical scenario like the counterexample to the second argument, it's clear that the first argument counts as valid. If we imagine a scenario in which either the butler or the gardener did it, and also the butler didn't do it, we're automatically imagining a scenario in which the gardener did it. So any hypothetical scenario in which the premises of our first argument are true automatically makes the conclusion of our first argument true. This makes the first argument valid. Making case more specific by interpreting it as hypothetical scenario is an advance, but it is not the end of the story. The first problem is that we don't know what to count as a hypothetical scenario. Are they limited by the laws of physics, by what is conceivable in a very general sense? What answers we give to these questions determine which arguments we count as valid. Suppose the answer to the first question is yes. Consider the following argument. The spaceship Rocinante took 6 hours to reach Jupiter from Tycho Space Station. The distance between Tycho Space Station and Jupiter is less than 14 billion kilometers. A counterexample to this argument would be a scenario in which the Rocinante makes a trip of over 14 billion kilometers in 6 hours, exceeding the speed of light. Since such a scenario is incompatible with the laws of physics, there is no such scenario if hypothetical scenarios have to conform to the laws of physics. If hypothetical scenarios are not limited by the laws of physics, however, there is a counterexample, a scenario where the Rocinante travels faster than the speed of light. Suppose the answer to the second question is yes, and consider another argument. Priya is an ophthalmologist, Priya is an eye doctor. If we're allowing only conceivable scenarios, this is also a valid argument. If you imagine Priya being an ophthalmologist, you thereby imagine Priya being an eye doctor. That's just what ophthalmologist and eye doctor mean. A scenario where Priya is an ophthalmologist but not an eye doctor is ruled out by the conceptual connection between these words. Depending on what kinds of cases we consider as potential counterexamples, then, we arrive at different notions of consequence and validity. We might call an argument nomologcly valid if there are no counterexamples that don't violate the laws of nature, and an argument conceptually valid if there are no counterexamples that don't violate conceptual connections between words. For both of these notions of validity, aspects of the world, e.g., what the laws of nature are, and aspects of the meaning of the sentences in the argument, e.g., that ophthalmologist just means a kind of eye doctor, figure into whether an argument is valid. 2.3 Formal validity. One distinguishing feature of logical consequence, however, is that it should not depend on the content of the premises and conclusion, but only on their logical form. In other words, as logicians, we want to develop a theory that can make finer-grained distinctions still. For instance, both either Priya is an ophthalmologist or a dentist. Priya isn't a dentist, therefore Priya is an eye doctor, and either Priya is an ophthalmologist or a dentist. Priya isn't a dentist, Priya is an ophthalmologist are valid arguments, but while the validity of the first depends on the content, i.e., the meaning of ophthalmologist and eye doctor, the second does not. The second argument is formally valid. We can describe the form of this argument as a pattern, something like this. Either A is an X or a Y. A isn't a Y. Therefore A is an X. Here, A, X, and Y are placeholders for appropriate expressions that, when substituted for A, X, and Y, turn the pattern into an argument consisting of sentences. For instance, either May is a mathematician or a botanist. May isn't a botanist, therefore May is a mathematician, is an argument of the same form, but the first argument above is not. We would have to replace Y by different expressions, once by ophthalmologist and once by eye doctor, to obtain it from the pattern. Moreover, the first argument is not formally valid. Its form is this. Either A is an X or a Y. A isn't a Y. Therefore A is a Z. In this pattern, we can replace X by ophthalmologist and Z by eye doctor to obtain the original argument. But here is another argument of the same form. Either May is a mathematician or a botanist. May isn't a botanist, therefore May is an acrobat. This argument is clearly not valid, since we can imagine a mathematician named May who is not an acrobat. Our strategy as logicians will be to come up with a notion of case on which an argument turns out to be valid if it is formally valid. Clearly, such a notion of case will have to violate not just some laws of nature but some laws of English. Since the first argument is invalid in this sense, we must allow as counterexample a case where Priya is an ophthalmologist but not an eye doctor. That case is not a conceivable situation. It is ruled out by the meanings of ophthalmologist and eye doctor. When we consider cases of various kinds in order to evaluate the validity of an argument, we will make a few assumptions. The first assumption is that every case makes every sentence true, or not true at least, every sentence in the argument under consideration. That means first of all that any imagined scenario which leaves it undetermined if a sentence in our argument is true will not be considered as a potential counterexample. For instance, a scenario where Priya is a dentist but not an ophthalmologist will count as a case to be considered in the first few arguments in this section, but not as a case to be considered in the last two. It doesn't tell us if May is a mathematician, a botanist, or an acrobat. If a case doesn't make a sentence true, we say it makes it false. We'll thus assume that cases make sentences true or false, but never both. 2.4 Sound arguments. Before we go on and execute this strategy, a few clarifications. Arguments in our sense as conclusions which supposedly follow from premises are of course used all the time in everyday and scientific discourse. When they are, arguments are given to support or even prove their conclusions. Now, if an argument is valid, it will support its conclusion, but only if its premises are all true. Validity rules out the possibility that the premises are true and the conclusion is not true at the same time. It does not, by itself, rule out the possibility that the conclusion is not true, period. In other words, it is perfectly possible for a valid argument to have a conclusion that isn't true. Consider this example. Oranges are either fruit or musical instruments. Oranges are not fruit, therefore oranges are musical instruments. The conclusion of this argument is ridiculous. Nevertheless, it follows from the premises. If both premises are true, then the conclusion just has to be true, so the argument is valid. Conversely, having true premises and a true conclusion is not enough to make an argument valid. Consider this example. London is in England. Beijing is in China, therefore Paris is in France. The premises and conclusion of this argument are, as a matter of fact, all true, but the argument is invalid. If Paris were to declare independence from the rest of France, then the conclusion would no longer be true, even though both of the premises would remain true. Thus, there is a case where the premises of this argument are true without the conclusion being true, so the argument is invalid. The important thing to remember is that validity is not about the actual truth or falsity of the sentences in the argument. It is about whether it is possible for all the premises to be true, and the conclusion to be not true at the same time in some hypothetical case. What is in fact the case has no special role to play, and what the facts are does not determine whether an argument is valid or not. Nothing about the way things are can by itself determine if an argument is valid. It is often said that logic doesn't care about feelings. Actually, it doesn't care about facts either. When we use an argument to prove that its conclusion is true, then we need two things. First, we need the argument to be valid, that is, we need the conclusion to follow from the premises. But we also need the premises to be true. We will say that an argument is sound if and only if it is both valid and all of its premises are true. The flip side of this is that when you want to rebut an argument, you have two options. You can show that one or more of the premises are not true, or you can show that the argument is not valid. Logic, however, will only help you with the latter. 2.5 Inductive Arguments. Many good arguments are invalid. Consider this one. Every winter so far it has snowed in Calgary, therefore it will snow in Calgary this coming winter. This argument generalizes from observations about many past cases to a conclusion about all future cases. Such arguments are called inductive arguments. Nevertheless, the argument is invalid. Even if it has snowed in Calgary every winter thus far, it remains possible that Calgary will stay dry all through the coming winter. In fact, even if it will henceforth snow every January in Calgary, we could still imagine a case in which this year is the first year it doesn't snow all winter. And that hypothetical scenario is a case where the premises of the argument are true, but the conclusion is not, making the argument invalid. The point of all this is that inductive arguments, even good inductive arguments, are not deductively valid. They are not watertight. Unlikely though it might be, it is possible for their conclusion to be false, even when all of their premises are true. In this book, we will set aside entirely the question of what makes for a good inductive argument. Our interest is simply in sorting the deductively valid arguments from the invalid ones. So we are interested in whether or not a conclusion follows from some premises. Don't, though, say that the premises infer the conclusion. Entailment is a relation between premises and conclusions. Inference is something we do. So if you want to mention inference when the conclusion follows from the premises, you could say that one may infer the conclusion from the premises. Practice exercises. A. Which of the following arguments are valid? Which are invalid? 1. Socrates is a man. 2. All men are carrots. Therefore Socrates is a carrot. 1. Abe Lincoln was either born in Illinois or he was once president. 2. Abe Lincoln was never president. Abe Lincoln was born in Illinois. 1. If I pull the trigger, Abe Lincoln will die. 2. I do not pull the trigger. Therefore Abe Lincoln will not die. 1. Abe Lincoln was either from France or from Luxembourg. 2. Abe Lincoln was not from Luxembourg. Therefore Abe Lincoln was from France. 1. If the world ends today, then I will not need to get up tomorrow morning. 2. I will need to get up tomorrow morning. The world will not end today. 1. Joe is now 19 years old. 2. Joe is now 87 years old. Therefore Bob is now 20 years old. B. Could there be 1. A valid argument that has one false premise and one true premise. 2. A valid argument that has only false premises. 3. A valid argument with only false premises and a false conclusion. 4. An invalid argument that can be made valid by the addition of a new premise. 5. A valid argument that can be made invalid by the addition of a new premise. In each case, if so, give an example. If not, explain why not. Chapter 3. Other logical notions. In Section 2, we introduce the ideas of consequence and a valid argument. This is one of the most important ideas in logic. In this section, we will introduce some similarly important ideas. They all rely as validity on the idea that sentences are true or not in cases. For the rest of this section, we'll take cases in the sense of conceivable scenario. That is, in the sense in which we use them to define conceptual validity. The points we made about different kinds of validity can be made about our new notions along similar lines. If we use a different idea of what counts as a case, we will get different notions. And as logicians, we will, eventually, consider a more permissive definition of case than we do here. 3.1 Joint possibility. Consider these two sentences. B1, Jane's only brother is shorter than her. B2, Jane's only brother is taller than her. Logic alone cannot tell us which if either of these sentences is true. Yet we can say that if the first sentence B1 is true, then the second sentence B2 must be false. Similarly, if B2 is true, then B1 must be false. There is no possible scenario where both sentences are true together. These sentences are incompatible with each other. They cannot all be true at the same time. This motivates the following definition.
Sentences are jointly possible if, and only if there is a case where they are all true together.
B1 and B2 are jointly impossible, while say the following two sentences are jointly possible. B1, Jane's only brother is shorter than her. B2, Jane's only brother is younger than her. We can ask about the joint possibility of any number of sentences. For example, consider the following 4 sentences. G1, there are at least 4 giraffes at the wild animal park. G2, there are exactly 7 gorillas at the wild animal park. G3, there are not more than 2 Martians at the wild animal park. G4, every giraffe at the wild animal park is a Martian. G1 and G4 together entail that there are at least 4 Martian giraffes at the park. This conflicts with G3, which implies that there are no more than 2 Martian giraffes there, so the sentences G1, G4 are jointly impossible. They cannot all be true together. Note that the sentences G1, G3, and G4 are jointly impossible, but if sentences are already jointly impossible, adding an extra sentence to the mix cannot make them jointly possible. 3.2 Necessary truths, necessary falsehoods, and contingency. In assessing arguments for validity, we care about what would be true if the premises were true, but some sentences just must be true. Consider these sentences. 1. It is raining. 2. Either it is raining here or it is not. 3. It is both raining here and not raining here. In order to know if sentence 1 is true, you would need to look outside or check the weather channel. It might be true, it might be false. A sentence which is capable of being true and capable of being false in different circumstances, of course, is called contingent. Sentence 2 is different. You do not need to look outside to know that it is true. Regardless of what the weather is like, it is either raining or it is not. That is a necessary truth. Equally, you do not need to check the weather to determine whether or not sentence 3 is true. It must be false simply as a matter of logic. It might be raining here and not raining across town. It might be raining now but stop raining even as you finish this sentence. But it is impossible for it to be both raining and not raining in the same place and at the same time. So whatever the world is like, it is not both raining here and not raining here. It is a necessary falsehood. Something might always be true and still be contingent. For instance, if there never were a time when the universe contained fewer than 7 things, then the sentence "at least 7 things exist" would always be true. Yet the sentence is contingent. The world could have been much, much smaller than it is, and then the sentence would have been false. 3.3 Necessary equivalence. We can also ask about the logical relations between 2 sentences. For example, John went to the store after he washed the dishes. John washed the dishes before he went to the store. These 2 sentences are both contingent, since John might not have gone to the store or washed dishes at all. Yet they must have the same truth value. If either of the sentences is true, then they both are. If either of the sentences is false, then they both are. When 2 sentences have the same truth value in every case, we say that they are necessarily equivalent. Summary of logical notions. Play button an argument is valid if there is no case where the premises are all true and the conclusion is not. It is invalid otherwise. Play button a necessary truth is a sentence that is true in every case. Play button a necessary falsehood is a sentence that is false in every case. Play button a contingent sentence is neither a necessary truth nor a necessary falsehood, a sentence that is true in some case and false in some other case. Play button 2 sentences are necessarily equivalent if in every case they are both true or both false. Play button a collection of sentences is jointly possible if there is a case where they are all true together. It is jointly impossible otherwise. Practice exercises. A. For each of the following, is it a necessary truth, a necessary falsehood, or contingent? 1. Caesar crossed the Rubicon. 2. Someone once crossed the Rubicon. 3. No one has ever crossed the Rubicon. 4. If Caesar crossed the Rubicon, then someone has. 5. Even though Caesar crossed the Rubicon, no one has ever crossed the Rubicon. 6. If anyone has ever crossed the Rubicon, it was Caesar. B. For each of the following, is it a necessary truth, a necessary falsehood, or contingent? 1. Elephants dissolve in water. 2. Wood is a light, durable substance useful for building things. 3. If wood were a good building material, it would be useful for building things. 4. I live in a 3-story building that is 2 stories tall. 5. If gerbils were mammals, they would nurse their young. See which of the following pairs of sentences are necessarily equivalent. 1. Elephants dissolve in water. If you put an elephant in water, it will disintegrate. 2. All mammals dissolve in water. If you put an elephant in water, it will disintegrate. 3. George Bush was the 43rd president. Barack Obama is the 44th president. 4. Barack Obama is the 44th president. Barack Obama was president immediately after the 43rd president. 5. Elephants dissolve in water. All mammals dissolve in water. D. Which of the following pairs of sentences are necessarily equivalent? 1. Thelonious Monk played piano. John Coltrane played tenor sax. 2. Thelonious Monk played gigs with John Coltrane. John Coltrane played gigs with Thelonious Monk. 3. All professional piano players have big hands. Piano player Bud Powell had big hands. 4. Bud Powell suffered from severe mental illness. All piano players suffer from severe mental illness. 5. John Coltrane was deeply religious. John Coltrane viewed music as an expression of spirituality. Consider the following sentences. G1. There are at least 4 giraffes at the wild animal park. G2. There are exactly 7 gorillas at the wild animal park. G3. There are not more than 2 Martians at the wild animal park. G4. Every giraffe at the wild animal park is a Martian. Now consider each of the following collections of sentences. Which are jointly possible, which are jointly impossible? 1. Sentences G2, G3, and G4. 2 sentences G1, G3, and G4. 3 sentences G1, G2, and G4. 4 sentences G1, G2, and G3. F. Consider the following sentences. M. When all people are mortal. M2. Socrates is a person. M3. Socrates will never die. M4. Socrates is mortal. Which combinations of sentences are jointly possible? Mark each possible or impossible. 1 sentences M1, M2, and M3. 2 sentences M2, M3, and M4. 3 sentences M2 and M3. 4 sentences M1 and M4. 5 sentences M1, M2, M3, and M4. G. Which of the following is possible? If it is possible, give an example. If it is not possible, explain why. 1. A valid argument that has 1 false premise and 1 true premise. 2. A valid argument that has a false conclusion. 3. A valid argument, the conclusion of which is a necessary falsehood. 4. An invalid argument, the conclusion of which is a necessary truth. 5. A necessary truth that is contingent. 6. 2 necessarily equivalent sentences, both of which are necessary truths. 7. 2 necessarily equivalent sentences, one of which is a necessary truth and one of which is contingent. 8. 2 necessarily equivalent sentences that together are jointly impossible. 9. A jointly possible collection of sentences that contains a necessary falsehood. 10. A jointly impossible set of sentences that contains a necessary truth. H. Which of the following is possible? If it is possible, give an example. If it is not possible, explain why. 1. A valid argument whose premises are all necessary truths and whose conclusion is contingent. 2. A valid argument with true premises and a false conclusion. 3. A jointly possible collection of sentences that contains 2 sentences that are not necessarily equivalent. 4. A jointly possible collection of sentences, all of which are contingent. 5. A false necessary truth. 6. A valid argument with false premises. 7. A necessarily equivalent pair of sentences that are not jointly possible. 8. A necessary truth that is also a necessary falsehood. 9. A jointly possible collection of sentences that are all necessary falsehoods. Part 2. Truth Functional Logic. Chapter 4. First Steps to Symbolization. 4.1 Validity and Virtue of Form. Consider this argument. It is raining outside. If it is raining outside, then Jenny is miserable, therefore Jenny is miserable. And another argument. Jenny is an anarcho-syndicalist. If Jenny is an anarcho-syndicalist, then Dipan is an avid reader of Tolstoy. Therefore Dipan is an avid reader of Tolstoy. Both arguments are valid, and there is a straightforward sense in which we can say that they share a common structure. We might express the structure thus. If A, then C, therefore C. This looks like an excellent argument structure. Indeed, surely any argument with this structure will be valid, and this is not the only good argument structure. Consider an argument like, Jenny is either happy or sad. Jenny is not happy. Jenny is sad. Again, this is a valid argument. The structure here is something like,
Code summary: the code represents a logical argument form. It takes two premises as input, one stating that either A or B is true, and another stating that it is not true. The output is the conclusion that B must be true. This is a relatively simple form of deductive reasoning.
A superb structure. Here's another example. It's not the case that Jim both studied hard and acted in lots of plays. Jim studied hard, therefore Jim did not act in lots of plays. This valid argument has a structure which we might represent thus.
Code summary: the code represents a logical argument form. It takes two premises as input, the negation of a conjunction of two statements and the assertion of the first statement. The output is the negation of the second statement. This is a valid argument structure, where if the premises are true, the conclusion must also be true.
These examples illustrate an important idea which we might describe as validity in virtue of form. The validity of the arguments just considered has nothing very much to do with the meanings of English expressions like Jenny is miserable, Dipin is an avid reader of Tolstoy, or Jim acted in lots of plays. If it has to do with meanings at all, it is with the meanings of phrases like and, or, not, and if, then. In parts 2 IV, we are going to develop a formal language which allows us to symbolize many arguments in such a way as to show that they are valid in virtue of their form. That language will be Truth Functional Logic, or TFL. 4.2 Validity for special reasons. There are plenty of arguments that are valid but not for reasons relating to their form. Take an example. Juanita is a vixen, therefore Juanita is a fox. It is impossible for the premise to be true and the conclusion false. So the argument is valid. However, the validity is not related to the form of the argument. Here is an invalid argument with the same form. Juanita is a vixen, therefore Juanita is a cathedral. This might suggest that the validity of the first argument is keyed to the meaning of the words vixen and fox. But whether or not that is right, it is not simply the shape of the argument that makes it valid. Equally, consider the argument. The sculpture is green all over. The sculpture is not red all over. Again, it seems impossible for the premise to be true and the conclusion false, for nothing can be both green all over and red all over. So the argument is valid, but here is an invalid argument with the same form. The sculpture is green all over. The sculpture is not shiny all over. The argument is invalid since it is possible to be green all over and shiny all over. One might paint their nails with an elegant shiny green varnish. Plausibly, the validity of the first argument is keyed to the way that colors or color words interact, but whether or not that is right, it is not simply the shape of the argument that makes it valid. The important moral can be stated as follows. At best, TFL will help us to understand arguments that are valid due to their form. 4.3 Atomic sentences. We started isolating the form of an argument in section 4.1 by replacing subsentences of sentences with individual letters. Thus, in the first example of this section, it is raining outside is a subsentence of if it is raining outside, then Jenny is miserable, and we replaced this subsentence with a. Our artificial language TFL pursues this idea absolutely ruthlessly. We start with some sentence letters. These will be the basic building blocks out of which more complex sentences are built. We will use single uppercase letters as sentence letters of TFL. There are only 26 letters of the alphabet, but there is no limit to the number of sentence letters that we might want to consider. By adding subscripts to letters, we obtain new sentence letters. So here are 5 different sentence letters of TFL.
Math summary: the expression lists several sentence letters. It presents the sentence letter A, the sentence letter P, the sentence letter P with a subscript of 1, the sentence letter P with a subscript of 2, and the sentence letter A with a subscript of 234.
We will use sentence letters to represent or symbolize certain English sentences. To do this, we provide a symbolization key, such as the following. A. It is raining outside. C. Jenny is miserable in doing this. We are not fixing this symbolization once and for all. We are just saying that for the time being we will think of the sentence letter of TFL A as symbolizing the English sentence it is raining outside, and the sentence letter of TFL C as symbolizing the English sentence Jenny is miserable. Later, when we are dealing with different sentences or different arguments, we can provide a new symbolization key, as it might be. A. Jenny is an anarcho-syndicalist. C. Dipin is an avid reader of Tolstoy. It is important to understand that whatever structure an English sentence might have is lost when it is symbolized by a sentence letter of TFL. From the point of view of TFL, a sentence letter is just a letter. It can be used to build more complex sentences, but it cannot be taken apart. Chapter 5. Connectives. In the previous chapter, we considered symbolizing fairly basic English sentences with sentence letters of TFL. This leaves us wanting to deal with the English expressions and, or, not, and so forth. These are connectives. They can be used to form new sentences out of old ones. In TFL, we will make use of logical connectives to build complex sentences from atomic components. There are 5 logical connectives in TFL. This table summarizes them, and they are explained throughout this section.
Table summary. The table presents the 5 logical connectives in TFL, including their symbols, names, and meanings.
These are not the only connectives of English of interest. Others are, for example, unless, neither, nor, and because. We will see that the first 2 can be expressed by the connectives we will discuss, while the last cannot, because, in contrast to the others, is not truth functional. 5.1 Negation. Consider how we might symbolize these sentences. 1. Mary is in Barcelona. 2. It is not the case that Mary is in Barcelona. 3. Mary is not in Barcelona. In order to symbolize sentence 1, we will need a sentence letter. We might offer this symbolization key. B. Mary is in Barcelona. Since sentence 2 is obviously related to sentence 1, we will not want to symbolize it with a completely different sentence letter. Roughly, sentence 2 means something like, it is not the case that B. In order to symbolize this, we need a symbol for negation. We will use not sign. Now we can symbolize sentence 2 with not sign B. Sentence 3 also contains the word not, and it is obviously equivalent to sentence 2. As such, we can also symbolize it with not sign B. A sentence can be symbolized as not A if it can be paraphrased in English as it is not the case that. It will help to offer a few more examples. 4. The widget can be replaced. 5. The widget is irreplaceable. 6. The widget is not irreplaceable. Let us use the following representation key. R. The widget is replaceable. Sentence 4 can now be symbolized by R. Moving on to sentence 5. Saying the widget is irreplaceable means that it is not the case that the widget is replaceable. So even though sentence 5 does not contain the word not, we will symbolize it as follows, not sign R. Sentence 6 can be paraphrased as it is not the case that the widget is irreplaceable, which can again be paraphrased as it is not the case that it is not the case that the widget is replaceable. So we might symbolize this English sentence with the TFL sentence R. But some care is needed when handling negations. Consider. 7. Jane is happy. 8. Jane is unhappy. If we let the TFL sentence, H, symbolize Jane is happy, then we can symbolize sentence 7 as H. However, it would be a mistake to symbolize sentence 8 with minus H. If Jane is unhappy, then she's not happy, but sentence 8 does not mean the same thing as it is not the case that Jane is happy. Jane might be neither happy nor unhappy. She might be in a state of blank indifference. In order to symbolize sentence 8, then, we would need a new sentence letter of TFL. 5.2 Conjunction. Consider these sentences. 9. Adam is athletic. 10. Barbara is athletic. 11. Adam is athletic, and also Barbara is athletic. We will need separate sentence letters of TFL to symbolize sentences 9 and 10, perhaps. A. Adam is athletic. B. Barbara is athletic. Sentence 9 can now be symbolized as A, and sentence 10 can be symbolized as B. Sentence 11 roughly says A and B. We need another symbol to deal with and we will use wedge, thus we will symbolize it as a wedge B. This connective is called conjunction. We also say that A and B are the 2 conjuncts of the conjunction, a wedge B. Notice that we make no attempt to symbolize the word also in sentence 11. Words like both and also function to draw our attention to the fact that 2 things are being conjoined. Maybe they affect the emphasis of a sentence, but we will not and cannot symbolize such things in TFL. Some more examples will bring out this point. 12. Barbara is athletic and energetic. 13. Barbara and Adam are both athletic. 14. Although Barbara is energetic, she is not athletic. 15. Adam is athletic, but Barbara is more athletic than him. Sentence 12 is obviously a conjunction. The sentence says 2 things about Barbara. In English, it is permissible to refer to Barbara only once. It might be tempting to think that we need to symbolize sentence 12 with something along the lines of be and energetic. This would be a mistake. Once we symbolize part of a sentence as be, any further structure is lost, as be is a sentence letter of TFL. Conversely, energetic is not an English sentence at all. What we are aiming for is something like be and Barbara is energetic, so we need to add another sentence letter to the symbolization key. Let E symbolize Barbara is energetic. Now the entire sentence can be symbolized as BE. Sentence 13 says one thing about two different subjects. It says of both Barbara and Adam that they are athletic, even though in English we use the word athletic only once. The sentence can be paraphrased as Barbara is athletic and Adam is athletic. We can symbolize this in TFL as B and A, using the same symbolization key that we have been using. Sentence 14 is slightly more complicated. The word although sets up a contrast between the first part of the sentence and the second part. Nevertheless, the sentence tells us both that Barbara is energetic and that she is not athletic. In order to make each of the conjuncts a sentence letter, we need to replace she with Barbara. So we can paraphrase sentence 14 as, both Barbara is energetic and Barbara is not athletic. The second conjunct contains a negation, so we paraphrase further. Both Barbara is energetic and it is not the case that Barbara is athletic. Now we can symbolize this with the TFL sentence E not B. Note that we have lost all sorts of nuance in this symbolization. There is a distinct difference in tone between sentence 14 and both Barbara is energetic and it is not the case that Barbara is athletic. TFL does not and cannot preserve these nuances. Sentence 15 raises similar issues. There is a contrastive structure, but this is not something that TFL can deal with. So we can paraphrase the sentence as both Adam is athletic and Barbara is more athletic than Adam. Notice that we once again replace the pronoun him with Adam. How should we deal with the second conjunct? We already have the sentence letter A, which is being used to symbolize Adam is athletic, and the sentence B, which is being used to symbolize Barbara is athletic, but neither of these concerns their relative athleticity. So to symbolize the entire sentence, we need a new sentence letter. Let the TFL sentence R symbolize the English sentence Barbara is more athletic than Adam. Now we can symbolize sentence 15 by R. A sentence can be symbolized as open parenthesis script a logical and script B close parenthesis if it can be paraphrased in English as both and, or as, but, or as although. You might be wondering why we put brackets around the conjunctions. The reason can be brought out by thinking about how negation interacts with conjunction. Consider. 16. It's not the case that you will get both soup and salad. 17. You will not get soup, but you will get salad. Sentence 16 can be paraphrased as it is not the case that both you will get soup and you will get salad, using this symbolization key. S1 you will get soup. S2 you will get salad. We would symbolize both you will get soup and you will get salad as left parenthesis S sub 1 logical and S sub 2 right parenthesis. To symbolize sentence 16 then, we simply negate the whole sentence, thus, logical not left parenthesis S sub 1 logical and S sub 2 right parenthesis. Sentence 17 is a conjunction, you will not get soup and you will get salad. You will not get soup is symbolized by not sign S1. So to symbolize sentence 17 itself, we offer not sign S1 S2. These English sentences are very different and their symbolizations differ accordingly. In one of them, the entire conjunction is negated. In the other, just one conjunct is negated. Brackets help us to keep track of things like the scope of the negation. 5.3 Disjunction. Consider these sentences. 18. Either Fatima will play video games or she will watch movies. 19. Either Fatima or Omar will play video games. For these sentences, we can use this symbolization key. F. Fatima will play video games. 0. Omar will play video games. M. Fatima will watch movies. However, we will again need to introduce a new symbol. Sentence 18 is symbolized by F or M. The connective is called disjunction. We also say that F and M are the disjuncts of the disjunction F or M. Sentence 19 is only slightly more complicated. There are two subjects, but the English sentence only gives the verb once. However, we can paraphrase sentence 19 as either Fatima will play video games or Omar will play video games. Now we can obviously symbolize it by F or O again. A sentence can be symbolized as left parenthesis script a logical or script B right parenthesis if it can be paraphrased in English as either or. Sometimes in English the word or is used in a way that excludes the possibility that both disjuncts are true. This is called an exclusive OR. An exclusive or is clearly intended when it says on a restaurant menu, entrees come with either soup or salad. You may have soup, you may have salad, but if you want both soup and salad then you have to pay extra. At other times, the word or allows for the possibility that both disjuncts might be true. This is probably the case with sentence 19 above. Fatima might play video games alone, Omar might play video games alone, or they might both play. Sentence 19 merely says that at least one of them plays video games. This is an inclusive OR. The TFL symbol always symbolizes an inclusive OR. It will also help to see how negation interacts with disjunction. Consider. 20. Either you will not have soup or you will not have salad. 21. You will have neither soup nor salad. 22. You get either soup or salad but not both. Using the same symbolization key as before, sentence 20 can be paraphrased in this way. Either it is not the case that you get soup or it is not the case that you get salad. To symbolize this in TFL, we need both disjunction and negation. It is not the case that you get soup is symbolized by not S1. It is not the case that you get salad is symbolized by not S2. So sentence 20 itself is symbolized by not S1 or not S2. Sentence 21 also requires negation. It can be paraphrased as, it is not the case that either you get soup or you get salad. Since this negates the entire disjunction, we symbolize sentence 21 with not sign, S1, S2. Sentence 22 is an exclusive, or we can break the sentence into two parts. The first part says that you get one or the other. We symbolize this as S1 or S2. The second part says that you do not get both. We can paraphrase this as, it is not the case both that you get soup and that you get salad. Using both negation and conjunction, we symbolize this with not, open parenthesis, S sub 1 and S sub 2, close parenthesis. Now we just need to put the two parts together, as we saw above, but can usually be symbolized with and. So sentence 22 can be symbolized as open parenthesis, S sub 1 or S sub 2, close parenthesis, and not, open parenthesis, S sub 1 and S sub 2, close parenthesis. This last example shows something important. Although the TFL symbol always symbolizes inclusive, or we can symbolize an exclusive or in TFL, we just have to use a few other symbols as well. 5.4 Conditional. Consider these sentences. 23. If Jean is in Paris, then Jean is in France. 24. Jean is in France only if Jean is in Paris. Let's use the following symbolization key. P. Jean is in Paris. F. Jean is in France. Sentence 23 is roughly of this form. If P, then F. We will use the symbol right arrow to symbolize this if, then, structure. So we symbolize sentence 23 by P right arrow F. The connective is called the conditional. Here P is called the antecedent of the conditional, P right arrow F, and F is called the consequent. Sentence 24 is also a conditional. Since the word if appears in the second half of the sentence, it might be tempting to symbolize this in the same way as sentence 23. That would be a mistake. Your knowledge of geography tells you that sentence 23 is unproblematically true. There is no way for Jean to be in Paris that doesn't involve Jean being in France. But sentence 24 is not so straightforward. Were Jean in Dieppe, Lyon, or Toulouse, Jean would be in France without being in Paris, thereby rendering sentence 24 false. Since geography alone dictates the truth of sentence 23, whereas travel plans, say, are needed to know the truth of sentence 24, they must mean different things. In fact, sentence 24 can be paraphrased as if Jean is in France, then Jean is in Paris, so we can symbolize it by F implies P. A sentence can be symbolized as A implies B if it can be paraphrased in English as if A then B or A only if B. In fact, the conditional can represent many English expressions. Consider. 25. For Jean to be in Paris, it is necessary that Jean be in France. 26. It is a necessary condition on Jean's being in Paris that she be in France. 27. For Jean to be in France, it is sufficient that Jean be in Paris. 28. It is a sufficient condition on Jean's being in France that she be in Paris. If we think about it, all four of these sentences mean the same as if Jean is in Paris, then Jean is in France, so they can all be symbolized by P to F. It is important to bear in mind that the connective right arrow tells us only that if the antecedent is true, then the consequent is true. It says nothing about a causal connection between two events, for example. In fact, we lose a huge amount when we use right arrow to symbolize English conditionals. We will return to this in section 10, 3 and 12.5. 5.5 by conditional. Consider these sentences. 29. Leica is a dog only if she is a mammal. 30. Leica is a dog if she is a mammal. 31. Leica is a dog if and only if she is a mammal. We will use the following symbolization key. D. Leica is a dog. M. Leica is a mammal for reasons discussed above. Sentence 29 can be symbolized by D implies M. Sentence 30 is importantly different. It can be paraphrased as, if Leica is a mammal, then Leica is a dog, so it can be symbolized by M to D. Sentence 31 says something stronger than either 29 or 30. It can be paraphrased as Leica is a dog if Leica is a mammal, and Leica is a dog only if Leica is a mammal. This is just the conjunction of sentences 29 and 30, so we can symbolize it as D to M and M to D. We call this a biconditional because it amounts to stating both directions of the conditional. We could treat every biconditional this way. So just as we do not need a new TFL symbol to deal with exclusive, or we do not really need a new TFL symbol to deal with biconditionals. Because the biconditional occurs so often, however, we will use the symbol left-right arrow for it. We can then symbolize sentence 31 with the TFL sentence, D left-right arrow M. The expression if and only if occurs a lot, especially in philosophy, mathematics, and logic. For brevity, we can abbreviate it with the snappier word if. We will follow this practice. So if with only one F is the English conditional, but if with two Fs is the English biconditional. Armed with this, we can say, a sentence can be symbolized as A if and only if B if it can be paraphrased in English as a if B, that is, as a if and only if B. A word of caution, ordinary speakers of English often use if, then, when they really mean to use something more like if and only if. Perhaps your parents told you when you were a child, if you don't eat your greens, you won't get any dessert. Suppose you ate your greens, but that your parents refused to give you any dessert on the grounds that they were only committed to the conditional roughly, if you get dessert, then you will have eaten your greens, rather than the biconditional roughly, you get dessert if you eat your greens. Well, a tantrum would rightly ensue. So be aware of this when interpreting people, but in your own writing, make sure you use the biconditional if you mean to. 5.6 Unless. We have now introduced all of the connectives of TFL. We can use them together to symbolize many kinds of sentences. An especially difficult case is when we use the English language connective unless. 32. Unless you wear a jacket, you will catch a cold. 33. You will catch a cold unless you wear a jacket. These two sentences are clearly equivalent. To symbolize them, we will use the symbolization key. J. You will wear a jacket. D. You will catch a cold. Both sentences mean that if you do not wear a jacket, then you will catch a cold. With this in mind, we might symbolize them as not J implies D. Equally, both sentences mean that if you do not catch a cold, then you must have worn a jacket. With this in mind, we might symbolize them as not D to J. Equally, both sentences mean that either you will wear a jacket or you will catch a cold. With this in mind, we might symbolize them as J or D. All three are correct symbolizations. Indeed, in Chapter 12 we will see that all three symbolizations are equivalent in TFL. If a sentence can be paraphrased as unless A, B, then it can be symbolized as left parenthesis script a logical or script B right parenthesis. Again, though, there is a little complication. Unless can be symbolized as a conditional, but as we said above, people often use the conditional on its own when they mean to use the biconditional. Equally, unless can be symbolized as a disjunction, but there are two kinds of disjunction, exclusive and inclusive. So it will not surprise you to discover that ordinary speakers of English often use unless to mean something more like the biconditional, or like exclusive disjunction. Suppose someone says, I will go running unless it rains. They probably mean something like, I will go running if it does not rain, i.e. the biconditional, or either I will go running or it will rain, but not both, i.e. exclusive disjunction. Again, be aware of this when interpreting what other people have said, but be precise in your writing. Practice exercises. A. Using the symbolization key given, symbolize each English sentence in TFL. M. Those creatures are men in suits. Z. Those creatures are chimpanzees. G. Those creatures are gorillas. 1. Those creatures are not men in suits. 2. Those creatures are men in suits or they are not. 3. Those creatures are either gorillas or chimpanzees. 4. Those creatures are neither gorillas nor chimpanzees. 5. If those creatures are chimpanzees, then they are neither gorillas nor men in suits. 6. Unless those creatures are men in suits, they are either chimpanzees or they are gorillas. B. Using the symbolization key given, symbolize each English sentence in TFL. A. Mr. Ace was murdered. B. The butler did it. C. The cook did it. D. The Duchess is lying. E. Mr. Edge was murdered. F. The murder weapon was a frying pan. 1. Either Mr. Ace or Mr. Edge was murdered. 2. If Mr. Ace was murdered, then the cook did it. 3. If Mr. Edge was murdered, then the cook did not do it. 4. Either the butler did it or the Duchess is lying. 5. The cook did it only if the Duchess is lying. 6. If the murder weapon was a frying pan, then the culprit must have been the cook. 7. If the murder weapon was not a frying pan, then the culprit was either the cook or the butler. 8. Mr. Ace was murdered if and only if Mr. Edge was not murdered. 9. The Duchess is lying unless it was Mr. Edge who was murdered. 10. If Mr. Ace was murdered, he was done in with a frying pan. 11. Since the cook did it, the butler did not. 12. Of course the Duchess is lying. See, using the symbolization key given, symbolize each English sentence in TFL. E sub 1, Ava is an electrician. E sub 2, Harrison is an electrician. F sub 1, Ava is a firefighter. F sub 2, Harrison is a firefighter. S sub 1, Ava is satisfied with her career. S sub 2, Harrison is satisfied with his career. 1. Ava and Harrison are both electricians. 2. If Ava is a firefighter, then she is satisfied with her career. 3. Ava is a firefighter unless she is an electrician. 4. Harrison is an unsatisfied electrician. 5. Neither Ava nor Harrison is an electrician. 6. Both Ava and Harrison are electricians, but neither of them find it satisfying. 7. Harrison is satisfied only if he is a firefighter. 8. If Ava is not an electrician, then neither is Harrison, but if she is, then he is too. 9. Ava is satisfied with her career if and only if Harrison is not satisfied with his. 10. If Harrison is both an electrician and a firefighter, then he must be satisfied with his work. 11. It cannot be that Harrison is both an electrician and a firefighter. 12. Harrison and Ava are both firefighters if and only if neither of them is an electrician. D. Using the symbolization key given, symbolize each English language sentence in TFL. J sub 1, John Coltrane played tenor sax. J2, John Coltrane played soprano sax. J sub 3, John Coltrane played tuba M1, Miles Davis played trumpet M sub 2, Miles Davis played tuba. 1. John Coltrane played tenor and soprano sax. 2. Neither Miles Davis nor John Coltrane played tuba. 3. John Coltrane did not play both tenor sax and tuba. 4. John Coltrane did not play tenor sax unless he also played soprano sax. 5. John Coltrane did not play tuba, but Miles Davis did. 6. Miles Davis played trumpet only if he also played tuba. 7. If Miles Davis played trumpet, then John Coltrane played at least one of these three instruments: tenor sax, soprano sax, or tuba. 8. If John Coltrane played tuba, then Miles Davis played neither trumpet nor tuba. 9. Miles Davis and John Coltrane both played tuba if and only if Coltrane did not play tenor sax and Miles Davis did not play trumpet. E. Give a symbolization key and symbolize the following English sentences in TFL. 1. Alice and Bob are both spies. 2. If either Alice or Bob is a spy, then the code has been broken. 3. If neither Alice nor Bob is a spy, then the code remains unbroken. 4. The German embassy will be in an uproar unless someone has broken the code. 5. Either the code has been broken or it has not, but the German embassy will be in an uproar regardless. 6. Either Alice or Bob is a spy, but not both. F. Give a symbolization key and symbolize the following English sentences in TFL. 1. If there is food to be found in the Pridelands, then Rafiki will talk about squashed bananas. 2. Rafiki will talk about squashed bananas unless Simba is alive. 3. Rafiki will either talk about squashed bananas or he won't, but there is food to be found in the Pridelands regardless. 4. Scar will remain as king if and only if there is food to be found in the Pridelands. 5. If Simba is alive, then Scar will not remain as king. G. For each argument, write a symbolization key and symbolize all of the sentences of the argument in TFL. 1. If Dorothy plays the piano in the morning, then Roger wakes up cranky. Dorothy plays piano in the morning unless she is distracted, so if Roger does not wake up cranky, then Dorothy must be distracted. 2. It will either rain or snow on Tuesday. If it rains, Neville will be sad. If it snows, Neville will be cold. Therefore, Neville will either be sad or cold on Tuesday. 3. If Zug remembered to do his chores, then things are clean but not neat. If he forgot, then things are neat but not clean. Therefore, things are either neat or clean, but not both. H for each argument, write a symbolization key and symbolize the argument as well as possible in TFL. The part of the passage in italics is there to provide context for the argument and doesn't need to be symbolized. 1. It is going to rain soon. I know because my leg is hurting and my leg hurts if it's going to rain. 2. Spider-Man tries to figure out the bad guy's plan. If Dr. Octopus gets the uranium, he will blackmail the city. I am certain of this because if Dr. Octopus gets the uranium, he can make a dirty bomb, and if he can make a dirty bomb, he will blackmail the city. 3. A Westerner tries to predict the policies of the Chinese government. If the Chinese government cannot solve the water shortages in Beijing, they will have to move the capital. They don't want to move the capital, therefore they must solve the water shortage, but the only way to solve the water shortage is to divert almost all the water from the Yangtze River northward. Therefore, the Chinese government will go with the project to divert water from the south to the north. 1. We symbolized an exclusive or using, and how could you symbolize an exclusive or using only two connectives? Is there any way to symbolize an exclusive or using only one connective? Chapter 6. Sentences of TFL. The sentence either apples are red or berries are blue is a sentence of English, and the sentence a bee is a sentence of TFL. Although we can identify sentences of English when we encounter them, we do not have a formal definition of sentence of English. But in this chapter we will define exactly what will count as a sentence of TFL. This is one respect in which a formal language like TFL is more precise than a natural language like English. 6.1 Expressions. We have seen that there are three kinds of symbols in TFL. Atomic sentences A, B, C, Z with subscripts as needed: a sub 1, B sub 1, Z sub 1, a sub 2, a sub 25, J sub 375. Connectives.
Math summary. This lists logical connectives. These include negation, conjunction, disjunction, implication, and biconditional.
Brackets.
Math summary. This represents a column vector or matrix, but the contents are unspecified.
Define an expression of TFL as any string of symbols of TFL. So, write down any sequence of symbols of TFL in any order and you have an expression of TFL. 6.2 Sentences. Given what we just said, left parenthesis A and B right parenthesis is an expression of TFL, and so is not left parenthesis V left parenthesis right parenthesis and left parenthesis not left parenthesis right parenthesis left parenthesis B right parenthesis. But the former is a sentence and the latter is gibberish. We want some rules to tell us which TFL expressions are sentences. Obviously, individual sentence letters like A and G subscript 13 should count as sentences. We'll also call them atomic sentences. We can form further sentences out of these by using the various connectives. Using negation, we can get not A and not G subscript 13. Using conjunction, we can get A and G subscript 13, G subscript 13 and A, and G subscript 13 and G subscript 13. We could also apply negation repeatedly to get sentences like not A, or apply negation along with conjunction to get sentences like not A and G subscript 13, and not G subscript 13 and not G subscript 13. The possible combinations are endless, even starting with just these two sentence letters, and there are infinitely many sentence letters, so there's no point in trying to list all the sentences one by one. Instead, we will describe the process by which sentences can be constructed. Consider negation. Given any sentence A of TFL, not A is a sentence of TFL. Why the funny fonts? We return to this in section 8.3. We can say similar things for each of the other connectives. For instance, if A and B are sentences of TFL, then open parenthesis A and B close parenthesis is a sentence of TFL. Providing clauses like this for all of the connectives, we arrive at the following formal definition for a sentence of TFL.
Table summary. The table provides an inductive definition of sentences in TFL. It starts with a base case and then provides rules for constructing more complex sentences from simpler ones.
Definitions like this are called inductive. Inductive definitions begin with some specifiable base elements and then present ways to generate indefinitely many more elements by compounding together previously established ones. To give you a better idea of what an inductive definition is, we can give an inductive definition of the idea of an ancestor of mine. We specify a base clause. My parents are ancestors of mine. And then offer further clauses like, if X is an ancestor of mine, then X's parents are ancestors of mine. Nothing else is an ancestor of mine. Using this definition, we can easily check to see whether someone is my ancestor. Just check whether she is the parent of one of my parents, and the same is true for our inductive definition of sentences of TFL. Just as the inductive definition allows complex sentences to be built up from simpler parts, the definition allows us to decompose sentences into their simpler parts. Once we get down to sentence letters, then we know we are okay. Let's consider some examples. Suppose we want to know whether or not D is a sentence of TFL. Looking at the second clause of the definition, we know that D is a sentence if D is a sentence. So now we need to ask whether or not D is a sentence. Again, looking at the second clause of the definition, D is a sentence if D is. So D is a sentence if D is a sentence. Now D is a sentence letter of TFL, so we know that D is a sentence by the first clause of the definition. So for a compound sentence like D, we must apply the definition repeatedly. Eventually, we arrive at the sentence letters from which the sentence is built up. Next, consider the example not P and not Q or R. Looking at the second clause of the definition, this is a sentence if P and not Q or R is, and this is a sentence if both P and not Q or R are sentences. The former is a sentence letter and the latter is a sentence if not Q or R is a sentence. It is. Looking at the fourth clause of the definition, this is a sentence if both not Q and R are sentences and both are. Ultimately, every sentence is constructed nicely out of sentence letters. When we are dealing with a sentence other than a sentence letter, we can see that there must be some sentential connective that was introduced last when constructing the sentence. We call that connective the main logical operator of the sentence. In the case of not D, the main logical operator is the very first not sign. In the case of P and not for all Q or R, the main logical operator is and. In the case of for all E or F implies not for all G, the main logical operator is implies. As a general rule, you can find the main logical operator for a sentence by using the following method. If the first symbol in the sentence is then that is the main logical operator. Otherwise, start counting the brackets. For each open bracket, that is, add 1. For each closing bracket, that is, subtract 1. When your count is at exactly 1, the first operator you hit apart from A is the main logical operator. Note, if you do use this method, then make sure to include all the brackets in the sentence, rather than omitting some as per the conventions of section 6.3. The inductive structure of sentences in TFL will be important when we consider the circumstances under which a particular sentence would be true or false. The sentence D is true if and only if the sentence D is false, and so on through the structure of the sentence until we arrive at the atomic components. We will return to this point in Part 3. The inductive structure of sentences in TFL also allows us to give a formal definition of the scope of a negation mentioned in Section 5.2. The scope of a not sign is the subsentence for which not sign is the main logical operator. Consider a sentence like,
Math summary. This expression performs a logical conjunction. It combines a first input with the result of a logical biconditional. The biconditional compares the output of a logical negation with a second input. The logical negation is applied to the result of a logical conjunction of a third and fourth input,
which was constructed by conjoining P with negation of R and B if and only if Q. This last sentence was constructed by placing a biconditional between negation of R and B and Q. The former of these sentences, a subsentence of our original sentence, is a sentence for which negation is the main logical operator. So the scope of the negation is just negation of R and B, more generally. The scope of a connective in a sentence is the subsentence for which that connective is the main logical operator. 6.3 Bracketing conventions. Strictly speaking, the brackets in Q and R are an indispensable part of the sentence. Part of this is because we might use Q and R as a subsentence in a more complicated sentence. For example, we might want to negate Q and R, obtaining negation of Q and R. If we just had Q and R without the brackets and put a negation in front of it, we would have negation of Q and R. It is most natural to read this as meaning the same thing as not Q and R, but as we saw in section 5.2, this is very different from not Q and R. Strictly speaking then, QR is not a sentence, it is a mere expression. When working with TFL, however, it will make our lives easier if we are sometimes a little less than strict. So here are some convenient conventions. First, we allow ourselves to omit the outermost brackets of a sentence. Thus we allow ourselves to write QR instead of the sentence QR. However, we must remember to put the brackets back in when we want to embed the sentence into a more complicated sentence. Second, it can be a bit painful to stare at long sentences with many nested pairs of brackets. To make things a bit easier on the eyes, we will allow ourselves to use square brackets and, instead of rounded ones, so there is no logical difference between PQ and PQ, for example. Combining these two conventions, we can rewrite the unwieldy sentence.
Math summary. This expression evaluates a logical statement. First, it checks if H implies I, or if I implies H, then it checks if J or K is true. Finally, it combines the results of these two checks using a logical AND, meaning that both must be true for the entire expression to be true.
Rather more clearly as follows.
Math summary. This expression evaluates a logical proposition. First, it evaluates whether H implies I or I implies H. Second, it evaluates whether J or K is true. Finally, it combines the result of the first evaluation with the result of the second evaluation using a logical AND.
The scope of each connective is now much easier to pick out. Practice exercises. A. For each of the following: A. Is it a sentence of TFL, strictly speaking? B. Is it a sentence of TFL, allowing for our relaxed bracketing conventions? $1 $8. 2 J sub 374, or not J sub 374. 3 not F. 4 not an S5, left parenthesis G and not G right parenthesis 6. I implies and not F or D if and only if E7. Left bracket Z double arrow S right bracket arrow W and left bracket J or X right bracket 8. F if and only if not D implies J or C and D. B. Are there any sentences of TFL that contain no sentence letters? Explain your answer. C. What is the scope of each connective in the sentence?
Math summary. The expression evaluates a logical proposition. First, it checks if H implies I, or if I implies H, then it checks if J or K is true. Finally, it combines the results of these two checks using a logical AND, meaning both must be true for the entire expression to be true.
Chapter 7. Ambiguity. In English, sentences can be ambiguous, that is, they can have more than one meaning. There are many sources of ambiguity. One is lexical ambiguity. A sentence can contain words which have more than one meaning. For instance, bank can mean the bank of a river or a financial institution. So I might say that I went to the bank when I took a stroll along the river or when I went to deposit a check. Depending on the situation, a different meaning of bank is intended, and so the sentence, when uttered in these different contexts, expresses different meanings. A different kind of ambiguity is structural ambiguity. This arises when a sentence can be interpreted in different ways, and depending on the interpretation, a different meaning is selected. A famous example due to Noam Chomsky is the following. Flying planes can be dangerous. There is one reading in which flying is used as an adjective which modifies planes. In this sense, what's claimed to be dangerous are airplanes which are in the process of flying. In another reading, flying is a gerund. What's claimed to be dangerous is the act of flying a plane. In the first case, you might use the sentence to warn someone who's about to launch a hot air balloon. In the second case, you might use it to counsel someone against becoming a pilot. When the sentence is uttered, usually only one meaning is intended. Which of the possible meanings an utterance of a sentence intends is determined by context, or sometimes by how it is uttered, which parts of the sentence are stressed, for instance. Often one interpretation is much more likely to be intended, and in that case it will even be difficult to see the unintended reading. This is often the reason why a joke works, as in this example from Groucho Marx. One morning I shot an elephant in my pajamas. How he got in my pajamas, I don't know. Ambiguity is related to, but not the same as vagueness. An adjective, for instance, rich or tall, is vague when it is not always possible to determine if it applies or not. For instance, a person who's 6'4" and 1.9 m tall is pretty clearly tall, but a building that size is tiny. Here, context has a role to play in determining what the clear cases and clear non-cases are: tall for a person, tall for a basketball player, tall for a building. Even when the context is clear, however, there will still be cases that fall in a middle range. In TFL, we generally aim to avoid ambiguity. We will try to give our symbolization keys in such a way that they do not use ambiguous words or disambiguate them if a word has different meanings. So for example, your symbolization key will need two different sentence letters for Rebecca went to the money bank and Rebecca went to the river bank. Vagueness is harder to avoid. Since we have stipulated that every case and later every valuation must make every basic sentence or sentence letter either true or false and nothing in between, we cannot accommodate borderline cases in TFL. It is an important feature of sentences of TFL that they cannot be structurally ambiguous. Every sentence of TFL can be read in one, and only one way. This feature of TFL is also strength. If an English sentence is ambiguous, TFL can help us make clear what the different meanings are. Although we are pretty good at dealing with ambiguity in everyday conversation, avoiding it can sometimes be terribly important. Logic can then be usefully applied. It helps philosophers express their thoughts clearly, mathematicians to state their theorems rigorously, and software engineers to specify loop conditions, database queries, or verification criteria unambiguously. Stating things without ambiguity is of crucial importance in the law as well. Here, ambiguity can, without exaggeration, be a matter of life and death. Here's a famous example of where a death sentence hinged on the interpretation of an ambiguity in the law. Roger Casement, 1864 to 1916, was a British diplomat who was famous in his time for publicizing human rights violations in the Congo and Peru, for which he was knighted in 1911. He was also an Irish nationalist. In 1914-16, Casement secretly traveled to Germany, with which Britain was at war at the time, and tried to recruit Irish prisoners of war to fight against Britain and for Irish independence. Upon his return to Ireland, he was captured by the British and tried for high treason. The law under which Casement was tried is the Treason Act of 1351. That act specifies what counts as treason, and so the prosecution had to establish at trial that Casement's actions met the criteria set forth in the Treason Act. The relevant passage stipulated that someone is guilty of treason
if a man is adherent to the king's enemies in his realm, giving to them aid and comfort in the realm or elsewhere.
Casement's defense hinged on the last comma in this sentence, which is not present in the original French text of the law from 1351. It was not under dispute that Casement had been adherent to the king's enemies, but the question was whether being adherent to the king's enemies constituted treason only when it was done in the realm, or also when it was done abroad. The defense argued that the law was ambiguous. The claimed ambiguity hinged on whether or elsewhere attaches only to giving aid and comfort to the king's enemies, the natural reading without the comma, or to both being adherent to the king's enemies and giving aid and comfort to the king's enemies, the natural reading with the comma. Although the former interpretation might seem far-fetched, the argument in its favor was actually not unpersuasive. Nevertheless, the court decided that the passage should be read with the comma, so Casement's antics in Germany were treasonous, and he was sentenced to death. Casement himself wrote that he was hanged by a comma. We can use TFL to symbolize both readings of the passage and thus to provide a disambiguation. First, we need a symbolization key. A. Casement was adherent to the king's enemies in the realm. G. Casement gave aid and comfort to the king's enemies in the realm. B. Casement was adherent to the king's enemies abroad. H. Casement gave aid and comfort to the king's enemies abroad. The interpretation according to which Casement's behavior was not treasonous is this.
Math summary: this expression performs a logical OR operation. First, it takes two inputs, G and H, and performs a logical OR between them. The result of this operation is then used as one input to another logical OR operation, with A as the second input. The final output is the result of the logical OR between A and the result of the logical OR between G and H.
The interpretation which got him executed, on the other hand, can be symbolized by.
Math summary: this expression performs a logical OR operation. It takes two logical inputs, A and B, and combines them using a logical OR. Then it takes two other logical inputs, G and H, and combines them using a logical OR. Finally, it combines the result of the first OR operation with the result of the second OR operation, using another logical OR. The final output is the result of this last OR operation.
Remember that in the case we're dealing with, Casement was adherent to the king's enemies abroad. B is true, but not in the realm, and he did not give the king's enemies aid or comfort in or outside the realm. A, G, and H are false. One common source of structural ambiguity in English arises from its lack of parentheses. For instance, if I say, I like movies that are not long and boring, you will most likely think that what I dislike are movies that are long and boring. A less likely but possible interpretation is that I like movies that are both A, not long, and B, boring. The first reading is more likely because who likes boring movies? But what about I like dishes that are not sweet and flavorful? Here, the more likely interpretation is that I like savory, flavorful dishes. Of course, I could have said that better. For example, I like dishes that are not sweet yet flavorful. Similar ambiguities result from the interaction of and with or. For instance, suppose I ask you to send me a picture of a small and dangerous or stealthy animal. Would a leopard count? It's stealthy but not small. So it depends whether I'm looking for small animals that are dangerous or stealthy, leopard doesn't count, or whether I'm after either a small, dangerous animal or a stealthy animal of any size. These kinds of ambiguities are called scope ambiguities since they depend on whether or not a connective is in the scope of another. For instance, the sentence, Avengers, Endgame is not long and boring is ambiguous between 1. Avengers Endgame is not both long and boring. 2. Avengers Endgame is both not long and boring. Sentence 2 is certainly false since Avengers Endgame is over 3 hours long. Whether you think one is true depends on if you think it is boring or not. We can use the symbolization key. B. Avengers Endgame is boring. L. Avengers Endgame is long. Sentence 1 can now be symbolized as not open parenthesis L and B close parenthesis, whereas sentence 2 would be not L and B. In the first case, the and is in the scope of not. In the second case, not is in the scope of and. The sentence Tai Lung is small and dangerous or stealthy is ambiguous between 3. Tai Lung is either both small and dangerous or stealthy. 4. Tai Lung is both small and either dangerous or stealthy. We can use the following symbolization key. D. Tai Lung is dangerous. S. Tai Lung is small. D. Tai Lung is stealthy. The symbolization of sentence 3 is left parenthesis S and D right parenthesis or T, and that of sentence 4 is S and left parenthesis D or T right parenthesis. In the first, and is in the scope of or, and in the second, or is in the scope of and. Practice exercises. A. The following sentences are ambiguous. Give symbolization keys for each and symbolize the different readings. 1. Haskell is a birder and enjoys watching cranes. 2. The zoo has lions or tigers and bears. 3. The flower is not red or fragrant. Chapter 8. Use and mention. In this part we have talked a lot about sentences, so we should pause to explain an important and very general point. 8.1 Quotation Conventions. Consider these two sentences. Justin Trudeau is the Prime Minister. The expression Justin Trudeau is composed of 2 uppercase letters and 11 lowercase letters. When we want to talk about the Prime Minister, we use his name. When we want to talk about the Prime Minister's name, we mention that name, which we do by putting it in quotation marks. There is a general point here. When we want to talk about things in the world, we just use words. When we want to talk about words, we typically have to mention those words. We need to indicate that we are mentioning them rather than using them. To do this, some convention is needed. We can put them in quotation marks or display them centrally in the page, say, so this sentence. Justin Trudeau is the Prime Minister. Says that some expression is the Prime Minister. That's false. The man is the Prime Minister, his name isn't. Conversely, this sentence. Justin Trudeau is composed of 2 uppercase letters and 11 lowercase letters. Also says something false. Justin Trudeau is a man made of flesh rather than letters. One final example. Justin Trudeau is the name of Justin Trudeau. On the left-hand side here we have the name of a name. On the right-hand side we have a name. Perhaps this kind of sentence only occurs in logic textbooks, but it is true nonetheless. Those are just general rules for quotation, and you should observe them carefully in all your work. To be clear, the quotation marks here do not indicate reported speech. They indicate that you are moving from talking about an object to talking about a name of that object. 8.2 Object language and metalanguage. These general quotation conventions are very important for us. After all, we are describing a formal language here, TFL, and so we must often mention expressions from TFL. When we talk about a language, the language that we are talking about is called the object language. The language that we use to talk about the object language is called the metalanguage. For the most part, the object language in this chapter has been the formal language that we have been developing, TFL. The metalanguage is English, not conversational English exactly, but English supplemented with some additional vocabulary to help us get along. Now we have used uppercase letters as sentence letters of TFL.
Math summary. This represents a sequence of uppercase letters, some with numerical subscripts. It lists A, B, C, Z, then A with a subscript of 1, B with a subscript of 4, A with a subscript of 25, J with a subscript of 375, and so on.
These are sentences of the object language TFL. They are not sentences of English, so we must not say, for example, D is a sentence letter of TFL. Obviously, we are trying to come out with an English sentence that says something about the object language TFL, but D is a sentence of TFL and not part of English. So the preceding is gibberish, just like Schnee ist weiß is a German sentence. What we surely meant to say in this case is Schnee ist weiß is a German sentence. Equally, what we meant to say above is just D is a sentence letter of TFL. The general point is that whenever we want to talk in English about some specific expression of TFL, we need to indicate that we are mentioning the expression rather than using it. We can either deploy quotation marks or we can adopt some similar convention, such as placing it centrally in the page. 8.3 Metavariables. However, we do not just want to talk about specific expressions of TFL. We also want to be able to talk about any arbitrary sentence of TFL. Indeed, we had to do this in section 6.2 when we presented the inductive definition of a sentence of TFL. We used uppercase script letters to do this, namely.
Math summary. This lists a series of uppercase script letters, specifically A, B, C, D, and so on.
These symbols do not belong to TFL. Rather, they are part of our augmented metalanguage that we use to talk about any expression of TFL. To explain why we need them, recall the second clause of the recursive definition of a sentence of TFL. 2. If A is a sentence, then not A is a sentence. This talks about arbitrary sentences, if we had instead offered. If A is a sentence, then not sign A is a sentence. This would not have allowed us to determine whether not sign B is a sentence. To emphasize,
A is a symbol called a metavariable in augmented English, which we use to talk about expressions of TFL. A is a particular sentence letter of TFL.
But this last example raises a further complication concerning quotation conventions. We did not include any quotation marks in the second clause of our inductive definition. Should we have done so? The problem is that the expression on the right-hand side of this rule, that is, not sign A, is not a sentence of English since it contains not sign. So we might try to write 2. If A is a sentence, then not sign A is a sentence. But this is no good. Not sign A is not a TFL sentence since A is a symbol of augmented English rather than a symbol of TFL. What we really want to say is something like this. 2. If A is a sentence, then the result of concatenating the symbol not sign with the sentence A is a sentence. This is impeccable but rather long-winded. But we can avoid long-windedness by creating our own conventions. We can perfectly well stipulate that an expression like not sign A should simply be read directly in terms of rules for concatenation. So officially, the metalanguage expression not sign A simply abbreviates the result of concatenating the symbol not sign with the sentence A, and similarly, for expressions like open parenthesis math calligraphy A logical and math calligraphy B close parenthesis open parenthesis math calligraphy A logical or math calligraphy B close parenthesis, etc. 8.4 Quotation conventions for arguments. One of our main purposes for using TFL is to study arguments, and that will be our concern in Chapter 3. In English, the premises of an argument are often expressed by individual sentences and the conclusion by a further sentence. Since we can symbolize English sentences, we can symbolize English arguments using TFL. Or rather, we can use TFL to symbolize each of the sentences used in an English argument. However, TFL itself has no way to flag some of them as the premises and another as the conclusion of an argument. Contrast this with natural English, which uses words like so, therefore, etc. to mark that a sentence is the conclusion of an argument. So we need another bit of notation. Suppose we want to symbolize the premises of an argument with a sub 1 through a sub n and the conclusion with c, then we will write.
Math summary. This notation represents an argument in logic. It indicates that a set of premises, labeled premise 1 through premise n, leads to a conclusion, labeled conclusion. The symbol in between the premises and the conclusion indicates that the premises support the conclusion. The role of the symbol, therefore, is simply to indicate which sentences are the premises and which is the conclusion. Strictly, the symbol, therefore, will not be a part of the object language but of the metalanguage. As such, one might think that we would need to put quote marks around the TFL sentences which flank it. That is a sensible thought, but adding these quote marks would make things harder to read. Moreover, and as above, recall that we are stipulating some new conventions. So we can simply stipulate that these quote marks are unnecessary. That is, we can simply write. Math summary. This expression represents a logical inference. Given A and the implication that implies B, the conclusion is B.
Without any quotation marks to indicate an argument whose premises are symbolized by R and A to B, and whose conclusion is symbolized by B. Part 3 Truth Tables. Chapter 9. Characteristic Truth Tables. Any sentence of TFL is composed of sentence letters, possibly combined using sentential connectives. The truth value of the compound sentence depends only on the truth value of the sentence letters that comprise it. In order to know the truth value of D and E, for instance, you only need to know the truth value of D and the truth value of E. We introduced 5 connectives in Chapter 5, so we just need to explain how they map between truth values. For convenience, we abbreviate true with T and false with F, but to be clear, the two truth values are true and false. The truth values are not letters. Negation for any sentence A: if A is true, then not A is false, and if not A is true, then A is false. We can summarize this in the characteristic truth table for negation. Conjunction for any sentences A and B is true if and only if both A and B are true. We can summarize this in the characteristic truth table for conjunction. Note that conjunction is symmetrical. The truth value for A and B is always the same as the truth value for B and A. Disjunction: recall that always represents inclusive, or, so, for any sentences A and B, a B is true if and only if either A or B is true. We can summarize this in the characteristic truth table for disjunction.
Table summary. The table illustrates the truth values for a disjunction statement. The disjunction is true unless both components are false.
Like conjunction, disjunction is symmetrical. Conditional: we're just going to come clean and admit it. Conditionals are a mess in TFL. Exactly how much of a mess they are is philosophically contentious. We'll discuss a few of these subtleties in sections 10.3 and 12.5. For now, we are going to stipulate the following. Implies B is false if and only if it is true and B is false. We can summarize this with a characteristic truth table for the conditional. The conditional is asymmetric. You cannot swap the antecedent and consequent without changing the meaning of the sentence. A implies B and B implies A have different truth tables. Biconditional: since a biconditional is to be the same as the conjunction of the conditionals running in both directions, we will want the truth table for the biconditional to be.
Table summary. The truth table shows the biconditional is true when both inputs are the same, and false otherwise.
Unsurprisingly, the biconditional is symmetrical. Chapter 10. Truth Functional Connectives.
Table 1 summary. The truth table for negation indicates that when a statement is true, its negation is false, and vice versa. The truth table for a conditional statement shows that it is only false when the first part is true and the second part is false, otherwise it is true. Table conjunction summary. The conjunction of two true statements is true, while the conjunction is false if at least one of the statements is false.
10.1 The idea of truth functionality. Let's introduce an important idea.
A connective is truth functional if the truth value of a sentence with that connective, as its main logical operator, is uniquely determined by the truth value, S, of the constituent sentence, S.
Every connective in TFL is truth functional. The truth value of a negation is uniquely determined by the truth value of the unnegated sentence. The truth value of a conjunction is uniquely determined by the truth value of both conjuncts. The truth value of a disjunction is uniquely determined by the truth value of both disjuncts, and so on. To determine the truth value of some TFL sentence, we only need to know the truth value of its components. This is what gives TFL its name. It is truth functional logic. Many languages use connectives that are not truth functional. In English, for example, we can form a new sentence from any simpler sentence by prefixing it with "it is necessarily the case that." The truth value of this new sentence is not fixed solely by the truth value of the original sentence. For consider two true sentences.
Math summary. The expression adds 2 and 2, resulting in 4.
2. Shostakovich wrote 15 string quartets. Whereas it is necessarily the case that 2 plus 2 equals 4, it is not necessarily the case that Shostakovich wrote 15 string quartets. If Shostakovich had died earlier, he would have failed to finish quartet number 15. If he had lived longer, he might have written a few more. So, it is necessarily the case that is not truth functional. 10.2 Symbolizing versus translating. All of the connectives of TFL are truth functional, but more than that, they really do nothing but map us between truth values. When we symbolize a sentence or an argument in TFL, we ignore everything besides the contribution that the truth values of a component might make to the truth value of the whole. There are subtleties to our ordinary claims that far outstrip their mere truth values. Sarcasm, poetry, snide implicature, emphasis. These are important parts of everyday discourse, but none of this is retained in TFL. As remarked in Section 5, TFL cannot capture the subtle differences between the following English sentences. 1. Dana is a logician, and Dana is a nice person. 2. Although Dana is a logician, Dana is a nice person. 3. Dana is a logician despite being a nice person. 4. Dana is a nice person but also a logician. 5. Dana's being a logician notwithstanding, he is a nice person. All of the above sentences will be symbolized with the same TFL sentence, perhaps LN. Now we keep saying that we use TFL sentences to symbolize English sentences. Many other textbooks talk about translating English sentences into TFL. However, a good translation should preserve certain facets of meaning, and as we just saw, TFL just cannot do that. This is why we will speak of symbolizing English sentences rather than of translating them. This affects how we should understand our symbolization keys. Consider a key like L. Dana is a logician, and Dana is a nice person. Other textbooks will understand this as a stipulation that the TFL sentence L should mean that Dana is a logician, and that the TFL sentence N should mean that Dana is a nice person. But TFL just is totally unequipped to deal with meaning. The preceding symbolization key is doing no more and no less than stipulating that the TFL sentence L should take the same truth value as the English sentence Dana is a logician, whatever that might be, and that the TFL sentence N should take the same truth value as the English sentence Dana is a nice person, whatever that might be. When we treat a TFL sentence as symbolizing an English sentence, we are stipulating that the TFL sentence is to take the same truth value as that English sentence. 10.3 Indicative versus Subjunctive Conditionals. We want to bring home the point that TFL can only deal with truth functions by considering the case of the conditional. When we introduced the characteristic truth table for the material conditional in Section 9, we did not say anything to justify it. Let's now offer a justification, which follows Dorothy Edgington. Suppose that Lara has drawn some shapes on a piece of paper and colored some of them in. We have not seen them, but nevertheless claim. If any shape is gray, then that shape is also circular. As it happens, Lara has drawn the following. In this case, our claim is surely true. Shapes C and D are not gray and so can hardly present counterexamples to our claim. Shape A is gray, but fortunately it is also circular. So our claim has no counterexamples. It must be true. That means that each of the following instances of our claim must be true too. If A is gray, then it is circular consequent. If C is gray, then it is circular, false antecedent, true consequent. If D is gray, then it is circular, false antecedent, false consequent. However, if Lara had drawn a fourth shape thus, then our claim would have been false, so this claim must also be false.
Image summary. The image shows a diagram consisting of shapes, specifically circles and diamonds, with some shapes shaded and others not. The diagram illustrates a logical argument about the relationship between the color of a shape and its form. The argument suggests that if a shape is shaded, it must be a circle. The diagram presents examples and counterexamples to test the validity of this statement. The presence of a shaded diamond would invalidate the claim, while the absence of such a shape supports it. The diagram serves as a visual aid to understand concepts of logical implication, counterexamples, and truth conditions.
If B is gray, then it is circular, true antecedent, false consequent. Now recall that every connective of TFL has to be truth functional. This means that merely the truth values of the antecedent and consequent must uniquely determine the truth value of the conditional as a whole. Thus, from the truth values of our four claims, which provide us with all possible combinations of truth and falsity in antecedent and consequent, we can read off the truth table for the material conditional. What this argument shows is that right arrow is the best candidate for a truth functional conditional. Otherwise put, it is the best conditional that TFL can provide. But is it any good as a surrogate for the conditionals we use in everyday language? Consider two sentences. 1. If Hillary Clinton had won the 2016 election, then she would have been the first woman president of the USA. 2. If Hillary Clinton had won the 2016 election, then she would have turned into a helium-filled balloon and floated away into the night sky. Sentence 1 is true, sentence 2 is false, but both have false antecedents and false consequence. Hillary did not win, she did not become the first woman president of the US, and she did not fill with helium and float away. So the truth value of the whole sentence is not uniquely determined by the truth value of the parts. The crucial point is that sentences 1 and 2 employ subjunctive conditionals, rather than indicative conditionals. They ask us to imagine something contrary to fact. After all, Hillary Clinton lost the 2016 election, and then ask us to evaluate what would have happened in that case. Such considerations simply cannot be tackled using right arrow. We will say more about the difficulties with conditionals in section 12.5. For now, we will content ourselves with the observation that right arrow is the only candidate for a truth functional conditional for TFL, but that many English conditionals cannot be represented adequately using right arrow. TFL is an intrinsically limited language. Chapter 11. Complete truth tables. So far, we have used symbolization keys to assign truth values to TFL sentences indirectly. For example, we might say that the TFL sentence B is to be true if Big Ben is in London. Since Big Ben is in London, this symbolization would make B true, but we can also assign truth values directly. We can simply stipulate that B is to be true or stipulate that it is to be false. Such stipulations are called valuations. A valuation is any assignment of truth values to particular sentence letters of TFL. The power of truth tables lies in the following. Each row of a truth table represents a possible valuation. The complete truth table represents all possible valuations. And the truth table provides us with a means to calculate the truth value of complex sentences on each possible valuation. But all of this is easiest to explain by example. 11.1 A worked example. Consider the sentence left parenthesis H and I right parenthesis implies H. There are 4 possible ways to assign true and false to the sentence letter H and I 4 valuations, which we can represent as follows.
Table summary. The table shows all possible combinations of truth values for 2 variables, and the resulting truth value of a logical expression involving those variables. The table illustrates how the truth value of the expression varies depending on the truth values of the individual variables.
To calculate the truth value of the entire sentence, open parenthesis H and I close parenthesis implies H, we first copy the truth values for the sentence letters and write them underneath the letters in the sentence.
Table summary. The table presents a truth table for the logical statement. The truth value of the statement depends on the truth values of H and I. The statement is true in most cases, except when H is false and I is true, or when both H and I are false.
Now consider the subsentence H and 1. This is a conjunction A and B, with H as A and with I as B. The characteristic truth table for conjunction gives the truth conditions for any sentence of the form A and B, whatever A and B might be. It represents the point that a conjunction is true if both conjuncts are true. In this case, our conjuncts are just H and I. They are both true on and only on the first line of the truth table. Accordingly, we can calculate the truth value of the conjunction on all 4 rows.
Table summary. The table illustrates the truth values for a conjunction and its implication, showing how the truth value of the combined statement varies depending on the truth values of its components. The truth value of the conjunction is only true when both components are true. The truth value of the implication depends on the truth values of the conjunction and H.
Now the entire sentence that we are dealing with is a conditional. A implies B, with H and I as A and with H as B on the second row. For example, H and I is false and H is true. Since a conditional is true when the antecedent is false, we write a T in the second row underneath the conditional symbol. We continue for the other 3 rows and get this.
Table summary. The table presents a truth table for a conditional statement. The conditional statement is true in most cases, with falsity only arising when the first variable is true and the second variable is false.
The conditional is the main logical operator of the sentence, so the column of T's underneath the conditional tells us that the sentence left parenthesis H and I right parenthesis implies H is true regardless of the truth values of H and I. They can be true or false in any combination, and the compound sentence still comes out true. Since we have considered all 4 possible assignments of truth and falsity to H and I, since that is, we have considered all the different valuations, we can say that left parenthesis H and I right parenthesis implies H is true on every valuation. In this example, we have not repeated all of the entries in every column in every successive table. When actually writing truth tables on paper, however, it is impractical to erase whole columns or rewrite the whole table for every step. Although it is more crowded, the truth table can be written in this way.
Table summary. The table illustrates that the conditional statement is true regardless of the truth values of its components. The truth values of the conditional statement are predominantly true, with some instances of falsity, depending on the specific combination of truth values of the components.
Most of the columns underneath the sentence are only there for bookkeeping purposes. The column that matters most is the column underneath the main logical operator for the sentence, since this tells you the truth value of the entire sentence. We have emphasized this by putting this column in bold. When you work through truth tables yourself, you should similarly emphasize it, perhaps by highlighting. 11.2 Building complete truth tables. A complete truth table has a line for every possible assignment of true and false to the relevant sentence letters. Each line represents a valuation, and a complete truth table has a line for all the different valuations. The size of the complete truth table depends on the number of different sentence letters in the table. A sentence that contains only one sentence letter requires only 2 rows, as in the characteristic truth table for negation. This is true even if the same letter is repeated many times, as in the sentence, left bracket, left parenthesis, C double arrow, C right parenthesis, arrow, C right bracket, and not left parenthesis, C arrow, C right parenthesis. The complete truth table requires only 2 lines because there are only 2 possibilities. C can be true or it can be false. The truth table for this sentence looks like this.
Math summary. This truth table evaluates a logical expression. The table shows the truth values of the expression for different truth assignments to the variable C. The first column lists the possible truth values of C, which are true and false. The subsequent columns evaluate sub-expressions. The second column evaluates the expression C, if and only if C, then that result implies C. The third column evaluates the negation of C implies C. The final column combines the results of the second and third columns, using a logical AND.
Looking at the column underneath the main logical operator, we see that the sentence is false on both rows of the table. That is, the sentence is false regardless of whether C is true or false. It is false on every valuation. There will be 4 lines in the complete truth table for a sentence containing 2 sentence letters, as in the characteristic truth tables, or the truth table for open parenthesis, H and I, close parenthesis, implies H prime. There will be 8 lines in the complete truth table for a sentence containing 3 sentence letters, for example.
Table summary. The truth value of a logical expression depends on the truth values of its components, with the truth table showing all possible combinations and their resulting truth values. The final column shows the truth value of the expression for each combination of the variables.
From this table, we know that the sentence M and N or P can be true or false depending on the truth values of M, N, and P. A complete truth table for a sentence that contains 4 different sentence letters requires 16 lines, 5 letters 32 lines, 6 letters 64 lines, and so on. To be perfectly general, if a complete truth table has n different sentence letters, then it must have 2 sub-n lines. In order to fill in the columns of a complete truth table, begin with the rightmost sentence letter and alternate between T and F. In the next column to the left, write 2 T's, write 2 F's, and repeat. For the third sentence letter, write 4 T's followed by 4 F's. This yields an 8-line truth table like the one above. For a 16-line truth table, the next column of sentence letters should have 8 T's followed by 8 F's. For a 32-line table, the next column would have 16 T's followed by 16 F's, and so on. 11.3 More about brackets. Consider these 2 sentences.
Math summary. The expression represents 2 logical statements. The first statement takes the logical AND of 2 input values, then takes the result and performs a logical AND with a third input value. The second statement takes the logical AND of the second and third input values, and then performs a logical AND with the first input value.
These are truth functionally equivalent. Consequently, it will never make any difference from the perspective of truth value, which is all that TFL cares about. See section 10, which of the 2 sentences we assert or deny. Even though the order of the brackets does not matter as to their truth, we should not just drop them. The expression.
Math summary. This expression represents a logical conjunction operation. It combines 3 logical inputs, A, B, and C, using the AND operator. The result is true only if all 3 inputs are true, otherwise the result is false.
Is ambiguous between the 2 sentences above. The same observation holds for disjunctions. the following sentences are logically equivalent.
Math summary. The expression represents two logical disjunction operations. The first expression performs a disjunction between input A and input B, and then performs a disjunction between the result and input C. The second expression performs a disjunction between input B and input C, and then performs a disjunction between input A and the result.
But we should not simply write.
Math summary. The expression performs a logical disjunction operation. It takes three inputs, A, B, and C, and outputs true if any of the inputs are true, and false only if all inputs are false.
In fact, it is a specific fact about the characteristic truth table of, and that guarantees that any two conjunctions or disjunctions of the same sentences are truth functionally equivalent, however you place the brackets. This is only true of conjunctions and disjunctions, however. The following two sentences have different truth tables.
Math summary. The expression represents two logical implications. The first implication takes the result of A implies B as input, and then uses that result to imply C. The second implication takes A as input to imply the result of B implies C.
So if we were to write,
Math summary. The expression represents a sequence of implications. The first implication takes an input A and produces an intermediate result. This intermediate result then serves as the input for a second implication, which produces the final outputs.
it would be dangerously ambiguous. Leaving out brackets in this case would be disastrous. Equally, these sentences have different truth tables.
Math summary. The expression describes two logical statements. The first statement performs a logical OR operation on inputs A and B, and then performs a logical AND operation on the result and input C. The second statement performs a logical AND operation on inputs B and C, and then performs a logical OR operation on input A and the result.
So if we were to write,
Math summary. This expression represents a logical operation. It performs a logical OR between the first input, A, and the result of a logical AND operation between the second input, B, and the third input. See, the final output is the result of this combined logical operation.
it would be dangerously ambiguous. Never write this. The moral is never drop brackets except the outermost ones. Practice exercises. A. Offer complete truth tables for each of the following. 1. A maps to A. 2. C implies not C. 3. A if and only if B, if and only if not, open parenthesis, A if and only if not B, close parenthesis. 4. Left parenthesis A implies B, right parenthesis, or left parenthesis B implies a right parenthesis. 5. A and B implies B or A. 6. Not open parenthesis A or B, close parenthesis, if and only if open parenthesis not A and not B, close parenthesis. The ceiling of open parenthesis A and B, close parenthesis, and not open parenthesis A and B, close parenthesis, close sailing, and C. 8. Left bracket left parenthesis A and B right parenthesis and C right bracket implies B. 9. Not open bracket open parenthesis C or a close parenthesis or B close bracket. B. Check all the claims made in introducing the new notational conventions in section 11.3, that is, show that 1. A and B and C and A and B and C have the same truth table. 2. Open parenthesis A or B close parenthesis or C and open parenthesis A or open parenthesis B or C close parenthesis have the same truth table. 3. A or B and C and O or B and C do not have the same truth table. 4. A implies B implies C and A implies B implies C do not have the same truth table. Also check whether 5. A double arrow B double arrow C and a double arrow B double arrow C have the same truth table. See write complete truth tables for the following sentences and mark the column that represents the possible truth values for the whole sentence. 1. Not open parenthesis S if and only if open parenthesis P implies S close parenthesis close parenthesis. 2. Not open bracket open parenthesis X and Y close parenthesis or open parenthesis X or Y close parenthesis close bracket. 3. A implies B, if and only if not B, if and only if not A. 4. C if and only if D or E and not C. 5. Not of left parenthesis G and left parenthesis B and H right parenthesis if and only if left parenthesis G or left parenthesis B or H right parenthesis right parenthesis. D. Write complete truth tables for the following sentences and mark the column that represents the possible truth values for the whole sentence. 1 left parenthesis D and not D right parenthesis implies G. 2 not P or not M if and only if M. 3 not of not A and not B. 4 left parenthesis D and R right parenthesis implies I right bracket implies not left parenthesis D or R right parenthesis. 5 not open bracket D if and only if O close bracket if and only if A implies open bracket not D and O close bracket. If you want additional practice, you can construct truth tables for any of the sentences and arguments in the exercises for the previous chapter. Chapter 12. Semantic Concepts. In the previous section, we introduced the idea of evaluation and showed how to determine the truth value of any TFL sentence on any valuation using a truth table. In this section, we will introduce some related ideas and show how to use truth tables to test whether or not they apply. 12.1 Tautologies and Contradictions. In Section 3, we explained necessary truth and necessary falsity. Both notions have surrogates in TFL. We will start with a surrogate for necessary truth. A is a tautology if it is true on every valuation. We can use truth tables to decide whether a sentence is a tautology. If the sentence is true on every line of its complete truth table, then it is true on every valuation, so it is a tautology. In the example of Section 11, H and 1 to H is a tautology. This is only, though, a surrogate for necessary truth. There are some necessary truths that we cannot adequately symbolize in TFL. One example is 2 plus 2 equals 4. This must be true, but if we try to symbolize it in TFL, the best we can offer is in sentence letter, and no sentence letter is a tautology. Still, if we can adequately symbolize some English sentence using a TFL sentence, which is a tautology, then that English sentence expresses a necessary truth. We have a similar surrogate for necessary falsity. A is a contradiction in TFL if it is false on every valuation. We can use truth tables to decide whether a sentence is a contradiction. If the sentence is false on every line of its complete truth table, then it is false on every valuation, so it is a contradiction. In the example of Section 11, C double arrow C and not C arrow C is a contradiction. 12.2 Equivalence. Here is a similar useful notion. A and B are equivalent in TFL if, for every valuation, their truth values agree, that is, if there is no valuation in which they have opposite truth values. We have already made use of this notion in effect in Section 11.3. The point was that left parenthesis A and B right parenthesis and C and A and left parenthesis B and C right parenthesis are equivalent. Again, it is easy to test for equivalence using truth tables. Consider the sentences not left parenthesis P or Q right parenthesis and not P and not Q. Are they equivalent? To find out, we construct a truth table.
Math summary. This truth table evaluates the equivalence of two logical expressions. It takes two input truth values, P and Q first. It computes the negation of the disjunction of P and Q second. It computes the conjunction of the negations of P and Q. The table then compares the resulting truth values for each combination of P and Q to determine if the two expressions are logically equivalent.
Look at the columns for the main logical operators, negation for the first sentence, conjunction for the second. On the first three rows, both are false. On the final row, both are true. Since they match on every row, the two sentences are equivalent. 12.3 Satisfiability. In Section 3, we said that sentences are jointly possible if it is possible for all of them to be true at once. We can offer a surrogate for this notion too. A sub 1, a sub 2 through a sub n are jointly satisfiable in TFL if and only if there is some valuation which makes them all true. Derivatively, sentences are jointly unsatisfiable if no valuation makes them all true. Again, it is easy to test for joint satisfiability using truth tables. 12.4 Entailment and Validity. The following idea is closely related to that of joint satisfiability. The sentences a sub 1, a sub 2 through a sub n entail in TFL the sentence C if no valuation of the relevant sentence letters makes all of a sub 1, a sub 2 through a sub n true and C false. Again, it is easy to test this with a truth table. To check whether not L implies open parenthesis J or L close parenthesis, and not L entail J, we simply need to check whether there is any valuation which makes both not L implies open parenthesis J or L close parenthesis, and not L true whilst making J false. So we use a truth table.
Table summary. The table represents a truth table, evaluating the logical statement. The truth values of the statement and its components vary depending on the truth values of J and L.
The only row on which both not L implies open parenthesis J or L close parenthesis and not L are true is the second row, and that is a row on which J is also true. So not L implies open parenthesis J or L close parenthesis and not L entail J. We now make an important observation. If a sub 1, a sub 2, all the way to a sub n entail C in TFL, then a sub 1, a sub 2, all the way to a sub n, therefore C is valid. Here's why. If a sub 1, a sub 2 through a sub n entail C, then there is no valuation which makes all of a sub 1, a sub 2 through a sub n true and also makes C false. Any case in which all of a sub 1, a sub 2 through a sub n are true and C is false would generate a valuation with this property. Take the truth value of any sentence letter to be just the truth value of the corresponding sentence in that case. Since there is no such valuation, there is no case in which all of a sub 1, a sub 2 through a sub n are true and C is false. But this is just what it takes for an argument with premises a sub 1, a sub 2 through a sub n and conclusion C to be valid. In short, we have a way to test for the validity of English arguments. First, we symbolize them in TFL, then we test for entailment in TFL using truth tables. 12.5 The limits of these tests. This is an important milestone, a test for the validity of arguments. However, we should not get carried away just yet. It is important to understand the limits of our achievement. We will illustrate these limits with 3 examples. First, consider the argument. 1. Daisy has 4 legs, so Daisy has more than 2 legs. To symbolize this argument in TFL, we would have to use 2 different sentence letters, perhaps F and T, for the premise and the conclusion respectively. Now, it is obvious that F does not entail T, but the English argument is surely valid. Second, consider the sentence. 2. Jan is neither bald nor not bald. To symbolize this sentence in TFL, we would offer something like not sign J, not J. This a contradiction, check this with a truth table, but sentence 2 does not itself seem like a contradiction, for we might have happily added Jan is on the borderline of baldness. Third, consider the following sentence. 3. It's not the case that if God exists, she answers malevolent prayers. Symbolizing this in TFL, we would offer something like not open parenthesis G implies M close parenthesis. Now not open parenthesis G implies M close parenthesis entails G. Again, check this with a truth table. So if we symbolize sentence 3 in TFL, it seems to entail that God exists. But that's strange. Surely even an atheist can accept sentence 3 without contradicting herself. One lesson of this is that the symbolization of 3 as not sign G to M shows that 3 does not express what we intend. Perhaps we should rephrase it as 3. If God exists, she does not answer malevolent prayers. And symbolize 3 as G to not sign M. Now, if atheists are right and there is no God, then G is false and so G to not sign M is true and the puzzle disappears. However, if G is false, G to M, that is, if God exists, she answers malevolent prayers, is also true. In different ways, these 4 examples highlight some of the limits of working with a language, like TFL, that can only handle truth-functional connectives. Moreover, these limits give rise to some interesting questions in philosophical logic. The case of Jan's baldness or otherwise raises the general question of what logic we should use when dealing with vague discourse. The case of the atheist raises the question of how to deal with the so-called paradoxes of the material conditional. Part of the purpose of this course is to equip you with the tools to explore these questions of philosophical logic. But we have to walk before we can run. We have to become proficient in using TFL before we can adequately discuss its limits and consider alternatives. 12.6 The double turnstile. In what follow, we will use the notion of entailment rather a lot in this book. It will help us then to introduce a symbol that abbreviates it. Rather than saying that the TFL sentences a sub 1, a sub 2, and a sub n together entail C, we will abbreviate this by.
Math summary. This expression represents logical entailment. It states that a collection of sentences, from the first sentence to the nth sentence, logically entails a conclusion sentence. In other words, the conclusion sentence is true whenever all the sentences in the collection are true.
The symbol is known as the double turnstile, since it looks like a turnstile with 2 horizontal beams. Let's be clear, pound is not a symbol of TFL. Rather, it is a symbol of our metalanguage, augmented English. Recall the difference between object language and metalanguage from section 8. So the metalanguage sentence.
Math summary. This expression represents an entailment in logic. It states that given the premise P, and the premise if P then Q, it follows that Q is true.
Is just an abbreviation for this metalanguage sentence. The TFL sentence is P and P implies Q until Q. Note that there is no limit on the number of TFL sentences that can be mentioned before the symbol F. Indeed, we can even consider the limiting case.
Math summary. This expression represents logical entailment. It states that the set of sentences on the left side of the double turnstile logically entails the sentence on the right side. In this specific case, it means that the set of sentences is empty and therefore entails the sentence represented by the symbol.
This says that there is no valuation, which makes all the sentences mentioned on the left side of pound true whilst making euros false. Since no sentences are mentioned on the left side of pound in this case, this just means that there is no valuation, which makes script C false. Otherwise put, it says that every valuation makes script C true. Otherwise put, it says that script C is a tautology. Equally, to say that script A is a contradiction, we can write.
Math summary. This expression represents a semantic entailment. It asserts that alpha entails something, meaning that in every possible valuation or interpretation where alpha is true, then what alpha entails is also true.
For this says that no valuation makes a true. Sometimes we will want to deny that there is a tautological entailment and say something of this shape.
Math summary. This expression asserts that it is not the case that a set of premises logically entails a conclusion. In other words, the conclusion does not necessarily follow from the premises.
In that case, we can just slash the turnstile through and write.
Math summary. This expression states that a set of elements from element 1 to element n are not contained within a set C.
This means that some valuation makes all of a sub 1 through a sub n true whilst making C false. But note that it does not immediately follow that a sub 1 through a sub n models not C, for that would mean that every valuation makes all of a sub 1 through a sub n true whilst making C false. 12.7 F versus right arrow. We now want to compare and contrast circled minus and implies. Observe, a model C if and only if no valuation of the sentence letters makes a true and C false. Observe, A to C is a tautology if and only if no valuation of the sentence letters makes it to C false. Since a conditional is true except when its antecedent is true and its consequent false, A to C is a tautology if and only if no valuation makes a true and C false. Combining these two observations, we see that A to C is a tautology if and only if a model C, but there is a really important difference between models and to. Indeed, when right arrow is flanked with two TFL sentences, the result is a longer TFL sentence. By contrast, when we form a metalinguistic sentence that mentions the surrounding TFL sentences. Practice exercises. A. Revisit your answers to section 11a. Determine which sentences were tautologies, which were contradictions, and which were neither tautologies nor contradictions. B. Use truth tables to determine whether these sentences are jointly satisfiable or jointly unsatisfiable. 1 implies A, not implies not A and A or A. 2 or B, A implies C, B implies C. 3 B and C or A implies B, not B or C. 4 if and only if B or C, C implies not A implies not B. C. Use truth tables to determine whether each argument is valid or invalid. 1 implies therefore A. 2 implies open parenthesis A and not a close parenthesis, therefore not A. 3 or B implies A, therefore not A implies not B. 4 or B, B or C, not a therefore B and C. 5 B and A implies C, C and A implies B, therefore C and B implies A. D. Determine whether each sentence is a tautology, a contradiction, or a contingent sentence using a complete truth table. 1 not B and B. 2 not D or D. 3 left parenthesis A and B right parenthesis or left parenthesis B and a right parenthesis. 4 not open bracket implies open parenthesis B implies a close parenthesis close bracket. 5 if and only if open bracket implies open parenthesis B and not B close parenthesis close bracket.
Math summary. This expression evaluates a logical implication. It takes the logical biconditional of the logical conjunction of A and B as input. The result of this biconditional is then used as the antecedent in a logical implication, where the consequent is the logical implication of implying B. The entire expression determines the truth value of this complex logical statement.
Determine whether each the following sentences are logically equivalent using complete truth tables. If the two sentences really are logically equivalent, write equivalent. Otherwise write not equivalent. 1. A and not a 2. A and not B if and only if B 3. Left bracket A or B right bracket or C right bracket and left bracket A or left bracket B or C right bracket 4. Or B and C and A or B and A or C. 5. A and A or B implies B and A implies BF. Determine whether each the following sentences are logically equivalent using complete truth tables. If the two sentences really are equivalent, write equivalent. Otherwise write not equivalent. 1. A maps to A and A is equivalent to a 2. Not, open parenthesis, A implies B, close parenthesis, and not A implies not B3, or B and not implies B4. Left parenthesis A implies B right parenthesis implies C and A implies left parenthesis B implies C right parenthesis 5. If and only if, open parenthesis, B if and only if C, close parenthesis, and, open parenthesis, B and C, close parenthesis G. Determine whether each collection of sentences is jointly satisfiable or jointly unsatisfiable using a complete truth table. 1. A and not B. Not A implies B, B implies a 2. A or B implies not A, B implies not B3. Not open parenthesis not A or B close parenthesis A implies not C. A implies open parenthesis B implies C close parenthesis 4. A implies B and not B5. A implies open parenthesis B implies C close parenthesis comma open parenthesis A implies B close parenthesis implies C comma A implies CH. Determine whether each collection of sentences is jointly satisfiable or jointly unsatisfiable using a complete truth table.
Math summary. This statement involves a collection of logical sentences. The first sentence is the negation of B. The second sentence is implies B. The third sentence is A. The task is to determine if this collection of sentences is jointly satisfiable or jointly unsatisfiable using a complete truth table.
2. Not open parenthesis A or B close parenthesis A if and only if B implies a 3. A or B not B implies not a 4. If and only if B not B or not A implies B5. Left parenthesis A or B right parenthesis or C, not or not B not C or not B. Determine whether each argument is valid or invalid using a complete truth table. 1. A implies B therefore a 2. A if and only if B if and only if C A if and only if C3. A implies B, A implies C therefore B implies C4. A implies B implies a therefore A if and only if BJ. Determine whether each argument is valid or invalid using a complete truth table. 1. Or open bracket implies open parenthesis, A if and only if A close parenthesis close bracket therefore 2. A or B or C not B therefore A and C3. Implies B not a therefore not B4. A B therefore not of open parenthesis A implies not B close parenthesis 5. Not A and B, A or B, if and only if B therefore CK. Answer each of the questions below and justify your answer. 1. Suppose that script A and script B are logically equivalent. What can you say about script A double arrow script B? 2. Suppose that A and B implies C is neither a tautology nor a contradiction. What can you say about whether A, B therefore C is valid? 3. Suppose that A, B and C are jointly unsatisfiable. What can you say about A and B and C? 4. Suppose that it is a contradiction. What can you say about whether A, B models C? 5. Suppose that script C is a tautology. What can you say about whether script A, script B models script C? 6. Suppose that A and B are logically equivalent. What can you say about A or B? 7. Suppose that A and B are not logically equivalent. What can you say about a logical or B? Consider the following principle. Suppose A and B are logically equivalent. Suppose an argument contains A either as a premise or as the conclusion. The validity of the argument would be unaffected if we replaced A with B. Is this principle correct? Explain your answer. Chapter 13. Truth Table Shortcuts. With practice, you will quickly become adept at filling out truth tables. In this section, we consider and justify some shortcuts which will help you along the way. 13.1 Working through truth tables. You will quickly find that you do not need to copy the truth value of each sentence letter, but can simply refer back to them, so you can speed things up by writing.
Table summary. The truth values of the expression are determined based on the truth values of P and Q. The expression is true when P is false and Q is true, and when both P and Q are true, or when P is true and Q is false, the expression is false.
You also know for sure that a disjunction is true whenever one of the disjuncts is true. So if you find a true disjunct, there is no need to work out the truth values of the other disjuncts. Thus you might offer.
Table summary. The truth table demonstrates the evaluation of a logical expression for different combinations of truth values for P and Q, showing the resulting truth value of the expression.
Equally, you know for sure that a conjunction is false whenever one of the conjuncts is false. So if you find a false conjunct, there is no need to work out the truth value of the other conjunct. Thus you might offer.
Math summary. This truth table evaluates a logical expression. It takes two Boolean inputs, P and Q. It computes the negation of P and the negation of Q, and then computes the conjunction of that result with the negation of P. The table shows the resulting truth value for all possible combinations of the inputs P and Q.
A similar shortcut is available for conditionals. You immediately know that a conditional is true if either its consequent is true or its antecedent is false. Thus you might present.
Math summary. This truth table evaluates a logical proposition. It takes two Boolean inputs, P and Q. It then calculates the result of the expression. If P implies Q, then that result implies P, and finally that result implies P again. The truth table shows that when P is false and Q is true, the final result is true. Also, when P is false and Q is false, the final result is true.
So open parenthesis P implies Q close parenthesis implies P is a tautology. In fact, it is an instance of Peirce's law named after Charles Sanders Peirce. 13.2 Testing for validity and entailment. In section 12, we saw how to use truth tables to test for validity. In that test, we look for bad lines, lines where the premises are all true and the conclusion is false. Now, if the conclusion is true on a line, then that line is not bad, and we don't need to evaluate anything else on that line to confirm this. If any premise is false on a line, then that line is not bad, and we don't need to evaluate anything else on that line to confirm this. With this in mind, we can speed up our tests for validity quite considerably. Let's consider how we might test the following.
Math summary. This expression represents a logical argument. It states that if not L is true, then J or L is true, and not L is given as true, therefore J is concluded to be true.
The first thing we should do is evaluate the conclusion. If we find that the conclusion is true on some line, then that is not a bad line, so we can simply ignore the rest of the line. So after our first stage, we are left with something like this, where the blanks indicate that we won't bother with any more investigation since the line is not bad, and the question marks indicate that we need to keep digging.
Table summary. The table shows a partially completed truth table. Some values are already determined, while others are marked with question marks to indicate further investigation is needed. Some rows are left blank, indicating no further investigation is necessary.
The easiest premise to evaluate is the second, so we do that next and get.
Table summary. The truth table illustrates a method to test validity, where certain lines are ignored if the conclusion is true, and only lines needing further investigation are marked. The table shows how evaluating the conclusion and premises can streamline the truth table process.
Note that we no longer need to consider the third line on the table. It is certainly not bad because some premise is false on that line. And finally, we complete the truth table.
Table summary. The truth table shows the possible truth values for a conditional statement and its components. The table indicates when the conditional statement is true or false based on the truth values of J and L.
The truth table has no bad lines, so the argument is valid. Any valuation which makes every premise true makes the conclusion true. It's probably worth illustrating the tactic again. Consider this argument.
Math summary. This expression represents a logical argument. It states that if A or B is true, and it is not the case that both B and C are true, then it follows that O or not C is true.
Again, we start by evaluating the conclusion. Since this is a disjunction, it is true whenever either disjunct is true, so we can speed things along a bit.
Table summary. The truth table shows the truth values for different combinations of A, B, and C, and evaluates the expressions of B, not sign BC, and a not C. The truth values for a not C are mostly true except in two cases where it is false. The values for a B and not sign BC are not fully determined.
We can now ignore all but the two lines where the sentence after the turnstile is false. Evaluating the two sentences on the left of the turnstile, we get
Table summary. The table presents a truth table analysis, where certain rows are filled in completely, while others are left incomplete, demonstrating a shortcut method. Some columns are fully computed and have a mix of true and false values. Other columns have some values computed.
So the entailment holds, and our shortcuts saved us a lot of work. We have been discussing shortcuts in testing for validity, but exactly the same shortcuts can be used in testing for entailment. By employing a similar notion of bad lines, you can save yourself a huge amount of work. Practice exercises. A. Using shortcuts, check whether each sentence is a tautology, a contradiction, or neither. 1. Not B and B. 2. Not D or D. 3. Left parenthesis A and B, right parenthesis or left parenthesis B, and a right parenthesis. 4. Not open bracket implies open parenthesis B implies a close parenthesis close bracket. 5. If and only if open bracket A implies open parenthesis B and not B close parenthesis close bracket. 6. Not open parenthesis A and B close parenthesis if and only if A. 7. Implies B or C. 8. Left parenthesis A and not a right parenthesis implies left parenthesis B or C right parenthesis. 9. B and D if and only if open bracket A if and only if open parenthesis A or C close parenthesis close bracket. Chapter 14. Partial truth tables. Sometimes we do not need to know what happens on every line of a truth table. Sometimes just a line or two will do. Tautology. In order to show that a sentence is a tautology, we need to show that it is true on every valuation. That is to say, we need to know that it comes out true on every line of the truth table, so we need a complete truth table. To show that a sentence is not a tautology, however, we only need one line, a line on which the sentence is false. Therefore, in order to show that some sentence is not a tautology, it is enough to provide a single valuation, a single line of the truth table which makes the sentence false. Suppose that we want to show that the sentence, open parenthesis U and T close parenthesis implies open parenthesis S and W close parenthesis, is not a tautology. We set up a partial truth table.
Math summary. This is a truth table with 4 input variables, S, T, U, and W. The table is set up to evaluate logical expressions based on different combinations of truth values assigned to these input variables.
We have only left space for one line rather than 16 since we are only looking for one line on which the sentence is false, hence also the F. The main logical operator of the sentence is a conditional. In order for the conditional to be false, the antecedent must be true and the consequent must be false. So we fill these in on the table.
Math summary. This truth table evaluates a logical conditional statement. The inputs are logical variables S, T, U, and W. The statement is if U and T, then S and W. The table shows a case where S is true, T is false, and U is false. This leads to the conditional statement being true.
In order for the left parenthesis U and T right parenthesis to be true, both U and T must be true.
Math summary. This truth table evaluates a conditional statement. The goal is to determine the conditions under which the statement is false. The table starts by assigning true values to variables T and U to make the conditional statement false. The antecedent must be true and the consequent must be false. The antecedent involves a conjunction of U and T, which is true when both are true. The consequent involves a conjunction of S and W to make the consequent false. At least one of S or W must be false. In this case, S is assigned false and W is assigned false. The final result is a row in the truth table where T and U are true, S and W are false, and the entire conditional statement is false. Now we just need to make S and W false. To do this, we need to make at least one of S and W false. We can make both S and W false if we want. All that matters is that the whole sentence turns out false on this line.
Making an arbitrary decision, we finish the table in this way.
Math summary, the expression evaluates a conditional statement. The antecedent is the logical AND of variables u and t, the consequent is the logical AND of variables s and w. The entire conditional statement, if u and t, then s and w, evaluates to false when u and t are true, and s and w are false.
We now have a partial truth table which shows that u and t implies s and w is not a tautology. Put otherwise, we have shown that there is a valuation which makes u and t implies s and w false, namely the valuation which makes s false, t true, u true, and w false. Contradictions, showing that something is a contradiction in TFL requires a complete truth table. We need to show that there is no valuation which makes the sentence true. That is, we need to show that the sentence is false on every line of the truth table. However, to show that something is not a contradiction, all we need to do is find a valuation which makes the sentence true, and a single line of a truth table will suffice. We can illustrate this with the same example.
Math summary, the expression represents a partial truth table evaluating a logical implication. The implication states, if u and t are both true, then s and w are both true. The truth table shows one possible assignment of truth values to the variables s, t, u, and w, where s is false, t is true, u is false, and w is false. Under this assignment, the implication evaluates to true.
To make the sentence true, it will suffice to ensure that the antecedent is false. Since the antecedent is a conjunction, we can just make one of them false. Making an arbitrary choice, let's make u false. We can then assign any truth value we like to the other sentence letters.
Math summary, the expression evaluates a logical implication. The implication's antecedent is the logical AND of input u and input t. The implication's consequent is the logical AND of input s and input w given specific truth values for s, t, u, and w. The entire implication is evaluated to determine its truth value, resulting in a final truth value of false.
Equivalence, to show that two sentences are equivalent, we must show that the sentences have the same truth value on every valuation, so this requires a complete truth table. To show that two sentences are not equivalent, we only need to show that there is a valuation on which they have different truth values, so this requires only a one-line partial truth table. Make the table so that one sentence is true and the other false. Consistency, to show that some sentences are jointly satisfiable, we must show that there is a valuation which makes all of the sentences true, so this requires only a partial truth table with a single line. To show that some sentences are jointly unsatisfiable, we must show that there is no valuation which makes all of the sentence true, so this requires a complete truth table. You must show that on every row of the table at least one of the sentences is false. Validity and entailment. To show that an argument is valid, we must show that there is no valuation which makes all of the premises true and the conclusion false, so this requires a complete truth table. Likewise for entailment. To show that argument is invalid, we must show that there is a valuation which makes all of the premises true and the conclusion false, so this requires only a one-line partial truth table on which all of the premises are true and the conclusion is false. Likewise for a failure of entailment. This table summarizes what is required.
Table summary. The table summarizes what is required for different logical properties. For tautology, contradiction, equivalence, validity, and entailment, a complete truth table is needed to confirm the property, while a one-line partial truth table suffices to refute it. Conversely, for satisfiability, a one-line partial truth table is enough to confirm it, but a complete truth table is needed to refute it.
Practice exercises. A. Use complete or partial truth tables as appropriate to determine whether these pairs of sentences are logically equivalent. 1A not A. 2A or A. 3 goes to A, it goes to and from A. 4 or not B, A implies B. 5A and not A, not B if and only if B. 6 not of A and B, not or not B. 7 not open parenthesis A implies B close parenthesis, not A implies not B. 8 A implies B, not B implies not A. B. Use complete or partial truth tables as appropriate to determine whether these sentences are jointly satisfiable or jointly unsatisfiable. 1 A and B C implies not B C. 2 implies B, B implies C, A not C. 3 or B, B or C, C implies not A. 4 A, B, C not D, not E, F.
Math summary. This expression represents a logical entailment check. It starts with the premise that it implies B, and B implies C. It then asserts the negation of implying C. The expression is testing whether the first two premises logically lead to implying C, and then checking if the negation of that implication holds true.
C. Use complete or partial truth tables as appropriate to determine whether each argument is valid or invalid. 1. Or open bracket A implies open parenthesis A if and only if a close parenthesis close bracket, therefore A. 2. A if and only if not open parenthesis B if and only if a close parenthesis, therefore A. 3. Implies B, therefore A. 4. Or B or C, not B, therefore A and C. 5. A if and only if B if and only if C, therefore A if and only if C. D. Determine whether each sentence is a tautology, a contradiction, or a contingent sentence. Justify your answer with a complete or partial truth table where appropriate. 1. Implies not A. 2. Implies an A or B. 3. A implies B if and only if B implies A. 4. A implies not of open parenthesis A and open parenthesis A or B close parenthesis close parenthesis. 5. Not B implies not A and A or B. 6. Not open parenthesis A or B close parenthesis if and only if open parenthesis not A and not B close parenthesis. 7. Left bracket open parenthesis A and B close parenthesis and C right bracket implies B. 8. Not open bracket open parenthesis C or A close parenthesis or B close bracket. 9. Left bracket open parenthesis A and B close parenthesis and not open parenthesis A and B close parenthesis right bracket and C. 10. And B implies open bracket A and C or B and D close bracket. E. Determine whether each sentence is a tautology, a contradiction, or a contingent sentence. Justify your answer with a complete or partial truth table where appropriate. 1. Not open parenthesis A or A close parenthesis. 2. A implies B or B implies A. 3. If implies B then implies A then implies A. 4. Not open bracket open parenthesis A implies B close parenthesis or open parenthesis B implies a close parenthesis close bracket. 5. Left parenthesis A and B right parenthesis or left parenthesis A or B right parenthesis. 6. Not of A and B if and only if A. 7. Implies B or C. 8. And not A implies B or C. 9. B and D if and only if A or C. 10. Not open bracket open parenthesis A implies B close parenthesis or open parenthesis C implies D close parenthesis close bracket F. Determine whether each the following pairs of sentences are logically equivalent using complete truth tables. If the two sentences really are logically equivalent, write equivalent. Otherwise write not equivalent. 1. And A or A. 2. A and A and A. 3. Or not B and implies B. 4. Implies B and not B implies not A. 5. Not open parenthesis A and B close parenthesis and not or not B. 6. U implies X or 10 or U and not X and X and U. 7. Left parenthesis C and left parenthesis N if and only if C right parenthesis if and only if C right parenthesis and left parenthesis not N implies C right parenthesis. 8. Left bracket left parenthesis A or B right parenthesis and C right bracket and left bracket A or left parenthesis B and C right parenthesis right bracket. 9. L and C and I and L or C. G. Determine whether each collection of sentences is jointly satisfiable or jointly unsatisfiable. Justify your answer with a complete or partial truth table where appropriate. 1. A goes to A, not a goes to not A and A or A. 2. Implies not A, not implies A. 3. Or B, A implies C, B implies C. 4. Or B, A implies C, B implies C, not C. 5. B and C or A implies B, not B or C. A double arrow B implies B, B implies not of a double arrow B, A or B. A if and only if B or C, C implies not A implies not B. 8. A if and only if B not B or not A implies B. 9. A if and only if B, A implies C, B implies D, not of C or D. 10. Not of open parenthesis A and not B close parenthesis, B implies not and not B. H. Determine whether each argument is valid or invalid. Justify your answer with a complete or partial truth table where appropriate. 1. Implies open parenthesis A and not a close parenthesis, therefore not A. O or B, A implies B, B implies a therefore A if and only if B. 3. O or B implies A, therefore not A implies not B. 4. O or B, A implies B, B implies a therefore A and B. 5. Left parenthesis B and a right parenthesis implies C, left parenthesis C and a right parenthesis implies B, therefore left parenthesis C and B right parenthesis implies A.
Math summary. This statement represents a logical argument. It takes the negation of the logical OR of the negations of A and B, and also implies the negation of C as premises. From these, it concludes that it implies B implies C.
7. A and left parenthesis B implies C right parenthesis, not C and left parenthesis not B implies not a right parenthesis, therefore C and not C. 8. A and B not A implies not C, B implies not D, therefore A or B. 9. A implies B, therefore open parenthesis A and B close parenthesis or open parenthesis not A and not B close parenthesis. Not A implies B, not B implies C, not C implies A, therefore not A implies not B or not C. 1. Determine whether each argument is valid or invalid. Justify your answer with a complete or partial truth table where appropriate. 1. A if and only if not open parenthesis B, if and only if a close parenthesis, therefore A. 2. Or B, B or C, not A, therefore B and C. Begin aligned left brace begin array LA implies C, E implies D or B, B implies not D, therefore A or C, or B implies E and D, end array right end aligned. 4. Or B, C implies A, C implies B, therefore implies B implies C. 5. Implies B, not B or therefore A if and only if B. Part 4. Natural deduction for TFL. Chapter 15. The very idea of natural deduction. Way back in section 2, we said that an argument is valid if there is no case in which all of the premises are true and the conclusion is false. In the case of TFL, this led us to develop truth tables. Each line of a complete truth table corresponds to a valuation. So when faced with a TFL argument, we have a very direct way to assess whether there is a valuation on which the premises are true and the conclusion is false. Just thrash through the truth table. However, truth tables may not give us much insight. Consider two arguments in TFL.
Math summary. The first expression represents a logical argument. Given the premise that either P or Q is true, and the premise that P is not true, the argument concludes that Q is true. The second expression represents another logical argument. Given the premise that if P is true then Q is true, and the premise that P is true, the argument concludes that Q is true.
Clearly, these are valid arguments. You can confirm that they are valid by constructing four-line truth tables, but we might say that they make use of different forms of reasoning. It might be nice to keep track of these different forms of inference. One aim of a natural deduction system is to show that particular arguments are valid in a way that allows us to understand the reasoning that the arguments might involve. We begin with very basic rules of inference. These rules can be combined to offer more complicated arguments. Indeed, with just a small starter pack of rules of inference, we hope to capture all valid arguments. This is a very different way of thinking about arguments. With truth tables, we directly consider different ways to make sentences true or false. With natural deduction systems, we manipulate sentences in accordance with rules that we have set down as good rules. The latter promises to give us a better insight, or at least a different insight, into how arguments work. The move to natural deduction might be motivated by more than the search for insight. It might also be motivated by necessity. Consider.
Math summary. The expression describes a logical implication. It states that if condition A1 implies condition C1, then the conjunction of conditions A1 through A5 implies the disjunction of conditions C1 through C5. In simpler terms, if A1 leads to C1, then if all the conditions are true, at least one of the C conditions must be true.
To test this argument for validity, you might use a 1024-line truth table. If you do it correctly, then you will see that there is no line on which all the premises are true and on which the conclusion is false. So you will know that the argument is valid. But as just mentioned, there is a sense in which you will not know why the argument is valid. But now consider.
Math summary. The expression represents a logical argument. It states that if premise 1 implies conclusion 1, then the conjunction of premises 1 through 10 implies the disjunction of conclusions 1 through 10.
This argument is also valid, as you can probably tell. but to test it requires a truth table with 2 sup 20 equals 1,048,576 lines. In principle, we can set a machine to grind through truth tables and report back when it is finished. In practice, complicated arguments in TFL can become intractable if we use truth tables. When we get to first-order logic, FOL, beginning in Chapter 22, though the problem gets dramatically worse. There's nothing like the truth table test for FOL. To assess whether or not an argument is valid, we have to reason about all interpretations, but as we will see, there are infinitely many possible interpretations. We cannot even in principle set a machine to grind through infinitely many possible interpretations and report back when it is finished. It will never finish. We either need to come up with some more efficient way of reasoning about all interpretations, or we need to look for something different. There are indeed systems that codify ways to reason about all possible interpretations. They were developed in the 1950s by Evert Bate and Jocko Hintica, but we will not follow this path. We will, instead, look to natural deduction. Rather than reasoning directly about all valuations, in the case of TFL, we will try to select a few basic rules of inference. Some of these will govern the behavior of the sentential connectives. Others will govern the behavior of the quantifiers and identity that are the hallmarks of FOL. The resulting system of rules will give us a new way to think about the validity of arguments. The modern development of natural deduction dates from simultaneous and unrelated papers by Gerhard Jensen and Stanislaw Jalkowski. However, the natural deduction system that we will consider is based largely around work by Frederick Fitch. Chapter 16. Basic rules for TFL. We will develop a natural deduction system. For each connective, there will be introduction rules that allow us to prove a sentence that has that connective as the main logical operator, and elimination rules that allow us to prove something given a sentence that has that connective as the main logical operator. 16.1 The idea of a formal proof. A formal proof is a sequence of sentences, some of which are marked as being initial assumptions or premises. The last line of the formal proof is the conclusion. Henceforth, we will simply call these proofs, but be aware that there are informal proofs too. As an illustration, consider.
Math summary. This expression represents De Morgan's law. It states that the negation of the disjunction of two statements is logically equivalent to the conjunction of the negations of those same two statements. In simpler terms, not A or B is equivalent to not A and not B.
We will start a proof by writing the premise.
Math summary. This expression presents a premise in a logical proof. Specifically, it asserts the negation of the disjunction of A or B. The expression is labeled with the number 1, indicating it's the first line or assumption in the proof.
Note that we have numbered the premise since we will want to refer back to it. Indeed, every line on of proof is numbered so that we can refer back to it. Note also that we have drawn a line underneath the premise. Everything written above the line is an assumption. Everything written below the line will either be something which follows from the assumptions, or it will be some new assumption. We are hoping to conclude not sign A, not sign B, so we are hoping ultimately to conclude our proof with.
Math summary. This represents a logical argument or proof step. It asserts that given a premise, which is the negation of A and the negation of B, this premise is valid at step number n within the proof.
For some number n, it doesn't matter what line number we end on, but we would obviously prefer a short proof to a long one. Similarly, suppose we wanted to consider.
Math summary. This expression represents a logical argument. It starts with 3 premises. O or B is true, not A and C is true, and not B and not D is true. The argument concludes that not C or D is true.
The argument has 3 premises, so we start by writing them all down, numbered, and drawing a line under them.
Math summary. This expression presents a set of logical statements. The first statement is A or B. The second statement is the negation of A and C. The third statement is the negation of B and the negation of D.
And we are hoping to conclude with some line.
Math summary. This expression asserts that on line number n, it is valid to infer not C or D.
All that remains to do is to explain each of the rules that we can use along the way from premises to conclusion. The rules are broken down by our logical connectives. 16.2 Reiteration. The very first rule is so breathtakingly obvious that it is surprising we bother with it at all. If you already have shown something in the course of a proof, the reiteration rule allows you to repeat it on a new line, for example.
Math summary. This represents a reiteration rule in a proof. A statement, A and B, appearing on line 4 is repeated on line 10. The repetition is justified by the reiteration rule, indicated by R, and citing line 4 as the source of the statement.
This indicates that we have written a B on line 4. Now, at some later line 10, for example, we have decided that we want to repeat this. So we write it down again. We also add a citation which justifies what we have written. In this case, we write R to indicate that we are using the reiteration rule, and we write 4 to indicate that we have applied it to line 4. Here is a general expression of the rule.
Math summary. This represents the reiteration rule in a proof. It states that if a sentence A occurs on line M, then it can be repeated on a later line. This later line is justified by the reiteration rule applied to line M.
The point is that if any sentence A occurs on some line, then we can repeat A on later lines. Each line of our proof must be justified by some rule, and here we have RM. This means reiteration applied to line M. Two things need emphasizing. First, A is not a sentence of TFL. Rather, it is a symbol in the meta-language, which we use when we want to talk about any sentence of TFL, see section 8. Second, and similarly, M is not a symbol that will appear on a proof. Rather, it is a symbol in the meta-language, which we use when we want to talk about any line number of a proof. In an actual proof, the lines are numbered 1, 2, 3, and so forth. But when we define the rule, we use variables like may to underscore the point that the rule may be applied at any point. 16.3 Conjunction. Suppose we want to show that Ludwig is both reactionary and libertarian. One obvious way to do this would be as follows. First, we show that Ludwig is reactionary, then we show that Ludwig is libertarian, then we put these two demonstrations together to obtain the conjunction. Our natural deduction system will capture this thought straightforwardly. In the example given, we might adopt the following symbolization key. R. Ludwig is reactionary. L. Ludwig is libertarian. Perhaps we are working through a proof and we have obtained R on line 8 and L on line 15. Then on any subsequent line we can obtain RL thus.
Math summary. This expression performs a logical conjunction. It takes two inputs, the statement R from line 8 and the statement L from line 15. It outputs the combined statement R and L, justified by the conjunction introduction rule applied to lines 8 and 15. The purpose is to show that both R and L are true.
Note that every line of our proof must either be an assumption or must be justified by some rule. We cite I8:15 here to indicate that the line is obtained by the rule of conjunction introduction, one applied to lines 8 and 15. We could equally well obtain with the citation reversed to reflect the order of the conjuncts. More generally, here is our conjunction introduction rule.
Table summary. The table describes the conjunction introduction rule, where if you have statements A and B on lines M and N respectively, you can infer A and B on a new line using the conjunction introduction rule, citing lines M and N.
To be clear, the statement of the rule is schematic. It is not itself a proof. A and B are not sentences of TFL. Rather, they are symbols in the meta-language, which we use when we want to talk about any sentence of TFL, see section 8. Similarly, M and N are not numerals that will appear on any actual proof. Rather, they are symbols in the meta-language, which we use when we want to talk about any line number of any proof. In an actual proof, the lines are numbered 1, 2, 3, and so forth, but when we define the rule, we use variables to emphasize that the rule may be applied at any point. The rule requires only that we have both conjuncts available to us somewhere in the proof. They can be separated from one another and they can appear in any order. The rule is called conjunction introduction because it introduces the symbol into our proof where it may have been absent. Correspondingly, we have a rule that eliminates that symbol. Suppose you have shown that Ludwig is both reactionary and libertarian. You are entitled to conclude that Ludwig is reactionary. Equally, you are entitled to conclude that Ludwig is libertarian. Putting this together, we obtain our conjunction elimination rule, S.
Math summary. This represents a logical argument. It starts with a premise M. Then, given that A and B is true, and A is true, it concludes, using the conjunction elimination rule, that M is true.
And equally.
Table summary. The table illustrates a rule in logic, where from a conjunction of two statements, either of the individual statements can be inferred.
The point is simply that when you have a conjunction on some line of a proof, you can obtain either of the conjuncts by E. One point is worth emphasizing. You can only apply this rule when conjunction is the main logical operator. So you cannot infer D just from C, D, E. Even with just these two rules, we can start to see some of the power of our formal proof system. Consider.
Math summary. This expression demonstrates a logical equivalence. It starts with a conjunction of two implications. The first implication states, if A or B is true, then C or D is true. The second implication states, if E or F is true, then G or H is true. The expression then restates this conjunction, but with the order of the two implications reversed. Thus, it shows that the order of the implications in the conjunction does not affect the overall truth value.
The main logical operator in both the premise and conclusion of this argument is, in order to provide a proof, we begin by writing down the premise, which is our assumption. We draw a line below this. Everything after this line must follow from our assumptions by repeated applications of our rules of inference. So the beginning of the proof looks like this.
Math summary: this expression represents a logical statement. It asserts the truth value of a conjunction. The conjunction connects two implications. The first implication states that if either A or B is true, then either C or D is true. The second implication states that if either E or F is true, then either G or H is true. The entire statement evaluates to true or false based on the truth values of A, B, C, D, E, F, G, and H.
From the premise, we can get each of the conjuncts by E. The proof now looks like this.
Math summary: this expression represents a logical proof. Line 1 states an initial assumption, the conjunction of two implications. The first implication is that if A or B is true, then C or D is true. The second implication is that if E or F is true, then G or H is true. Line 2 extracts the first implication, that if A or B is true, then C or D is true, from the initial assumption on line 1 using conjunction elimination. Line 3 extracts the second implication, that if E or F is true, then G or H is true, from the initial assumption on line 1, also using conjunction elimination.
So by applying the I rule to lines 3 and 2 in that order, we arrive at the desired conclusion. The finished proof looks like this.
Math summary: this is a logical proof. Line 1 states the initial premise, the conjunction of two implications. Line 2 extracts the first implication from line 1 using conjunction elimination. Line 3 extracts the second implication from line 1, also using conjunction elimination. Line 4 forms a new conjunction by combining the implication from line 3 with the implication from line 2, using conjunction introduction with lines 3 and 2.
This is a very simple proof, but it shows how we can chain rules of proof together into longer proofs. In passing, note that investigating this argument with a truth table would have required 256 lines. Our formal proof required only 4 lines. It is worth giving another example. Back in section 11.3, we noted that this argument is valid.
Math summary: the expression demonstrates the associative property of logical conjunction. It starts with the logical conjunction of A with the logical conjunction of B and C. It then concludes that this is logically equivalent to the logical conjunction of the logical conjunction of A and B with C.
To provide a proof corresponding to this argument, we start by writing.
Math summary: this line represents a logical argument. It asserts the truth of A and the truth of B, and C, the number 1, indicates that this is the first line in a proof or derivation.
From the premise, we can get each of the conjuncts by applying an E twice. We can then apply an E twice more, so our proof looks like.
Table summary: the table illustrates a proof where each of the conjuncts is derived by applying the rule of conjunction elimination twice.
But now we can merely reintroduce conjunctions in the order we wanted them, so that our final proof is.
Table summary: the table shows a step-by-step logical deduction, starting from an initial expression and deriving subsequent expressions using logical rules. The final expression is a logically derived consequence of the initial one.
Recall that our official definition of sentences in TFL only allowed conjunctions with 2 conjuncts. The proof just given suggests that we could drop inner brackets in all of our proofs. However, this is not standard, and we will not do this. Instead, we will maintain our more austere bracketing conventions, though we will still allow ourselves to drop outermost brackets for legibility. Let's give one final illustration. When using the I rule, there is no requirement to apply it to different sentences. So if we want, we can formally prove A from A thus.
Math summary: the expression presents a logical deduction. In step 1, from an initial statement A, it infers an A using the conjunction introduction rule, referencing line 1. Step 2 repeats the same deduction. From the initial statement A, it infers an A using the conjunction introduction rule, referencing line 1.
Simple but effective.
Algorithm 1 summary: the algorithm demonstrates a conjunction introduction rule in a formal system. It takes 2 separate statements as input and combines them into a single conjunctive statement. the order of the input statements can be changed without affecting the validity of the resulting conjunction.
16.4 Conditional. Consider the following argument. If Jane is smart, then she is fast. Jane is smart, therefore Jane is fast. This argument is certainly valid, and it suggests a straightforward conditional elimination rule, 2e. This rule is also sometimes called modus ponens. Again, this is an elimination rule because it allows us to obtain a sentence that may not contain right arrow, having started with a sentence that did contain right arrow. Note that the conditional A to B and the antecedent A can be separated from one another in the proof, and they can appear in any order. However, in the citation for 2e, we always cite the conditional first, followed by the antecedent. The rule for conditional introduction is also quite easy to motivate. The following argument should be valid. Ludwig is reactionary, therefore if Ludwig is libertarian, then Ludwig is both reactionary and libertarian. If someone doubted that this was valid, we might try to convince them otherwise by explaining ourselves as follows. Assume that Ludwig is reactionary. Now additionally assume that Ludwig is libertarian. Then by conjunction introduction, which we just discussed, Ludwig is both reactionary and libertarian. Of course, that's conditional on the assumption that Ludwig is libertarian. But this just means that if Ludwig is libertarian, then he is both reactionary and libertarian. Transferred into natural deduction format, here is the pattern of reasoning that we just used. We started with one premise, Ludwig is reactionary, thus. The next thing we did is to make an additional assumption, Ludwig is libertarian, for the sake of argument. To indicate that we are no longer dealing merely with our original assumption, R, but with some additional assumption, we continue our proof as follows. Note that we are not claiming on line 2 to have proved L from line 1, so we do not write in any justification for the additional assumption on line 2. We do, however, need to mark that it is an additional assumption. We do this by drawing a line under it to indicate that it is an assumption and by indenting it with a further vertical line to indicate that it is additional. With this extra assumption in place, we are in a position to use I, so we can continue our proof.
Table summary. The table shows the derivation of a logical conclusion using additional assumptions. The third row combines the first two rows using a logical operation.
So we have now shown that on the additional assumption L, we can obtain R in L. We can therefore conclude that if L obtains, then so does R in L. Or to put it more briefly, we can conclude L implies the quantity R in L.
Table summary. The table illustrates a proof involving an additional assumption, where an initial assumption is combined with the additional assumption to derive a new statement, which is then used to conclude a conditional statement.
Observe that we have dropped back to using one vertical line on the left. We have discharged the additional assumption, L, since the conditional itself follows just from our original assumption, R. The general pattern at work here is the following. We first make an additional assumption, A, and from that additional assumption we prove B. In that case, we know the following. If it is true, then B is true. This is wrapped up in the rule for conditional introduction.
Math summary. This expression describes a conditional proof rule. It starts with an assumption labeled A on line I. Then, from assumption A, a statement labeled B is derived on line J. The rule concludes that if it is true, then B is true, indicated by A implies B. This implication is introduced, and it depends on lines I and J.
There can be as many or as few lines as you like between lines I and J. It will help to offer a second illustration of to I in action. Suppose we want to consider the following.
Math summary. This expression represents a logical deduction. It states that if P implies Q and Q implies R, then P implies R. This is a form of transitive inference, where the implication flows from P to Q and then from Q to R, resulting in the conclusion that P implies R.
We start by listing both of our premises. Then, since we want to arrive at a conditional, namely P to R, we additionally assume the antecedent to that conditional. Thus our main proof starts.
Math summary. This represents a logical argument or proof. It starts with two conditional statements. If P then Q, and if Q then R, it then introduces P as an assumption. Finally, it restates P, possibly to continue the logical derivation.
Note that we have made P available by treating it as an additional assumption, but now we can use TUI on the first premise. This will yield Q. We can then use TUI on the second premise. So by assuming P, we were able to prove R, so we apply the right arrow I rule discharging P and finish the proof. Putting all this together, we have
Math summary, this expression demonstrates a logical deduction. It starts with two implications. If P then Q, and if Q then R, it then infers that if P is true, then Q is true, and subsequently if Q is true, then R is true. Finally, it concludes that if P is true, then R is true, establishing a transitive relationship. Figure 16 summary. The table presents a specific logical rule, showing how to derive a conclusion from a conditional statement and its antecedent. The conclusion is derived by applying the elimination rule to the conditional statement and the antecedent. Table 2 summary. The table shows two different assumptions, R and L.
16.5 Additional assumptions and subproofs. The Rule 2I invoked the idea of making additional assumptions. These need to be handled with some care. Consider this proof.
Math summary. The expression appears to describe a series of logical deductions or transformations within a proof. First, there is a matrix or arrangement involving elements A and B. Second, another matrix involving B is transformed using rule R2, leading to a statement where B implies B, derived by applying rule I to steps 2 and 3.
This is perfectly in keeping with the rules we have laid down already, and it should not seem particularly strange. Since B to B is a tautology, no particular premises should be required to prove it. But suppose we now tried to continue the proof as follows. If we were allowed to do this, it would be a disaster. It would allow us to prove any sentence letter from any other sentence letter. However, if you tell me that Anne is fast, symbolized by A, we shouldn't be able to conclude that Queen Boudica stood 20 feet tall, symbolized by B. We must be prohibited from doing this, but how are we to implement the prohibition? We can describe the process of making an additional assumption as one of performing a subproof, a subsidiary proof within the main proof. When we start a subproof, we draw another vertical line to indicate that we are no longer in the main proof. Then we write in the assumption upon which the subproof will be based. A subproof can be thought of as essentially posing this question: what could we show if we also make this additional assumption? When we are working within the subproof, we can refer to the additional assumption that we made in introducing the subproof, and to anything that we obtained from our original assumptions. After all, those original assumptions are still in effect. At some point, though, we will want to stop working with the additional assumption. We will want to return from the subproof to the main proof. To indicate that we have returned to the main proof, the vertical line for the subproof comes to an end. At this point, we say that the subproof is closed. Having closed a subproof, we have set aside the additional assumption, so it will be illegitimate to draw upon anything that depends upon that additional assumption. Thus, we stipulate to cite an individual line when applying a rule. 1. The line must come before the line where the rule is applied, but 2. Not occur within a subproof that has been closed before the line where the rule is applied. This stipulation rules out the disastrous attempted proof above. The rule of TE requires that we cite two individual lines from earlier in the proof. In the purported proof above, one of these lines, namely line 4, occurs within a subproof that has by line 5 been closed. This is illegitimate. Closing a subproof is called discharging the assumptions of that subproof. So we can put the point this way: you cannot refer back to anything that was obtained using discharged assumptions. Subproofs then allow us to think about what we could show if we made additional assumptions. The point to take away from this is not surprising. In the course of a proof, we have to keep very careful track of what assumptions we are making at any given moment. Our proof system does this very graphically. Indeed, that's precisely why we have chosen to use this proof system. Once we have started thinking about what we can show by making additional assumptions, nothing stops us from posing the question of what we could show if we were to make even more assumptions. This might motivate us to introduce a subproof within a subproof. Here is an example using only the rules which we have considered so far.
Math summary: the expression represents a logical proof or derivation. It starts with initial assumptions labeled A, B, and C. It then derives new statements based on these assumptions using logical rules. Specifically, it derives A and B, then if C then A and B, and finally, if B then if C then A and B. The labels on the right indicate the rules and line numbers used in each derivation step.
Notice that the citation on line 4 refers back to the initial assumption on line 1 and an assumption of a subproof on line 2. This is perfectly in order since neither assumption has been discharged at the time, i.e., by line 4. Again, though, we need to keep careful track of what we are assuming at any given moment. Suppose we tried to continue the proof as follows.
Image summary: the image shows a logical proof and a demonstration of an incorrect attempt to apply a rule within that proof. The proof constructs a conditional statement through a series of assumptions and applications of logical rules, specifically conjunction introduction and conditional introduction. The proof demonstrates how assumptions are made and discharged to arrive at a conclusion. The incorrect attempt violates the proper scope of assumptions, leading to an invalid inference. The correct proof shows the valid application of logical rules within the scope of assumptions. The incorrect attempt highlights the importance of adhering to the rules of inference and the scope of assumptions in logical proofs.
This would be awful. If we tell you that Anne is smart, you should not be able to infer that if Kath is smart, symbolized by C, then both Anne is smart and Queen Boudica stood 20 feet tall. But this is just what such a proof would suggest if it were permissible. The essential problem is that the subproof that began with the assumption C depended crucially on the fact that we had assumed B on line 2. By line 6, we have discharged the assumption B. We have stopped asking ourselves what we could show if we also assumed B. So it is simply cheating to try to help ourselves on line 7 to the subproof that began with the assumption C. Thus we stipulate, much as before, that a subproof can only be cited on a line if it does not occur within some other subproof which is already closed at that line. The attempted disastrous proof violates this stipulation. The subproof of lines 3 to 4 occurs within a subproof that ends on line 5, so it cannot be invoked on line 7. Here is one further case we have to exclude.
Image summary. The image shows a proof attempt. The proof includes a series of logical statements and justifications. The proof starts with assumption A, followed by assumption B, then assumption C. These assumptions lead to the conclusion B implies. See, the proof attempt is marked as incorrect because it violates a rule about discharging assumptions within subproofs. The final line is a failed attempt to invoke a rule because the subproof cited relies on assumptions that have not been discharged.
Here we are trying to cite a subproof that begins on line 2 and ends on line 5, but the sentence on line 5 depends not only on the assumption on line 2, but also on one another assumption, line 3, which we have not discharged at the end of the subproof. The subproof started on line 3 is still open at line 3. But Paper2Audio requires that the last line of the subproof only relies on the assumption of the subproof being cited, that is, the subproof beginning on line 2 and anything before it, and not on assumptions of any subproofs within it. In particular, the last line of the subproof cited must not itself lie within a nested subproof. To cite a subproof when applying a rule. 1. The cited subproof must come entirely before the application of the rule where it is cited. 2. The cited subproof must not lie within some other closed subproof which is closed at the line it is cited, and 3. Its last line of the cited subproof must not occur inside a nested subproof. One last point to emphasize how rules can be applied. Where a rule requires you to cite an individual line, you cannot cite a subproof instead, and where it requires you to cite a subproof, you cannot cite an individual line instead. So for instance, this is incorrect.
Image summary. The image shows a proof tree. The proof demonstrates an attempt to derive a conclusion from a set of premises using logical inference rules. The proof proceeds through several steps, introducing assumptions and applying rules such as conjunction introduction and elimination. The proof contains an error, specifically an invalid application of a rule, which is explicitly noted. The overall structure of the proof involves nested subproofs, indicating conditional reasoning. The proof aims to show the derivation of a conditional statement, but the error in applying a rule prevents the successful conclusion. The attempted derivation is flawed due to the incorrect application of a rule, leading to an invalid step in the proof. The error highlights the importance of correctly applying inference rules in formal proofs.
Here we have tried to justify C on line 6 by the reiteration rule, but we have cited the subproof on lines 3 to 5 with it. That subproof is closed and can in principle be cited on line 6. For instance, we could use it to justify C to C by 2I, but the reiteration rule R requires you to cite an individual line, so citing the entire subproof is inadmissible, even if that subproof contains the sentence C we want to reiterate. It is always permissible to open a subproof with any assumption. However, there is some strategy involved in picking a useful assumption. Starting a subproof with an arbitrary, wacky assumption would just waste lines of the proof. In order to obtain a conditional by 2I, for instance, you must assume the antecedent of the conditional in a subproof. Equally, it is always permissible to close a subproof and discharge its assumptions. However, it will not be helpful to do so until you have reached something useful. Once the subproof is closed, you can only cite the entire subproof in any justification. Those rules that call for a subproof or subproofs, in turn, require that the last line of the subproof is a sentence of some form or other. For instance, you are only allowed to cite a subproof for 2I if the line you are justifying is of the form A to B. A is the assumption of your subproof, and B is the last line of your subproof. 16.6 Biconditional. The rules for the biconditional will be like double-barreled versions of the rules for the conditional. In order to prove F if and only if G, for instance, you must be able to prove G on the assumption F and prove F on the assumption G. The biconditional introduction rule if and only if introduction therefore requires two subproofs. Schematically, the rule works like this. There can be as many lines as you like between I and J, and as many lines as you like between K and L. Moreover, the subproofs can come in any order, and the second subproof does not need to come immediately after the first. The biconditional elimination rule left-right arrow E lets you do a bit more than the conditional rule. If you have the left-hand subsentence of the biconditional, you can obtain the right-hand subsentence. If you have the right-hand subsentence, you can obtain the left-hand subsentence. So we allow.
Math summary. This represents a biconditional elimination rule. It starts with two inputs. The first, premise A, is biconditionally related to premise B. The second input is premise A. The output is premise B, derived by biconditional elimination using the indices M and N.
And equally. Note that the biconditional and the right or left half can be separated from one another, and they can appear in any order. However, in the citation for if and only if E, we always cite the biconditional first.
Figure 1 summary. The image displays some basic rules for TFL, including rules for biconditional elimination. It shows how to derive conclusions from biconditional statements and highlights the flexibility in the order of subproofs and the separation of biconditional components. Algorithm 2 summary. The algorithm describes a biconditional elimination rule. Given a biconditional statement and one of its components, the algorithm derives the other component. The order of the biconditional statement and its component is not important.
16.7 Disjunction. Suppose Ludwig is reactionary, then Ludwig is either reactionary or libertarian. After all, to say that Ludwig is either reactionary or libertarian is to say something weaker than to say that Ludwig is reactionary. Let's emphasize this point. Suppose Ludwig is reactionary. It follows that Ludwig is either reactionary or a kumquat. Equally, it follows that either Ludwig is reactionary or that kumquats are the only fruit. Equally, it follows that either Ludwig is reactionary or that God is dead. Many of these are strange inferences to draw, but there is nothing logically wrong with them, even if they maybe violate all sorts of implicit conversational norms. Armed with all this, we present the disjunction introduction rule, S, and
Math summary. This represents a disjunction introduction rule in logic. Given a premise indexed by M, it allows you to infer a disjunction. Specifically, if you have statement A, you can infer or B, where B can be any statement. This inference is indexed by M.
Notice that B can be any sentence whatsoever, so the following is a perfectly acceptable proof.
Math summary. This represents a two-step logical proof. Step 1 introduces a premise, labeled M. Step 2 performs a disjunction, combining the initial premise M with a complex statement involving logical equivalences and implications. The complex statement involves a B, C, D, E, and F. The final result is the initial premise M or the complex statement. The disjunction introduction rule is applied to derive this result from step 1.
Using a truth table to show this would have taken 128 lines. The disjunction elimination rule is, though, slightly trickier. Suppose that either Ludwig is reactionary or he is libertarian. What can you conclude? Not that Ludwig is reactionary, it might be that he is libertarian instead. Equally, not that Ludwig is libertarian, for he might merely be reactionary. Disjunctions, just by themselves, are hard to work with. But suppose that we could somehow show both of the following. First, that Ludwig's being reactionary entails that he is an Austrian economist. Second, that Ludwig's being libertarian entails that he is an Austrian economist. Then if we know that Ludwig is either reactionary or libertarian, then we know that whichever he is, Ludwig is an Austrian economist. This insight can be expressed in the following rule, which is our disjunction elimination, VE rule.
Image summary. The image shows a logical rule diagram. The diagram illustrates a disjunction elimination rule in logic. It shows that if either A or B is true, and if A implies C and B implies C, then C must be true. The diagram provides a visual representation of how to derive a conclusion from a disjunction by considering each possibility separately and showing that each leads to the same conclusion. The diagram demonstrates a way to infer a conclusion from a disjunction by showing that each disjunct leads to the same result. Math summary, this represents the disjunction elimination rule. It takes as input a disjunction, labeled M. It also takes two subproofs. The first subproof starts at line I and ends at line J. The second subproof starts at line K and ends at line L. The output is the conclusion that follows from both subproofs.
This is obviously a bit clunkier to write down than our previous rules, but the point is fairly simple. Suppose we have some disjunction, logical A or logical B. Suppose we have two subproofs, showing us that logical C follows from the assumption that logical A, and that logical C follows from the assumption that logical B. Then we can infer logical C itself. As usual, there can be as many lines as you like between I and J, and as many lines as you like between K and L. Moreover, the subproofs and the disjunction can come in any order and do not have to be adjacent. Some examples might help illustrate this. Consider this argument.
Math summary, the expression describes a logical argument. It states that if either proposition P and Q are both true, or proposition P and R are both true, then proposition P is true.
An example proof might run thus.
Table summary. The table presents a series of logical deductions, where each row represents a step in a proof. The initial rows decompose a disjunction, followed by conjunctions and further deductions to arrive at a final conclusion.
Here is a slightly harder example. Consider.
Math summary. This expression demonstrates a logical equivalence. It starts with an input that is a and B or C. The conclusion is a and B or A and C. This shows the distributive property of and over or in logic.
Here is a proof corresponding to this argument.
Table summary. The table presents a series of logical deductions and inferences, starting from an initial statement and progressing through several steps to arrive at a final conclusion. Each step builds upon previous ones, utilizing logical rules to derive new statements. The later steps involve more complex combinations of previous results.
Don't be alarmed if you think that you wouldn't have been able to come up with this proof yourself. The ability to come up with novel proofs comes with practice, and we'll cover some strategies for finding proofs in section 17. The key question at this stage is whether, looking at the proof, you can see that it conforms to the rules that we have laid down. That just involves checking every line and making sure that it is justified in accordance with the rules we have laid down. 16.8 Contradiction and Negation. We have only one connective left to deal with, negation, but to tackle it, we must connect negation with contradiction. An effective form of argument is to argue your opponent into contradicting themselves. At that point, you have them on the ropes. They have to give up at least one of their assumptions. We are going to make use of this idea in our proof system by adding a new symbol to our proofs. This should be read as something like contradiction or reductio or, but that's absurd. The rule for introducing this symbol is that we can use it whenever we explicitly contradict ourselves, that is, whenever we find both a sentence and its negation appearing in our proof.
Math summary. This represents a contradiction rule. If at line M we have the negation of a statement A, and at line N we have the statement A, then we can infer a contradiction, which is represented by the bottom symbol. This inference is justified by the negation elimination rule applied to lines M and N.
It does not matter what order the sentence and its negation appear in, and they do not need to appear on adjacent lines. However, we always cite the line number of the negation first, followed by that of the sentence it is a negation of. There is obviously a tight link between contradiction and negation. The rule not E lets us proceed from two contradictory sentences, A and its negation not A, to an explicit contradiction bottom. We choose the label for a reason. It is the most basic rule that lets us proceed from a premise containing a negation, that is, not A, to a sentence not containing it, that is, bottom. So it is a rule that eliminates not. We have said that it should be read as something like contradiction, but this does not tell us much about the symbol. There are roughly 3 ways to approach the symbol. We might regard as a new atomic sentence of TFL, but one which can only ever have the truth value false. We might regard the bottom symbol as an abbreviation for some canonical contradiction, such as A and not A. This will have the same effect as the above. Obviously, A and not A only ever has the truth value false, but it means that officially we do not need to add a new symbol to TFL. We might regard A not as a symbol of TFL, but as something more like a punctuation mark that appears in our proofs. It is on a par with the line numbers and the vertical lines, say. There is something very philosophically attractive about the third option, but here we will officially adopt the first. Perpendicular is to be read as a sentence letter that is always false. This means that we can manipulate it in our proofs just like any other sentence. We still have to state a rule for negation introduction. The rule is very simple. If assuming something leads you to a contradiction, then the assumption must be wrong. This thought motivates the following rule.
Math summary, this represents a logical inference rule. The first row states that from premise I, we can infer statement A or a contradiction. The second row states that from premise J, we can infer statement A or the negation of I, where I is a statement indexed by I minus J.
There can be as many lines between I and J as you like. To see this in practice and interacting with negation, consider this proof.
Math summary, this represents a logical proof sequence. Line 1 introduces the assumption D. Line 2 introduces the assumption not D. Line 3 infers a contradiction from not D and E at line 2 and 1. Line 4 infers not D from the contradiction derived from lines 2 to 3.
If the assumption that A is true leads to a contradiction, a cannot be true, that is, it must be false, that is, not a must be true. Of course, if the assumption that A is false, i.e., the assumption that not A is true leads to a contradiction, then a cannot be false, that is, a must be true. So we can consider the following rule.
Math summary, this represents an indirect proof. If assuming the negation of statement A leads to a contradiction, then statement A is true. The indices I and J represent the scope of the assumption and the conclusion, respectively. The expression indicates that from line I, where the negation of A is assumed and leads to a contradiction, we can conclude A on line J using indirect proof, indicated by IP, with the scope from I to J.
This rule is called indirect proof since it allows us to prove it indirectly by assuming its negation. Formally, the rule is very similar to not I, but A and not A have changed places. Since not A is not the conclusion of the rule, we are not introducing not, so IP is not a rule that introduces any connective. It also doesn't eliminate a connective since it has no freestanding premises which contain not, only a subproof with an assumption of the form not A. By contrast, not E does have a premise of the form not A, that's why not E eliminates not, but IP does not. Using not I, we were able to give a proof of not script D from script D using IP. We can go the other direction with essentially the same proof.
Math summary, this represents a logical derivation in a proof system. It starts with the assumption of a double negation of D from this. A contradiction is derived using rule E1, 2. Then, D is inferred using the rule IP2-3.
We need one last rule. It is a kind of elimination rule for it and known as explosion. If we obtain a contradiction symbolized by, then we can infer whatever we like. How can this be motivated as a rule of argumentation? Well, consider the English rhetorical device, and if that's true, I'll eat my hat. Since contradictions simply cannot be true, if one is true, then not only will I eat my hat, I'll have it too. Here is the formal rule.
Math summary, this represents a logical inference rule. If M leads to a contradiction, represented by the upside-down T symbol, then it implies X and M can be inferred.
Note that it can be any sentence whatsoever. The explosion rule is a bit odd. It looks like it arrives in our proof like a bunny out of a hat. When trying to find proofs, it is very tempting to try to use it everywhere since it seems so powerful. Resist this temptation. You can only apply it when you already have perpendicular, and you get perpendicular only when your assumptions are contradictory. Still, isn't it odd that from a contradiction anything whatsoever should follow? Not according to our notion of entailment and validity. For it entails B if there's no valuation of the sentence letters, which makes it true and B false at the same time. Now as a contradiction, it is never true whatever the valuation of the sentence letters. Since there is no valuation which makes true, there of course is also no valuation that makes true and B false. So according to our definition of entailment, B, whatever B is, a contradiction entails anything. These are all of the basic rules for the proof system for TFL. Practice exercises. A. The following two proofs are incorrect. Explain the mistakes they make.
Table summary. The table presents an example of an incorrect proof, demonstrating a series of logical deductions that lead to a contradiction and ultimately an erroneous conclusion.
B. The following three proofs are missing their citations, rule, and line numbers. Add them to turn them into bona fide proofs. Additionally, write down the argument that corresponds to each proof.
Table summary. The table presents a series of logical statements and derivations. It starts with certain premises and applies logical rules to arrive at subsequent statements, eventually deriving a conclusion. Table summary. The table presents a series of logical inferences, where each row represents a step in a proof. The steps build upon previous ones to arrive at a final conclusion.
C. Give a proof for each of the following arguments.
Math summary. This logical argument starts with the premise that if J is true, then not J is true. The conclusion of the argument is that not J is true.
2Q implies open parenthesis Q and not Q close parenthesis, therefore not Q3. Implies B implies C, therefore A and B implies C4. K and L, therefore K if and only if L5. Left parenthesis C and D, right parenthesis, or E, therefore E or D6. If and only if B, B if and only if C, therefore A if and only if C7. Not F implies G, F implies H, therefore G or H8. Left parenthesis Z and K, right parenthesis, or left parenthesis K and M, right parenthesis. K implies D, therefore D9. P and Q or R, P implies not R, therefore Q or E10. S if and only if T, therefore S if and only if T or S. 11 not open parenthesis P implies Q close parenthesis, therefore not Q. 12 not of open parenthesis P implies Q close parenthesis, therefore P. Chapter 17. Constructing proofs. There is no simple recipe for finding proofs and there is no substitute for practice. Here, though, are some rules of thumb and strategies to keep in mind.
Table B summary. The table presents a series of logical deductions, where each line represents a step in a proof. Each step is derived from previous steps using logical rules, demonstrating how conclusions are reached from initial premises. Table 3 summary. The table presents a series of logical deductions. The conclusion in each row is derived from the premises in the preceding rows.
17.1 Working backward from what we want. So you're trying to find a proof of some conclusion C, which will be the last line of your proof. The first thing you do is look at C and ask what the introduction rule is for its main logical operator. This gives you an idea of what should happen before the last line of the proof. The justifications for the introduction rule require one or two other sentences above the last line or one or two subproofs. Moreover, you can tell from C what those sentences are, or what the assumptions and conclusions of the subproof S are. Then you can write down those sentence or outline the subproof S above the last line and treat those as your new goals. For example, if your conclusion is a conditional A implies B, plan to use the implies I rule. This requires starting a subproof in which you assume A. The subproof ought to end with B. Then, continue by thinking about what you should do to get B inside that subproof, and how you can use the assumption A. If your goal is a conjunction, conditional, or negated sentence, you should start by working backward in this way. We'll describe what you have to do in each of these cases in detail. Working backward from a conjunction. If we want to prove a wedge B, working backward means we should write a wedge B at the bottom of our proof and try to prove it using wedge introduction. At the top, we'll write out the premises of the proof if there are any. Then, at the bottom, we write the sentence we want to prove. If it is a conjunction, we'll prove it using wedge introduction.
Code summary. The algorithm demonstrates how to construct a proof for a conjunction by working backward. It starts with premises and the desired conjunction, and then proves each part of the conjunction separately. Finally, it combines the proofs of the individual parts to prove the conjunction using a conjunction introduction rule. The input is a set of premises and a conjunction to prove, and the output is a structured proof demonstrating the validity of the conjunction based on the premises.
For wedge I, we need to prove a first, then prove B. For the last line, we have to cite the lines where we will have proved A and B, and use wedge I. The parts of the proof labeled vertical ellipsis have to still be filled in. We'll mark the line numbers M, N for now. When the proof is complete, these placeholders can be replaced by actual numbers. Working backward from a conditional. If our goal is to prove a conditional A implies B, we'll have to use implies introduction. This requires a subproof starting with A and ending with B. We'll set up our proof as follows.
Math summary. This represents a proof structure. It starts with a subproof from assumption A to conclusion B. Then, it applies the inference rule I to derive the conditional statement A implies B, citing the subproof which spans from line N to line M.
Again, we'll leave placeholders in the line number slots. We'll record the last inference as to I, citing the subproof. Working backward from a negated sentence. If we want to prove not script A, we'll have to use not I.
Math summary. The expression describes a proof structure. It represents a subproof starting at line N with an assumption, proceeding through a series of steps, and ending with a contradiction symbol. Another subproof starts at line M plus 1 with the same assumption, applies a negation introduction rule, and concludes at line N minus M.
For not I, we have to start a subproof with assumption A. The last line of the subproof has to be bottom. We'll cite the subproof and use not I as the rule. When working backward, continue to do so as long as you can. So if you're working backward to prove A implies B and have set up a subproof in which you want to prove B, now look at B. If, say, it is a conjunction, work backward from it and write down the two conjuncts inside your subproof, etc. Working backward from a disjunction. Of course, you can also work backward from a disjunction A or B, if that is your goal. The OR rule requires that you have one of the disjuncts in order to infer A or B, so to work backward, you pick a disjunct, infer A or B from it, and then continue to look for a proof of the disjunct you picked.
Math summary. This represents a matrix or determinant-like structure. It contains elements such as a variable A, a logical disjunction of A or B, and a logical disjunction of A or B, or another variable in. The structure implies some form of logical or mathematical operation involving these elements.
However, you may not be able to prove the disjunct you picked. In that case, you have to backtrack. When you can't fill in the therefore, delete everything and try with the other disjunct.
Math summary. This represents a step in a logical proof. It shows a transition from a proposition B to a disjunction of propositions A or B, using a rule I at step n+1, given step n.
Obviously, deleting everything and starting over is frustrating, so you should avoid it. If your goal is a disjunction, therefore, you should not start by working backward. Try working forward first, and apply the I strategy only when working forward and working backward using I to I, and not sin I no longer work. 17.2 Work forward from what you have. Your proof may have premises, and if you've worked backward in order to prove a conditional or a negated sentence, you will have set up subproofs with an assumption and be looking to prove a final sentence in the subproof. These premises and assumptions are sentences you can work forward from in order to fill in the missing steps in your proof. That means applying elimination rules for the main operators of these sentences. The form of the rules will tell you what you'll have to do. Working forward from a conjunction. To work forward from a sentence of the form a logical and B, we use logical and E. That rule allows us to do two things: infer A and infer B. So in a proof where we have a logical and B, we can work forward by writing A and or B immediately below the conjunction.
Math summary. This represents a logical deduction process. Starting with a statement A and B at line n, the process infers A at line n+1 and infers B at line n+2. Each inference is combined with another statement E and n.
Usually it will be clear in the particular situation you're in which one of A or B you'll need. It doesn't hurt, however, to write them both down. Working forward from a disjunction. Working forward from a disjunction works a bit differently. To use a disjunction, we use the E rule. In order to apply that rule, it is not enough to know what the disjuncts of the disjunction are that we want to use. We must also keep in mind what we want to prove. Suppose we want to prove F and we have FF to work with. That FF may be a premise of the proof, an assumption of a subproof, or something already proved. In order to be able to apply the E rule, we'll have to set up two subproofs.
Math summary. This expression represents a proof by cases. It starts with a statement that either condition A or condition B is true. Then it shows that if condition A is true, then condition C follows. Similarly, it shows that if condition B is true, then condition C also follows. Finally, it concludes that condition C is true, using the elimination rule for disjunction, referencing the initial statement and the two derivations.
The first subproof starts with the first disjunct, A, and ends with the sentence we're looking for. See, the second subproof starts with the other disjunct, B, and also ends with the goal sentence. See, each of these subproofs have to be filled in further. We can then justify the goal sentence C by using E, citing the line with a B and the two subproofs. Working forward from a conditional. In order to use a conditional A implies B, you also need the antecedent A in order to apply implies elimination. So to work forward from a conditional, you will derive B, justify it by implies elimination, and set up A as a new subgoal.
Math summary. This expression represents a conditional elimination rule. It takes as input a conditional statement from A to B, labeled with line number, and it also takes a subproof starting at line M which derives A. The output is B, derived at line M+1, justified by conditional elimination, referencing lines N and M.
Working forward from a negated sentence. Finally, to use a negated sentence not sin A, you would apply not sin E. It requires, in addition to not sin A, also the corresponding sentence without the negation. The sentence you'll get is always the same. So working forward from a negated sentence works especially well inside a subproof that you'll want to use for not sin I or IP. You work forward from not sin A if you already have not sin A and you want to prove. To do it, you set up as a new subgoal. 17.3 Strategies at work. Suppose we want to show that the argument left parenthesis A and B right parenthesis or left parenthesis A and C right parenthesis, therefore A and left parenthesis B or C right parenthesis is valid. We start the proof by writing the premise and conclusion down. On a piece of paper, you would want as much space as possible between them, so write the premises at the top of the sheet and the conclusion at the bottom.
Math summary, this represents a logical argument or proof. It starts with a premise, A and B, or A and C. There are a series of intermediate steps, indicated by a colon. The argument concludes with A and B or C. The numbers 1 and n likely indicate line numbers in the proof.
We now have two options, either work backward from the conclusion or work forward from the premise. We'll pick the second strategy. We use the disjunction on line 1 and set up the subproofs we need for or elimination. The disjunction on line 1 has two disjuncts, A and B and A and C. The goal sentence you want to prove is in open parenthesis B or C close parenthesis. So in this case, you have to set up two subproofs, one with assumption A and B and last line A and B or C, the other with assumption A and C and last line A and B or C. The justification for the conclusion on line N will be or E, citing the disjunction on line 1 and the two subproofs. So your proof now looks like this.
Math summary, the expression represents a proof using disjunction elimination. It starts with the disjunction of A and B or A and C. Then it contains two subproofs. The first subproof assumes A and B and derives A and B or C. The second subproof assumes A and C and also derives A and B or C. Finally, it concludes A and B or C by applying disjunction elimination to the initial disjunction and the two subproofs.
You now have two separate tasks, namely to fill in each of the two subproofs. In the first subproof, we now work backward from the conclusion A, B, C. That is a conjunction, so inside the first subproof, you will have two separate subgoals, proving A and proving B, C. These subgoals will let you justify line N using I. Your proof now looks like this.
Math summary, this represents a logical proof. It starts with the disjunction of two conjunctions, and B or A and C then, through a series of logical deductions, including conjunction introduction and disjunction elimination, it derives A and B or C. The proof involves intermediate steps and subgoals to arrive at the final conclusion.
We immediately see that we can get line I from line 2 by E. So line I is actually line 3 and can be justified with E from line 2. The other subgoal BC is a disjunction. We'll apply the strategy for working backward from a disjunctions to line N1. We have a choice of which disjunct to pick as a subgoal. B or C. Picking C wouldn't work and we'd end up having to backtrack. And you can already see that if you pick B as a subgoal, you could get that by working forward again from the conjunction of B on line 2. So we can complete the first subproof as follows.
Math summary, this expression constructs a logical proof. It starts with the premise that either A and B are true or A and C are true. It then derives that A and B are true, from which it extracts A and extracts B from B. It infers that either B or C is true. Combining A and the statement that either B or C is true, it concludes that A and the statement B or C are both true. A similar process is applied assuming A and C are true, eventually leading to the same conclusion that A and the statement B or C are both true. Finally, using the initial premise and the derived conclusions, it concludes that A and the statement B or C are both true.
Like line 3, we get line 4 from 2 by an elimination. Line 5 is justified by or introduction from line 4, since we were working backward from a disjunction there. That's it for the first subproof. The second subproof is almost exactly the same. We'll leave it as an exercise. Remember that when we started, we had the option of working forward from the premise or working backward from the conclusion, and we picked the first option. The second option also leads to proof, but it will look different. The first steps would be to work backward from the conclusion and set up two subgoals A and B, C, and then work forward from the premise to prove them, for example.
Math summary, this expression represents steps in a logical proof. It starts with initial statements, then applies rules of inference. Specifically, it uses disjunction elimination and conjunction introduction to derive new statements from existing ones, ultimately aiming to reach a final conclusion based on the initial assumptions and the applied logical rules.
We'll leave you to fill in the missing pieces indicated by therefore. Let's give another example to illustrate how to apply the strategies to deal with conditionals and negation. The sentence, open parenthesis A implies B close parenthesis implies open parenthesis not B implies not a close parenthesis, is a tautology. Let's see if we can find a proof of it from no premises using the strategies. We first write the sentence at the bottom of a sheet of paper. Since working forward is not an option, there's nothing to work forward from. We work backward and set up a subproof to establish the sentence we want. Open parenthesis A implies B close parenthesis implies open parenthesis not B implies not a close parenthesis using implies introduction. Its assumption must be the antecedent of the conditional we want to prove, that is, A implies B, and its last line the consequent not B implies not A.
Math summary, this represents a logical proof. It starts with the assumption that A implies B through a series of logical steps. It arrives at the conclusion that not B implies not A. The final step shows that the implication of A to B implies the implication of not B to not A, referencing the initial steps of the proof.
The new goal, not B implies not A, is itself a conditional, so working backward we set up another subproof.
Math summary: this represents a proof in logic. It begins with the assumption A implies B. A subproof is then started, assuming not B through a series of steps, not A is derived. This allows the conclusion of not B implies not A. Finally, it concludes that A implies B, implies not B implies not A.
From not A we again work backward. To do this, look at the not I rule. It requires a subproof with A as assumption and bottom as its last line, so the proof is now.
Math summary: this represents a proof sequence in logic. It starts with the assumption of A implies B and not B. It proceeds through a series of logical steps, indicated by the vertical bars and ellipses. Eventually it derives not A, and from that it infers not B implies not A. Finally it concludes with A implies B implies not B implies not A, with annotations indicating the steps and rules applied in the proof.
Now our goal is to prove. We said above, when discussing how to work forward from a negated sentence, that the not sign E rule allows you to prove, which is our goal in the innermost subproof. So we look for a negated sentence which we can work forward from. That would be not sign B on line 2. That means we have to derive B inside the subproof, since not sign E requires not just not sign B, which we have already, but also B, and B in turn we get by working forward from A to B, since not sign E will allow us to justify the consequent of that conditional B by E. The rule not sign E also requires the antecedent A of the conditional, but that is also already available on line 3. So we finish with
Math summary: this represents a logical proof. It starts with the assumption that A implies B is true. Then assuming not B is true and A is true, B is derived using implication elimination from the first assumption. A contradiction is then derived. From this contradiction, not A is inferred. Finally, it concludes with not B implies not A. The proof proceeds by implication elimination at steps 4 and 5, and implication introduction at steps 6, 7, and 8, using the results from prior steps.
17.4 Working forward from. When applying the strategies, you will sometimes find yourself in a situation where you can justify. Using the explosion rule, this would allow you to justify anything. So it works like a wildcard in proofs. For instance, suppose you want to give a proof of the argument of B, not sign A, therefore B. You set up your proof, writing the premises of B and not sign A at the top on lines 1 and 2, and the conclusion B at the bottom of the page. B has no main connective, so you can't work backward from it. Instead, you must work forward from a B. That requires two subproofs, like so.
Math summary: the expression represents a logical proof. It starts with the premise A or B, and not A. It then assumes A, derives B, and concludes B at step m+1. Separately, it shows B at step k, and concludes B at step k+1. Finally, it concludes B. Image summary: the image shows a symbolic logic proof structure. The proof starts with two premises, a disjunction of A and B, and the negation of A. A subproof is initiated assuming A, leading to the conclusion B. Another subproof also leads to the conclusion B from these subproofs. The main proof concludes B. The structure demonstrates a proof by cases, where the disjunction is resolved by showing that B follows from both A and its negation.
Notice that you have not on line 2 and A as the assumption of your first subproof. That gives you bottom using not E, and from bottom you get the conclusion B of the first subproof using X. Recall that you can repeat a sentence you already have by using the reiteration rule R, so our proof would be.
Table summary: the table presents the steps of a logical proof, showing how to derive a conclusion from initial statements and assumptions using rules of inference. The proof involves disjunction elimination, negation, contradiction, and reiteration.
17.5 Proceed indirectly. In very many cases, the strategies of working forward and backward will eventually pan out, but there are cases where they do not work. If you cannot find a way to show a directly using those, use IP instead. To do this, set up a subproof in which you assume not sign A and look for a proof of inside that subproof.
Math summary: this represents a proof structure. It starts with a subproof from line N containing a negated statement A, continuing to a contradiction. Then on line m+1, the statement A is inferred using the indirect proof rule, referencing lines N through M.
Here, we have to start a subproof with assumption not A. The last line of the subproof has to be contradiction. We'll cite the subproof and use IP as the rule. In the subproof, we now have an additional assumption on line N to work with. Suppose we use the indirect proof strategy, or we're in some other situation where we're looking for a proof of what's a good candidate. Of course, the obvious candidate would be to use a negated sentence, since, as we saw above, not sign E always yields. If you set up a proof as above, trying to prove delta A using IP, you will have not sign A as the assumption of your subproof. So working forward from it to justify inside your subproof, you would next set up delta A as a goal inside your subproof. If you are using this IP strategy, you will find yourself in the following situation.
Math summary, this represents a proof structure using indirect proof. It starts with an assumption, the negation of a statement A, at line N within this subproof. There are intermediate steps leading to a contradiction, represented by the perpendicular symbol. At line M, this contradiction is derived using a negation elimination rule applied to lines N and M-1. Then at line M+1, the statement A is asserted using the indirect proof rule, which depends on lines N through M.
This looks weird. We wanted to prove A and the strategies failed us, so we used IP as a last resort. And now we find ourselves in the same situation. We are again looking for a proof of A, but notice that we are now inside a subproof, and in that subproof we have an additional assumption to work with which we didn't have before. Let's look at an example. 17.6 Indirect proof of excluded middle. The sentence A or not A is a tautology, and so should have a proof even without any premises. But working backward fails us. To get or not A using, or we would have to prove either or not A again from no premises. Neither of these is a tautology, so we won't be able to prove either. Working forward doesn't work either, since there is nothing to work forward from, so the only option is indirect proof.
Math summary, this represents an indirect proof. It starts with an assumption, specifically the negation of a statement. From this assumption, a contradiction is derived. Based on this contradiction, the original statement without the negation is proven using indirect proof, referencing the initial assumption and the contradiction.
Now we do have something to work forward from, the assumption not of open parenthesis A or not a close parenthesis. To use it, we justify bottom by not E, citing the assumption on line 1 and also the corresponding unnegated sentence A or not A, yet to be proved.
Math summary, this represents a proof by contradiction. It starts with an initial assumption, the negation of a statement. From this assumption, a contradiction is derived. This contradiction allows us to conclude the original statement is true using indirect proof. The process involves assuming the opposite of what you want to prove, deriving a contradiction, and then concluding the original statement.
At the outset, working backward to prove or not A by for all introduction did not work. But we are now in a different situation. We want to prove or not A inside a subproof. In general, when dealing with new goals, we should go back and start with the basic strategies. In this case, we should first try to work backward from the disjunction A or not A. That is, we have to pick a disjunct and try to prove it. Let's pick not A. This would let us justify A or not A on line M-1 using for all introduction. Then working backward from not A, we start another subproof in order to justify not A using not introduction. That subproof must have A as the assumption and bottom as its last line.
Image summary, the image shows a proof in propositional logic. The proof demonstrates that the formula A or not A is a tautology. The proof proceeds by assuming the negation of A or not A and deriving a contradiction, which allows one to conclude A or not A.
Inside this new subproof, we again need to justify. The best way to do this is to work forward from a negated sentence. A not sign A on line 1 is the only negated sentence we can use. The corresponding unnegated sentence, a not sign A, however, directly follows from a which we have on line 2 by I. Our complete proof is.
Math summary, this expression constructs a proof. It starts by assuming the negation of A or not A. It then assumes A. From A, it infers A or not A. From the negation of A or not A and A or not A, it derives a contradiction. From this contradiction, it infers not A. From A and not A, it infers A or not A. It then uses the negation of A or not A and A or not A to derive a contradiction. Finally, it infers A or not A using indirect proof, concluding that A or not A is true.
Practice exercises. A. Use the strategies to find proofs for each of the following arguments. 1 implies B, A implies C, therefore implies B and C. 2 left parenthesis A and B right parenthesis implies C, therefore A implies left parenthesis B implies C right parenthesis. 3 A implies open parenthesis B implies C close parenthesis, therefore open parenthesis A implies B close parenthesis implies open parenthesis A implies C close parenthesis. A or B and C, therefore A or B and A or C. 5. Left parenthesis A and B right parenthesis or left parenthesis A and C right parenthesis therefore A and left parenthesis B or C right parenthesis. 6. Or B, A implies C, B implies D therefore C or D. 7. Not or not B therefore not of A and B. 8. A and not B therefore not, open parenthesis, A implies B, close parenthesis. B. Formulate strategies for working backward and forward from a double arrow B. C. Use the strategies to find proofs for each of the following sentences. 1. Not implies bottom. 2. Not open parenthesis A and not a close parenthesis.
Math summary. The first expression states that if it implies C and B implies C, then A or B implies C. The second expression states that if it is not the case that it implies B, then A and not B. The third expression states that if not A or B, then it implies B.
Since these should be proofs of sentences from no premises, you will start with the respective sentence at the bottom of the proof, which will have no premises. D. Use the strategies to find proofs for each one of the following arguments and sentences. 1. Not A implies A. 2. Not implies not B therefore B implies. 3. A implies B therefore not A or B. 4. Not of A and B implies not or not B. 5. Implies B or C therefore A implies B or A implies C. 6. A implies B or B implies A. 7. A implies B, implies A. These all will require the IP strategy. The last three especially are quite hard. Chapter 18. Additional rules for TFL. In section 16, we introduced the basic rules of our proof system for TFL. In this section, we will add some additional rules to our system. Our extended proof system is a bit easier to work with. However, in section 20, we will see that they are not strictly speaking necessary. 18.1 Disjunctive Syllogism. Here is a very natural argument form. Elizabeth is either in Massachusetts or in DC. She is not in DC, so she is in Massachusetts. This is called disjunctive syllogism. We add it to our proof system as follows, and as usual, the disjunction and the negation of one disjunct may occur in either order and need not be adjacent. However, we always cite the disjunction first.
Image summary. The image shows a symbolic logic proof. It displays a disjunctive syllogism, where from a disjunction and the negation of one disjunct, the other disjunct is inferred. The proof shows that from the premise A or B and the premise not A, one can conclude B using the disjunctive syllogism rule. Table summary. The table illustrates a rule of inference, showing how a conclusion is derived from two premises using disjunctive syllogism.
18.2 Modus tollens. Another useful pattern of inference is embodied in the following argument. If Hillary has won the election, then he is in the White House. She is not in the White House, so she has not won the election. This inference pattern is called modus tollens. The corresponding rule is.
Math summary. This represents two instances of modus tollens. For the first instance, given a premise if a then B and the premise not B, the conclusion not A is derived. The second instance follows the exact same logical structure. Given if a then B and not B, the conclusion not A is derived.
As usual, the premises may occur in either order, but we always cite the conditional first. 18.3 Double negation elimination. Another useful rule is double negation elimination. It does exactly what it says on the tin.
Table summary. The table presents the double negation elimination rule, where a double negation of a statement is equivalent to the statement itself.
The justification for this is that, in natural language, double negations tend to cancel out. That said, you should be aware that context and emphasis can prevent them from doing so. Consider, Jane is not happy. Arguably, one cannot infer Jane is happy, since the first sentence should be understood as meaning the same as Jane is not unhappy. This is compatible with Jane is in a state of profound indifference. As usual, moving to TFL forces us to sacrifice certain nuances of English expressions. 18.4 Excluded middle. Suppose that we can show that if it's sunny outside, then Bill will have brought an umbrella for fear of burning. Suppose we can also show that if it's not sunny outside, then Bill will have brought an umbrella for fear of rain. Well, there is no third way for the weather to be, so whatever the weather, Bill will have brought an umbrella. This line of thinking motivates the following rule.
Table summary. The table presents symbolic representations of logical relationships. Some expressions are shown as absolute values of ratios, with variations in the numerator's sign. One expression involves the absolute value of a single term.
The rule is sometimes called the law of excluded middle, since it encapsulates the idea that a may be true or not a may be true, but there is no middle way where neither is true. There can be as many lines as you like between I and J, and as many lines as you like between K and L. Moreover, the subproofs can come in any order, and the second subproof does not need to come immediately after the first. To see the rule in action, consider.
Math summary: the expression represents a logical argument. It states that from a premise P, it follows that either P and D are both true, or P is true and D is not true.
Here is a proof corresponding with the argument.
Math summary: the expression presents a logical proof in 3 parts. The first part starts with premises P and D, then performs a logical AND operation on P and D. Finally, it performs a logical OR operation between the result of the AND operation and the AND of P and the negation of D. The second part starts with the negation of D, then performs a logical AND operation on P and the negation of D. Finally, it performs a logical OR operation between the result of the AND operation from the first part and the AND operation from this part. The third part takes the result of the logical OR operation from both previous parts.
Here is another example.
Math summary: the expression presents a logical argument. It starts with an initial statement A implying not A from this, not A is derived, then not A is repeated. Finally, using a rule called lem, not A is concluded.
18.5 De Morgan Rules. Our final additional rules are called De Morgan's laws, named after Augustus De Morgan. The shape of the rules should be familiar from truth tables. The first De Morgan rule is: the second De Morgan is the reverse of the first. The third De Morgan rule is the dual of the first. And the fourth is the reverse of the third.
Table summary: the table presents an equivalence, where one expression is rewritten into another, using De Morgan's law.
These are all of the additional rules of our proof system for TFL.
Algorithm M summary: the algorithm takes a logical expression as input and applies De Morgan's law to it. Specifically, it transforms the negation of a conjunction of a logical variable with itself into the disjunction of the negation of the variable with itself. The input is a logical expression, and the output is a logically equivalent, but structurally different, expression. Algorithm None summary: the algorithm applies De Morgan's law to transform a logical expression. It takes a logical expression as input and outputs an equivalent expression where the negation is distributed and the conjunction is changed to a disjunction, or vice versa. The specific transformation involves negating individual components and switching between conjunction and disjunction. Figure M summary: the code block presents a logical equivalence rule. It takes a negated disjunction as input and transforms it into a conjunction of negated components. This transformation is based on De Morgan's law.
Practice exercises. A. The following proofs are missing their citations, rule, and line numbers. Add them wherever they are required.
Table summary: the table presents 2 distinct logical derivations. The first derivation involves a series of implications and conjunctions, leading to the extraction of a specific element. The second derivation uses a biconditional statement and disjunction, ultimately resulting in a contradiction and subsequent reaffirmation of an element. Table summary: the table presents different logical statements and their corresponding derivations or implications. Each row illustrates a step-by-step deduction process, leading to a conclusion, often a contradiction.
B. Give a proof for each of these arguments. 1. E or F, F or G, not F, therefore E and G. 2. M or N implies M, therefore not M implies not N. 3. Left parenthesis M or N right parenthesis and left parenthesis O or P right parenthesis. N implies P, not P, therefore M and O. 4. X and Y or X and Z, not of X and D, D or M, therefore M. Chapter 19. Proof Theoretic Concepts. In this chapter we will introduce some new vocabulary. The following expression.
Math summary: this expression represents a proof theoretic concept. It states that there exists a proof that ends with a conclusion, given a set of assumptions. The assumptions are a list of items, and the turnstile symbol indicates that the conclusion can be proven from these assumptions.
Means that there is some proof which ends with calligraphic C whose undischarged assumptions are among calligraphic A sub 1, calligraphic A sub 2, through calligraphic A sub n, when we want to say that it is not the case that there is some proof which ends with calligraphic C from calligraphic A sub 1, calligraphic A sub 2, through calligraphic A sub n, we write.
Math summary: this expression states that a collection of items, named a sub 1, a sub 2, and so on up to a sub n, are not a subset of the collection named C.
The symbol A is called the single turnstile. We want to emphasize that this is not the double turnstile symbol that we introduced in Chapter 12 to symbolize entailment. The single turnstile concerns the existence of proofs. The double turnstile concerns the existence of valuations or interpretations when used for FOL. They are very different notions. Armed with our symbol, we can introduce some more terminology. To say that there is a proof of A with no undischarged assumptions, we write A. In this case, we say that it is a theorem.
Code summary. The provided text defines what a theorem is in terms of provability. A statement is a theorem if and only if it can be proven. It also defines provable equivalence between two statements. Two statements are provably equivalent if each can be proven from the other.
To illustrate this, suppose we want to show that A naught sin A is a theorem. So we need a proof of A naught sin A, which has no undischarged assumptions. However, since we want to prove a sentence whose main logical operator is a negation, we will want to start with a subproof within which we assume a naught sin A and show that this assumption leads to contradiction. All told, then, the proof looks like this.
Math summary. This expression represents a proof by contradiction. It starts by assuming a statement A and not A is true. From this assumption, it derives A and not A individually. These contradictory conclusions lead to a contradiction symbol. Finally, it concludes that the negation of the initial assumption, not A and not A, is true, based on the contradiction derived from lines 1 through 4.
We have therefore proved A naught sin A on no undischarged assumptions. This particular theorem is an instance of what is sometimes called the law of non-contradiction. To show that something is a theorem, you just have to find a suitable proof. It is typically much harder to show that something is not a theorem. To do this, you would have to demonstrate not just that certain proof strategies fail, but that no proof is possible. Even if you fail in trying to prove a sentence in 1,000 different ways, perhaps the proof is just too long and complex for you to make out. Perhaps you just didn't try hard enough. Here is another new bit of terminology. Two sentences A and B are provably equivalent if and only if each can be proved from the other. That is, both A proves B and B proves A. As in the case of showing that a sentence is a theorem, it is relatively easy to show that two sentences are provably equivalent. It just requires a pair of proofs. Showing that sentences are not provably equivalent would be much harder. It is just as hard as showing that a sentence is not a theorem. Here's a third related bit of terminology. The sentences a sub 1, a sub 2, and so on to a sub n are provably inconsistent if and only if a contradiction can be proved from them. That is, a sub 1, a sub 2, and so on to a sub n perpendicular. If they are not inconsistent, we call them provably consistent. It is easy to show that some sentences are provably inconsistent. You just need to prove a contradiction from assuming all the sentences. Showing that some sentences are not provably inconsistent is much harder. It would require more than just providing a proof or two. It would require showing that no proof of a certain kind is possible. This table summarizes whether one or two proofs suffice, or whether we must reason about all possible proofs.
Table summary. The table contrasts the number of proofs needed to establish whether a statement is a theorem, inconsistent, equivalent, or consistent. For theorem and inconsistent statements, a single proof is sufficient to confirm, while all possible proofs are needed to deny. Equivalence requires two proofs for confirmation, but all possible proofs for denial. Consistency demands all possible proofs for affirmation, but only one proof for negation.
Practice exercises. A. Show that each of the following sentences is a theorem. 1 0 goes to 0. 2 n or not n. 3 j if and only if open bracket j or open parenthesis l and not l close parenthesis close bracket. 4 A implies B implies A. B. Provide proofs to show each of the following. 1 C implies the quantity E and G, not C implies G, therefore G. 2 M and not N implies not M proves N and M or not M. 3 Z and K if and only if Y and M, D and D implies M proves Y implies C. 4 left parenthesis W or X right parenthesis or left parenthesis Y or Z right parenthesis. X implies Y not Z, therefore W or Y. C. Show that each of the following pairs of sentences are provably equivalent. 1 R if and only if E, E if and only if R. 2 G not G. 3 T implies S, not S implies not T. 4 U implies I, not of open parenthesis U, and not I close parenthesis. 5 not open parenthesis C implies D, close parenthesis, comma, C and not D. 6. Not G if and only if H, not G if and only if H. D. If you know that approves script B, what can you say about open parenthesis script A and script C close parenthesis proves script B? What about open parenthesis script A or script C close parenthesis proves script B? Explain your answers. E. In this chapter, we claimed that it is just as hard to show that two sentences are not provably equivalent as it is to show that a sentence is not a theorem. Why did we claim this? Hint, think of a sentence that would be a theorem if A and B were provably equivalent. Chapter 20. Derived Rules. In this section, we will see why we introduced the rules of our proof system in two separate batches. In particular, we want to show that the additional rules of Section 18 are not strictly speaking necessary, but can be derived from the basic rules of Section 16. 20.1 Derivation of Reiteration. To illustrate what it means to derive a rule from other rules, first consider reiteration. It is a basic rule of our system, but it is also not necessary. Suppose you have some sentence on some line of your deduction.
Math summary. This expression represents a statement that is provable from the set of assumptions. A.
You now want to repeat yourself on some line K. You could just invoke the rule R, but equally well, you can do this with other basic rules of Section 16.
Math summary. This represents a logical derivation. It starts with a statement A on line M, then on line K. It forms the conjunction of A with itself, A and A finally, on line K plus 1. It extracts A from the conjunction using the elimination rule applied to line K.
To be clear, this is not a proof. Rather, it is a proof scheme. After all, it uses a variable, rather than a sentence of TFL, but the point is simple. Whatever sentences of TFL we plugged in for A, and whatever lines we were working on, we could produce a bona fide proof. So you can think of this as a recipe for producing proofs. Indeed, it is a recipe which shows us the following. Anything we can prove using the rule R, we can prove with one more line, using just the basic rules of Section 16 without R. That is what it means to say that the rule R can be derived from the other basic rules. Anything that can be justified using R can be justified using only the other basic rules. 20.2 Derivation of Disjunctive Syllogism. Suppose that you are in a proof and you have something of this form.
Math summary. This represents a logical argument. On line M, we have either statement O or statement B. On line N, we have the negation of statement A.
You now want, on line K, to prove B. You can do this with the rule of DS, introduced in Section 18, but equally well, you can do this with the basic rules of Section 16.
Math summary. This describes a proof sequence in logic. It starts with premises on lines M and N on line M. It states A or B on line N. It states not A line K begins a subproof, assuming A line K plus 1 derives a contradiction using not E applied to lines N, and K line K plus 2 states B, derived by rule X from line K plus 1. Line K plus 3 states B. Line K plus 4 states B, derived by rule R from line K plus 3. Line K plus 5 concludes B, derived by rule or E applied to lines M, K minus K plus 2, and K plus 3 minus K plus 4.
So the DS rule again can be derived from our more basic rules. Adding it to our system did not make any new proofs possible. Anytime you use the DS rule, you could always take a few extra lines and prove the same thing using only our basic rules. It is a derived rule. 20.3 Derivation of Modus tollens. Suppose you have the following in your proof.
Math summary. This expression represents a logical deduction rule. It states that if statement A implies statement B and statement B is false, then statement A must also be false. This rule is applied twice, once on line M and again on line N.
You now want, on line K, to prove not A. You can do this with the rule of MT, introduced in Section 18. Equally well, you can do this with the basic rules of Section 16.
Math summary. The expression represents a logical derivation within a proof system. It starts with premises and implies B and not B subsequently. It introduces a series of steps indexed by K, K plus 1, and K plus 2, where A and B are asserted, leading to a contradiction, represented by the perpendicular symbol, and the negation of an expression E. The final step at K plus 3 concludes with not A, derived from the negation introduction rule applied to a range of steps.
Again, the rule of MT can be derived from the basic rules of Section 16. 20.4 Derivation of Double Negation Elimination. Consider the following deduction scheme.
Math summary. The expression represents a logical derivation. It starts with a premise at step M, containing a double negation of statement A and a variable k. Then, at step k plus 1, it introduces a matrix-like structure. This structure contains the negation of statement A, a contradiction symbol, the negation of an elimination rule applied to M and K, statement A, and an identity proof involving k minus k plus 1.
Again, we can derive the DNE rule from the basic rules of section 16. 20.5 Derivation of excluded middle. Suppose you want to prove something using the lem rule, that is, you have in your proof.
Math summary, there are two separate expressions. The first expression has a vertical bar containing a above b, which is preceded by the variable m. The result is associated with the variable, and the second expression has two parts, one associated with k and the other with l. The part associated with k has a vertical bar containing the negation of above b. The part associated with l has a vertical bar containing a repeating sequence of b above a repeated 4 times.
You now want on line L plus 1 to prove B. The rule lem from section 18 would allow you to do it, but can do this with the basic rules of section 16. One option is to first prove O or not A, and then apply or E, that is proof by cases.
Math summary, this represents a logical argument or proof structure. It involves assumptions labeled M and N, which introduce propositions A and B respectively. There are also assumptions labeled K and L, which introduce the negation of A and B respectively. Further, there is a step labeled I which introduces the tautology A or not A from this. It derives B at step I plus 1. The final line applies the or elimination rule, using the steps I, the range M to N, and the range K to L.
We gave a proof of O or not A using only our basic rules in section 17.6. Here is another way that is a bit more complicated than the ones before. What you have to do is embed your two subproofs inside another subproof. The assumption of the subproof will be not B, and the last line will be contradiction. Thus, the complete subproof is the kind you need to conclude B using IP. Inside the proof, you'd have to do a bit more work to get contradiction.
\\\begin array L, m \begin array L, m plus 1 \\n n plus 1 n plus 2 end array, \quad begin array L, underline text, \quad box day box v dots, box perp, box quad l not, a box v dots, box quad mathcal b, box perp, end array, quad begin array L, text, quad textdm. In text, text, quad text, quad text, text, quad text, quad text, quad text, 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 quad text, quad text, quad text, text, quad text, quad text, quad text. Text, text, quad text, quad text, quad text, text, quad text, quad text, quad text, text, quad text, quad text, quad text, text, quad text, quad text. Quad text, 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 quad text, quad text, quad text, text, quad text, quad text, quad text, text, quad text, quad text, quad text, text, quad text. Quad text, quad text, text, quad text, quad text, quad text, text, quad text, quad text, quad text, text, quad text, quad text, quad text, text. Quad text, quad text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text, backslash quad backslash text, backslash 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 text, backslash quad backslash text, backslash quad backslash text.
Note that because we add an assumption at the top and additional conclusions inside the subproofs, the line numbers change. You may have to stare at this for a while before you understand what's going on. 20.6 Derivation of De Morgan Rules. Here is a demonstration of how we could derive the first De Morgan rule.
Math summary: the expression represents a series of logical deductions. It starts with an initial statement and applies logical rules to derive new statements. The process involves negations, conjunctions, disjunctions, and the application of inference rules. The final result is a logical statement derived from the initial assumptions through a series of logical steps.
Here is a demonstration of how we could derive the second De Morgan rule.
Math summary: this represents a proof or derivation in a logical system. It starts with an assumption at line M, which is the negation of A or the negation of B at line K plus 1. A and B is introduced, derived from line K at line K plus 3. The negation of A is introduced, leading to a contradiction, derived using negation elimination from lines K plus 3 and K plus 1. At line K plus 5, another contradiction is reached, derived using negation elimination from lines K plus 5 and K plus 2. At line K plus 6, a contradiction is shown. Finally, at line K plus 8, A and B is introduced, derived using negation introduction from lines K to K plus 7.
Similar demonstrations can be offered explaining how we could derive the third and fourth De Morgan rules. These are left as exercises. Practice exercises. A. Provide proof schemes that justify the addition of the third and fourth De Morgan rules as derived rules. B. The proofs you offered in response to the practice exercises of section 18 to 19 use derived rules. Replace the use of derived rules in such proofs with only basic rules. You will find some repetition in the resulting proofs. In such cases, offer a streamlined proof using only basic rules. This will give you a sense both of the power of derived rules and of how all the rules interact. C. Give a proof of or not. A. Then give a proof that uses only the basic rules. D. Show that if you had lem as a basic rule, you could justify IP as a derived rule. That is, suppose you had the proof.
Math summary: this represents a proof structure. It begins with an assumption labeled M, followed by a derivation involving the negation of a proposition A, continuing with further steps represented by ellipsis, and ultimately leading to a contradiction, represented by the symbol for falsity. The proof concludes at line N.
How could you use it to prove A without using IP, but with using lem as well as all the other basic rules? E. Give a proof of the first De Morgan rule, but using only the basic rules in particular without using lem. Of course, you can combine the proof using lem with the proof of lem. try to find a proof directly. Chapter 21. Soundness and Completeness. In Section 19, we saw that we could use derivations to test for the same concepts we use truth tables to test for. Not only could we use derivations to prove that an argument is valid, we could also use them to test if a sentence is a tautology or a pair of sentences are equivalent. We also started using the single turnstile the same way we used the double turnstile. If we could prove that it was a tautology with a truth table, we wrote A, and if we could prove it using a derivation, we wrote A. You may have wondered at that point if the two kinds of turnstiles always worked the same way. If you can show that it is a tautology using truth tables, can you also always show that it is a theorem using a derivation? Is the reverse true? Are these things also true for valid arguments and pairs of equivalent sentences? As it turns out, the answer to all these questions and many more like them is yes. We can show this by defining all these concepts separately and then proving them equivalent. That is, we imagine in E that we actually have two notions of validity, valid sub E and valid sub F, and then show that the two concepts always work the same way. To begin with, we need to define all of our logical concepts separately for truth tables and derivations. A lot of this work has already been done. We handled all of the truth table definitions in Section 12. We have also already given syntactic definitions for tautologies, theorems, and pairs of logically equivalent sentences. The other definitions follow naturally. For most logical properties, we can devise a test using derivations, and those that we cannot test for directly can be defined in terms of the concepts that we can define. For instance, we defined a theorem as a sentence that can be derived without any premises, p. 170. Since the negation of a contradiction is a tautology, we can define a syntactic contradiction in TFL as a sentence whose negation can be derived without any premises. The syntactic definition of a contingent sentence is a little different. We don't have any practical finite method for proving that a sentence is contingent using derivations, the way we did using truth tables. So we have to content ourselves with defining contingent sentence negatively. A sentence is syntactically contingent in TFL if it is not a theorem or a contradiction. A collection of sentences are provably inconsistent in TFL if and only if one can derive a contradiction from them. Consistency, on the other hand, is like contingency, in that we do not have a practical finite method to test for it directly. So again, we have to define a term negatively. A collection of sentences is provably consistent in TFL if and only if they are not provably inconsistent. Finally, an argument is provably valid in TFL if and only if there is a derivation of its conclusion from its premises. All of these definitions are given in Table 21.1.
Table 21.1 Summary. The table provides both semantic and syntactic definitions for various logical concepts. The semantic definitions rely on truth tables, while the syntactic definitions are based on derivability and theorems.
All of our concepts have now been defined both semantically and syntactically. How can we prove that these definitions always work the same way? A full proof here goes well beyond the scope of this book. However, we can sketch what it would be like. We will focus on showing the two notions of validity to be equivalent. From that, the other concepts will follow quickly. The proof will have to go in two directions. First, we will have to show that things which are syntactically valid will also be semantically valid. In other words, everything that we can prove using derivations could also be proven using truth tables. Put symbolically, we want to show that valid plus implies valid plus. Afterwards, we will need to show things in the other directions. Valid plus implies valid plus. This argument from 2 is the problem of soundness. A proof system is sound if there are no derivations of arguments that can be shown invalid by truth tables. Demonstrating that the proof system is sound would require showing that any possible proof is the proof of a valid argument. It would not be enough simply to succeed when trying to prove many valid arguments and to fail when trying to prove invalid ones. The proof that we will sketch depends on the fact that we initially defined a sentence of TFL using an inductive definition, CP 51. We could have also used inductive definitions to define a proper proof in TFL and a proper truth table. Although we didn't. If we had these definitions, we could then use an inductive proof to show the soundness of TFL. An inductive proof works the same way as an inductive definition. With the inductive definition, we identified a group of base elements that were stipulated to be examples of the thing we were trying to define. In the case of a TFL sentence, the base class was the set of sentence letters A, B, C. We just announced that these were sentences. The second step of an inductive definition is to say that anything that is built up from your base class using certain rules also counts as an example of the thing you are defining. In the case of a definition of a sentence, the rules corresponded to the 5 sentential connectives, CP 51. Once you have established an inductive definition, you can use that definition to show that all the members of the class you have defined have a certain property. You simply prove that the property is true of the members of the base class, and then you prove that the rules for extending the base class don't change the property. This is what it means to give an inductive proof. Even though we don't have an inductive definition of a proof in TFL, we can sketch how an inductive proof of the soundness of TFL would go. Imagine a base class of one-line proofs, one for each of our 11 rules of inference. The members of this class would look like this: A, B entails A and B entails A or B, not A entails B, and so on. Etc. Since some rules have a couple different forms, we would have to add some members to this base class. For instance, A and B entails B. Notice that these are all statements in the metalanguage. The proof that TFL is sound is not a part of TFL because TFL does not have the power to talk about itself. You can use truth tables to prove to yourself that each of these one-line proofs in this base class is valid. For instance, the proof A, B right tack a wedge B corresponds to a truth table that shows A, B double right tack a wedge B. This establishes the first part of our inductive proof. The next step is to show that adding lines to any proof will never change a valid underscore proof into an invalid underscore one. We would need to do this for each of our 11 basic rules of inference. So for instance, for an introduction we need to show that for any proof a sub 1 through a sub n direct sum be adding a line where we use an introduction to infer C and D, where C and D can be legitimately inferred from a sub 1 through a sub n b would not change a valid proof into an invalid proof. But wait, if we can legitimately derive C and D from these premises, then C and D must be already available in the proof. They are either already among a sub 1 through a sub n b or can be legitimately derived from them. As such, any truth table line in which the premises are true must be a truth table line in which C and D are true. According to the characteristic truth table for, this means that CD is also true on that line. Therefore, CD validly follows from the premises. This means that using the wedge E rule to extend a valid proof produces another valid proof. In order to show that the proof system is sound, we would need to show this for the other inference rules. Since the derived rules are consequences of the basic rules, it would suffice to provide similar arguments for the 11 other basic rules. This tedious exercise falls beyond the scope of this book. So we have shown that a proves B implies a models B. What about the other direction? That is why I think that every argument that can be shown valid using truth tables can also be proven using a derivation. This is the problem of completeness. A proof system has the property of completeness if and only if there is a derivation of every semantically valid argument. Proving that a system is complete is generally harder than proving that it is sound. Proving that a system is sound amounts to showing that all of the rules of your proof system work the way they are supposed to. Showing that a system is complete means showing that you have included all the rules you need, that you haven't left any out. Showing this is beyond the scope of this book. The important point is that happily the proof system for TFL is both sound and complete. This is not the case for all proof systems or all formal languages. Because it is true of TFL, we can choose to give proofs or give truth tables, whichever is easier for the task at hand. Now that we know that the truth table method is interchangeable with the method of derivations, you can choose which method you want to use for any given problem. Students often prefer to use truth tables because they can be produced purely mechanically, and that seems easier. However, we have already seen that truth tables become impossibly large after just a few sentence letters. On the other hand, there are a couple situations where using proofs simply isn't possible. We syntactically defined a contingent sentence as a sentence that couldn't be proven to be a tautology or a contradiction. There is no practical way to prove this kind of negative statement. We will never know if there isn't some proof out there that a statement is a contradiction and we just haven't found it yet. We have nothing to do in this situation but resort to truth tables. Similarly, we can use derivations to prove two sentences equivalent, but what if we want to prove that they are not equivalent? We have no way of proving that. We will never find the relevant proof, so we have to fall back on truth tables again. Table 21.2 summarizes when it is best to give proofs and when it is best to give truth tables.
Table 21.2 Summary. The table describes how to prove the presence or absence of logical properties. Proving presence often involves derivation, while proving absence typically involves finding specific lines in truth tables. There are some exceptions, such as proving the absence of contingency, requiring proving the sentence or its negation.
Practice exercises. A. Use either a derivation or a truth table for each of the following. 1. Show that it implies open bracket B and C or D close bracket implies A is a theorem. 2. Show that A implies open parenthesis A implies B close parenthesis is not a theorem. 3. Show that the sentence A implies not A is not a contradiction. 4. Show that the sentence A if and only if not A is a contradiction. 5. Show that the sentence not open parenthesis W implies open parenthesis J or J close parenthesis is contingent. 6. Show that the sentence not open parenthesis X or open parenthesis Y or Z close parenthesis or open parenthesis X or open parenthesis Y or Z close parenthesis is not contingent. 7. Show that the sentence B implies not S is equivalent to the sentence not B implies not S. 8. Show that the sentence not open parenthesis X or O close parenthesis is not equivalent to the sentence X and O. 9. Show that the sentences not of open parenthesis A or B close parenthesis C implies are jointly inconsistent. 10. Show that the sentences not open parenthesis A or B close parenthesis not B implies are jointly consistent. 11. Show that not of open parenthesis A or open parenthesis B or C close parenthesis therefore not C is valid. 12. Show that not of open parenthesis A and open parenthesis B or C close parenthesis therefore not C is invalid. B. Use either a derivation or a truth table for each of the following. 1. Show that implies B implies is a theorem. 2. Show that not open parenthesis N if and only if Q close parenthesis or Q or N is not a theorem. 3. Show that Z or open parenthesis not Z if and only if Z close parenthesis is contingent. 4. Show that L if and only if open parenthesis N implies N close parenthesis implies L or H is not contingent. 5. Show that open parenthesis A if and only if a close parenthesis and open parenthesis B and not B close parenthesis is a contradiction. 6. Show that open parenthesis B if and only if open parenthesis C or B close parenthesis is not a contradiction. 7. Show that the expression open parenthesis not X if and only if X close parenthesis or X is equivalent to X. 8. Show that F and K in R is not equivalent to F if and only if K if and only if R. 9. Show that the sentences not W implies W if and only if W and W, E or W implies not E and W are jointly inconsistent. 10. Show that the sentences not R or C and R implies not R or R implies R are jointly consistent. 11. Show that not C if and only if not C, G or G therefore G implies C and G is valid. 12. Show that not L, C implies not 50 implies C therefore not C is invalid. Part 5. First order logic. Chapter 22. Building blocks of FOL. 22.1 The need to decompose sentences. Consider the following argument, which is obviously valid in English. Willard is a logician. All logicians wear funny hats. Willard wears a funny hat. To symbolize it in TFL, we might offer a symbolization key. L. Willard is a logician. A. All logicians wear funny hats. F. Willard wears a funny hat. And the argument itself becomes.
Math summary. This represents a logical argument. It starts with two premises, L, which stands for Willard is a logician, and A, which stands for all logicians wear funny hats. The therefore symbol indicates a conclusion, F, which stands for Willard wears a funny hat.
But the truth table test will now indicate that this is invalid. What has gone wrong? The problem is not that we have made a mistake while symbolizing the argument. This is the best symbolization we can give in TFL. The problem lies with TFL itself. All logicians wear funny hats is about both logicians and hat wearing. By not retaining this structure in our symbolization, we lose the connection between Willard's being a logician and Willard's wearing a hat. The basic units of TFL are sentence letters, and TFL cannot decompose these. To symbolize arguments like the preceding one, we will have to develop a new logical language which will allow us to split the atom. We will call this language first-order logic, or FOL. The details of FOL will be explained throughout this chapter, but here is the basic idea for splitting the atom. First, we have names. In FOL, we indicate these with lowercase italic letters. For instance, we might let B stand for Bertie or let I stand for Willard. Second, we have predicates. English predicates are expressions like is a dog or is a logician. These are not complete sentences by themselves. In order to make a complete sentence, we need to fill in the gap. We need to say something like Bertie is a dog or Willard is a logician. In FOL, we indicate predicates with uppercase italic letters. For instance, we might let the FOL predicate D symbolize the English predicate is a dog. Then the expression DB will be a sentence in FOL which symbolizes the English sentence Bertie is a dog. Equally, we might let the FOL predicate L symbolize the English predicate is a logician. Then the expression LI will symbolize the English sentence Willard is a logician. Third, we have quantifiers. For instance, will roughly convey there is at least one, so we might symbolize the English sentence there is a dog with the FOL sentence XDX, which we might read aloud as there is at least one thing X such that X is a dog. That is the general idea, but FOL is significantly more subtle than TFL, so we will come at it slowly. 22.2 Names. In English, a singular term is a word or phrase that refers to a specific person, place, or thing. The word dog is not a singular term because there are a great many dogs. The phrase Bertie is a singular term because it refers to a specific terrier. Likewise, the phrase Philip's dog Bertie is a singular term because it refers to a specific little terrier. Proper names are a particularly important kind of singular term. These are expressions that pick out individuals without describing them. The name Emerson is a proper name, and the name alone does not tell you anything about Emerson. Of course, some names are traditionally given to boys and others are traditionally given to girls. If Hillary is used as a singular term, you might guess that it refers to a woman. You might, though, be guessing wrongly. Indeed, the name does not necessarily mean that the person referred to is even a person. Hillary might be a giraffe for all you could tell just from the name. In FOL, our NAMES are lowercase letters A through to R. We can add subscripts if we want to use some letter more than once. So here are some singular terms in FOL.
Math summary. This represents a sequence of names in formal logic. The names consist of lowercase letters from A to R, and also include subscripted letters such as a sub 1, F sub 32, J sub 390, and M sub 12.
These should be thought of along the lines of proper names in English, but with one difference. Tim Butt is a proper name, but there are several people with this name. Equally, there are at least two people with the name P.D. Magnus. We live with this kind of ambiguity in English, allowing context to individuate the fact that Tim Butt refers to an author of this book and not some other Tim. In FOL, we do not tolerate any such ambiguity. Each name must pick out exactly one thing. However, two different names may pick out the same thing. As with TFL, we can provide symbolization keys. These indicate temporarily what a name will pick out, so we might offer Elsa. 22.3 Predicates. The simplest predicates are properties of individuals. They are things you can say about an object. Here are some examples of English predicates. Is a dog is a member of Monty Python. A piano fell on. In general, you can think about predicates as things which combine with singular terms to make sentences. Conversely, you can start with sentences and make predicates out of them by removing terms. Consider the sentence, Vinny borrowed the family car from Nunzio. By removing a singular term, we can obtain any of three different predicates. Underscore text borrowed the family car from Nunzio. Vinny borrowed from Nunzio. Vinny borrowed the family car from. In FOL, predicates are capital letters A through Z with or without subscripts. We might write a symbolization key for predicates thus. Of X is angry. H of X is happy. Y the subscripts on the gaps. We will return to this in section 24. If we combine our two symbolization keys, we can start to symbolize some English sentences that use these names and predicates in combination. For example, consider the English sentences. 1. Elsa is angry. 2. Gregor and Maribeth are angry. 3. If Elsa is angry, then so are Gregor and Maribeth. Sentence 1 is straightforward. We symbolize it by AE. Sentence 2, this is a conjunction of two simpler sentences. The simple sentences can be symbolized just by AG and AM. Then we help ourselves to our resources from TFL and symbolize the entire sentence by AG, AM. This illustrates an important point. FOL has all of the truth functional connectives of TFL. Sentence 3, this is a conditional whose antecedent is sentence 1 and whose consequent is sentence 2. So we can symbolize this with A of E implies open parenthesis A of G and A of M close parenthesis. 22.4 Quantifiers. We are now ready to introduce quantifiers. Consider these sentences. 4. Everyone is happy. 5. Someone is angry. It might be tempting to symbolize sentence 4 as HEHGHM, yet this would only say that Elsa, Gregor, and Maribeth are happy. We want to say that everyone is happy, even those with no names. In order to do this, we introduce the symbol. This is called the universal quantifier. The quantifier must always be followed by a variable. In FOL, variables are italic lowercase letters through Z with or without subscripts. So we might symbolize sentence 4 as ForAllX HX. The variable x is serving as a kind of placeholder. The expression ForAllX intuitively means that you can pick anyone and put them in as x. The subsequent hx indicates of that thing you picked out that it is happy. It should be pointed out that there is no special reason to use x rather than some other variable. The sentences for all x h of x, for all y h of y, for all z h of z, and for all x sub 5 h of x sub 5 use different variables, but they will all be logically equivalent. To symbolize sentence 5, we introduce another new symbol, the existential quantifier. There exists. Like the universal quantifier, the existential quantifier requires a variable. Sentence 5 can be symbolized by there exists x a of x. Whereas for all x a of x is read naturally as for all x is angry, there exists x a of x is read naturally as there is something x such that x is angry. Once again, the variable is a kind of placeholder. We could just as easily have symbolized sentence 5 by there exists z a of z, there exists w sub 256, a of w sub 256, or whatever. Some more examples will help. Consider these further sentences. 6. No one is angry. 7. There is someone who is not happy. 8. Not everyone is happy. Sentence 6 can be paraphrased as, it is not the case that someone is angry. We can then symbolize it using negation and an existential quantifier, not x. Yet sentence 6 could also be paraphrased as, everyone is not angry. With this in mind, it can be symbolized using negation and a universal quantifier, for all x not ax. Both of these are acceptable symbolizations. Indeed, it will transpire that in general, for all x not a is logically equivalent to not xa. Notice that we have here returned to the practice of using a as a meta-variable from section 8. Symbolizing a sentence one way rather than the other might seem more natural in some contexts, but it is not much more than a matter of taste. Sentence 7 is most naturally paraphrased as, there is some x such that x is not happy. This then becomes x not sin h, x. Of course, we could equally have written not xhx, which we would naturally read as it is not the case that everyone is happy. That too would be a perfectly adequate symbolization of sentence 8. 22.5 Domains. Given the symbolization key we have been using, xhx symbolizes everyone is happy. Who is included in this everyone? When we use sentences like this in English, we usually do not mean everyone now alive on the earth. We certainly do not mean everyone who is ever alive or who will ever live. We usually mean something more modest, everyone now in the building, everyone enrolled in the ballet class, or whatever. In order to eliminate this ambiguity, we will need to specify a domain. The domain is the collection of things that we are talking about. So if we want to talk about people in Chicago, we define the domain to be people in Chicago. We write this at the beginning of the symbolization key like this. Domain people in Chicago. The quantifiers range over the domain. Given this domain, x is to be read roughly as every person in Chicago is such that, and x is to be read roughly as some person in Chicago is such that. In FOL, the domain must always include at least one thing. Moreover, in English, we can legitimately infer something is angry from Gregor is angry. In FOL, then, we will want to be able to infer exists xax from ag. So we will insist that each name must pick out exactly one thing in the domain. If we want to name people and places besides Chicago, then we need to include those people in the domain. A domain must have at least one member. Every name must pick out exactly one member of the domain, but a member of the domain may be picked out by one name, many names, or none at all. Even allowing for a domain with just one member can produce some strange results. Suppose we have this as a symbolization key, domain, the Eiffel Tower P of x is in Paris. The sentence for all x, P of x might be paraphrased in English as everything is in Paris. Yet that would be misleading. It means that everything in the domain is in Paris. This domain contains only the Eiffel Tower, so with this symbolization key for all x, P of x just means that the Eiffel Tower is in Paris. Non-referring terms. In FOL, each name must pick out exactly one member of the domain. A name cannot refer to more than one thing, it is a singular term. Each name must still pick out something. This is connected to a classic philosophical problem, the so-called problem of non-referring terms. Medieval philosophers typically used sentences about the chimera to exemplify this problem. Chimera is a mythological creature. It does not really exist. Consider these two sentences. 9. Chimera is angry. 10. Chimera is not angry. It is tempting just to define a name to mean chimera. The symbolization key would look like this. Domain, creatures on Earth A of X, is angry. See, chimera. We could then symbolize sentence 9 as A of C and sentence 10 as not A of C. Problems will arise when we ask whether these sentences are true or false. One option is to say that sentence 9 is not true because there is no chimera. If sentence 9 is false because it talks about a non-existent thing, then sentence 10 is false for the same reason. Yet this would mean that O of C and not A of C would both be false. Given the truth conditions for negation, this cannot be the case. Since we cannot say that they are both false, what should we do? Another option is to say that sentence 9 is meaningless because it talks about a non-existent thing. So AC would be a meaningful expression in FOL for some interpretations but not for others. Yet this would make our formal language hostage to particular interpretations. Since we are interested in logical form, we want to consider the logical force of a sentence like A, C, apart from any particular interpretation. If A, C were sometimes meaningful and sometimes meaningless, we could not do that. This is the problem of non-referring terms, and we will return to it later, CP 242. The important point for now is that each name of FOL must refer to something in the domain, although the domain can contain any things we like. If we want to symbolize arguments about mythological creatures, then we must define a domain that includes them. This option is important if we want to consider the logic of stories. We can symbolize a sentence like Sherlock Holmes lived at 221B Baker Street by including fictional characters like Sherlock Holmes in our domain. Chapter 23. Sentences with one quantifier. We now have all of the pieces of FOL. Symbolizing more complicated sentences is just a matter of knowing how to combine predicates, names, quantifiers, and connectives. There is a knack to this, and there is no substitute for practice. 23.1 Common quantifier phrases. Consider these sentences. 1. Every coin in my pocket is a quarter. 2. Some coin on the table is a dime. 3. Not all the coins on the table are dimes. 4. None of the coins in my pocket are dimes. In providing a symbolization key, we need to specify a domain. Since we are talking about coins in my pocket and on the table, the domain must at least contain all of those coins. Since we are not talking about anything besides coins, we let the domain be all coins. Since we are not talking about any specific coins, we do not need to deal with any names. So here is our key. Domain, all coins P of X, is in my pocket T of X, is on the table Q of X, blank is a quarter D of X, blank is a dime. Sentence 1 is most naturally symbolized using a universal quantifier. The universal quantifier says something about everything in the domain, not just about the coins in my pocket. Sentence 1 can be paraphrased as for any coin, if that coin is in my pocket, then it is a quarter. So we can symbolize it as for all X PX to QX. Since sentence 1 is about coins that are both in my pocket and that are quarters, it might be tempting to symbolize it using a conjunction. However, the sentence for all X PX and QX would symbolize the sentence every coin is both a quarter and in my pocket. This obviously means something very different than sentence 1, and so we see. A sentence can be symbolized as for all X, open parenthesis, script F of X implies script G of X, close parenthesis, if it can be paraphrased in English as every F is G. Sentence 2 is most naturally symbolized using an existential quantifier. It can be paraphrased as there is some coin which is both on the table and which is a dime. So we can symbolize it as there exists X, open parenthesis, T of X and D of X, close parenthesis. Notice that we needed to use a conditional with the universal quantifier, but we used a conjunction with the existential quantifier. Suppose we had instead written, there exists X, open parenthesis, T of X, arrow, D of X, close parenthesis. That would mean that there is some object in the domain of which open parenthesis, T of X, arrow, D of X, close parenthesis is true. Recall that in TFL, a arrow B is logically equivalent in TFL to not A or B. This equivalence will also hold in FOL. So there exists X, open parenthesis, T of X, arrow, D of X, close parenthesis is true if there is some object in the domain such that open parenthesis, not T of X or D of X, close parenthesis is true of that object. That is, there exists x open parenthesis t of x arrow d of x close parenthesis is true if some coin is either not on the table or is a dime. Of course, there is a coin that is not on the table. There are coins in lots of other places. So it is very easy for exists x and t x to d x to be true. A conditional will usually be the natural connective to use with a universal quantifier, but a conditional within the scope of an existential quantifier tends to say something very weak indeed. As a general rule of thumb, do not put conditionals in the scope of existential quantifiers unless you are sure that you need one. A sentence can be symbolized as there exists x open parenthesis f of x and g of x close parenthesis, if it can be paraphrased in English as some f is g. Sentence 3 can be paraphrased as, it is not the case that every coin on the table is a dime, so we can symbolize it by not for all x open parenthesis t of x implies d of x close parenthesis. You might look at sentence 3 and paraphrase it instead as, some coin on the table is not a dime. You would then symbolize it by there exists x open parenthesis t of x and not d of x close parenthesis. Although it is probably not immediately obvious yet, these two sentences are logically equivalent. This is due to the logical equivalence between not for all x partial and there exists x not for all, mentioned in section 22, along with the equivalence between not open parenthesis partial partial implies partial close parenthesis and not partial. Sentence 4 can be paraphrased as, it is not the case that there is some dime in my pocket. This can be symbolized by not exists x open parenthesis p of x and d of x close parenthesis. It might also be paraphrased as, everything in my pocket is a non-dime, and then could be symbolized by for all x open parenthesis p of x implies not d of x close parenthesis. Again, the two symbolizations are logically equivalent. Both are correct symbolizations of sentence 4. A sentence that can be paraphrased as no f is g can be symbolized as not exists x open parenthesis script f of x and script g of x close parenthesis, and also as for all x open parenthesis script f of x implies not script g of x close parenthesis. Finally, consider only as in 5 only dimes are on the table. How should we symbolize this? A good strategy is to consider when the sentence would be false. If we are saying that only dimes are on the table, we are excluding all the cases where something on the table is a non-dime, so we can symbolize the sentence the same way we would symbolize no non-dimes are on the table. Remembering the lesson we just learned, and symbolizing x as a non-dime as not d of x, the possible symbolizations are, not there exists an x such that t of x and not d of x, or alternatively, for all x t of x implies not d of x. Since double negations cancel out, the second is just as good as for all x t of x implies d of x. In other words, only dimes are on the table, and everything on the table is a dime are symbolized the same way. A sentence that can be paraphrased as only f sub s or g sub s can be symbolized as negation of exists x open parenthesis curly g of x and not curly f of x close parenthesis, and also as for all x open parenthesis curly g of x implies curly f of x close parenthesis. 23.2 Empty predicates. In section 22, we emphasized that a name must pick out exactly one object in the domain. However, a predicate need not apply to anything in the domain. A predicate that applies to nothing in the domain is called an empty predicate. This is worth exploring. Suppose we want to symbolize these two sentences. 6. Every monkey knows sign language. 7. Some monkey knows sign language. It is possible to write the symbolization key for these sentences in this way. Domain, animals m of x, blank is a monkey. S of x, x knows sign language. Sentence 6 can now be symbolized by for all x, m of x implies s of x. Sentence 7 can be symbolized as there exists x, m of x, and s of x. It is tempting to say that sentence 6 entails sentence 7. That is, we might think that it is impossible that every monkey knows sign language unless some monkey knows sign language. But this would be a mistake. It is possible for the sentence for all x, m of x implies s of x to be true even though the sentence there exists x, m of x, and s of x is false. How can this be? The answer comes from considering whether these sentences would be true or false if there were no monkeys. If there were no monkeys at all in the domain, then for all x, m of x implies s of x would be vacuously true. Take any monkey you like, it knows sign language. But if there were no monkeys at all in the domain, then there exists x, m of x, and s of x would be false. Another example will help to bring this home. Suppose we extend the above symbolization key by adding r of x is a refrigerator. Now consider the sentence for all x r x to mx. This symbolizes every refrigerator as a monkey. This sentence is true given our symbolization key, which is counterintuitive since we presumably do not want to say that there are a whole bunch of refrigerator monkeys. It is important to remember though that for all x, Rx to Mx is true if any member of the domain that is a refrigerator is a monkey. Since the domain is animals, there are no refrigerators in the domain. Again, then, the sentence is vacuously true. If you were actually dealing with the sentence, all refrigerators are monkeys, then you would most likely want to include kitchen appliances in the domain. Then the predicate R would not be empty and the sentence for all x, R of x implies M of x would be false. When script f is an empty predicate, any sentence for all x, script f of x implies ellipsis is vacuously true. 23.3 Picking a domain. The appropriate symbolization of an English language sentence in FOL will depend on the symbolization key. Choosing a key can be difficult. Suppose we want to symbolize the English sentence. 8. Every rose has a thorn. We might offer this symbolization key. R of x, x is a rose, T of x. X has a thorn. It is tempting to say that sentence 8 should be symbolized as for all x, Rx to Tx, but we have not yet chosen a domain. If the domain contains all roses, this would be a good symbolization. Yet if the domain is merely things on my kitchen table, then for all x, Rx to Tx would only come close to covering the fact that every rose on my kitchen table has a thorn. If there are no roses on my kitchen table, the sentence would be trivially true. This is not what we want. To symbolize sentence 8 adequately, we need to include all the roses in the domain, but now we have two options. First, we can restrict the domain to include all roses, but only roses. Then sentence 8 can, if we like, be symbolized with for all x, Tx. This is true if everything in the domain has a thorn. Since the domain is just the roses, this is true if every rose has a thorn. By restricting the domain, we have been able to symbolize our English sentence with a very short sentence of FOL. So this approach can save us trouble if every sentence that we want to deal with is about roses. Second, we can let the domain contain things besides roses, rhododendrons, rats, rifles, whatever, and we will certainly need to include a more expansive domain if we simultaneously want to symbolize sentences like 9. Every cowboy sings a sad, sad song. Our domain must now include both all the roses so that we can symbolize sentence 8 and all the cowboys so that we can symbolize sentence 9. So we might offer the following symbolization key. Domain, people and plants, C of x. X is a cowboy, S of x. Sings a sad, sad song, R of x. X is a rose, T of x. X has a thorn. Now we will have to symbolize sentence 8 with for all x, R of x implies T of x, since for all x, T of x would symbolize the sentence every person or plant has a thorn. Similarly, we will have to symbolize sentence 9 with for all x, C of x implies S of x. In general, the universal quantifier can be used to symbolize the English expression everyone if the domain only contains people. If there are people and other things in the domain, then everyone must be treated as every person. 23.4 The utility of paraphrase. In symbolizing English sentences in FOL, it is important to understand the structure of the sentences you want to symbolize. What matters is the final symbolization in FOL, and sometimes you will be able to move from an English language sentence directly to a sentence of FOL. Other times, it helps to paraphrase the sentence one or more times. Each successive paraphrase should move from the original sentence closer to something that you can easily symbolize directly in FOL. For the next several examples, we will use this symbolization key. Domain, people B of x, blank is a bassist. R of x is a rock star. Okay, Kim Deal. Now consider these sentences. 10. If Kim Deal is a bassist, then she is a rock star. 11. If a person is a bassist, then she is a rock star. The same words appear as the consequent in sentences 10 and 11. She is a rock star, but they mean very different things. To make this clear, it often helps to paraphrase the original sentences, removing pronouns. Sentence 10 can be paraphrased as, if Kim Deal is a bassist, then Kim Deal is a rock star. This can obviously be symbolized as B of K implies R of K. Sentence 11 must be paraphrased differently. If a person is a bassist, then that person is a rock star. This sentence is not about any particular person, so we need a variable. As an intermediate step, we can paraphrase this as, for any person x, if x is a bassist, then x is a rock star. Now this can be symbolized as for all x, b x to rx. This is the same sentence we would have used to symbolize, everyone who is a bassist is a rock star. On reflection, that is surely true if sentence 11 is true, as we would hope. Consider these further sentences. 12. If anyone is a bassist, then Kim Deal is a rock star. 13. If anyone is a bassist, then she is a rock star. The same words appear as the antecedent in sentences 12 and 13. If anyone is a bassist, but it can be tricky to work out how to symbolize these two uses. Again, paraphrase will come to our aid. Sentence 12 can be paraphrased: if there is at least one bassist, then Kim Deal is a rock star. It is now clear that this is a conditional whose antecedent is a quantified expression, so we can symbolize the entire sentence with a conditional as the main logical operator. Exists x b x to r k. Sentence 13 can be paraphrased: for all people x, if x is a bassist, then x is a rock star. Or, in more natural English, it can be paraphrased by all bassists are rock stars. It is best symbolized as for all x b x to r x, just like sentence 11. The moral is that the English words any and anyone should typically be symbolized using quantifiers, and if you are having a hard time determining whether to use an existential or a universal quantifier, try paraphrasing the sentence with an English sentence that uses words besides any or anyone. 23.5 Quantifiers in scope. Continuing the example, suppose we want to symbolize these sentences. 14. If everyone is a bassist, then Lars is a bassist. 15. Everyone is such that if they are a bassist, then Lars is a bassist. To symbolize these sentences, we will have to add a new name to the symbolization key, namely Lars. Sentence 14 is a conditional whose antecedent is everyone is a bassist, so we will symbolize it with for all x b of x arrow b of l. This sentence is necessarily true. If everyone is indeed a bassist, then take anyone you like, for example Lars, and he will be a bassist. Sentence 15, by contrast, might best be paraphrased by every person x is such that if x is a bassist, then Lars is a bassist. This is symbolized by for all x open parenthesis b of x arrow b of l close parenthesis. This sentence is false. Kim Deal is a bassist, so b of k is true. Suppose that Lars is not a bassist, say he's a drummer instead, so b of l is false. Accordingly, b of k arrow b of l will be false, so for all x open parenthesis b of x arrow b of l close parenthesis will be false as well. In short, for all x b of x implies b of l, and for all x b of x implies b of l are very different sentences. We can explain the difference in terms of the scope of the quantifier. The scope of quantification is very much like the scope of negation, which we considered when discussing TFL, and it will help to explain it in this way. In the sentence not b of k implies b of l, the scope of not is just the antecedent of the conditional. We are saying something like, if b of k is false, then b of l is true. Similarly, in the sentence for all x b of x implies b of l, the scope of for all x is just the antecedent of the conditional. We are saying something like, if b of x is true of everything, then b of l is also true. In the sentence not open parenthesis b of k implies b of l close parenthesis, the scope of not is the entire sentence. We are saying something like, open parenthesis b of k implies b of l close parenthesis is false. Similarly, in the sentence for all x open parenthesis b of x implies b of l close parenthesis, the scope of for all x is the entire sentence. We are saying something like, open parenthesis b of x implies b of l close parenthesis is true of everything. The moral of the story is simple. When you are using conditionals, be very careful to make sure that you have sorted out the scope correctly. Ambiguous predicates. Suppose we just want to symbolize this sentence. 16. Adna is a skilled surgeon. Let the domain be people, let k of x mean x is a skilled surgeon, and let a mean Adna. Sentence 16 is simply k of a. Suppose instead that we want to symbolize this argument. The hospital will only hire a skilled surgeon. All surgeons are greedy. Billy is a surgeon but is not skilled. Therefore, Billy is greedy, but the hospital will not hire him. We need to distinguish being a skilled surgeon from merely being a surgeon. So we define this symbolization key, domain, people g of x, blank x is greedy. H of x, the hospital will hire x. R of x, blank is a surgeon. K of x is skilled, b, Billy. Now the argument can be symbolized in this way.
Math summary, the argument states, for all x, if it is not the case that x has property r and property k, then it is not the case that x has property h also. For all x, if x has property r, then x has property g. It is given that a specific individual b has property r and does not have property k. Therefore, the argument concludes that individual b has property g and does not have property h.
Next, suppose that we want to symbolize this argument. Carol is a skilled surgeon and a tennis player. Therefore, Carol is a skilled tennis player. If we start with the symbolization key we used for the previous argument, we could add a predicate, let t, x mean x is a tennis player, and a name, let's C, mean Carol. Then the argument becomes.
Math summary, the expression begins with the conjunction of three conditions. The first condition is that Carol is a surgeon. The second condition is that Carol is skilled. These two conditions are combined with a logical and. The third condition is that Carol is a tennis player. The entire expression states that Carol is a surgeon and Carol is skilled and Carol is a tennis player. The conclusion is that Carol is a tennis player and Carol is skilled.
This symbolization is a disaster. It takes what in English is a terrible argument and symbolizes it as a valid argument in FOL. The problem is that there is a difference between being skilled as a surgeon and skilled as a tennis player. Symbolizing this argument correctly requires two separate predicates, one for each type of skill. If we let K1x mean X is skilled as a surgeon and K2x mean X is skilled as a tennis player, then we can symbolize the argument in this way.
Math summary, the expression represents a logical argument. The premise states that a subject has a certain property, is skilled as a surgeon, and is a tennis player. The conclusion states that the subject is a tennis player and is skilled as a tennis player.
Like the English language argument it symbolizes, this is invalid. The moral of these examples is that you need to be careful of symbolizing predicates in an ambiguous way. Similar problems can arise with predicates like good, bad, big, and small. Just as skilled surgeons and skilled tennis players have different skills, big dogs, big mice, and big problems are big in different ways. Is it enough to have a predicate that means X is a skilled surgeon, rather than two predicates X is skilled and X is a surgeon? Sometimes. As sentence 16 shows, sometimes we do not need to distinguish between skilled surgeons and other surgeons. Must we always distinguish between different ways of being skilled, good, bad, or big? No, as the argument about Billy shows, sometimes we only need to talk about one kind of skill. If you're symbolizing an argument that is just about dogs, it is fine to define a predicate that means X is big. If the domain includes dogs and mice, however, it is probably best to make the predicate mean X is big for a dog. Practice exercises. A. Here are the syllogistic figures identified by Aristotle and his successors, along with their medieval names. 1. Barbara all grf all hrgiso, all hrf. 2. Celerant no grf all hrgiso, no hrf. 3. Furio no grf some h is giso, some h is not f. 4. Darii all grf some h is giso, some h is f. 5. Camsters all f or g no h or giso, no h or f. 6. Cessair no f or g all h or giso, no h or f. Barocco all f or g some h is not giso, some h is not f. 8. Festino no f or g some h or giso, some h is not f. Dataci all grf some g is h so, some h is f. 10. Dasamis some g is f all grh so, some h is f. 11. Farrison no grf some g is h so, some h is not f. 12. Picardo some g is not f all grh so, some h is not f. 13. Camines all f or g no grh so, no h is f. 14. Demaris some f is g all grh so, some h is f. 15. Fresison, no f or g some g is h so, some h is not f. Symbolize each argument in FOL. B. Using the following symbolization key. Domain people. K of x, x knows the combination to the safe S of x, is a spy V of x is a vegetarian h, Hofthor I, Ingmar symbolize the following sentences in FOL. 1. Neither Hofthor nor Ingmar is a vegetarian. 2. No spy knows the combination to the safe. 3. No one knows the combination to the safe unless Ingmar does. 4. Hofthor is a spy but no vegetarian is a spy. See, using the symbolization key. Domain all animals of x, blank is an alligator. M of x blank is a monkey. R of x blank is a reptile. Z of x lives at the zoo. I Amos B, Bouncer C, Cleo symbolize each of the following sentences in FOL. 1. Amos, Bouncer, and Cleo all live at the zoo. 2. Bouncer is a reptile but not an alligator. 3. Some reptile lives at the zoo. 4. Every alligator is a reptile. 5. Any animal that lives at the zoo is either a monkey or an alligator. 6. There are reptiles which are not alligators. 7. If any animal is a reptile then Amos is. 8. If any animal is an alligator then it is a reptile. D. For each argument, write a symbolization key and symbolize the argument in FOL. 1. Willard is a logician. All logicians wear funny hats, so Willard wears a funny hat. 2. Nothing on my desk escapes my attention. There is a computer on my desk. As such, there is a computer that does not escape my attention. 3. All my dreams are black and white. Old TV shows are in black and white. Therefore, some of my dreams are old TV shows. 4. Neither Holmes nor Watson has been to Australia. A person could see a kangaroo only if they had been to Australia or to a zoo. Although Watson has not seen a kangaroo, Holmes has. Therefore, Holmes has been to a zoo. 5. No one expects the Spanish Inquisition. No one knows the troubles I've seen. Therefore, anyone who expects the Spanish Inquisition knows the troubles I've seen. 6. All babies are illogical. Nobody who is illogical can manage a crocodile. Berthold is a baby. Therefore, Berthold is unable to manage a crocodile. Chapter 24. Multiple generality. So far, we have only considered sentences that require one place predicates and one quantifier. The full power of FOL really comes out when we start to use many place predicates and multiple quantifiers. For this insight, we largely have to think, but also see S pairs. 24.1 Many place predicates. All of the predicates that we have considered so far concern properties that objects might have. Those predicates have one gap in them, and to make a sentence, we simply need to slot in one term. They are one-place predicates. However, other predicates concern the relation between two things. Here are some examples of relational predicates in English. Loves is to the left of is in debt to. These are two-place predicates. They need to be filled in with two terms in order to make a sentence. Conversely, if we start with an English sentence containing many singular terms, we can remove two singular terms to obtain different two-place predicates. Consider the sentence, Vinny borrowed the family car from Nunzio. By deleting two singular terms, we can obtain any of three different two-place predicates. Vinny borrowed from borrowed the family car from borrowed from Nunzio, and by removing all three singular terms, we obtain a three-place predicate. Text borrowed text from text. Indeed, there is no in principle upper limit on the number of places that our predicates may contain. 24.2 Mind the gap S. We have used the same symbol to indicate a gap formed by deleting a term from a sentence. However, as Frege emphasized, these are different gaps. To obtain a sentence, we can fill them in with the same term, but we can equally fill them in with different terms and in various different orders. The following are three perfectly good sentences obtained by filling in the gaps in loves in different ways, but they all have distinctively different meanings. 1. Carl loves Imre. 2. Imre loves Carl. 3. Carl loves Carl. The point is that we need to keep track of the gaps in predicates so that we can keep track of how we are filling them in. To keep track of the gaps, we assign them variables. Suppose we want to symbolize the preceding sentences. Then I might start with the following representation key. Domain, people I, Imre K, Carl L of X, Y, X loves Y. Sentence 1 will be symbolized by L of K, I. Sentence 2 will be symbolized by L of I, K. And sentence 3 will be symbolized by L of K, K. Here are a few more sentences that we can symbolize with the same key. 4. Imre loves himself. 5. Carl loves Imre but not vice versa. 6. Carl is loved by Imre. Sentence 4 can be paraphrased as Imre loves Imre and so symbolized by Lii. Sentence 5 is a conjunction. We can paraphrase it as Carl loves Imre and Imre does not love Carl and so symbolize it as Lki not sign Lik. Sentence 6 can be paraphrased by Imre loves Carl and so symbolized as Lik. In this last case, of course, we have lots the difference in tone between the active and passive voice, but we have at least preserved the truth conditions. But the relationship between Imre loves Carl and Carl is loved by Imre highlights something important. To see what, suppose we add another entry to our symbolization key. M of X, Y, Y loves X. The entry for M uses exactly the same English word loves as the entry for L, but the gaps have been swapped around. Just look closely at the subscripts, and this matters. To explain, when we see a sentence like Lk1, we are being told to take the first name, i.e., K, and associate its value, i.e., Carl, with the gap labeled X. Then take the second name, i.e., I, and associate its value, i.e., Imre, with the gap labeled Y, and so come up with Carl loves Imre. The sentence M-I-K also tells us to take the first name, i.e., I, and plug its value into the gap labeled X, and take the second name, i.e., K, and plug its value into the gap labeled Y, and so come up with Imre loves Carl. So L of I, comma K and M of K, comma I both symbolize Imre loves Carl, whereas L of K, comma I and M of I, comma K both symbolize Carl loves Imre. Since love can be unrequited, these are different claims. One last example might be helpful. Suppose we add this to our symbolization key. P of X, Y, X prefers X to Y. Now the sentence P, I, K symbolizes Imre prefers Imre to Carl, and P, K, I symbolizes Carl prefers Carl to Imre. And note that we could have achieved the same effect if we had instead specified P of X, comma Y, X prefers themselves to Y. In any case, the overall moral of this is simple. When dealing with predicates with more than one place, pay careful attention to the order of the gaps. 24.3 The order of quantifiers. Consider the sentence, everyone loves someone. This is potentially ambiguous. It might mean either of the following. 7. For every person X, there is some person that X loves. 8. There is some particular person whom every person loves. Sentence 7 can be symbolized by for all X exists YL, XY, and would be true of a love triangle. For example, suppose that our domain of discourse is restricted to Imre, Juan, and Carl. Suppose also that Carl loves Imre but not Juan, that Imre loves Juan but not Carl, and that Juan loves Carl but not Imre. Then sentence 7 is true. Sentence 8 is symbolized by exists if for all XL, X, Y. Sentence 8 is not true in the situation just described. Again, suppose that our domain of discourse is restricted to Imre, Juan, and Carl. Then all of Juan, Imre, and Carl must converge on at least one object of love. The point of the example is to illustrate that the order of the quantifiers matters a great deal. Indeed, to switch them around is called a quantifier shift fallacy. Here is an example which comes up in various forms throughout the philosophical literature. For every person there is some truth they cannot know. For all there is some particular truth that no person can know. There exists. This argument form is obviously invalid. It's just as bad as when every dog has its day. There is a day for all the dogs. The order of quantifiers is also important in definitions in mathematics. For instance, there is a big difference between pointwise and uniform continuity of functions. A function f is pointwise continuous if.
Math summary. This expression defines pointwise continuity for a function. It states that for every positive value epsilon, and for all input values x and y, there exists a positive value delta such that if the absolute difference between x and y is less than delta, then the absolute difference between the function evaluated at x and the function evaluated at y is less than epsilon.
A function f is uniformly continuous if.
Math summary. This expression defines continuity. It states that for every positive value epsilon, there exists a positive value delta such that for all input values x and y, if the absolute difference between x and y is less than delta, then the absolute difference between the function f evaluated at x and the function f evaluated at y is less than epsilon.
The moral is simple. Take great care with the order of your quantifiers. 24.4 Stepping stones to symbolization. As we are starting to see, symbolization in FOL can become a bit tricky. So when symbolizing a complex sentence, you should lay down several stepping stones. As usual, the idea is best illustrated by example. Consider this symbolization key, domain, people and dogs d of x. X is a dog f of x, y. Blank is a friend of blank o of x, comma y. Blank x owns blank y g. Geraldo. Now let's try to symbolize these sentences. 9. Geraldo is a dog owner. 10. Someone is a dog owner. 11. All of Geraldo's friends are dog owners. 12. Every dog owner is a friend of a dog owner. 13. Every dog owner's friend owns a dog of a friend. Sentence 9 can be paraphrased as, there is a dog that Geraldo owns. This can be symbolized by there exists x, open parenthesis, d of x, logical, and o of g, comma x, close parenthesis. Sentence 10 can be paraphrased as, there is some y such that y is a dog owner. Dealing with part of this, we might write y is a dog owner. Now the fragment we have left as y is a dog owner is much like sentence 9, except that it is not specifically about Geraldo. So we can symbolize sentence 10 by.
Math summary. This expression asserts the existence of some y and some x such that x is a dog and y owns x. In simpler terms, it states that there exists someone who owns a dog.
We should pause to clarify something here. In working out how to symbolize the last sentence, we wrote down y is a dog owner. To be very clear, this is neither an FOL sentence nor an English sentence. It uses bits of FOL, y, and bits of English, dog owner. It is just a stepping stone on the way to symbolizing the entire English sentence with a FOL sentence. You should regard it as a bit of rough working out, on a par with the doodles that you might absent-mindedly draw in the margin of this book, whilst you are concentrating fiercely on some problem. Sentence 11 can be paraphrased as, everyone who is a friend of Geraldo is a dog owner. Using our stepping stone tactic, we might write,
Math summary. This expression states that for all individuals, if that individual is a friend of Geraldo, then that individual is a dog owner.
Now the fragment that we have left to deal with, X is a dog owner, is structurally just like sentence 9. However, it would be a mistake for us simply to write.
Math summary. The expression states that for all entities X, if X has a certain property F with respect to G, then there exists an entity X such that X has property D, and X has property O with respect to itself.
We would here have a clash of variables. The scope of the universal quantifier for all X is the entire conditional, so the X in dx should be governed by that, but dx also falls under the scope of the existential quantifier exists X, so the X in dx should be governed by that. Now confusion reigns. Which X are we talking about? Suddenly the sentence becomes ambiguous if it is even meaningful at all, and logicians hate ambiguity. The broad moral is that a single variable cannot serve two quantifier masters simultaneously. To continue our symbolization, then, we must choose some different variable for our existential quantifier. What we want is something like.
Math summary. The expression states that for all input values X, if the relation F holds between X and a constant G, then there exists a Z such that D holds for Z, and the relation O holds between X and Z.
This adequately symbolizes sentence 11. Sentence 12 can be paraphrased as, for any X that is a dog owner, there is a dog owner who X is a friend of. Using our stepping stone tactic, this becomes for all X open bracket, X is a dog owner, implies there exists a Y open parenthesis, Y is a dog owner, and F of X, Y close parenthesis, close bracket. Completing the symbolization, we end up with.
Math summary. The expression states that for all entities X, if there exists an entity Z such that Z has property D and X relates to Z through relation O, then there exists an entity Y such that there exists an entity Z where Z has property D and Y relates to Z through relation O, and X relates to Y through relation F.
Note that we have used the same letter, Z, in both the antecedent and the consequent of the conditional, but that these are governed by two different quantifiers. This is okay, there is no clash here because it is clear which quantifier that variable falls under. We might graphically represent the scope of the quantifiers thus.
Table summary. The table shows the scope of quantifiers in a logical expression. The scope varies for each quantifier, with the universal quantifier having the broadest scope, encompassing the entire conditional statement.
This shows that no variable is being forced to serve two masters simultaneously. Sentence 13 is the trickiest yet. First, we paraphrase it as, for any X that is a friend of a dog owner, X owns a dog which is also owned by a friend of X. Using our stepping stone tactic, this becomes. For all X open bracket, X is a friend of a dog owner, implies X owns a dog which is owned by a friend of X. Breaking this down a bit more.
Math summary. The expression describes a logical statement that applies to all entities X. If there exists an entity Y, where X is related to Y through a relationship F, and Y is a dog owner, then the statement proceeds to a conclusion, which is not fully provided in the given expression.
There exists a Y such that D of Y and O of X, Y and Y is owned by a friend of X, and a bit more.
Math summary. The expression describes a logical implication that holds for all entities X. The left side of the implication states that there exists an entity, Y, such that X is related to Y, and there exists an entity Z, where Z has property D and Y is related to Z. The right side of the implication states that there exists an entity, Y, that has property D, X is related to Y, and there exists an entity, Z, such that Z is related to X, and Z is related to Y.
And we are done. 24.5 Suppressed quantifiers. Logic can often help to get clear on the meanings of English claims, especially where the quantifiers are left implicit or their order is ambiguous or unclear. The clarity of expression and thinking afforded by FOL can give you a significant advantage in argument, as can be seen in the following takedown by British political philosopher of her contemporary, the theologian William Nishalls. In Discourse IV, the duty of wives to their husbands of his, the duty of inferiors towards their superiors in 5 practical discourses, Nichols argued that women are naturally inferior to men. In the preface to the third edition of her treatise, Some Reflections upon Marriage, occasioned by the Duke and Duchess of Mazarine's case, which is also considered, Estelle responded as follows.
"'Tis true through want of learning, and of that superior genius which men as men lay claim to, she Estelle was ignorant of the natural inferiority of our sex, which our masters lay down as a self-evident and fundamental truth. She saw nothing in the reason of things, to make this either a principle or a conclusion, but much to the contrary, it being sedition at least, if not treason to assert it in this reign.
For if by the natural superiority of their sex, they mean that every man is by nature superior to every woman, which is the obvious meaning, and that which must be stuck to if they would speak sense, it would be a sin in any woman to have dominion over any man, and the greatest queen ought not to command but to obey her footman, because no municipal laws can supersede or change the law of nature. So that if the dominion of the men be such, the Salic law, as unjust as English men have ever thought it, ought to take place over all the earth, and the most glorious reigns in the English, Danish, Castilian, and other annals were wicked violations of the law of nature. If they mean that some men are superior to some women, this is no great discovery. Had they turned the tables, they might have seen that some women are superior to some men. Or had they been pleased to remember their oaths of allegiance and supremacy, they might have known that one woman is superior to all the men in these nations, or else they have sworn to very little purpose, and it must not be supposed that their reason and religion would suffer them to take oaths, contrary to the laws of nature and reason of things. We can symbolize the different interpretations Estelle offers of Nichols' claim that men are superior to women. He either meant that every man is superior to every woman, that is.
Math summary, the expression states that for all men, it implies that for all women, a certain superiority relationship holds between the man and the woman.
Or that some men are superior to some women.
Math summary, this statement asserts the existence of an entity, let's call it X, that satisfies two conditions. First, X has the property M. Second, there exists another entity, let's call it Y, such that Y has the property W, and X has the relation S with Y.
The latter is true, but so is.
Math summary, this statement asserts the existence of a woman, such that there exists a man, and the woman is superior to the man.
Some women are superior to some men, so that would be no great discovery. In fact, since the queen is superior to all her subjects, it's even true that some woman is superior to every man, that is.
Math summary, the expression states that there exists a woman, such that the woman has a certain property, and for all men, if a man has a certain property, then the woman is superior to the man.
But this is incompatible with the obvious meaning of Nichols' claim, that is, the first reading. So what Nichols claims amounts to treason against the queen. Practice exercises. A. Using the symbolization key. Domain, all animals O of X, blank is an alligator M of X, blank is a monkey R of X, blank is a reptile Z of X, lives at the zoo L of X, Y, blank X loves blank YA, Amos B, Bouncer C, Cleo. Symbolize each of the following sentences in FOL. 1. If Cleo loves Bouncer, then Bouncer is a monkey. 2. If both Bouncer and Cleo are alligators, then Amos loves them both. 3. Cleo loves a reptile. 4. Bouncer loves all the monkeys that live at the zoo. 5. All the monkeys that Amos loves love him back. 6. Every monkey that Cleo loves is also loved by Amos. 7. There is a monkey that loves Bouncer, but sadly Bouncer does not reciprocate this love. B. Using the following symbolization key. Domain, all animals D of X, X is a dog S of X, like samurai movies L of X, Y, blank is larger than blank R, Rave H, Shane D, Daisy. Symbolize the following sentences in FOL. 1. Rave is a dog who likes samurai movies. 2. Rave, Shane, and Daisy are all dogs. 3. Shane is larger than Rave, and Daisy is larger than Shane. 4. All dogs like samurai movies. 5. Only dogs like samurai movies. 6. There is a dog that is larger than Shane. 7. If there is a dog larger than Daisy, then there is a dog larger than Shane. 8. No animal that likes samurai movies is larger than Shane. 9. No dog is larger than Daisy. 10. Any animal that dislikes samurai movies is larger than Rave. 11. There is an animal that is between Rave and Shane in size. 12. There is no dog that is between Rave and Shane in size. 13. No dog is larger than itself. 14. Every dog is larger than some dog. 15. There is an animal that is smaller than every dog. 16. If there is an animal that is larger than any dog, then that animal does not like samurai movies. C. Using the symbolization key given, symbolize each English language sentence into FOL. Domain, candies C of X, blank X has chocolate in it. M of X, X has marzipan in it. S of X, X has sugar in it. T of X, Boris has tried X. B of X, Y is better than. 1. Boris has never tried any candy. 2. Marzipan is always made with sugar. 3. Some candy is sugar-free. 4. The very best candy is chocolate. 5. No candy is better than itself. 6. Boris has never tried sugar-free chocolate. 7. Boris has tried marzipan and chocolate but never together. 8. Any candy with chocolate is better than any candy without it. 9. Any candy with chocolate and marzipan is better than any candy that lacks both. D. Using the following symbolization key. Domain, people and dishes at a potluck R of X, X has run out. T of X is on the table. F of X is food. P of X, X is a person. L of X, comma Y, blank likes blank E, Eli F, Francesca G. The guacamole symbolize the following English sentences in FOL. 1. All the food is on the table. 2. If the guacamole has not run out, then it is on the table. 3. Everyone likes the guacamole. 4. If anyone likes the guacamole, then Eli does. 5. Francesca only likes the dishes that have run out. 6. Francesca likes no one and no one likes Francesca. 7. Eli likes anyone who likes the guacamole. 8. Eli likes anyone who likes the people that he likes. 9. If there is a person on the table already, then all of the food must have run out. Using the following symbolization key. Domain, people DX, dances ballet. F of X is female. M of X is male. C of XY, blank X is a child of blank Y. S of XY, blank X is a sibling of blank YE, Elmer J, Jane P, Patrick. Symbolize the following sentences in FOL. 1. All of Patrick's children are ballet dancers. 2. Jane is Patrick's daughter. 3. Patrick has a daughter. 4. Jane is an only child. 5. All of Patrick's sons dance ballet. 6. Patrick has no sons. 7. Jane is Elmer's niece. 8. Patrick is Elmer's brother. 9. Patrick's brothers have no children. 10. Jane is an aunt. 11. Everyone who dances ballet has a brother who also dances ballet. 12. Every woman who dances ballet is the child of someone who dances ballet. Chapter 25. Identity. Consider this sentence. 1. Pavel owes money to everyone. Let the domain be people. This will allow us to symbolize everyone with a universal quantifier, offering the symbolization key.
Math summary. This expression defines a relationship where one person owes money to another. The expression, O of X and Y, states that person X owes money to person Y. Additionally, P is defined as Pavel.
We can symbolize sentence 1 by ForAllX O P10, but this has a perhaps odd consequence. It requires that Pavel owes money to every member of the domain, whatever the domain may be. The domain certainly includes Pavel, so this entails that Pavel owes money to himself, and maybe we did not want to say that, maybe we meant to say. 2. Pavel owes money to everyone else. 3. Pavel owes money to everyone other than Pavel. 4. Pavel owes money to everyone except Pavel himself. But we do not have any way for dealing with the italicized words yet. The solution is to add another symbol to FOL. 25.1 Adding identity. The symbol equals will be a two-place predicate. Since it will have a special meaning, we shall write it a bit differently. We put it between two terms rather than out front. This should also be familiar. Consider a mathematical equation like 1 over 2 equals 0.5, and the special meaning for equals is given by the fact that we always adopt the following symbolization key. X equals Y is identical to. This does not mean merely that the objects in question are indistinguishable or that all of the same things are true of them. Rather, it means that the objects in question are the very same object. To put this to use, suppose we want to symbolize this sentence. 5. Pavel is Mr. Chekhov. Let us add to our symbolization key. Z Mr. Chekhov. Now sentence 5 can be symbolized as P equals C. This tells us that the names P and C both name the same thing. We can also now deal with sentences 2 to 4. All of these sentences can be paraphrased as everyone who is not Pavel is owed money by Pavel. Paraphrasing some more, we get, for all x, if x is not Pavel, then x is owed money by Pavel. Now that we are armed with our new identity symbol, we can symbolize this as for all x, not x equals p to o p10. This last sentence contains the formula not sign x equals p. That might look a bit strange because the symbol that comes immediately after the not sign is a variable rather than a predicate, but this is not a problem. We are simply negating the entire formula, x equals p. In addition to sentences that use the word else, other than, and, except, identity will be helpful when symbolizing some sentences that contain the words besides and only. Consider these examples. 6. No one besides Pavel owes money to Hikaru. 7. Only Pavel owes Hikaru money. Let H name Hikaru. Sentence 6 can be paraphrased as no one who is not Pavel owes money to Hikaru. This can be symbolized by not exists x, such that not x equals p and o of x and h. Equally, sentence 6 can be paraphrased as for all x, if x owes money to Hikaru, then x is Pavel. It can then be symbolized as for all x, o of x and h implies x equals p. Sentence 7 can be treated similarly, but there is one subtlety here. Do either sentence 6 or 7 entail that Pavel himself owes money to Hikaru? 25.2 There are at least. We can also use identity to say how many things there are of a particular kind. For example, consider these sentences. 8. There's at least one apple. 9. There are at least 2 apples. 10. There are at least 3 apples. We will use the symbolization k. O of x is an apple. Sentence 8 does not require identity. It can be adequately symbolized by x. There is an apple, perhaps many, but at least one. It might be tempting to also symbolize sentence 9 without identity. Yet consider the sentence there exists x, there exists y open parenthesis a of x and a of y close parenthesis. Roughly this says that there is some apple x in the domain and some apple y in the domain. Since nothing precludes these from being one and the same apple, this would be true even if there were only one apple. In order to make sure that we are dealing with different apples, we need an identity predicate. Sentence 9 needs to say that the 2 apples that exist are not identical, so it can be symbolized by there exists x, there exists y, open parenthesis, a of x, logical, and a of y, close parenthesis, logical, and logical not x equals y, close parenthesis. Sentence 10 requires talking about 3 different apples. Now we need 3 existential quantifiers, and we need to make sure that each will pick out something different.
Math summary. This statement asserts the existence of 3 distinct objects, named x, y, and z, that all satisfy the condition A specifically. It checks if there exist x, y, and z such that it is true for x, A is true for y, and it is true for z. Additionally, it verifies that x is not equal to y is not equal to z, and x is not equal to z, ensuring that all 3 objects are different from each other.
Note that it is not enough to use not x equals y and not y equals z to symbolize x, y, and z are all different. For that would be true if x and y were different, but x equals z in general. To say that x sub 1 through x sub n are all different, we must have a conjunction of not x sub I equals x sub j for every different pair I and j. 25.3 There are at most. Now consider these sentences. 11. There is at most 1 apple. 12. There are at most 2 apples. Sentence 11 can be paraphrased as, it is not the case that there are at least 2 apples. This is just the negation of sentence 9.
Math summary. This expression checks if it is not the case that there exist 2 distinct objects, where both objects satisfy a given property. It starts by negating the existence of such objects. Then, it checks if there exists a first object and a second object such that both objects have the specified property, and the first object is not equal to the second object.
But sentence 11 can also be approached in another way. It means that if you pick out an object and it's an apple, and then you pick out an object and it's also an apple, you must have picked out the same object both times. With this in mind, it can be symbolized by.
Math summary. The expression states that for all objects x and y, if x is an apple and y is an apple, then x and y are the same object. In simpler terms, there is at most 1 apple.
The 2 sentences will turn out to be logically equivalent. Similarly, sentence 12 can be approached in 2 equivalent ways. It can be paraphrased as, it is not the case that there are 3 or more distinct apples, so we can offer.
Math summary. This expression checks for the absence of 3 distinct objects that all satisfy a certain property. It asserts that it is not the case that there exist 3 different objects, named x, y, and z, such that x, y, and z all have property A, and x is not equal to y, and x is not equal to z, and y is not equal to z.
Alternatively, we can read it as saying that if you pick out an apple and an apple and an apple, then you will have picked out at least one of these objects more than once. Thus,
Math summary, this statement checks if there are at most two distinct objects with property A. It states that for all objects x, y, and z, if x, y, and z all have property A, then at least two of them must be the same object. In other words, x equals y, or x equals z, or y equals z.
25.4 There are exactly. We can now consider precise of numerical quantity, like 13 there is exactly one apple. 14 there are exactly two apples. 15 there are exactly three apples. Sentence 13 can be paraphrased as, there is at least one apple and there is at most one apple. This is just the conjunction of sentence 8 and sentence 11, so we can offer.
Math summary, this expression asserts that there exists an input value that satisfies a condition, and also that for all input values, if two input values satisfy the condition, then those two input values must be equal. In simpler terms, there is exactly one input value that satisfies the condition.
But it is perhaps more straightforward to paraphrase sentence 13 as, there is a thing x which is an apple, and everything which is an apple is just x itself. Thought of in this way, we offer.
Math summary, this statement asserts the existence of an item, let's call it x, that satisfies two conditions. The first condition is that x has a certain property, denoted by A. The second condition is that for all items y, if y has property A, then y must be identical to x. In simpler terms, there exists exactly one item with property A.
Similarly, sentence 14 may be paraphrased as, there are at least two apples and there are at most two apples. Thus we could offer.
Math summary, the expression asserts that there exist two distinct objects that both satisfy a condition. Furthermore, for any three objects that satisfy the condition, at least two of them must be identical.
More efficiently, though, we can paraphrase it as, there are at least two different apples and every apple is one of those two apples. Then we offer.
Math summary, the expression asserts the existence of two distinct objects, let's call them object x and object y, that both satisfy a certain property A. Furthermore, it states that for any object z, if object z satisfies property A, then object z must be identical to either object x or object y. In simpler terms, there exist exactly two distinct objects that have property A.
Finally, consider the sentence. 16 There are exactly two things. 17 There are exactly two objects. It might be tempting to add a predicate to our symbolization key to symbolize the English predicate is a thing or is an object, but this is unnecessary. Words like thing and object do not sort wheat from chaff. They apply trivially to everything, which is to say, they apply trivially to everything. So we can symbolize either sentence with either of the following.
Math summary, the expression asserts the existence of two distinct elements, x and y. It also states that there do not exist three distinct elements, x, y, and z. The second expression asserts the existence of two distinct elements, x and y, such that for all z, z is equal to either x or y.
Practice exercises. A. Explain why. There exists an x such that for all y, a of y if and only if x equals y is a good symbolization of there is exactly one apple. There exists x, there exists y, open bracket, not x equals y, and for all z, open bracket, a of z, if and only if, open bracket, x equals z, or y equals z, close bracket, is a good symbolization of there are exactly two apples. Chapter 26. Sentences of FOL. We know how to represent English sentences in FOL. The time has finally come to define the notion of a sentence of FOL. 26.1 Expressions. There are 6 kinds of symbols in FOL. Predicates A, B, C, and so on to Z, or with subscripts as needed. A sub 1, B sub 1, Z sub 1, a sub 2, a sub 25, J sub 375, and so on. Names A, B, C, R, or with subscripts as needed. A sub 1, B sub 224, H sub 7, M sub 32, and so on. Variables S, T, U, V, W, X, Y, Z, or with subscripts as needed. X sub 1, Y sub 1, Z sub 1, X sub 2, and so on. Connectives negation, and or implies if and only if brackets. Quantifiers. For all there exists, we define an expression of FOL as any string of symbols of FOL. Take any of the symbols of FOL and write them down in any order and you have an expression. 26.2 Terms and Formulas. In Section 6, we went straight from the statement of the vocabulary of TFL to the definition of a sentence of TFL. In FOL, we will have to go via an intermediary stage, via the notion of a formula. The intuitive idea is that a formula is any sentence, or anything which can be turned into a sentence by adding quantifiers out front, but this intuitive idea will take some time to unpack. We start by defining the notion of a term. A term is any name or any variable. So here are some terms.
Math summary. This expression lists a series of terms, including a b, x, x sub 1, x sub 2, y sub 254, and z. These terms are names or variables.
Next, we need to define atomic formulas. 1. Any sentence letter is an atomic formula. 2. If script R is an n-place predicate and t sub 1, t sub 2 through t sub n are terms, then script R of t sub 1, t sub 2 through t sub n is an atomic formula. 3. If t sub 1 and t sub 2 are terms, then t sub 1 equals t sub 2 is an atomic formula. 4. Nothing else is an atomic formula. Note that we consider sentence letters also formulas of FOL, so every sentence of TFL is also a formula of FOL. The use of script letters here follows the conventions laid down in Section 8. So R is not itself a predicate of FOL. Rather, it is a symbol of our meta-language augmented English that we use to talk about any predicate of FOL. Similarly, T1 is not a term of FOL, but a symbol of the meta-language that we can use to talk about any term of FOL. So where F is a one-place predicate, G is a three-place predicate, and S is a six-place predicate, here are some atomic formulas.
Math summary. The expression presents a list of atomic formulas. It includes a symbol D, equalities where x equals a and a equals b. It also includes functions. F of x, f of a g of x are in y, g of a and a and s of x1, x2, a b, y, and x1.
Once we know what atomic formulas are, we can offer recursion clauses to define arbitrary formulas. The first few clauses are exactly the same as for TFL. 9. Nothing else is a formula. So, assuming again that F is a one-place predicate, G is a three-place predicate, and S is a six-place predicate, here are some formulas you can build this way.
Math summary. The expression represents a series of logical statements. First, there's a function f of input x, a function g of inputs a y and z, and a function s of inputs y, z, y, a y, and x. Then there's a logical implication. If g of a y and z is true, then s of y, z, y, a y, and x is true. Next, for all z, if g of a y and z is true, then s of y, z, y, a y, and x is true. Then f of x is true, and for all z, if g of a y and z is true, then s of y, z, y, a y, and x is true. Then there exists a y such that f of x is true. And for all z, if g of a y and z is true, then s of y, z, y, a y, and x is true. Finally, for all x, there exists a y such that f of x is true. And for all z, if g of a y and z is true, then s of y, z, y, a y, and x is true.
We can now give a formal definition of scope which incorporates the definition of the scope of a quantifier. Here we follow the case of TFL, though we note that a logical operator can be either a connective or a quantifier. The main logical operator in a formula is the operator that was introduced most recently, when that formula was constructed using the recursion rules. The scope of a logical operator in a formula is the subformula for which that operator is the main logical operator. So we can graphically illustrate the scope of the quantifiers in the preceding example thus.
Math summary. This refers to the scope of the universal quantifier for all x. The scope defines the portion of a logical formula to which the quantifier applies.
Scope of there exists a y scope of for all z.
Math summary. The expression states that for all inputs x, there exists an input y such that a condition f of x is equivalent to the statement that for all inputs z, if a condition g of a y and z holds, then a condition s of y, z, y, a y, and x holds. Algorithm 1 summary. The code defines the rules for constructing formulas in first-order logic. It starts with atomic formulas and then recursively builds more complex formulas using negation, conjunction, disjunction, implication, equivalence, universal quantification, and existential quantification. The input is a set of atomic formulas and variables. The output is a set of valid formulas according to the defined rules. It also shows an example of how to derive a formula using inference rules.
26.3 Sentences and free variables. Recall that we are largely concerned in logic with assertoric sentences. sentences that can be either true or false. Many formulas are not sentences. Consider the following symbolization key: domain, people L of X, Y equals, loves B, Boris. Consider the atomic formula LZZ. All atomic formula are formulas, so LZZ is a formula, but can it be true or false? You might think that it will be true just in case the person named by Z loves themselves, in the same way that LBB is true just in case Boris, the person named by B, loves himself. However, Z is a variable and does not name anyone or anything. Of course, if we put an existential quantifier out front, obtaining there exists ZL of Z, Z, then this would be true if someone loves themselves. Equally, if we wrote for all ZL of Z, Z, this would be true if everyone loves themselves. The point is that we need a quantifier to tell us how to deal with a variable. Let's make this idea precise. An occurrence of a variable x is bound if it falls within the scope of either for all x or exists x. An occurrence of a variable which is not bound is free. For example, consider the formula.
Math summary: this statement describes a logical implication. It states that for all x, if either e of x is true or d of y is true, then there exists a z such that if e of x is true, then L of z and x is true.
The scope of the universal quantifier for all x is for all x, e of x or d of y, so the first x is bound by the universal quantifier. However, the second and third occurrence of x are free. Equally, the y is free. The scope of the existential quantifier there exists z is e of x implies L of z, x, so z is bound. Finally, you can say the following. A sentence of FOL is any formula of FOL that contains no free variables. 26.4 Bracketing conventions. We will adopt the same notational conventions governing brackets that we did for TFL, see section 6 and section 11.3. First, we may omit the outermost brackets of a formula. Second, we may use square brackets and, in place of brackets, to increase the readability of formulas. Sentences of FOL used in our examples can become quite cumbersome, and so we also introduce a convention to deal with conjunctions and disjunctions of more than two sentences. We stipulate that a sub 1 and a sub 2 and continuing 2 and a sub n and a sub 1 or a sub 2 or continuing 2 or a sub n are to be interpreted as, respectively.
Math summary: the first expression performs a series of logical AND operations. It takes a sequence of input values and cumulatively combines them using the AND operator. The second expression performs a series of logical OR operations. It takes a sequence of input values and cumulatively combines them using the OR operator.
In practice, this just means that you are allowed to leave out parentheses in long conjunctions and disjunctions. But remember that unless they are the outermost parentheses of the sentence, you must still enclose the entire conjunction or disjunction in parentheses. Also, you cannot mix conjunctions and disjunctions with each other or with other connectives. So the following are still not allowed and would be ambiguous if they were.
Math summary: the first expression is a logical statement that evaluates the disjunction of A with the conjunction of B, C, and D. The second expression is a logical implication, where the disjunction of B and C implies D.
26.5 Superscripts on predicates. Above, we said that an n-place predicate followed by n terms is an atomic formula. But there is a small issue with this definition. The symbols we use for predicates do not themselves indicate how many places the predicate has. Indeed, in some places in this book, we have used the letter G as a one-place predicate. In other places, we have used it as a three-place predicate. So, unless we state explicitly whether we want to use G as a one-place predicate or as a three-place predicate, it is indeterminate whether GA is an atomic formula or not. There's an easy way to avoid this, which many books adopt. Instead of saying that our predicates are just capital letters with numerical subscripts as necessary, we could say that they're capital letters with numerical superscripts and with numerical subscripts as necessary. The purpose of the superscript would be to say explicitly how many places the predicate has. On this approach, G1 would be a one-place predicate, and G3 would be an entirely different three-places predicate. They would need to have different entries in any symbolization key, and G1A would be an atomic formula, whereas G3A would not. Likewise, G3ABC would be an atomic formula, and G1ABC would not. So we could add superscripts to all our predicates. This would have the advantage of making certain things completely explicit. However, it would have the disadvantage of making our formulas much harder to read. The superscripts would distract the eye. So we will not bother to make this change. Our predicates will remain without superscripts. And in practice, any book which includes superscripts almost immediately stops including them. However, this leaves open a possibility of ambiguity. So when any ambiguity could arise in practice, very rarely you should say explicitly how many places your predicate s have. Practice exercises. A. Identify which variables are bound and which are free. 1. There exists x such that L of x, y, and for all y, L of y, x. 2. For all x, A of x and B of x. 3. For all x, A of x and B of x, and for all y, C of x and D of y. For all x, there exists a y such that R of x and y implies J of z and K of x, or R of y and x.
Math summary. This statement asserts that for all x1, M of x2 is equivalent to L of x2 and x1, and there exists an x2 such that L of x3 and x2 is true.
Chapter 27. Definite descriptions. Consider sentences like 1. Nick is the traitor. 2. The traitor went to Cambridge. 3. The traitor is the deputy. These are definite descriptions. They are meant to pick out a unique object. They should be contrasted with indefinite descriptions such as Nick is a traitor. They should equally be contrasted with generics such as the whale is a mammal when it's inappropriate to ask which whale. The question we face is, how should we deal with definite descriptions in FOL? 27.1 Treating definite descriptions as terms. One option would be to introduce new names whenever we come across a definite description. This is probably not a great idea. We know that the traitor, whoever it is indeed a traitor. We want to preserve that information in our symbolization. A second option would be to use a new definite description operator, such as gamma. The idea would be to symbolize the f as letter 2113x fx, think the x such that fx, or to symbolize the g as letter 2113x gx, etc. Expressions of the form letter 2113x ax would then behave like names. If we were to follow this path, we could use the following symbolization key. Domain people t of x, blank is a traitor d of x, blank is a deputy c of x, blank x went to Cambridge n. Nick. Then we could symbolize sentence 1 with n equals the ode of x times t of x, sentence 2 with c of the ode of x times t of x, and sentence 3 with the iota of x times t of x equals the iota of x times d of x. However, it would be nice if we didn't have to add a new symbol to FOL, and we might be able to make do without one. 27.2 Russell's analysis. Bertrand Russell offered an analysis of definite descriptions. Very briefly put, he observed that when we say the f in the context of a definite description, our aim is to pick out the one and only thing that is f in the appropriate context. Thus, Russell analyzed the notion of a definite description as follows. The f is g if there is at least one f, and there is at most one f in every f is g. Note a very important feature of this analysis, though it does not appear on the right side of the equivalence. Russell is aiming to provide an understanding of definite descriptions in terms that do not presuppose them. Now one might worry that we can say the table is brown without implying that there is one and only one table in the universe. But this is not yet a fantastic counterexample to Russell's analysis. The domain of discourse is likely to be restricted by context, e.g., to salient objects in my vicinity. If we accept Russell's analysis of definite descriptions, then we can symbolize sentences of the form the f is g, using our strategy for numerical quantification in FOL. After all, we can deal with the three conjuncts on the right-hand side of Russell's analysis as follows.
Math summary. The expression asserts three conditions. First, there exists an x such that f of x is true. Second, for all x and all y, if f of x and f of y are true, then x and y are equal. Third, for all x, if f of x is true, then g of x is true.
In fact, we could express the same point rather more crisply, by recognizing that the first two conjuncts just amount to the claim that there is exactly one f, and that the last conjunct tells us that that object is g, so, equivalently, we could offer.
Math summary. This expression asserts the existence of an input x such that two conditions hold. First, x has property f, and for all inputs y, if y has property f, then x and y are the same. Second, this specific input x also has property g.
Using these sorts of techniques, we can now symbolize sentences 1 to 3 without using any newfangled fancy operator, such as gamma. Sentence 1 is exactly like the examples we have just considered, so we would symbolize it by.
Math summary. This expression asserts the existence of an element, let's call it x, that satisfies three conditions. First, x has a certain property, let's call it t. Second, for all elements y, if y has property t, then y is equal to x. This means X is the unique element with property T. Third, X is equal to a specific element N. Therefore, the expression states that there exists a unique element with property T, and that element is N.
Sentence 2 poses no problems either.
Math summary. This expression asserts the existence of an element, called X, that satisfies three conditions. First, X has a certain property T. Second, for all elements Y, if Y has property T, then X and Y are the same element, meaning X is the unique element with property T. Third, X also has another property C. In simpler terms, it states that there exists a unique X with property T, and this unique X also has property C.
Sentence 3 is a little trickier because it links two definite descriptions. But deploying Russell's analysis, it can be paraphrased by there is exactly one traitor X and there is exactly one deputy Y and X equals Y. So we can symbolize it by.
Math summary. This expression asserts the existence of an X and a Y such that X is a traitor and for all Z. If Z is a traitor, then X equals Z, and Y is a deputy, and for all Z. If Z is a deputy, then Y equals Z, and X equals Y. In simpler terms, it states that there exists exactly one traitor and exactly one deputy, and that these two are the same individual.
Note that the formula X equals Y must fall within the scope of both quantifiers. 27.3 Empty definite descriptions. One of the nice features of Russell's analysis is that it allows us to handle empty definite descriptions neatly. France has no king at present. Now, if we were to introduce a name, K, to name the present king of France, then everything would go wrong. Remember from section 22 that a name must always pick out some object in the domain, and whatever we choose as our domain, it will contain no present kings of France. Russell's analysis neatly avoids this problem. Russell tells us to treat definite descriptions using predicates and quantifiers instead of names. Since predicates can be empty, see section 23, this means that no difficulty now arises when the definite description is empty. Indeed, Russell's analysis helpfully highlights two ways to go wrong in a claim involving a definite description. To adapt an example from Stephen Neal, 1990, suppose Alex claims, 4. I'm dating the present king of France. Using the following symbolization key, A, Alex K of X, is a present king of France D of 10, Y, blank X is dating blank Y. Note that the symbolization key speaks of a present king of France, not the present king of France. That is, it employs indefinite rather than definite description. Sentence 4 would be symbolized by there exists X open bracket K of X and for all Y open bracket K of Y implies X equals Y close bracket and D of a X close bracket. Now, this can be false in at least two ways corresponding to these two different sentences. 5. There is no one who is both the present king of France and such that he and Alex are dating. 6. There is a unique present king of France, but Alex is not dating him. Sentence 5 might be paraphrased by it is not the case that the present king of France and Alex are dating. It will then be symbolized by not exists X open bracket open parenthesis K of X, and for all Y open parenthesis K of Y, implies X equals Y close parenthesis and D of a comma X close bracket. We might call this outer negation since the negation governs the entire sentence. Note that the sentence is true if there is no present king of France. Sentence 6 can be symbolized by there exists an X open bracket K of X and for all Y open parenthesis K of Y implies X equals Y close bracket and not D of a X. We might call this inner negation since the negation occurs within the scope of the definite description. Note that its truth requires that there is a present king of France, albeit one who is not dating Alex. 27.4 Possessives, both, neither. We can use Russell's analysis of definite descriptions also to deal with singular possessive constructions in English. For instance, Smith's murderer means something like the person who murdered Smith, that is, it is a disguised definite description. On Russell's analysis, the sentence 7. Smith's murderer is insane can be false in one of three ways. It can be false because the one person who murdered Smith is not, in fact, insane. But it can also be false if the definite description is empty, namely if either no one murdered Smith, e.g., if Smith met with an unfortunate accident, or if more than one person murdered Smith. To symbolize sentences containing singular possessives such as Smith's murderer, you should paraphrase them using an explicit definite description. For example, the person who murdered Smith is insane, and then symbolize it according to Russell's analysis. In our case, we would use the symbolization key. Domain people I of x is insane m of x comma y, blank x murdered blank ys. Smith our symbolization then reads, there exists x open bracket m of x in s, and for all y open parenthesis m of y in s implies x equals y close parenthesis and I of x close bracket. Two other determiners that we can extend Russell's analysis to are both and neither. To say both fs are g is to say that there are exactly two fs, and each of them is g. To say that neither f is g is to also say that there are exactly two fs and neither of them is g and FOL. The symbolizations would read, respectively.
Math summary. The expression describes two scenarios. The first scenario asserts the existence of two distinct entities, x and y, that both satisfy property f. Furthermore, for all entities z, if z satisfies property f, then z must be either x or y. In addition, both x and y satisfy property g. The second scenario also asserts the existence of two distinct entities, x and y, that both satisfy property f. Similarly, for all entities z, if z satisfies property f, then z must be either x or y. However, in this scenario, neither x nor y satisfies property g.
Compare these symbolizations with the symbolizations of exactly two fs are gs from section 25.4, that is, of there are exactly two things that are both f and g.
Math summary. This statement asserts the existence of two distinct entities. Let's call them the first entity and the second entity. Both the first entity and the second entity possess properties f and g. Furthermore, for any other entity, if that entity also possesses both properties f and g, then that entity must be identical to either the first entity or the second entity. In simpler terms, there are exactly two things that have properties f and g.
The difference between the symbolization of this and that of both fs or g's lies in the antecedent of the conditional. For exactly two fs or gs, we only require that there are no fs that are also gs other than x and y, whereas for both fs or gs, there cannot be any fs whether they are gs or not other than x and y. In other words, both fs are gs implies that exactly two fs are gs. However, exactly two fs are gs does not imply that both fs are gs. There might be a third f which isn't a g. 27.5 The adequacy of Russell's analysis. How good is Russell's analysis of definite descriptions? This question has generated a substantial philosophical literature, but we will restrict ourselves to two observations. One worry focuses on Russell's treatment of empty definite descriptions. If there are no fs, then on Russell's analysis, both the f is g is and the f is non-g are false. P.F. Strawson suggested that such sentences should not be regarded as false exactly but involve presupposition failure, and so need to be treated as neither true nor false. If we agree with Strawson here, we will need to revise our logic, for in our logic there are only two truth values, true and false, and every sentence is assigned exactly one of these truth values. But there is room to disagree with Strawson. Strawson is appealing to some linguistic intuitions, but it is not clear that they are very robust. For example, isn't it just false, not gappy, that Tim is dating the present king of France? Keith Donnellan raised a second sort of worry which, very roughly, can be brought out by thinking about a case of mistaken identity. Two men stand in the corner, a very tall man drinking what looks like a gin martini, and a very short man drinking what looks like a pint of water. Seeing them, Malika says, 8. The gin drinker is very tall. Russell's analysis will have us render Malika's sentence as 8. There is exactly one gin drinker in the corner, and whoever is a gin drinker in the corner is very tall. Now suppose that the very tall man is actually drinking water from a martini glass, whereas the very short man is drinking a pint of neat gin. By Russell's analysis, Malika has said something false, but don't we want to say that Malika has said something true? Again, one might wonder how clear our intuitions are on this case. We can all agree that Malika intended to pick out a particular man and say something true of him, that he was tall. On Russell's analysis, she actually picked out a different man, the short one, and consequently said something false of him. But maybe advocates of Russell's analysis only need to explain why Malika's intentions were frustrated, and so why she said something false. This is easy enough to do. Malika said something false because she had false beliefs about the men's drinks. If Malika's beliefs about the drinks had been true, then she would have said something true. To say much more here would lead us into deep philosophical waters. That would be no bad thing, but for now it would distract us from the immediate purpose of learning formal logic. So for now we will stick with Russell's analysis of definite descriptions when it comes to putting things into FOL. It is certainly the best that we can offer without significantly revising our logic, and it is quite defensible as an analysis. Practice exercises. A. Using the following symbolization key. Domain, people K of X, X knows the combination to the safe. S of X, X is a spy. V of X, X is a vegetarian. T of X, Y, X trusts Y H Hofter. I. Ingmar. Symbolize the following sentences in FOL. 1. Hofter trusts a vegetarian. 2. Everyone who trusts Ingmar trusts a vegetarian. 3. Everyone who trusts Ingmar trusts someone who trusts a vegetarian. 4. Only Ingmar knows the combination to the safe. 5. Ingmar trusts Hofter but no one else. 6. The person who knows the combination to the safe is a vegetarian. 7. The person who knows the combination to the safe is not a spy. B. Using the following symbolization key. Domain, cards in a standard deck B of X, X is black. C of X, blank X is a club. D of X is a deuce. J of X is a jack. M of X, blank is a man with an axe. O of X, blank is one-eyed. W of X is wild. Symbolize each sentence in FOL. 1. All clubs are black cards. 2. There are no wild cards. 3. There are at least 2 clubs. 4. There's more than one one-eyed jack. 5. There are at most 2 one-eyed jacks. 6. There are 2 black jacks. 7. There are 4 deuces. 8. The deuce of clubs is a black card. 9. One-eyed jacks and the man with the axe are wild. 10. If the deuce of clubs is wild, then there is exactly 1 wild card. 11. The man with the axe is not a jack. 12. The deuce of clubs is not the man with the axe. C. Using the following symbolization key. Domain, animals in the world BX, is in Farmer Brown's field. H of X, X is a horse. P of X, blank is a Pegasus. W of X, X has wings. Symbolize the following sentences in FOL. 1. There are at least 3 horses in the world. 2. There are at least 3 animals in the world. 3. There is more than 1 horse in Farmer Brown's field. 4. There are 3 horses in Farmer Brown's field. 5. There is a single winged creature in Farmer Brown's field. Any other creatures in the field must be wingless. 6. The Pegasus is a winged horse. 7. The animal in Farmer Brown's field is not a horse. 8. The horse in Farmer Brown's field does not have wings. D. In this chapter we symbolized Nick is the traitor by there exists X such that T of X and for all Y, T of Y implies X equals Y and X equals N. Explain why these would be equally good symbolizations. T of N and for all Y, T of Y implies N equals Y. For all Y, T of Y if and only if Y equals N. Chapter 28. Ambiguity. In Chapter 7, we discussed the fact that sentences of English can be ambiguous, and pointed out that sentences of TFL are not. One important application of this fact is that the structural ambiguity of English sentences can often, and usefully be straightened out using different symbolizations. One common source of ambiguity is scope ambiguity, where the English sentence does not make it clear which logical word is supposed to be in the scope of which other. Multiple interpretations are possible. In FOL, every connective and quantifier has a well-determined scope, and so whether or not one of them occurs in the scope of another in a given sentence of FOL is always determined. For instance, consider the English idiom. 1. Everything that glitters is not gold. If we think of this sentence as of the form, every F is not G, where F of X symbolizes X glitters and G of X is not gold, we would symbolize it as.
Math summary. This statement asserts that for all input values X, if property F holds for X, then property G does not hold for X. In other words, if X has the attribute F, then it does not have the attribute G.
In other words, we symbolize it the same way as we would nothing that glitters is gold. But the idiom does not mean that. It means that one should not assume that just because something glitters, it is gold. Not everything that appears valuable is in fact valuable. To capture the actual meaning of the idiom, we would have to symbolize it instead as we would not everything that glitters is gold, that is, in the following way.
Math summary. This expression represents the negation of a universal statement. It asserts that it is not the case that for all input values X, if property F holds for X, then property G also holds for X. In simpler terms, it denies that F always implies G.
Compare the first of these with the previous symbolization. Again, we see that the difference in the two meanings of the ambiguous sentence lies in whether the is in the scope of the in the first symbolization or is in the scope of in the second. Of course, we can alternatively symbolize the two readings using existential quantifiers as well.
Math summary. The first statement asserts that there does not exist an X such that both properties f and g are true for X. The second statement asserts that there exists an X such that property f is true for X, and property g is not true for X.
In Chapter 23, we discussed how to symbolize sentences involving only. Consider the sentence. Do only young cats are playful? According to our schema, we would symbolize it this way.
Math summary. This statement describes a conditional relationship that holds for all input values. For every input value, if the first condition is true, then both the second and third conditions are also true.
The meaning of this sentence of FOL is something like, if an animal is playful, it is a young cat, assuming that the domain is animals, of course. This is probably not what's intended in uttering sentence 2, however. It's more likely that we want to say that old cats are not playful. In other words, what we mean to say is that if something is a cat and playful, it must be young. This would be symbolized as.
Math summary. This statement expresses a universal conditional relationship. It means for all entities X, if X is both a cat and playful, then X is young.
There is even a third reading. Suppose we're talking about young animals and their characteristics. And suppose you wanted to say that of all the young animals, only the cats are playful. You could symbolize this reading as.
Math summary. This expression states that for all input values X, if X satisfies conditions Y and P, then X also satisfies condition C. In other words, if input X has properties Y and P, then it must also have property C.
Each of the last two readings can be made salient in English by placing the stress appropriately. For instance, to suggest the last reading, you would say only young cats are playful, and to get the other reading, you would say only young cats are playful. The very first reading can be indicated by stressing both young and cats. Only young cats are playful, but not old cats or dogs of any age. In sections 24.3 and 24.5, we discussed the importance of the order of quantifiers. This is relevant here because in English, the order of quantifiers is sometimes not completely determined. When both universal, all, and existential, some, a quantifiers are involved, this can result in scope ambiguities. Consider. 3. Everyone went to see a movie. This sentence is ambiguous. In one interpretation, it means that there is a single movie that everyone went to see. In the other, it means that everyone went to see some movie or other, but not necessarily the same one. The two readings can be symbolized, respectively, by.
Math summary. The first expression states that there exists a movie such that for all people, if they are a person, then they went to see that movie. The second expression states that for all people, if they are a person, then there exists a movie that they went to see.
We assume here that the domain contains at least people and movies, and the symbolization key P of Y, blank is a person, M of X, blank is a movie, S of Y, X, Y went to see X. In the first reading, we say that the existential quantifier has wide scope, and its scope contains the universal quantifier, which has narrow scope, and the other way round in the second. In Chapter 27, we encountered another scope ambiguity arising from definite descriptions interacting with negation. Consider Russell's own example. 4. The King of France is not bald. If the definite description has wide scope, and we are interpreting the not as an inner negation as we said before, sentence 4 is interpreted to assert the existence of a single king of France to whom we are ascribing non-baldness. In this reading, it is symbolized as there exists an X open bracket K of X, and for all Y open parenthesis K of Y implies X equals Y close parenthesis close bracket and B of X. In the other reading, the not denies the sentence, the King of France is bald, and we would symbolize it as not there exists an X open bracket K of X, and for all Y open parenthesis K of Y implies X equals Y close parenthesis close bracket and B of X. In the first case, we say that the definite description has wide scope, and in the second that it has narrow scope. Practice exercises. A. Each of the following sentences is ambiguous. Provide a symbolization key for each and symbolize all readings. 1. No one likes a quitter. 2. CSI found only red hair at the scene. 3. Smith's murderer hasn't been arrested. B. Russell gave the following example in his paper on denoting.
I have heard of a touchy owner of a yacht to whom a guest, on first seeing it, remarked, "I thought your yacht was larger than it is," and the owner replied, "No, my yacht is not larger than it is."
Explain what's going on. Part 6 Interpretations. Chapter 29. Extensionality. Recall that TFL is a truth-functional language. Its connectives are all truth-functional, and all that we can do with TFL is key sentences to particular truth values. We can do this directly, For example, we might stipulate that the TFL sentence P is to be true. Alternatively, we can do this indirectly, offering a symbolization key, for example. P. Big Ben is in London. But recall from section 10 that this is just a means of specifying P's truth value. The symbolization key statement amounts to something like the following stipulation. The TFL sentence P is true if Big Ben is in London. And we emphasized in section 10 that TFL cannot handle differences in meaning that go beyond mere differences in truth value. 29.1 Symbolizing versus translating. FOL has some similar limitations. It gets beyond mere truth values since it enables us to split up sentences into terms, predicates, and quantifiers. This enables us to consider what is true of some particular object or of some or all objects. But that's it. To unpack this a bit, consider the symbolization key. C of x blank x teaches logic 3 in Calgary. This stipulation does not carry the meaning of the English predicate across into our FOL predicate. We are simply stipulating something like this. C of x and x teaches logic III in Calgary are to be true of exactly the same things. So in particular, Cx is to be true of exactly those things which teach logic III in Calgary, whatever those things might be. This is an indirect way of stipulating which things a predicate is true of. Alternatively, we can stipulate predicate extensions directly. For example, we can stipulate that Cx is to be true of Richard Zach and Richard Zach alone. As it happens, this direct stipulation would have the same effect as the indirect stipulation, since Richard and Richard alone teaches logic III in Calgary. Note, however, that the English predicates is Richard Zach and teaches logic III in Calgary have very different meanings. The point is that FOL has no resources for dealing with nuances of meaning. When we interpret FOL, all we are considering is what the predicates are true of, regardless of whether we specify these things directly or indirectly. The things a predicate is true of are known as the extension of that predicate. We say that FOL is an extensional language because FOL does not represent differences of meaning between predicates that have the same extension. This is why we speak of symbolizing English sentences in FOL. It is doubtful that we are translating English into FOL, for translation should preserve meaning. 29.2 A word on extensions. We can stipulate directly what predicates are to be true of, and our stipulations can be as arbitrary as we like. For example, we could stipulate that HX should be true of and only of the following objects. Every top F key on every piano ever made armed with this interpretation of HX. Suppose we now add to our symbolization key. J. Justin Trudeau A. Angela Merkel P. The number pi then HJ and HP will both be true on this interpretation, but HA will be false since Angela Merkel was not among the stipulated objects. This process of explicit stipulation is sometimes described as stipulating the extension of a predicate. Note that in the stipulation we just gave, the objects we listed have nothing particularly in common. This doesn't matter. Logic doesn't care about what we humans, at a particular moment, think naturally go together. To logic, all objects are on an equal footing. 29.3 Many-place predicates. All of this is quite easy to understand when it comes to one-place predicates, but it gets messier when we consider two-place predicates. Consider a symbolization key like L of x, y, x loves y. Given what we said above, this symbolization key should be read as saying L of x, y, and x loves y are to be true of exactly the same things. So in particular, LXY is to be true of x and y in that order if x loves y. It is important that we insist upon the order here since love famously is not always reciprocated. Note that x and y on the right here are symbols of augmented English and that they are being used. By contrast, x and y in LXY are symbols of FOL and they are being mentioned. That is an indirect stipulation. What about a direct stipulation? This is also tricky. If we simply list objects that fall under L, X, Y, we will not know whether they are the lover or the beloved or both. We have to find a way to include the order in our explicit stipulation. To do this, we can specify that two-place predicates are true of pairs of objects where the order of the pair is important. Thus, we might stipulate that B, X, Y is to be true of and only of the following pairs of objects. The angle bracket Lenin, comma, Marx angle bracket. Angle bracket de Beauvoir, Sartre angle bracket. Angle bracket Sartre, comma, de Beauvoir angle bracket. Here the angle brackets keep us informed concerning order. Suppose we now add the following stipulations. L. Lenin. M. Marx, B. de Beauvoir, R. Sartre. Then BLM will be true since the angle bracket Lenin Marx angle bracket is in our explicit list, but BML will be false since the angle bracket Marx Lenin angle bracket is not in our list. However, both BBR and BRB will be true since both de Beauvoir Sartre and Sartre de Beauvoir are in our explicit list. To make these ideas more precise, we would need to develop some very elementary set theory. Set theory has formal apparatus which allows us to deal with extensions, ordered pairs, and so forth. However, set theory is not covered in this book, so I shall leave these ideas at an imprecise level. Nevertheless, the general idea should be clear. 29.4 Semantics for identity. Identity is a special predicate of FOL. We write it a bit differently than other two-place predicates. X equals Y instead of I, X, Y, for example. More important though, its interpretation is fixed once and for all. If two names refer to the same object, then swapping one name for another will not change the truth value of any sentence. So in particular, if A and B name the same object, then all of the following will be true.
Math summary. The expression defines a set of logical equivalences. The first equivalence states that statement A being true for object A is equivalent to statement A being true for object B. The second equivalence states that statement B being true for object A is equivalent to statement B being true for object B. The third equivalence states that relation R holding between object A and itself is equivalent to relation R holding between object B and itself. The fourth equivalence states that relation R holding between object A and itself is equivalent to relation R holding between object A and object B. The fifth equivalence states that relation R holding between object C and object A is equivalent to relation R holding between object C and object B. The sixth equivalence states that for all objects X, relation R holding between X and is equivalent to relation R holding between X and B.
Some philosophers have believed the reverse of this claim. That is, they have believed that when exactly the same sentences not containing equals are true of and B, then and B are the very same object. This is a highly controversial philosophical claim, sometimes called the identity of indiscernibles, and our logic will not subscribe to it. We allow that exactly the same things might be true of two distinct objects. To bring this out, consider the following interpretation. For every primitive predicate we care to consider, that predicate is true of nothing. Suppose A is a one-place predicate, then AA is false and AB is false, so AA corresponds to AB is true. Similarly, if R is a two-place predicate, then RAA is false and RAB is false, so that RA corresponds to RAB is true. And so it goes, every atomic sentence not involving equals is false, so every biconditional linking such sentences is true. For all that, Tim Button and P.D. Magnus are two distinct people, not one and the same. 29.5 Interpretations. We defined evaluation in TFL as any assignment of truth and falsity to sentence letters. In FOL, we are going to define an interpretation as consisting of four things. The specification of a domain. For each sentence letter we care to consider, a truth value. For each name that we care to consider, an assignment of exactly one object within the domain. For each predicate that we care to consider apart from equals, a specification of what things in what order the predicate is to be true of. We don't need to specify an interpretation of equals since it has a fixed interpretation. The symbolization keys that we considered in Part 5 consequently give us one very convenient way to present an interpretation. We will continue to use them in this chapter. However, it is sometimes also convenient to present an interpretation diagrammatically. To illustrate literally, suppose we want to consider just a single two-place predicate, RXY, then we can represent it just by drawing an arrow between two objects and stipulate that RXY is to hold of X and Y just in case there's an arrow running from X to Y in our diagram. As an example, we might offer.
Image summary. The image is a directed graph. The graph consists of 4 nodes, numbered 1 through 4, with directed edges connecting them. There are edges from 1 to 2, 2 to 3, 3 to 4, 4 to 1, and 1 to 3. The graph indicates a cyclical relationship among the nodes, with node 1 having an additional connection to node 3.
This diagram could be used to describe an interpretation whose domain is the first 4 positive whole numbers, and which interprets R, X, Y as being true of and only of.
Math summary. The expression lists several pairs of numbers. Each pair represents an ordered relationship between two numbers. The pairs are 1 and 2, 2 and 3, 3 and 4, 4 and 1, and finally 1 and 3.
Equally, we might offer this diagram for an interpretation with the same domain which takes the extension of RxY as
Image summary. The image is a directed graph. The graph contains 4 nodes and several directed edges. One node has a self loop, one node has both incoming and outgoing edges, and one node has only an incoming edge. One node is isolated. The graph indicates relationships between the nodes, with some nodes being connected to themselves or other nodes, while one node is disconnected from the rest. Math summary. This expression represents a sequence of ordered pairs. Each pair consists of 2 numbers. The sequence includes the pairs 1, 3, 3, 1, 3, 4, 1, 1, and 3, 3.
If we wanted, we could make our diagrams more complex. For example, we could add names as labels for particular objects. Equally, to symbolize the extension of a one-place predicate, we might simply draw a ring around some particular objects and stipulate that the thus encircled objects, and only them, are to fall under the predicate hx, say. Chapter 30. Truth in FOL. We have introduced you to interpretations. Since, among other things, they tell us which predicates are true of which objects, they will provide us with an account of the truth of atomic sentences. However, we now need to say precisely what it is for an arbitrary FOL sentence to be true or false in an interpretation. We know from section 26 that there are 3 kinds of sentence in FOL. Atomic sentences. Sentences whose main logical operator is a sentential connective. Sentences whose main logical operator is a quantifier. We need to explain truth for all 3 kinds of sentence. We will provide a completely general explanation in this section. However, to try to keep the explanation comprehensible, we will, at several points, use the following interpretation. This will be our go-to example in what follows. 30.1 Atomic sentences. The truth of atomic sentences should be fairly straightforward. For sentence letters, the interpretation specifies if it is true or false. The sentence PA should be true just in case PX is true of a. Given our go-to interpretation, this is true if Aristotle is a philosopher. Aristotle is a philosopher, so the sentence is true. Equally, PB is false on our go-to interpretation. Likewise, on this interpretation, R of a B is true if and only if the object named by A was born before the object named by B. Well, Aristotle was born before Beyonce, so R of a B is true. Equally, R of a is false. Aristotle was not born before Aristotle. Dealing with atomic sentences, then, is very intuitive. When script R is an M-place predicate in alpha sub 1, alpha sub 2, through alpha sub n are names, recall, though, that there's a special kind of atomic sentence. 2 names connected by an identity sign constitute an atomic sentence. This kind of atomic sentence is also easy to handle, where alpha and beta are any names, so in our go-to interpretation, equals B is false, since Aristotle is distinct from Beyonce.
Code summary. The algorithm determines the truth of an identity statement in an interpretation. The input is an identity statement consisting of 2 names. The output is whether the statement is true, which is true if and only if the 2 names refer to the identical object within that interpretation. The truth evaluation is more straightforward.
30.2 Sentential connectives. We saw in section 26 that FOL sentences can be built up from simpler ones using the truth functional connectives that were familiar from TFL. The rules governing these truth functional connectives are exactly the same as they were when we considered TFL. Here they are.
Code summary. The code defines the truth conditions for logical connectives, such as conjunction, disjunction, negation, implication, and equivalence. It specifies when a formula using these connectives is true based on the truth values of its components. For example, a conjunction is true if and only if both parts are true, while a disjunction is true if at least one part is true. The code provides a similar definition for all the logical connectives.
This presents the very same information as the characteristic truth tables for the connectives, it just does so in a slightly different way. Some examples will probably help to illustrate the idea. Make sure you understand them on our go-to interpretation. A equals n P of A is true. R of a comma B and P of B is false because, although R of a comma B is true, P of B is false. A equals B or P of A is true. Not sign A equals B is true. P of A and not of open parenthesis A equals B and R of a comma B close parenthesis is true because P of A is true and A equals B is false. Make sure you understand these examples. 30.3 When the main logical operator is a quantifier. The exciting innovation in FOL, though, is the use of quantifiers, but expressing the truth conditions for quantified sentences is a bit more fiddly than one might first expect. Here is a naive first thought. We want to say that for all x, f of x is true if and only if f of x is true of everything in the domain. This should not be too problematic. Our interpretation will specify directly what f of x is true of. Unfortunately, this naive thought is not general enough. For example, we want to be able to say that for all x there exists y L of x comma y is true just in case, speaking roughly, there exists y L of x comma y is true of everything in the domain. But our interpretation does not directly specify what there exists y L of x comma y is true of. Instead, whether or not this is true of something should follow just from the interpretation of the predicate L, the domain, and the meanings of the quantifiers. So here's a second naive thought. We might try to say that for all x there exists y L of x and y is to be true in an interpretation if and only if there exists y L of alpha and y is true for every name alpha that we have included in our interpretation. Similarly, we might try to say that there exists y L of alpha and y is true just in case 50 of alpha and beta is true for some name beta that we have included in our interpretation. Unfortunately, this is not right either. To see this, observe that our go-to interpretation only interprets two names, A and B, but the domain all people born before the year 2000 CE contains many more than two people, and we have no intention of trying to correct for this by naming all of them. So here is a third thought, and this thought is not naive but correct. Although it is not the case that we have named everyone, each person could have been given a name. So we should focus on this possibility of extending an interpretation by adding a new name. We will offer a few examples of how this might work, centering on our go-to interpretation, and we will then present the formal definition. In our go-to interpretation, there exists an x such that R of bx should be true. After all, in the domain, there is certainly someone who was born after Beyoncé. Lady Gaga is one of those people. Indeed, if we were to extend our go-to interpretation temporarily mined by adding the name C to refer to Lady Gaga, then R of BC would be true on this extended interpretation. This surely should suffice to make there exists an x such that R of bx true on the original go-to interpretation. In our go-to interpretation, there exists x such that p of x and R of x comma should also be true. After all, in the domain, there is certainly someone who is both a philosopher and born before Aristotle. Socrates is one such person. Indeed, if we were to extend our go-to interpretation by letting a new name, C, denote Socrates, then W of C and R of C comma A would be true on this extended interpretation. Again, this should surely suffice to make there exists x such that p of x and R of x comma A true on the original go-to interpretation. In our go-to interpretation, for all x there exists y R of x, y should be false. After all, consider the last person born in the year 1999. We don't know who that was, but if we were to extend our go-to interpretation by letting a new name to denote that person, then we would not be able to find anyone else in the domain to denote with some further new name, perhaps E, in such a way that R of D, E would be true. Indeed, no matter whom we named with E, R of D, E would be false. This observation is surely sufficient to make there exists y R of D, y false in our extended interpretation, which in turn is surely sufficient to make for all x there exists y R of x, y false on the original go-to interpretation. If you have understood these three examples, that's what matters. It provides the basis for a formal definition of truth for quantified sentences. Strictly speaking, though, we still need to give that definition. The result, sadly, is a bit ugly and requires a few new definitions. Brace yourself. Suppose that it is a formula containing at least one occurrence of the variable x, and that x is free in A. We will write this thus.
Math summary: this represents a formula, named script A, that contains at least one occurrence of a variable, named x. The variable x is free in script A. The expression shows that script A is a function of x, where x appears multiple times within the function.
Suppose also that C is a name, then we will write.
Math summary: this expression represents a formula A where every instance of a variable x is replaced by a name C. This creates a substitution instance of the original formula.
For the formula we obtain by replacing every occurrence of x in A with C, the resulting formula is called a substitution instance of for all xa, and there exists xa also. C is called the instantiating name. So,
Math summary: this statement asserts the existence of some input x, such that the relation R holds between constant E and x, if and only if the property f holds for x.
Is a substitution instance of.
Math summary, the expression states that for every y, there exists an x such that r of y in x is true if and only if f of x is true. In simpler terms, for each y, there is an x where a relationship r between y and x holds exactly when a property f holds for x.
With the instantiating name e and instantiated variable y. Our interpretation will include a specification of which names correspond to which objects in the domain. Take any object in the domain, say D, and a name C which is not already assigned by the interpretation. If our interpretation is I, then we can consider the interpretation bold I, with D over C in brackets, which is just like bold I except it also assigns the name C to the object D. Then we can say that D satisfies the formula script A, with ellipses x ellipses x ellipses, in the interpretation bold I if, and only if script A with ellipses C ellipses C ellipses is true in bold I, with D over C in brackets. If D satisfies script A with ellipses x ellipses x ellipses, we also say that script A with ellipses x ellipses x ellipses is true of D. The interpretation ID/C is just like the interpretation I, except it also assigns the name C to the object D. An object D satisfies script A with ellipses x ellipses x ellipses, in interpretation bold I if and only if script A with ellipses C ellipses C ellipses is true in bold I with D over C. So for instance, Socrates satisfies the formula P of x. Since P of C is true in the interpretation I with Socrates over C, that is, the interpretation domain, all people born before 2000 CE, Aristotle B, Beyonce C, Socrates P of x, x is a philosopher R of x, y, blank was born before blank. Armed with this notation, the rough idea is as follows. The sentence for all x, A, xx, will be true in I if and only if for any object D in the domain, A, C, C, is true in ID/C, that is, no matter what object in the domain we name with C. In other words, for all x, A, xx, is true if every object in the domain satisfies A, xx. Similarly, the sentence there exists x will be true if and only if there is some object that satisfies A, xx, that is, A, C, C, true in ID/C for some object D.
Code summary, the algorithm defines the truth conditions for universal and existential quantifiers in an interpretation. A universally quantified formula is true if every object in the domain satisfies the formula. An existentially quantified formula is true if at least one object in the domain satisfies the formula.
To be clear, all this is doing is formalizing very pedantically the intuitive idea expressed on the previous page. The result is a bit ugly and the final definition might look a bit opaque. Hopefully, though, the spirit of the idea is clear. Finally, let us note that the concept of an object satisfying a formula with a free variable can also be extended to formulas with more than one free variable. If we have a formula script A of x and y with two free variables x and y, then we can say that a pair of objects angle bracket A, B angle bracket satisfies script A of x and y if and only if script A of C and D is true in the interpretation extended by two names C and D, where C names A and D names B. So for instance, angle bracket Socrates, Plato angle bracket satisfies R of x and y since R of C and D is true in the interpretation. Domain, all people born before 2000 CE, Aristotle B, Beyonce C, Socrates D, Plato P of x, blank x is a philosopher R of x, y. Blank was born before blank for atomic formulas. The objects, pairs of objects, etc., that satisfy them are exactly the extension of the predicate given in the interpretation. But the notion of satisfaction also applies to non-atomic formulas. For example, the formula P of x and R of x, B is satisfied by all philosophers born before Beyonce. It even applies to formulas involving quantifiers. For example, P of x and not there exists a y such that P of y and R of y, x is satisfied by all people who are philosophers, and for whom it is true that no philosopher was born before them. In other words, it is true of the first philosopher. Practice exercises. A. Consider the following interpretation. The domain comprises only Corwin and Benedict. AX is to be true of both Corwin and Benedict. BX is to be true of Benedict only. NX is to be true of no one. C is to refer to Corwin. Determine whether each of the following sentences is true or false in that interpretation. 1. B of C. 2. Of C if and only if not N of C. 3. N of C implies of C or B of C. 4. For all x, A of x. 5. For all x not B of x. 6. There exists x such that A of x and B of x. 7. There exists x such that O of x implies N of x. 8. For all x, N of x or not N of x. 9. There exists x b of x implies for all x a of x. B. Consider the following interpretation. The domain comprises only Lemmy, Courtney, and Eddie. Gx is to be true of Lemmy, Courtney, and Eddie. Hx is to be true of and only of Courtney. Mx is to be true of and only of Lemmy and Eddie. Z is to refer to Courtney. E is to refer to Eddie. Determine whether each of the following sentences is true or false in that interpretation. 1h of C. 2h of E. 3m of C or m of E. 4g of C or not g of C. 5m of C maps to g of C. 6. There exists x such that h of x. 7. For all x h of x. 8. There exists x such that not m of x. 9. There exists x such that h of x and g of x. 10. There exists x such that m of x and g of x. 11. For all x h of x or m of x. 12. There exists x such that h of x and there exists x such that m of x. 13. For all x h of x if and only if not m of x. 14. There exists x g of x and there exists x not g of x. 15. For all x there exists a y such that g of x and h of y. See following the diagram conventions introduced at the end of section 29, consider the following interpretation.
Image summary. The image is a directed graph. The graph depicts relationships between 5 nodes, labeled 1 through 5. Node 1 has a self-loop and edges directed towards nodes 2, 3, 4, and 5. Node 2 has an edge directed towards node 5. Node 5 also has a self-loop. Node 1 has more outgoing connections than any other node. Nodes 3 and 4 have no outgoing connections.
Determine whether each of the following sentences is true or false in that interpretation. 1. There exists an x such that r of x, x2. For all x r of x, x3. There exists x such that for all y r of x and y4. There exists x such that for all y r of y x for all y for all z open parenthesis r of x and r of y and z close parenthesis implies r of x and z close parenthesis. 6. For all x for all y for all z open parenthesis r of x and y and r of x and z close parenthesis implies r of y and z close parenthesis. 7. There exists x such that for all y not r of x, y for all x there exists a y such that r of x, y implies there exists a y such that r of y x. There exists an x, there exists a y such that not x equals y and r of x, y and r of y, x. 10. There exists x for all y r of x and y, if and only if x equals y. 11. There exists x such that for all y r of y and x if and only if x equals y. 12. There exists x, there exists y such that not x equals y and r of x, y and for all z r of z x if and only if y equals z. Chapter 31. Semantic Concepts. Defining truth in FOL was quite fiddly, but now that we are done, we can define various other central logical notions. These definitions will look very similar to those for TFL from section 12. However, remember that they concern interpretations rather than valuations. We will use the symbol for FOL much as we did for TFL, so.
Math summary. The expression states that given a collection of interpretations, there is no interpretation in which all of the interpretations are true and a condition is false.
Means that there is no interpretation in which all of a sub 1, a sub 2 through a sub n are true and in which C is false. Derivatively not equal to a means that A is true in every interpretation. The other logical notions also have corresponding definitions in FOL. Play button in FOL sentence A is a validity if it is true in every interpretation, that is, A. A is a contradiction if it is false in every interpretation, that is, A. A sub 1, a sub 2 through a sub n, therefore C is valid in FOL if and only if there is no interpretation in which all of the premises are true and the conclusion is false. That is, a sub 1, a sub 2 through a sub n model C it is invalid in FOL otherwise. Play button 2 FOL sentences A and B are equivalent if they are true in exactly the same interpretations as each other, that is, both a B and BA. Play button the FOL sentences a sub 1, a sub 2, and so on, a sub n are jointly satisfiable if some interpretation makes all of them true. They are jointly UNSATISFIABLE if there is no such interpretation. Chapter 32. Using interpretations. 32.1 Validities and contradictions. Suppose we want to show that exists XA, XX to be D is not a validity. This requires showing that the sentence is not true in every interpretation, that is, that it is false in some interpretation. If we can provide just one interpretation in which the sentence is false, then we will have shown that the sentence is not a validity. In order for there exists XA of XX implies B of D to be false, the antecedent there exists XA of XX must be true and the consequent B of D must be false. To construct such an interpretation, we start by specifying a domain. Keeping the domain small makes it easier to specify what the predicates will be true of, so we will start with a domain that has just one member. For concreteness, let's say it is just the city of Paris. Domain Paris. The named must refer to something in the domain, so we have no option but D. Paris. Recall that we want exists XA, XX to be true, so we want all members of the domain to be paired with themselves in the extension of A. We can just offer of XY blank is identical with blank. Now ADD is true, so it is surely true that XAXX. Next, we want BD to be false, so the referent of D must not be in the extension of B. We might simply offer BX is in Germany. Now we have an interpretation where there exists XA of XX is true, but where B of D is false. So there is an interpretation where there exists XA of XX implies B of D is false. So there exists XA of XX implies B of D is not a validity. We can just as easily show that there exists XA of X, X implies B of D is not a contradiction. We need only specify an interpretation in which there exists XA of X, X implies B of D is true. That is, an interpretation in which either there exists XA of X, X is false or B of D is true. Here is one domain, Paris D, Paris A of X, Y, blank is identical with blank B of X. Blank is in France. This shows that there is an interpretation where there exists X, A of XX implies B of D is true. So there exists X, A of XX implies B of D is not a contradiction. To show that A is not a validity, it suffices to find an interpretation where A is false. To show that A is not a contradiction, it suffices to find an interpretation where A is true. 32.2 Logical equivalence. Suppose we want to show that for all x, s of x, and there exists an x such that s of x are not logically equivalent. We need to construct an interpretation in which the two sentences have different truth values. We want one of them to be true and the other to be false. We start by specifying a domain. Again, we make the domain small so that we can specify extensions easily. In this case, we will need at least two objects. If we chose a domain with only one member, the two sentences would end up with the same truth value. In order to see why, try constructing some partial interpretations with one-member domains. For concreteness, let's take domain Ornette Coleman Miles Davis. We can make there exists xs of x true by including something in the extension of s, and we can make for all xs of x false by leaving something out of the extension of s. For concreteness, let's say
Math summary. This expression defines a function s of x, where s of x is true if x plays saxophone.
Now there exists s of x is true because s of x is true of Ornette Coleman. Slightly more precisely, extend our interpretation by allowing C' to name Ornette Coleman. S of C is true in this extended interpretation, so there exists s of x was true in the original interpretation. Similarly, for all s of x is false because s of x is false of Miles Davis. Slightly more precisely, extend our interpretation by allowing prime to name Miles Davis, and s of D is false in this extended interpretation. So for all s of x was false in the original interpretation. We have provided a counterinterpretation to the claim that for all s of x and there exists s of x are logically equivalent. To show that A and B are not logically equivalent, it suffices to find an interpretation where one is true and the other is false. 32.3 Validity, entailment, and satisfiability. To test for validity, entailment, or satisfiability, we typically need to produce interpretations that determine the truth value of several sentences simultaneously. Consider the following argument in FOL.
Math summary. The expression presents a logical argument. It starts with a premise that there exists an x such that g of x implies g of a. From this, it concludes that there exists an x such that g of x implies g of a.
To show that this is invalid, we must make the premise true and the conclusion false. The conclusion is a conditional, so to make it false, the antecedent must be true and the consequent must be false. Clearly, our domain must contain two objects. Let's try domain Karl Marx, Ludwig von Mises G(x). X hated communism of Karl Marx. Given that Marx wrote the Communist Manifesto, G of A is plainly false in this interpretation. But von Mises famously hated communism, so there exists an X such that G of X is true in this interpretation. Hence, there exists an X such that G of X implies G of A is false, as required. Does this interpretation make the premise true? Yes, it does. Note that G of A implies G of A is true. Indeed, it is a validity. But then certainly there exists an X such that G of X implies G of A is true, so the premise is true and the conclusion is false in this interpretation. The argument is therefore invalid. In passing, note that we have also shown that there exists X open parenthesis G of X implies G of A close parenthesis. Does not entail there exists X G of X implies G of A, that is, that there exists X open parenthesis G of X implies G of A close parenthesis, not element of there exists X G of X implies G of A equally. We have shown that the sentences there exists X open parenthesis G of X implies G of A close parenthesis, and negation of open parenthesis there exists X G of X implies G of A close parenthesis are jointly satisfiable. Let's consider a second example. Consider
Math summary. The expression presents a logical argument. It starts with the premise. For every x there exists a y such that L of x and y is true. The argument concludes, there exists a y such that for every x, L of x and y is true. The double arrow indicates the argument's implication.
Again, we want to show that this is invalid. To do this, we must make the premises true and the conclusion false. Here's a suggestion. Domain. Canadian citizens currently in a domestic partnership with another Canadian citizen L of x, y. Blank is in a domestic partnership with blank. The premise is clearly true on this interpretation. Anyone in the domain is a Canadian citizen in a domestic partnership with some other Canadian citizen. That other citizen will also then be in the domain. So for everyone in the domain, there will be someone else in the domain with whom they are in a domestic partnership. Hence, for all x there exists a y such that L of x and y is true. However, the conclusion is clearly false, for that would require that there is some single person who is in a domestic partnership with everyone in the domain, and there is no such person, so the argument is invalid. We observe immediately that the sentences, for all x there exists a y such that L of x and y, and negation of there exists a y such that for all x L of x and y, are jointly satisfiable, and that for all x there exists a y such that L of x and y does not entail there exists a y such that for all x L of x and y. For our third example, we'll mix things up a bit. In section 29, we described how we can present some interpretations using diagrams. For example,
Image summary. The image is a directed graph. The graph contains 3 nodes, labeled 1, 2, and 3. There are directed edges from node 1 to node 2, node 1 to node 3, and node 2 to node 3. Node 1 also has a self-loop. Node 1 has more outgoing edges than the other nodes. Node 3 has no outgoing edges.
Using the conventions employed in section 29, the domain of this interpretation is the first 3 positive whole numbers, and R, x, y is true of x and y just in case there is an arrow from x to y in our diagram. Here are some sentences that the interpretation makes true. For all x there exists a y such that R of y x. There exists x for all y R of x y. Witness 1. There exists an x such that for all y, R of y in x if and only if x equals y. Witness 1.
Math summary. This expression asserts the existence of 3 elements. Let's call them element 1, element 2, and element 3, such that element 2 is not equal to element 3, and there is a relation between element 1 and element 2, and there is also a relation between element 3 and element 1.
Witness 2. There exists x for all y not R of x, y. Witness 3. There exists x open parenthesis there exists y R of y in x and not there exists y R of x and y close parenthesis. Witness 3. This immediately shows that all of the preceding 6 sentences are jointly satisfiable. We can use this observation to generate invalid arguments, for example, and many more besides.
Code summary. The code presents 2 logical arguments using predicate logic notation. The first argument involves quantifiers and a relation R, attempting to derive a conclusion from 2 premises. The second argument also uses quantifiers and a relation R, along with its negation, to derive a more complex conclusion involving the non-existence of certain relationships between elements. Code summary. The code explains when an argument is invalid. An argument is invalid if there exists an interpretation where all premises are true, but the conclusion is false. In this case, the premises do not entail the conclusion, and the premises along with the negation of the conclusion are consistent.
An interpretation which refutes a claim to logical truth, say, or to entailment is called a counterinterpretation or a countermodel. We'll close this section, though, with a caution about the relationship between invalidity and non-entailment. Recall FOL's limitations. It is an extensional language, it ignores issues of vagueness, and it cannot handle cases of validity for special reasons. To take one illustration of these issues, consider this natural language argument. Every fox is cute, therefore all vixens are cute. This is valid. Necessarily every vixen is a fox, so it is impossible for the premise to be true and the conclusion false. Now we might sensibly symbolize the argument as follows.
Math summary: this expression represents a logical argument. The premise states that for all x, if x has property f, then x has property c. The conclusion states that for all x, if x has property v, then x has property c. The argument attempts to infer the conclusion from the premise.
However, it is easy to find countermodels which show that for all x, f of x implies c of x is not in for all x, v of x implies c of x. Exercise. Find one. So, it would be wrong to infer that the English argument is invalid just because there is a countermodel to the relevant FOL entailment. The general moral is this. If you want to infer from the absence of an entailment in FOL to the invalidity of some English argument, then you need to argue that nothing important is lost in the way you have symbolized the English argument. Practice exercises. A. Show that each of the following is neither a validity nor a contradiction. B. Show that the following pairs of sentences are not logically equivalent. C. Show that the following sentences are jointly satisfiable. 1. M of a not N of a P of a not Q of a. 2. L of E, E, L of E, G, not L of G, E, not L of G, G. 3. Not open parenthesis M of a and there exists X A of X close parenthesis comma M of a or F of a comma for all X open parenthesis F of X implies A of X close parenthesis.
Math summary: this expression consists of two statements. The first statement is a logical OR between M of a and M of B. The second statement is a logical implication. If M of a is true, then for all X, not M of X is true.
5. For all y, g of y, for all x, g of x implies h of x. There exists a y such that not I of y there exists x, such that b of x or a of x, for all x, not c of x, for all x, open parens, a of x and b of x, close parens, implies c of x there exists x, x of x, there exists x, y of x, for all x of x, if and only if not y of x 8. For all x, p of x or q of x, there exists an x such that not q of x and p of x 9. There exists a z such that n of z and o of z, z for all x and for all y, o of x, y implies o of y, x. 10. Not exists x for all y, r of x, y, for all x exists y, r of x, y 11. Not r of a for all x equals or r of x at 12. For all x, for all y, for all z, open bracket, open parenthesis, x equals y, or y equals z, close parenthesis, or x equals z, close bracket, and there exists x, there exists y, not x equals y. 13. There exists x, there exists y, open parenthesis, z of x and z of y, close parenthesis, and x equals y, close parenthesis, not z of d, d equals e.
Algorithm: a summary. The algorithm presents a series of logical statements in symbolic form. The input is a set of these statements. The task is to demonstrate that each statement is neither a validity nor a contradiction, meaning it can be true or false depending on the interpretation of its symbols. The output is a determination of whether each statement can be both true and false. Algorithm B summary. The algorithm checks if pairs of logical statements are not logically equivalent. It takes pairs of logical statements as input. The output is a determination of whether the two input statements are logically equivalent or not. The algorithm checks for non-equivalence, meaning it seeks to demonstrate that the two statements do not have the exact same truth values under all possible interpretations.
D. Show that the following arguments are invalid. 1. For all x, a of x implies b of x, therefore there exists x, b of x. 2. For all x, r of x implies d of x, for all x, r of x implies f of x, therefore there exists an x such that d of x and f of x. 3. There exists x open parenthesis p of x implies q of x close parenthesis, therefore there exists x p of x for n of a and n of b and n of c, therefore for all x n of x 5 r of d e there exists x r of x d, therefore r of e d 6. There exists x open parenthesis e of x and f of x close parenthesis, there exists x f of x implies there exists x g of x, therefore there exists x open parenthesis e of x and g of x close parenthesis for all x o of x comma c for all x o of c comma x, therefore for all x o of x comma x 8. There exists x such that j of x and k of x, there exists x such that not k of x, there exists x such that not j of x, therefore there exists x such that not j of x and not k of x. L of a b implies for all x L of x b exists x L of x b, therefore L of b b for all x. D of x implies there exists a y such that t of y x, therefore there exists a y, there exists a z such that not y equals z. Chapter 33. Reasoning about all interpretations. 33.1 Validities and contradictions. We can show that a sentence is not a validity just by providing one carefully specified interpretation, an interpretation in which the sentence is false. To show that something is a validity, on the other hand, it would not be enough to construct 10, 100, or even 1,000 interpretations in which the sentence is true. A sentence is only a validity if it is true in every interpretation, and there are infinitely many interpretations. We need to reason about all of them, and we cannot do this by dealing with them one by one. Sometimes we can reason about all interpretations fairly easily. For example, we can offer a relatively simple argument that R of a or not R of a is a validity. Any relevant interpretation will give R of a truth value. If R of a is true in an interpretation, then R of a or not R of a is true in that interpretation. If R of a is false in an interpretation, then not R of a is true, and so R of a or not R of a is true in that interpretation. These are the only alternatives. So R of a or not R of a is true in every interpretation, therefore it is a validity. This argument is valid, of course, and its conclusion is true. However, it is not an argument in FOL. Rather, it is an argument in English about FOL. It is an argument in the metalanguage. Note another feature of the argument. Since the sentence in question contained no quantifiers, we did not need to think about how to interpret a and r. The point was just that, however we interpreted them, a would have some truth value or other. We could ultimately have given the same argument concerning TFL sentences. Let's have another example. The sentence for all x open parenthesis R of x comma x or not R of x comma x close parenthesis should obviously be a validity. However, saying precisely why is quite tricky. We cannot say that R of x comma x or not R of x comma x is true in every interpretation, since R of x comma x or not R of x comma x is not even a sentence of FOL. Remember that x is a variable, not a name. Instead, we should say something like this. Consider some arbitrary interpretation. For all x, R of x comma x or not R of x comma x is true in our interpretation if and only if R of x comma x or not R of x comma x is satisfied by every object of its domain. Consider some arbitrary member of the domain which for convenience we will call Fred. Either Fred satisfies R of x comma x or it does not. If Fred satisfies R of x comma x, then Fred also satisfies R of x comma x, or not R of x comma x. If Fred does not satisfy R of x comma x, it does satisfy not R of x comma x and so also R of x comma x, or not R of x comma x. So either way, Fred satisfies R of x comma x or not R of x comma x. Since there was nothing special about Fred, we might have chosen any object. We see that every object in the domain satisfies R of x comma x or not R of x comma x. So for all x, R of x comma x or not R of x comma x is true in our interpretation. But we chose our interpretation arbitrarily, so for all x, R of x comma x or not R of x comma x is true in every interpretation. It is therefore a validity. This is quite long-winded, but as things stand, there is no alternative. In order to show that a sentence is a validity, we must reason about all interpretations. 33.2 Other cases. Similar points hold of other cases too. Thus, we must reason about all interpretations if we want to show that a sentence is a contradiction, for this requires that it is false in every interpretation. That two sentences are logically equivalent, for this requires that they have the same truth value in every interpretation. That some sentences are jointly unsatisfiable, for this requires that there is no interpretation in which all of those sentences are true together. that is that, in every interpretation, at least one of those sentences is false. That an argument is valid, for this requires that the conclusion is true in every interpretation where the premises are true. That some sentences entail another sentence. The problem is that with the tools available to you so far, reasoning about all interpretations is a serious challenge. For a final example, here is a perfectly obvious entailment.
Math summary. This expression represents a logical entailment. It states that if for all x, h of x and j of x are true, then it logically follows that for all x, h of x is true.
After all, if everything is both h and j, then everything is h, but we can only establish the entailment by considering what must be true in every interpretation in which the premise is true. To show this, we would have to reason as follows. Consider an arbitrary interpretation in which for all x, open parenthesis h of x and j of x close parenthesis is true. It follows that open angle bracket h of x and j of x close angle bracket is satisfied by every object in this interpretation. Open angle bracket h of x close angle bracket will then also be satisfied by every object. So it must be that open angle bracket for all x h of x close angle bracket is true in the interpretation. We've assumed nothing about the interpretation, except that it was one in which open angle bracket for all x open parenthesis h of x and j of x close parenthesis close angle bracket is true. So any interpretation in which open angle bracket for all x open parenthesis h of x and j of x close parenthesis close angle bracket is true is one in which open angle bracket for all x h of x close angle bracket is true. Even for a simple entailment like this one, the reasoning is somewhat complicated. For more complicated entailments, the reasoning can be extremely torturous. The following table summarizes whether a single interpretation or counterinterpretation suffices, or whether we must reason about all interpretations.
Table summary. The table shows whether all interpretations or a single interpretation counterinterpretation are sufficient to determine different logical properties. For validity, contradiction, equivalence, validity, and entailment, all interpretations are required to confirm the property, while a single counterinterpretation is enough to refute it. Conversely, for satisfiability, a single interpretation suffices, but all interpretations are needed to prove it is not satisfiable.
You might want to compare this table with the table at the end of section 14. The key difference resides in the fact that TFL concerns truth tables, whereas FOL concerns interpretations. This difference is deeply important since each truth table only ever has finitely many lines, so that a complete truth table is a relatively tractable object. By contrast, there are infinitely many interpretations for any given sentence, S, so that reasoning about all interpretations can be a deeply tricky business. Part 7. Natural Deduction for FOL. Chapter 34. Basic Rules for FOL. The language of FOL makes use of all of the connectives of TFL, so proofs in FOL will use all of the basic and derived rules from Part 4. We will also use the proof-theoretic notions, particularly the symbol, introduced there. However, we will also need some new basic rules to govern the quantifiers and to govern the identity sign. 34.1 Universal Elimination. From the claim that everything is F, you can infer that any particular thing is F, you name it. It's F, so the following should be fine.
Math summary. This expression performs a universal elimination. It starts with the premise that for all x, the relation R holds for x, x, and d. It then infers that the relation R also holds for a, and d, using universal elimination on line 1.
We obtained line 2 by dropping the universal quantifier and replacing every instance of x with a. Equally, the following should be allowed.
Math summary. The expression demonstrates the application of the universal elimination rule. It starts with a universally quantified statement. For all x, the relation R holds for x, x, and d. The rule allows us to infer that the relation R holds for specific instances, in this case, d, d, and d. The expression shows this inference twice, resulting in the statement R, d, d, d each time.
We obtained line 2 here by dropping the universal quantifier and replacing every instance of x with d. We could have done the same with any other name we wanted. This motivates the universal elimination rule for all e.
Math summary. This represents the universal elimination rule. It starts with a universally quantified statement, meaning for all x, a statement A involving x is true. The rule then allows us to infer that the statement A is true for a specific instance, C, by substituting C for every instance of x in the original statement.
The notation here was introduced in section 30. The point is that you can obtain any substitution instance of a universally quantified formula, replace every instance of the quantified variable with any name you like. We should emphasize that, as with every elimination rule, you can only apply the ForAllE rule when the universal quantifier is the main logical operator, so the following is banned.
Math summary. This represents an attempt to apply a universal elimination rule in logic. Line 1 states that for all x, b of x implies b of k. Line 2 attempts to derive that b of b implies b of k, but this is flagged as an incorrect application of the universal elimination rule.
This is illegitimate since ForAllX is not the main logical operator in line 1. If you need a reminder as to why this sort of inference should be banned, reread section 23. 34.2 Existential Introduction. From the claim that some particular thing is f, you can infer that something is f, so we ought to allow.
Math summary. This represents an existential introduction in logic. First, we have the premise R applied to the constant A, and the constant D. From this, we infer that there exists an x such that R applied to the constant A, and x holds. This is achieved using the existential introduction rule.
Here we have replaced the name D with a variable x and then existentially quantified over it. Equally, we would have allowed.
Math summary. The expression demonstrates an existential introduction rule. Starting with a relation R that includes the constants A, and D, it derives a new statement. This new statement asserts the existence of an x such that the relation R holds for x, and D. This is achieved through existential generalization.
Here we have replaced both instances of the name A with a variable and then existentially generalized. But we do not need to replace both instances of a name with a variable. If Narcissus loves himself, then there is someone who loves Narcissus, so we also allow.
Math summary. The expression presents a logical inference. Starting with a relation R involving elements A and D, it infers the existence of an element x such that the relation R holds between x, and D. This is an existential introduction rule.
Here we have replaced one instance of the name A with a variable and then existentially generalized. These observations motivate our introduction rule, although to explain it, we will need to introduce some new notation. Whereas a sentence containing the name C, we can emphasize this by writing A, say C. We will write A, x C, to indicate any formula obtained by replacing some or all of the instances of the name C with the variable x. Armed with this, our introduction rule is. The constraint is included to guarantee that any application of the rule yields a sentence of FOL. Thus the following is allowed.
Table summary. The table illustrates examples of valid applications of existential quantifier introduction rules, showing how to introduce existential quantifiers based on existing statements.
But this is banned since the expression on line 3 contains clashing variables and so is not a sentence of FOL.
Code summary. The provided example demonstrates the existential introduction rule in first-order logic. It shows a valid application where a constant is generalized to an existentially quantified variable. It also shows an invalid attempt where the same variable is used multiple times within the same quantifier, which is disallowed due to variable clashing. Algorithm M summary. The algorithm describes two rules for introducing quantifiers. The first rule introduces an existential quantifier, stating that if a formula holds for a specific constant, then there exists a variable for which the formula holds. The variable must not occur freely in the original formula. The second rule introduces a universal quantifier, stating that if a formula holds for a specific constant, then the formula holds for all variables. The constant must not occur in any undischarged assumption, and the variable must not occur freely in the original formula.
34.3 Empty domains. The following proof combines our two new rules for quantifiers.
Table summary. The table illustrates a proof combining rules for quantifiers, showing how an existential quantifier can be introduced from a universally quantified statement.
Could this be a bad proof? If anything exists at all, then certainly we can infer that something is f from the fact that everything is f, but what if nothing exists at all? Then it is surely vacuously true that everything is f. However, it does not follow that something is f, for there is nothing to be f, so if we claim that as a matter of logic alone exists x f x follows from for all x f x, then we are claiming that as a matter of logic alone there is something rather than nothing. This might strike us as a bit odd. Actually, we are already committed to this oddity. In section 22, we stipulated that domains in FOL must have at least one member. We then defined a validity of FOL as a sentence which is true in every interpretation. Since XX equals X will be true in every interpretation, this also had the effect of stipulating that it is a matter of logic that there is something rather than nothing. Since it is far from clear that logic should tell us that there must be something rather than nothing, we might well be cheating a bit here. If we refuse to cheat though, then we pay a high cost. Here are 3 things that we want to hold on to. For all x, f of x entails f of a. After all, that was for all elimination. F of a entails there exists x such that f of x. After all, that was exists introduction. The ability to copy and paste proofs together. After all, reasoning works by putting lots of little steps together into rather big chains. If we get what we want on all 3 counts, then we have to countenance that for all x f x exists x f x. So, if we get what we want on all 3 counts, the proof system alone tells us that there is something rather than nothing. And if we refuse to accept that, then we have to surrender one of the 3 things that we want to hold on to. Before we start thinking about which to surrender, we might want to ask how much of a cheat this is. Granted, it may make it harder to engage in theological debates about why there is something rather than nothing, but the rest of the time we will get along just fine. So maybe we should just regard our proof system and FOL more generally as having a very slightly limited purview. If we ever want to allow for the possibility of nothing, then we will have to cast around for a more complicated proof system. But for as long as we are content to ignore that possibility, our proof system is perfectly in order. As, similarly, is the stipulation that every domain must contain at least one object. 34.4 Universal Introduction. Suppose you had shown of each particular thing that it is F, and that there are no other things to consider. Then you would be justified in claiming that everything is F. This would motivate the following proof rule. If you had established each and every single substitution instance of for all x, f of x, then you can infer for all x, f of x. Unfortunately, that rule would be utterly unusable. To establish each and every single substitution instance would require proving FA, FB, FJ2, FR sub 79002, and so on. Indeed, since there are infinitely many names in FOL, this process would never come to an end. So we could never apply that rule. We need to be a bit more cunning in coming up with our rule for introducing universal quantification. A solution will be inspired by considering.
Math summary. This expression describes a logical inference. It states that if a predicate f is true for all x, then it follows that the predicate f is true for all y. Essentially, it's a renaming of the variable.
This argument should obviously be valid. After all, alphabetical variation ought to be a matter of taste and of no logical consequence. But how might our proof system reflect this? Suppose we begin a proof thus.
Math summary. The expression presents 2 lines of logical inference. Each line states that if for all x, f of x is true, then f of a is also true. This is derived using the rule of universal elimination, denoted as for all E1.
We have proved f of a, and of course nothing stops us from using the same justification to prove f of b, f of c, f of j sub 2, f of r sub 79002, and so on until we run out of space, time, or patience. But reflecting on this, we see that there's a way to prove f sub c for any name c, and if we can do it for anything, we should surely be able to say that f is true of everything. This therefore justifies us in inferring for all y, f of y thus.
Math summary. This derivation shows a logical inference. It starts with the premise that for all x, f of x is true. From this, it infers that f of a is true for some arbitrary a. Finally, it generalizes to conclude that for all y, f of y is true.
The crucial thought here is that a was just some arbitrary name. There was nothing special about it. We might have chosen any other name and still the proof would be fine. And this crucial thought motivates the universal introduction rule 6. A crucial aspect of this rule, though, is bound up in the first constraint. This constraint ensures that we are always reasoning at a sufficiently general level. To see the constraint in action, consider this terrible argument. Everyone loves Kylie Minogue, therefore everyone loves themselves. We might symbolize this obviously invalid inference pattern as.
Math summary. The expression represents a logical inference. It starts with the premise that for all x, x loves k. It then concludes that for all x, x loves x, meaning everyone loves themselves. This inference is invalid because the constant k occurs in the initial assumption.
Now suppose we tried to offer a proof that vindicates this argument.
Math summary. This represents a logical argument or proof attempt. The first row contains the premise. For all x, L of x and k, the second row contains L of k and k, derived by applying the for-all elimination rule to the first row. The third row attempts to conclude, for all x, L of x and x, which is described as a naughty attempt to invoke the for-all introduction rule.
This is not allowed because k occurred already in an undischarged assumption, namely, on line 1. The crucial point is that, if we have made any assumptions about the object we are working with, then we are not reasoning generally enough to license for all I. Although the name may not occur in any undischarged assumption, it may occur in a discharged assumption. That is, it may occur in a subproof that we have already closed. For example, this is just fine.
Math summary: this demonstrates a logical proof. First, g of d is asserted. Second, g of d is asserted again. Third, an implication is formed stating that g of d implies g of d. Finally, a universal quantification is applied, stating for all z, g of z implies g of z.
This tells us that for all z, g of z implies g of z is a theorem, and that is as it should be. We should emphasize one last point. As per the conventions of section 30.3, the use of for all I requires that we are replacing every instance of the name c in script A of ellipsis x ellipsis x ellipsis with the variable x. If we only replace some names and not others, we end up proving silly things. For example, consider the argument. Everyone is as old as themselves, so everyone is as old as Judi Dench. We might symbolize this as follows.
Math summary: this expression attempts to make a logical deduction. Given that for all x, O of x and x is true, it tries to conclude that for all x, O of x and d is true. In simpler terms, if something is true when applied to itself, the expression attempts to conclude it's also true when applied to a specific element.
But now suppose we tried to vindicate this terrible argument with the following.
Math summary: this represents a symbolic logic derivation or proof attempt, structured as a matrix. The first row contains the statement for all x, O of x and x, and the symbol for all E1. The second row contains O of d and d, and a note indicating a problematic attempt to apply for all I2.
Fortunately, our rules do not allow for us to do this. The attempted proof is banned, since it doesn't replace every occurrence of d in line 2 with an x. 34.5 Existential elimination. Suppose we know that something is f. The problem is that simply knowing this does not tell us which thing is f, so it would seem that from there exists x, f of x, we cannot immediately conclude f of a, f of e sub 23, or any other substitution instance of the sentence. What can we do? Suppose we know that something is f and that everything which is f is also g. In almost natural English, we might reason thus. Since something is f, there is some particular thing which is an f. We do not know anything about it. Other than that, it's an f, but for convenience, let's call it Becky. So Becky is f. Since everything which is f is g, it follows that Becky is g, but since Becky is g, it follows that something is g and nothing depended on which object exactly Becky was. So something is g. We might try to capture this reasoning pattern in a proof as follows. Breaking this down, we started by writing down our assumptions. At line 3, we made an additional assumption, f of b. This was just a substitution instance of there exists an x such that f of x. On this assumption, we established there exists an x such that g of x. Note that we had made no special assumptions about the object named by b. We had only assumed that it satisfies f of x, so nothing depends upon which object it is. And line 1 told us that something satisfies f of x, so our reasoning pattern was perfectly general. We can discharge the specific assumption f of b and simply infer there exists an x such that g of x on its own. Putting this together, we obtain the existential elimination rule: there exists e. As with universal introduction, the constraints are extremely important. To see why, consider the following terrible argument. Tim Button is a lecturer, someone is not a lecturer. So Tim Button is both a lecturer and not a lecturer. We might symbolize this obviously invalid inference pattern as follows.
Math summary: this expression presents a logical argument. It starts with the premise that a property applies to an element b, and that there exists an element x for which that property does not apply. From these premises, the argument concludes that the property both applies and does not apply to element b, resulting in a contradiction.
Now, suppose we tried to offer a proof that vindicates this argument.
Code summary: the code attempts to demonstrate a logical proof involving existential quantifiers and conjunction. It starts with an assumption and an existential statement. It then tries to derive a contradiction and invoke existential elimination, but the attempt is flawed because the variable used in the substitution instance appears in an earlier undischarged assumption. The code highlights a common mistake in applying existential elimination and emphasizes the importance of choosing a fresh variable to avoid invalid inferences.
The last line of the proof is not allowed. The name that we used in our substitution instance for there exists x such that not L of x on line 3, namely b, occurs in line 4. This would be no better.
Code summary: the code attempts to derive a contradiction using existential elimination. It starts with a statement about an object having a property and another statement asserting that there exists an object that does not have that property. The derivation incorrectly applies existential elimination, leading to an invalid conclusion. The input is a set of logical statements, and the output is an attempted proof with an error in applying a logical rule. The derivation is flawed because it uses a variable that already appears in an undischarged assumption, violating the restrictions on existential elimination.
The last line is still not allowed. For the name that we used in our substitution instance for exists x not L x, namely b, occurs in an undischarged assumption, namely line 1. The moral of the story is this: if you want to squeeze information out of an existential quantifier, choose a new name for your substitution instance. That way, you can guarantee that you meet all the constraints on the rule for exists E.
Algorithm E summary. The image describes the existential elimination rule in logic. It shows how to infer a statement from the existence of something satisfying a condition, subject to certain restrictions. The input is a statement asserting the existence of something with a certain property, and a derivation based on assuming a specific instance of that thing. The output is the conclusion of the derivation, provided that the specific instance does not appear in the assumptions or the existential statement itself. The algorithm emphasizes that certain constraints are important.
Practice exercises. A. Explain why these two proofs are incorrect. Also, provide interpretations which would invalidate the fallacious argument forms the proofs enshrine.
Math summary. The expression represents a logical proof. The first line states that for all x, Rx is true, and on the right side, for all x, there exists a y such that Rxy is true. The second line infers that Raa is true based on the first line, and on the right side it infers that there exists a y such that Ray is true based on the first line. The third line infers that for all y, Ray is true based on the second line. The fourth line infers that for all x and for all y, Rxy is true based on the third line. Finally, the fifth line infers that there exists an x such that Rxx is true based on lines 2, 3, and 4.
B. The following three proofs are missing their citations, rule, and line numbers. Add them to turn them into bona fide proofs.
Table summary. The table presents a series of logical statements and derivations, starting from universally quantified statements and progressing through existential instantiations and disjunctions to arrive at conclusions about the existence of relationships.
1. For all x and y. L of x, y implies for all z, L of z. x2, L of a b3, there exists y, L of a y implies for all z, L of z. A4, there exists y, L of a y5 for all z, L of z. A6, L of c. A7, there exists y, L of c, y implies for all z, L of z. C8, there exists y, L of c, y9 for all z, L of z. C10, L of c, C11 for all x, L of x, x12 for all x. J of x implies k of x13, there exists x. For all y, L of x, y14 for all x. J of x15 left vertical bar begin array. C for all y, L of a y double backslash, L of a end array right 16. J of implies k of a 17, k of a 18, k of an L of a 19, there exists x. K of x and L of x, x20, there exists x. K of x and L of x, x. See in section 23 problem A, we considered 15 syllogistic figures of Aristotelian logic. Provide proofs for each of the argument forms. In B, you will find it much easier if you symbolize, for example, no f is g, as for all x, open parenthesis f of x implies not g of x close parenthesis. D. Aristotle and his successors identified other syllogistic forms which depended upon existential import. Symbolize each of these argument forms in FOL and offer proofs. 1. Barbari, something is h all g or f all h or g so, some h is f. 2. Celerant, something is h no g or f all h or g so, some h is not f. 3. Cesaro, something is h no f or g all h or g so, some h is not f. 4. Kamstros, something is h all f or g no h or g so, some h is not f. 5. Phelopton, something is g no g or f all g or h so, some h is not f. 6. Derupti, something is G all G R F all G R H so, some H is F. 7. Kalimos, something is H all F or G no G R H so, some H is not F. 8. Fesapo, something is G no F is G all G R H so, some H is not F. 9. Bamali, something is F all F or G all G R H so, some H or F. Provide a proof of each claim. 1. Proves for all x, f of x implies for all y, open parenthesis, f of y, and f of y, close parenthesis. 2. For all x, a of x implies b of x, there exists x, o of x proves there exists x, b of x. 3. For all x, m of x, if and only if n of x, m of a, and there exists an x, r of x, a, proves there exists an x, n of x. 4. For all x, for all y, g of x and y, entails there exists an x such that g of x and x. 5. Proves for all x, r of x, x implies there exists x, there exists y, r of x, y. 6. Turnstile symbol for all y, there exists x, open parenthesis, q of y, implies q of x, close parenthesis. 7. N of a implies for all x, m of x if and only if m of a, not m of b proves not n of a. 8. For all x, for all y, open parenthesis, g of x, y, implies g of y, x, close parenthesis, proves for all x, for all y, open parenthesis, g of x, y, if and only if g of y, x, close parenthesis.
Math summary: this expression represents a logical argument in predicate logic. It asserts that given the premises for all x not m, x, or ljx, for all x bx implies ljx, and for all x m, x, or bx, one can conclude for all x ljx. The symbol between the premises and the conclusion indicates logical entailment.
F. Write a symbolization key for the following argument, symbolize it, and prove it. There is someone who likes everyone that she likes. Therefore, there is someone who likes herself. G. Show that each pair of sentences is provably equivalent.
Math summary 1. This statement involves universal quantification over x, stating that for all x, if a of x is true, then not b of x is true. It also states that there does not exist an x such that both a of x and b of x are true. 2. This statement involves universal quantification over x, stating that for all x, if not a of x is true, then b of d is true. It also states that for all x, a of x or b of d is true. 3. This statement says that if there exists an x such that p of x is true, then q of c is true. It also states that for all x, if p of x is true, then q of c is true.
H. For each of the following pairs of sentences, if they are provably equivalent, give proofs to show this. If they are not, construct an interpretation to show that they are not logically equivalent. 1. For all x, p of x implies q of c. For all x, p of x implies q of c. 2. For all x, for all y, for all z, b of x, y, z. For all x, b of x, x, x. 3. For all x, for all y, d of x and y. For all y, for all x, d of x and y. 4. There exists x such that for all y, d of x and y. For all y, there exists x such that d of x and y.
Math summary: the expression presents two logical equivalences. The first equivalence states that for all x, the relation R holds between constant c and constant a if, and only if the relation R holds between x and a. The second equivalence states that the relation R holds between constant c and constant a if, and only if for all x, the relation R holds between x and a.
1. For each of the following arguments, if it is valid in FOL, give a proof. If it is invalid, construct an interpretation to show that it is invalid. 1. There exists a y such that for all x, r of x and y. Therefore, for all x, there exists a y such that r of x and y. 2. For all x, there exists a y such that r of x and y. Therefore, there exists a y such that for all x, r of x and y. 3. There exists x such that p of x and not q of x. Therefore, for all x, p of x implies not q of x. 4. For all x, s of x implies t of a s of d. Therefore, t. 5. For all x, a of x implies b of x, and for all x, b of x implies c of x. Therefore, for all x, a of x implies c of x.
Math summary: this logical argument has two premises and a conclusion. The first premise states that there exists an x, such that x has property d or property e. The second premise states that for all x, if x has property d, then x has property f. The conclusion states that there exists an x, such that x has property d and property f.
7 for all x for all y, r of x comma y or r of y comma x, therefore r of j comma j. 8 there exists x, there exists y, open parenthesis r of x comma y or r of y comma x close parenthesis, therefore r of j comma j. 9 for all x p of x implies for all x q of x there exists x not p of x, therefore there exists x not q of x. 10 there exists x m of x implies there exists x n of x and not there exists x n of x, therefore for all x not m of x. Chapter 35. Proofs with quantifiers. In section 17, we discuss strategies for constructing proofs using the basic rules of natural deduction for TFL. The same principles apply to the rules for the quantifiers. If we want to prove a quantifier sentence for all x, a of x, or there exists x, a of x, we can work backward by justifying the sentence we want by for all introduction or there exists introduction, and trying to find a proof of the corresponding premise of that rule. And to work forward from a quantified sentence, we apply for all elimination or there exists elimination, as the case may be. Specifically, suppose you want to prove for all x, a of x. To do so using for all I, we would need a proof of a of c for some name c which does not occur in any undischarged assumption. To apply the corresponding strategy, that is, to construct a proof of for all x, a of x by working backward, is thus to write a of c above it, and then to continue to try to find a proof of that sentence.
Math summary, this represents a step in a formal proof. It starts with a proof of a statement involving a specific element, denoted as a of c. Then, at step n+1, it generalizes this to a universal statement, saying for all x, a of x, which is justified by universal introduction at step n. Of c is obtained from a of x by replacing every free occurrence of x in a of x by c. For this to work, c must satisfy the special condition. We can ensure that it does by always picking a name that does not already occur in the proof constructed so far. Of course, it will occur in the proof we end up constructing, just not in an assumption that is undischarged at line n+1. To work backward from a sentence there exists x script a of x, we similarly write a sentence above it that can serve as a justification for an application of the there exists introduction rule, that is, a sentence of the form script a of c. Math summary, the expression represents a segment of a proof. It shows a statement a of c, followed by the existential quantification of a of x, and the existential quantification of I of n. This is followed by n+1, indicating a step in the proof. This looks just like what we would do if we were working backward from a universally quantified sentence. The difference is that whereas for all we have to pick a name c which does not occur in the proof, so far, for exists we may and in general must pick a name c which already occurs in the proof. Just like in the case of for all, it is often not clear which c will work out, and so to avoid having to backtrack you should work backward from existentially quantified sentences only when all other strategies have been applied. By contrast, working forward from sentences there exists 10 script a of 10 generally always works and you won't have to backtrack. Working forward from an existentially quantified sentence takes into account not just there exists x script a of x, but also whatever sentence script b you would like to prove. It requires that you set up a subproof above script b, wherein script b is the last line, and a substitution instance script a of c of there exists x script a of x as the assumption. In order to ensure that the condition on c that governs there exists e is satisfied, choose a name c which does not already occur in the proof. Code summary, the provided structure represents a step in a formal proof involving an existential quantifier. It illustrates how to introduce a specific instance to prove the existence of something with a certain property. The input is a statement asserting the existence of an element with a specific property. The output is a subproof where a specific instance is used to demonstrate the property, ultimately leading to a conclusion about the existence statement. You'll then continue with the goal of proving b, but now inside a subproof in which you have an additional sentence to work with, namely a of c. Lastly, working forward from for all 10 script a of 10 means that you can always write down script a of c and justify it using for all e. For any name c, of course, you wouldn't want to do that willy-nilly. Only certain name c will help in your task of proving whatever goal sentence you're working on. So like working backward from there exists 10 script a of 10, you should work forward from for all x script a of x only after all other strategies have been applied. Let's consider as an example the argument for all x open parenthesis a of x implies b close parenthesis implies exists x, a of x implies b. To start constructing a proof, we write the premise at the top and the conclusion at the bottom. Math summary, this represents a step in a formal proof. It starts with line 1, which contains a universally quantified statement. for all x, if a of x is true, then b is true. Then there are intermediate steps represented by the vertical dots. Finally, at line n, the proof reaches a certain point.
The strategies for connectives of TFL still apply, and you should apply them in the same order. First, work backward from conditionals, negated sentences, conjunctions, and now also universal quantifiers. Then forward from disjunctions and now existential quantifiers. And only then try to apply arrow E, not EVI for all E, or there exists I in our case. That means working backward from the conclusion.
Math summary: this expression represents a logical proof. It starts with a universal statement. For all x, if a of x is true, then b is true. It then introduces an existential statement. There exists an x for which a of x is true. From this existential statement, through a series of logical steps, it derives b. Finally, it concludes that if there exists an x for which a of x is true, then b is true, which is derived by implication introduction from line 2 to line n-1.
Our next step should be to work forward from exists x on line 2. For that, we have to pick a name not already in our proof. Since no names appear, we can pick any name, say d.
Math summary: the expression represents a logical proof. It starts with a universal quantification stating for all x, if ax is true, then b is true. It also assumes the existence of an x such that ax is true. Through a series of logical deductions, it derives that b is true. Finally, it concludes that if there exists an x such that ax is true, then b is true, using an implication introduction rule.
Now we've exhausted our primary strategies, and it is time to work forward from the premise for all x. A of x implies b. Applying for all e means we can justify any instance of a of c implies b, regardless of what c we choose. Of course, we'll do well to choose d, since that will give us a of d implies b, then we can apply implies e to justify b, finishing the proof.
Math summary: this expression represents a logical proof. It starts with the premise that for all x, if a of x is true, then b is true. It also assumes that there exists an x for which a of x is true. From these premises, it derives that of d is true for some specific d using the initial premise. It infers that if a of d is true, then b is true. Therefore, b is true. It then concludes that if there exists an x such that a of x is true, then b is true.
Now let's construct a proof of the converse. We begin with
Math summary: the expression outlines a logical deduction process. It starts with the premise that there exists an x such that O of x implies b. Through a series of logical steps, it arrives at the conclusion that for all x, a of x implies b.
Note that the premise is a conditional, not an existentially quantified sentence, so we should not yet work forward from it. Working backward from the conclusion for all x, a of x implies b, leads us to look for a proof of a of d implies b.
Math summary: this expression represents a logical proof. It begins with the assumption that for some x, a of x implies b. Through a series of steps, it arrives at the conclusion that for all x, a of x implies b. This conclusion is reached by applying a universal introduction rule, based on the preceding steps from step 1 to step n-1.
And working backward from O of d implies b means we should set up a subproof with a of d as an assumption and b as the last line.
Math summary: this represents a logical proof. It starts with the assumption that there exists an x such that O of x implies b. It then proceeds with a of d, where d is a specific instance. Through a series of logical deductions, it arrives at b next. It infers that O of d implies b. Finally, it generalizes to say that for all x, a of x implies b.
Now we can work forward from the premise on line 1. That's a conditional, and its consequent happens to be the sentence b we are trying to justify. So we should look for a proof of its antecedent, exists x. Of course, that is now readily available by exists I from line 2, and we're done.
Table summary: the table presents a logical argument, demonstrating the steps to derive a universal statement from an existential conditional statement. It starts with the conditional statement and proceeds through intermediate steps involving existential instantiation, conditional proof, and universal generalization to reach the final conclusion.
Practice exercises. A. Use the strategies to find proofs for each of the following arguments and theorems.
Math summary: this expression represents a logical inference. It starts with the premise that implies for all x, b of x. It then concludes that for all x, a implies b of x. There exists x, open parenthesis, a implies b of x, close parenthesis. Therefore, implies there exists x, b of x. Math summary: the first expression states that for all input values x, a of x and b of x is equivalent to for all x, a of x and for all x, B of x, the second expression states that there exists an input x, such that a of x or b of x is equivalent to there exists an x, such that a of x or there exists an x such that b of x. The third expression states that or for all x, b of x implies that for all x. A or b of x, the fourth expression states that for all x, a of x implies b. Therefore there exists an x such that o of x implies b. The fifth expression states that there exists an x such that o of x implies b. Therefore for all x, a of x implies b.
8. For all x, a of x implies there exists a y such that a of y. Use only the basic rules of TFL in addition to the basic quantifier rules. B. Use the strategies to find proofs for each of the following arguments and theorems. 1. For all x, r of x, x. Therefore, for all x, there exists a y such that r of x, y.
Math summary. The expression represents a series of logical statements and deductions using quantifiers. Statement 2 says for all x, y, and z, if r of x and y and r of y and z, then r of x and z. Therefore, for all x and y, if r of x and y, then for all z, if r of y and z, then r of x and z. Statement 3 says for all x, y, and z, if r of x and y and r of y and z, then r of x and z, and for all x and y, if r of x and y, then r of y and x. Therefore, for all x, y, and z, if r of x and y and r of x and z, then r of y and z. Statement 4 says for all x and y, if r of x and y, then r of y and x. Therefore, for all x, y, and z, if r of x and y and r of x and z, then there exists a u such that r of y in u and r of z in u. Statement 5 says it is not the case that there exists an x such that for all y, a of x and y, if and only if not a of y and y.
C. Use the strategies to find proofs for each of the following arguments and theorems.
Math summary. 1. This expression takes a universal quantification of a of x implying b, and infers the existence of x such that o of x implies b2. This expression takes implying the existence of x of b of x, and infers the existence of x such that it implies b of x3. This expression takes the universal quantification of x of a or b of x, and infers o or the universal quantification of x of b of x4. This expression asserts the existence of x such that o of x implies the universal quantification of y of a of y5. This expression asserts the existence of x such that the existence of y of a of y implies a of x.
These require the use of IP. Use only the basic rules of TFL in addition to the basic quantifier rules. Chapter 36. Conversion of quantifiers. In this section, we will add some additional rules to the basic rules of the previous section. These govern the interaction of quantifiers and negation. In section 22, we noted that not exists x a is logically equivalent to for all x not a. We will add some rules to our proof system that govern this. In particular, we add an m not exists x script a for all x not script a. CQ hem equally we add.
Table summary. The table illustrates quantifier conversions. It shows that a universally quantified statement's negation is equivalent to an existentially quantified negation, and vice versa, under the principle of quantifier conversion.
Practice exercises. A. Show in each case that the sentences are provably inconsistent.
Math summary. This statement represents a logical argument with three parts. First, S of implies T of M. Second, T of M implies S of A. Third, T of M and not S of A.
2. Not exists x r of x comma a for all x for all y r of y comma x. 3. Not exists x exists y l of x comma y l of a comma a. 4. For all x, p of x implies q of x for all z, p of z implies r of z for all y, p of y not q of a and not r of b. B. Show that each pair of sentences is provably equivalent.
Math summary. The expression states two logical rules. The first rule states that for all x, if a of x is true, then b of x is not true. The second rule states that it is not the case that there exists an x such that both a of x and b of x are true.
See, in section 23, we considered what happens when we move quantifiers across various logical operators. Show that each pair of sentences is provably equivalent.
Math summary. The expression presents 6 pairs of logical statements and asks to show that each pair of sentences is provably equivalent. The first pair involves a universal quantifier applied to a conjunction. The second pair involves an existential quantifier applied to a disjunction. The third, fourth, fifth, and sixth pairs involve combinations of universal and existential quantifiers with implications.
In B, the variable x does not occur in G, A, When all the quantifiers occur at the beginning of a sentence, that sentence is said to be in pronounced normal form. These equivalences are sometimes called pronouncing rules since they give us a means for putting any sentence into pronounced normal form. Chapter 37. Rules for Identity. In section 29, we mentioned the philosophically contentious thesis of the identity of indiscernibles. This is the claim that objects which are indiscernible in every way are, in fact, identical to each other. It was also mentioned that we will not subscribe to this thesis. It follows that no matter how much you learn about two objects, we cannot prove that they are identical. That is, unless, of course, you learn that the two objects are, in fact, identical, but then the proof will hardly be very illuminating. The general point, though, is that no sentences which do not already contain the identity predicate could justify an inference to A equals B. So our identity introduction rule cannot allow us to infer to an identity claim containing two different names. However, every object is identical to itself. No premises, then, are required in order to conclude that something is identical to itself. So this will be the identity introduction rule.
Math summary. This expression represents an identity introduction rule. It states that for any object, that object is identical to itself, and this identity is equal to 1.
Notice that this rule does not require referring to any prior lines of the proof. For any name C, you can write C equals C on any point with only the equals I rule as justification. Our elimination rule is more fun. If you have established A equals B, then anything that is true of the object named by A must also be true of the object named by B. For any sentence with A in it, you can replace some or all of the occurrences of A with B and produce an equivalent sentence. For example, from RAA and A equals B, you are justified in inferring RAB, RBA, or RBB more generally.
Math summary. The expression describes a substitution rule. If object A is equal to object B, then a formula containing multiple instances of object A is equivalent to a formula where one or more instances of object A are replaced with object B. This equivalence is denoted by E and depends on lines M and N.
The notation here is as for there exists ISO script A of ellipsis alpha ellipsis is a formula containing the name alpha, and script A of ellipsis beta ellipsis alpha ellipsis is a formula obtained by replacing one or more instances of the name alpha with the name beta. Lines M and N can occur in either order and do not need to be adjacent, but we always cite the statement of identity first. Symmetrically, we allow.
Math summary. This describes a rule of identity. If item A equals item B, then a statement involving item A, where item A appears multiple times, can be transformed by replacing one or more instances of item A with item B. The result is logically equivalent. The expression E represents this equivalence.
This rule is sometimes called Leibniz's law, after Gottfried Leibniz. To see the rules in action, we will prove some quick results. First, we will prove that identity is symmetric.
Begin aligned and begin aligned and 1 quad and left begin erasea equals b h line a equals a ender ray right. In 2 quad and left begin array cb equals a ender ray right. In 3 quad and left begin erasea equals b right row b equals a ender ray right. Quad left begin array c4 y equals y right row y equals a ender ray right. Quad left begin array c4 x 4 y x equals y right row y equals x ender ray right. Quad left begin array c4 I quad ender ray right. In end align quad equals mathemi and equals mathemi1 2 in right row mathemi1 -3 in left begin array c 4 I quad ender ray right in left begin array c 4 I quad ender ray right. In left begin array c 4 I quad ender ray right. In left begin array c 4 I quad ender ray right. In left begin array c We obtain line 3 by replacing one instance of A in line 2 with an instance of B. This is justified given A equals B. Second, we will prove that identity is transitive. Math summary. The expression demonstrates the transitive property of equality. It starts with the premise that A equals B and B equals C. It then uses these equalities to deduce that A equals C. This deduction is then generalized using universal quantification to show that for all x, y, and z, if x equals y and y equals z, then x equals z.
We obtain line 4 by replacing B in line 3 with A. This is justified given A equals B. Practice exercises. A. Provide a proof of each claim.
Math summary: the first statement represents a logical argument. Given P of A or Q of B, and Q of B implies B equals C, and not P of A, it proves Q of C. The second statement represents another logical argument. Given M equals N or N equals O, and O of N, it proves A of M or A of O.
3. For all x, x equals m, r of m, entails there exists an x such that r of x, x.
Math summary 4. Given that for all x and for all y, if r of x and y is true, then x equals y, it proves that if r of A and b is true, then r of b and it is true. 5. Given that it is not the case that there exists an x such that x is not equal to m, it proves that for all x and for all y, if p of x is true, then p of y is true. 6. Given that there exists an x such that j of x is true, and there exists an x such that not j of x is true, it proves that there exists an x and there exists a y such that x is not equal to y. 7. Given that for all x, x equals n if and only if m of x is true, and for all x, o of x is true or not m of x is true, it proves that o of n is true. 8. Given that there exists an x such that d of x is true, and for all x, x equals p if and only if d of x is true, it proves that d of p is true. 9. Given that there exists an x such that k of x is true, and for all y, if k of y is true, then x equals y, and b of x is true, and k of d is true, it proves that b of d is true.
10. Proves P of implies for all x, P of x or not x equals A. B. Show that the following are provably equivalent.
Math summary: the expression asserts the existence of a unique entity, named n, that possesses a certain property f. It states that there exists an x such that x has the property f, and for all y, if y has the property f, then x and y are the same and x is equal to n. The second expression states that n has the property f, and for all y, if y has the property f, then n and y are the same.
And hence that both have a decent claim to symbolize the English sentence, Nick is the F. See in section 25 we claimed that the following are logically equivalent symbolizations of the English sentence. There is exactly one F.
Math summary: the expression describes a logical statement asserting the existence of exactly one entity, x, that satisfies a property, f. The first part of the expression states that there exists an x such that f of x is true, and for all x and y, if f of x and f of y are true, then x and y are the same. The second expression states that there exists an x such that f of x is true, and for all y, if f of y is true, then x and y are the same. The third expression states that there exists an x such that for all y, f of y is true if and only if x and y are the same.
Show that they are all provably equivalent. Hint: to show that 3 claims are provably equivalent, it suffices to show that the first proves the second proves the third, and the third proves the first. Think about why. D. Symbolize the following argument. There is exactly one F, there is exactly one G. Nothing is both F and G, so there are exactly 2 things that are either F or G. And offer a proof of it. Chapter 38. Derived rules. As in the case of TFL, we first introduced some rules for FOL as basic in section 34, and then added some further rules for conversion of quantifiers in section 36. In fact, the CQ rules should be regarded as derived rules, for they can be derived from the basic rules of section 34. The point here is as in section 20. Here is a justification for the first CQ rule.
Table summary: the table presents a derivation consisting of multiple steps, starting from universal and existential quantifications, leading to a contradiction, and finally deriving the negation of the existential quantification.
Here is a justification of the third CQ rule.
Math summary: this expression presents a logical proof. It starts with the premise that there exists an x for which a of x is false, and also assumes that for all x, a of x is true. From the second assumption, it infers that a of c is true for some constant c. It then shows a contradiction by using the initial premise that a of c is false. From this contradiction, it concludes that the initial assumption, that for all x, a of x is true, must be false. Therefore, it concludes that it is not the case that for all x, a of x is true.
This explains why the CQ rules can be treated as derived. Similar justifications can be offered for the other 2 CQ rules. Practice exercises. A. Offer proofs which justify the addition of the second and fourth CQ rules as derived rules. Chapter 39. Proofs and Semantics. We have used two different turnstiles in this book. This
Math summary, the expression represents a proof-theoretic notion. It states that there exists a proof that ends with conclusion C, given a set of assumptions A1, A2 through N. The assumptions A1 through N are the only undischarged assumptions in the proof.
means that there is some proof which ends with C and whose only undischarged assumptions are among a sub 1, a sub 2, through a sub n. This is a proof-theoretic notion. By contrast, this
Math summary, this expression asserts that given a collection of assumptions, it is semantically true that no valuation or interpretation makes all of the assumptions true and the conclusion false. This concerns assignments of truth and falsity to sentences.
means that no valuation or interpretation makes all of a sub 1, a sub 2 through a sub n true and C false. This concerns assignments of truth and falsity to sentences. It is a semantic notion. It cannot be emphasized enough that these are different notions, but we can emphasize it a bit more. They are different notions. Once you have internalized this point, continue reading. Although our semantic and proof-theoretic notions are different, there is a deep connection between them. To explain this connection, we will start by considering the relationship between validities and theorems. To show that a sentence is a theorem, you need only produce a proof. Granted, it may be hard to produce a 20-line proof, but it is not so hard to check each line of the proof and confirm that it is legitimate. And if each line of the proof individually is legitimate, then the whole proof is legitimate. Showing that a sentence is a validity, though, requires reasoning about all possible interpretations. Given a choice between showing that a sentence is a theorem and showing that it is a validity, it would be easier to show that it is a theorem. Contrawise, to show that a sentence is not a theorem is hard. We would need to reason about all possible proofs. That is very difficult. However, to show that a sentence is not a validity, you need only construct an interpretation in which the sentence is false. Granted, it may be hard to come up with the interpretation, but once you have done so, it is relatively straightforward to check what truth value it assigns to a sentence. Given a choice between showing that a sentence is not a theorem and showing that it is not a validity, it would be easier to show that it is not a validity. Fortunately, a sentence is a theorem if and only if it is a validity. As a result, if we provide a proof of A on no assumptions and thus show that it is a theorem, that is, A, we can legitimately infer that it is a validity. That is, similarly, if we construct an interpretation in which it is false and thus show that it is not a validity, that is, not in a, it follows that it is not a theorem, that is, for all A. More generally, we have the following powerful result.
Math summary, this expression states that a conclusion B is provable from a set of premises, A1 through N if, and only if B is semantically entailed by the set of premises A1 through N. In other words, provability and semantic entailment are equivalent.
This shows that whilst provability and entailment are different notions, they are extensionally equivalent. As such, an argument is valid if the conclusion can be proved from the premises. Two sentences are logically equivalent if they are provably equivalent. Sentences are satisfiable if they are not provably inconsistent. For this reason, you can pick and choose when to think in terms of proofs and when to think in terms of valuations interpretations, doing whichever is easier for a given task. The table on the next page summarizes which is usually easier. It is intuitive that provability and semantic entailment should agree. But let us repeat this, do not be fooled by the similarity of the symbols, and these two symbols have very different meanings. The fact that provability and semantic entailment agree is not an easy result to come by. In fact, demonstrating that provability and semantic entailment agree is, very decisively, the point at which introductory logic becomes intermediate logic. Give an interpretation in which it is false, give a proof which shows plus or minus. A given interpretation in which it is true, give a proof which shows entails not a is a contradiction. Give an interpretation in which A and B have different truth values, give two proofs. One for a plus B and one for B plus A are A and B equivalent. Prove a contradiction from assumptions a sub 1, a sub 2 through a sub n. Give an interpretation in which all of a sub 1, a sub 2 through a sub n are true are a sub 1, a sub 2 through a sub n jointly satisfiable. Give an interpretation in which each of a sub 1, a sub 2 through a sub n is true and C is false. Give a proof with assumptions a sub 1, a sub 2 through a sub n and concluding with C is a sub 1, a sub 2 ellipsis, a sub n, therefore C valid. Part 8 Modal Logic. Chapter 40. Introducing Modal Logic. Modal logic ML is the logic of modalities, ways in which a statement can be true. Necessity and possibility are two such modalities. A statement can be true, but it can also be necessarily true no matter how the world might have been. For instance, logical truths are not just true because of some accidental feature of the world, but true come what may. A possible statement may not actually be true, but it might have been true. We use to express necessity and to express possibility. So you can read A as it is necessarily the case that A, and A as it is possibly the case that A. There are lots of different kinds of necessity. It is humanly impossible for me to run at 100 mph. Given the sorts of creatures that we are, no human can do that. But still, it isn't physically impossible for me to run that fast. We haven't got the technology to do it yet, but it is surely physically possible to swap my biological legs for robotic ones which could run at 100 mph. By contrast, it is physically impossible for me to run faster than the speed of light. The laws of physics forbid any object from accelerating up to that speed, but even that isn't logically impossible. It isn't a contradiction to imagine that the laws of physics might have been different and that they might have allowed objects to move faster than light. Which kind of modality does ML deal with? All of them. ML is a very flexible tool. We start with a basic set of rules that govern and then add more rules to fit whatever kind of modality we are interested in. In fact, ML is so flexible that we do not even have to think of N as expressing necessity and possibility. We might instead read as expressing provability, so that A means it is provable that A, and A means it is not refutable that A. Similarly, we can interpret to mean S knows that A or S believes that A, or we might read as expressing moral obligation, so that A means it is morally obligatory that A, and A means it is morally permissible that A. All we would need to do is cook up the right rules for these different readings of N. Modal formula is one that includes modal operators such as N, depending on the interpretation we assign to, and different modal formulas will be provable or valid. For instance, I might say that if I is necessary, it is true, if is interpreted as necessity. It might express if I is known, then it is true, if expresses known truth. Under both these interpretations, A to I is valid. All necessary propositions are true come what may, so are true in the actual world. And if a proposition is known to be true, it must be true. One can't know something that's false. However, when is interpreted as it is believed that, or it ought to be the case that, A to I is not valid, we can believe false propositions. Not every proposition that ought to be true is in fact true. For example, every murderer will be brought to justice. This ought to be true, but it isn't. We will consider different kinds of systems of ML. They differ in the rules of proof allowed and in the semantics we use to define our logical notions. The different systems we'll consider are called K, T, S4, and S5. K is the basic system. Everything that is valid or provable in K is also provable in the others. But there are some things that K does not prove, such as the formula A to A for sentence letter A, so K is not an appropriate modal logic for necessity and possibility, where A to A should be provable. This is provable in the system T, so T is more appropriate when dealing with necessity and possibility, but less appropriate when dealing with belief or obligation, since then T should not always be provable. The perhaps best system of ML for necessity and possibility, and in any case the most widely accepted, is the strongest of the systems we consider, S5. 40.1 The language of ML. In order to do modal logic, we have to do two things. First, we want to learn how to prove things in ML. Second, we want to see how to construct interpretations for ML, but before we can do either of these things, we need to explain how to construct sentences in ML. The language of ML is an extension of TFL. We could have started with FOL, which would have given us quantified modal logic, QML. QML is much more powerful than ML, but it is also much more complicated, so we are going to keep things simple and start with TFL. Just like TFL, ML starts with an infinite stock of atoms. These are written as capital letters with or without numerical subscripts. A, B, a sub 1, B sub 1. We then take all of the rules about how to make sentences from TFL and add two more for and. Every atom of ML is a sentence of ML. If A is a sentence of ML, then not A is a sentence of ML. If A and B are sentences of ML, then A and B is a sentence of ML. If A and B are sentences of ML, then open parenthesis, a logical, or B, close parenthesis, is a sentence of ML. If A and B are sentences of ML, then open parenthesis, math bold A implies math bold B, close parenthesis, is a sentence of ML. If A and B are sentences of ML, then A if and only if B is a sentence of ML. If A is a sentence of ML, then A is a sentence of ML. If A is a sentence of ML, then A is a sentence of ML. Nothing else is a sentence of ML. Here are some examples of ML sentences. A P or Q, box A, C or box D, box, open parenthesis. A implies R, close parenthesis, box diamond, open parenthesis, S and open parenthesis, Z if and only if, open parenthesis, box W or diamond Q, close parenthesis, chapter 41. Natural deduction for ML. Now that we know how to make sentences in ML, we can look at how to prove things in ML. We will use to express provability. So a sub 1, a sub 2 through a sub n entails C means that C can be proven from a sub 1, a sub 2 through a sub n. However, we will be looking at a number of different systems of ML, and so it will be useful to add a subscript to indicate which system we are working with. So for example, if we want to say that we can prove C from a sub 1, a sub 2 through a sub n in system K, we will write a sub 1, a sub 2 through a sub n entails KC. 41.1 System K. We start with a particularly simple system called K in honor of the philosopher and logician Saul Kripke. K includes all of the natural deduction rules from TFL, including the derived rules as well as the basic ones. K then adds a special kind of subproof, plus 2 new basic rules for. The special kind of subproof looks like an ordinary subproof, except it has a in its assumption line instead of a formula. We call them strict subproofs. They allow us to reason and prove things about alternate possibilities. What we can prove inside a strict subproof holds in any alternate possibility, in particular in alternate possibilities where the assumptions in force in our proof may not hold. In a strict subproofs, all assumptions are disregarded, and we are not allowed to appeal to any lines outside the strict subproof, except as allowed by the modal rules given below. The I rule allows us to derive a formula A if we can derive A inside a strict subproof. It is our fundamental method of introducing into proofs. The basic idea is simple enough. If it is a theorem, then A should be a theorem too. Remember that to call A theorem is to say that we can prove A without relying on any undischarged assumptions. Suppose we wanted to prove box of open parenthesis A implies a close parenthesis. The first thing we need to do is prove that A implies A is a theorem. You already know how to do that using TFL. You simply present a proof of A implies A which doesn't start with any premises like this.
Math summary: the expression shows a series of logical deductions. First, there is a statement A, followed by its negation. This is justified by rule R1. Then there is the statement A implies A, which is justified by implication introduction using lines 1 and 2. Finally, the expression shows a numbered step.
But to apply I, we need to have proven the formula inside a strict subproof. Since our proof of A to A makes use of no assumptions at all, this is possible.
Math summary: the expression represents a series of logical deductions and proofs within strict subproofs. It involves deriving new statements from existing ones using inference rules. The process includes introducing assumptions, applying rules like R2 and implication introduction, and ultimately deriving a final statement within a box, indicating it's proven within a specific context. The expression uses a series of symbols and notations to represent these logical steps and the relationships between them.
No line above line M may be cited by any rule within the strict subproof begun at line M unless the rule explicitly allows it. It is essential to emphasize that in strict subproof you cannot use any rule which appeals to anything you proved outside of the strict subproof. There are exceptions, for example, the E rule below. These rules will explicitly state that they can be used inside strict subproofs and cite lines outside the strict subproof. This restriction is essential, otherwise we would get terrible results. For example, we could provide the following proof to vindicate a therefore box A.
Math summary: this expression represents a matrix with 2 rows and 2 columns. The first row contains the variable A in the first column, and the phrase incorrect use of R1 in the second column. The second row contains the term box A in the first column, and the term box I23 in the second column. The entire matrix is then followed by the number 4.
This is not a legitimate proof because at line 3 we appeal to line 1, even though line 1 comes before the beginning of the strict subproof at line 2. We said above that a strict subproof allows us to reason about arbitrary alternate possible situations. What can be proved in a strict subproof holds in all alternate possible situations, and so is necessary. This is the idea behind the I rule. On the other hand, if we've assumed that something is necessary, we have therewith assumed that it is true in all alternate possible situations. Hence we have the rule E. E can only be applied if line M containing A lies outside of the strict subproof in which line N falls, and this strict subproof is not itself part of a strict subproof not containing M. E allows you to assert A inside a strict subproof if you have A outside the strict subproof. The restriction means that you can only do this in the first strict subproof. You cannot apply the E rule inside a nested strict subproof. So the following is not allowed. Incorrect use of E1. The incorrect use of E on line 4 violates the condition, because although line 1 lies outside the strict subproof in which line 4 falls, the strict subproof containing line 4 lies inside the strict subproof beginning on line 2 which does not contain line 1.
Image summary. The image is a diagram illustrating a concept related to natural deduction. The diagram presents a structure involving variables and logical operators. It demonstrates a specific configuration or relationship between these elements. The diagram likely represents a rule or constraint within a natural deduction system, possibly related to the application of certain logical operators or the scope of variables. Table summary. The table shows an example of the incorrect usage of a rule, where a line is incorrectly derived within nested subproofs due to violating the rule's condition. Image summary. The image shows an example of an incorrect application of a rule in a natural deduction system. The figure presents a deduction sequence where a formula is derived. The deduction sequence is flawed because it violates a specific restriction on the application of the rule. The error stems from attempting to apply the rule within a nested subproof, which is not permissible according to the rules of the system. The conclusion is that the presented derivation is invalid due to the improper use of the rule within the nested subproof structure.
Let's begin with an example.
Math summary. This expression represents a proof in a natural deduction system. It begins with assumptions, indicated by boxed A and numbers 2 through 7. Then it uses inference rules, denoted by triangles, to derive new statements. Specifically, it starts with A, then B, then A and B, and finally boxed A and B. The inference rules applied include E1, E2, I45, and I37. The overall purpose is to derive boxed A and B from the initial assumptions using the rules of inference.
We can also mix regular subproofs and strict subproofs.
Math summary. This appears to be the beginning of a proof in modal logic. Line 1 states that it is necessary, that it implies B. Line 2 states that it is necessary, that A. Line 3 states that it is necessary. Line 4 states A.
This is called the distribution rule because it tells us that box distributes over right arrow. The rules I and E look simple enough, and indeed K is a very simple system, but K is more powerful than you might have thought. You can prove a fair few things in it. 41.2 Possibility. In the last subsection, we looked at all of the basic rules for K, but you might have noticed that all of these rules were about necessity, and none of them were about possibility. That's because we can define possibility in terms of necessity.
Math summary. This expression defines possibility in terms of necessity. It states that a statement is possibly true if, and only if, it is not necessarily false. The possibility of a statement is defined as the negation of the necessity of the negation of that statement.
In other words, to say that A is possibly true is to say that it is not necessarily false. As a result, it isn't really essential to add a special symbol for possibility into system K. Still, the system will be much easier to use if we do, and so we will add the following definitional rules.
Math summary. The expression defines possibility in terms of necessity using inference rules. The first rule states that if it is not necessarily not A, then it is defined as D of M. The second rule states that if it is possible, then it is not necessarily not A, which is defined as diamond of M.
Importantly, you should not think of these rules as any real addition to K. They just record the way that is defined in terms of. If we wanted, we could leave our rules for K here, but it will be helpful to add some modal conversion rules, which give us some more ways of flipping between and.
Table summary. The table presents modal conversion rules, showing that a modal operator with negation is interconvertible with the negation of the dual modal operator, marked by MCM. These modal conversion rules are also no addition to the power of K, because they can be derived from the basic rules, along with the definition of. In system bold K using def diamond or the modal conversion rules, one can prove diamond A is equivalent to not box not A when laying out system bold K. We started with box as our primitive modal symbol, and then defined diamond in terms of it. But if we had preferred, we could have started with diamond as our primitive, and then defined box as follows.
box script A is equivalent by definition to not diamond not script A, there is, then, no sense in which necessity is somehow more fundamental than possibility. Necessity and possibility are exactly as fundamental as each other. 41.3 System T. So far we have focused on K, which is a very simple modal system. K is so weak that it will not even let you prove A from A. But if we are thinking of as expressing necessity, then we will want to be able to make this inference. If it is necessarily true, then it must surely be true. This leads us to a new system, T, which we get by adding the following rule to K.
Math summary, this represents a rule of inference. Given a statement, box A, at line M, you can infer statement A at a later line. Applying rule RT also at line M, the application of rule RT must not occur within a strict subproof that begins after line M.
The line N on which rule RT is applied must not lie in a strict subproof that begins after line M. The restriction on rule T is in a way the opposite of the restriction on E. You can only use E in a nested strict subproof, but you cannot use T in a nested strict subproof. We can prove things in T which we could not prove in K. For example, box A implies A. 41.4 System S4. T allows you to strip away the necessity boxes. From A, you may infer A, but what if we wanted to add extra boxes? That is, what if we wanted to go from A to A? Well, that would be no problem if we had proved A by applying I to a strict subproof of a which itself does not use E. In that case, A is a tautology. And by nesting the strict subproof inside another strict subproof and applying I again, we can prove A. For example, we could prove box left parenthesis P implies P right parenthesis like this.
Math summary, this expression outlines a proof in modal logic. It starts with assumptions P in box P, then derives P implies P using implication introduction. Next, it derives box of P implies P using box introduction. Finally, it derives box of P implies P using another box introduction.
But what if we didn't prove A in this restricted way, but used E inside the strict subproof of A if we put that strict subproof inside another strict subproof? The requirement of rule E to not cite a line containing A which lies in another strict subproof that has not yet concluded is violated. Or what if A were just an assumption we started our proof with? Could we infer A then? Not in T, we couldn't. And this might well strike you as a limitation of T, at least if we are reading as expressing necessity. It seems intuitive that if A is necessarily true, then it couldn't have failed to be necessarily true. This leads us to another new system, S4, which we get by adding the following rule to T.
Image summary. The figure is a diagram that displays logical reasoning. The diagram illustrates a rule, denoted as R4, which involves logical statements and their relationships. The diagram shows how one statement can be derived from another under certain conditions. The rule R4 is applicable only when a specific line lies outside the strict subproof in which another line falls. The rule allows importing a certain logical construct into a strict subproof, but not into a strict subproof nested inside a strict subproof itself.
Note that R4 can only be applied if line M, containing A, lies outside of the strict subproof in which line N falls, and this strict subproof is not itself part of a strict subproof not containing N. Rule R4 looks just like E, except that instead of yielding A from A, it yields A inside a strict subproof. The restriction is the same, however. R4 allows us to import A into a strict subproof, but not into a strict subproof itself nested inside a strict subproof. However, if that is necessary, an additional application of R4 would have the same result. Now we can prove even more results. For instance,
Image summary. The image shows a proof in a natural deduction system. The proof demonstrates the derivation of a formula involving boxes. The proof starts with an assumption of a boxed formula and proceeds through several steps involving the introduction and elimination of boxes, ultimately deriving an implication between a single box and a double box. The deduction shows how to infer a double box from a single box.
Similarly, we can prove A to A. This shows us that as well as letting us add extra boxes, S4 lets us delete extra diamonds. From A, you can always infer A. 41.5 System S5. In S4, we can always add a box in front of another box, but S4 does not automatically let us add a box in front of a diamond. That is, S4 does not generally permit the inference from A to A. But again, that might strike you as a shortcoming, at least if you are reading and as expressing necessity and possibility. It seems intuitive that if A is possibly true, then it couldn't have failed to be possibly true. This leads us to our final modal system, S5, which we get by adding the following rule to S4.
Image summary. The image shows a logical inference rule diagram. It illustrates a rule, denoted as R5, which allows inferring a statement involving a negation and a necessity operator from another statement, also involving negation and necessity. The rule is applicable under specific conditions related to the scope of the statements within a proof structure. The diagram demonstrates the logical flow and dependencies between the statements, showcasing how the conclusion is derived from the premise using the given rule.
Rule R5 can only be applied if line M, containing not A, lies outside of the strict subproof in which line N falls, and this strict subproof is not itself part of a strict subproof not containing line M. This rule allows us to show, for instance, that AS5A.
Image summary. The image shows a proof in a formal system, specifically a natural deduction system for modal logic. The proof demonstrates a derivation starting from a premise involving a diamond operator applied to a box operator. The proof proceeds through a series of logical steps, including the introduction and elimination of negation, box, and diamond operators, ultimately deriving a conclusion involving a box operator. The proof utilizes a specific rule denoted as R5, along with other standard rules like implication introduction and elimination, and indirect proof. The proof establishes a relationship between the diamond and box operators, showing how, under certain conditions and rules within the system, an expression involving a diamond and a box can be transformed into an expression involving only a box.
So, as well as adding boxes in front of diamonds, we can also delete diamonds in front of boxes. We got S5 just by adding the rule R5 rule to S4. In fact, we could have added rule R5 to T alone and leave out rule R4. Everything we can prove by rule R4 can also be proved using RT together with R5. For instance, here is a proof that shows a S5A without using R4.
Image summary. The image is a proof in natural deduction. It presents a logical argument involving modal operators, specifically boxes and diamonds, along with negation and implication. The proof demonstrates a derivation within a modal logic system, likely S5, showing how a formula involving nested modal operators can be derived from simpler assumptions. The overall inference is that the system is sound and complete with respect to the rules of inference applied, and highlights the properties of modal operators within that logical framework.
S5 is strictly stronger than S4. There are things which can be proved in S5 but not in S4, e.g., A to A. The important point about section 5 can be put like this. If you have a long string of boxes and diamonds in any combination whatsoever, you can delete all but the last of them. So for example, A can be simplified down to just A. Practice exercises. A. Provide proofs for the following. One box of open parenthesis A and B, close parenthesis, entails sub K box of A and box of B. 2 box A and box B, turnstile sub K box of A and B. 3 box A or box B entails in the system K box of A or B. 4 box of open parenthesis a double arrow B, close parenthesis, turnstile sub K box A double arrow box B. B. Provide proofs for the following without using modal conversion. 1 not sign A K not A. 2 diamond not a bottom K not box A. 3 not diamond a bottom K box not A. 4 A K not sign A. C. Provide proofs of the following, and now feel free to use modal conversion. 1 box of open parenthesis A implies B, close parenthesis, comma, diamond A, turnstile sub K, diamond B. 2 A K not A. 3 not diamond not a bottom K box A. D. Provide proofs for the following. 1 P proof sub T diamond P. 2 turnstile sub T, open parenthesis A and B close parenthesis, or open parenthesis not box or not box B close parenthesis. E. Provide proofs for the following. Box of box A implies B, box of box B implies C, box of sub S4 box C. 2 box A entails in the system S4, box of the quantity box A or B. 3 AS4A. F. Provide proofs in S5 for the following. 1 not box not A diamond B proves in system S5, box open parenthesis diamond A and diamond B close parenthesis. 2 approves in S5 box diamond A. 3 AS5A. Chapter 42. Semantics for ML. So far, we have focused on laying out various systems of natural deduction for ML. Now we will look at the semantics for ML. A semantics for a language is a method for assigning truth values to the sentences in that language. So a semantics for ML is a method for assigning truth values to the sentences of ML. 42.1 Interpretations of ML. The big idea behind the semantics for ML is this. In ML, sentences are not just true or false, full stop. A sentence is true or false at a given possible world, and a single sentence may well be true at some worlds and false at others. We then say that A is true if it is true at every world, and A is true if it is true at some world. That's the big idea, but we need to refine it and make it more precise. To do this, we need to introduce the idea of an interpretation of ML. The first thing you need to include in an interpretation is a collection of possible worlds. Now, at this point, you might well want to ask, what exactly is a possible world? The intuitive idea is that a possible world is another way that this world could have been. But what exactly does that mean? This is an excellent philosophical question, and we will look at it in a lot of detail later. But we do not need to worry too much about it right now. As far as the formal logic goes, possible worlds can be anything you like. All that matters is that you supply each interpretation with a non-empty collection of things labeled possible worlds. Once you have chosen your collection of possible worlds, you need to find some way of determining which sentences of ML are true at which possible worlds. To do that, we need to introduce the notion of a valuation function. Those of you who have studied some maths will already be familiar with the general idea of a function. But for those of you who haven't, a function is a mathematical entity which maps arguments to values. That might sound a little bit abstract, but some familiar examples will help. Take the function x plus 1. This is a function which takes in a number as argument and then spits out the next number as value. So if you feed in the number 1 as an argument, the function x plus 1 will spit out the number 2 as a value. If you feed in 2, it will spit out 3. If you feed in 3, it will spit out 4. Or here is another example, the function x plus y. This time, you have to feed 2 arguments into this function if you want it to return a value. If you feed in 2 and 3 as your arguments, it spits out 5. If you feed in 1003 and 2005, it spits out 3008, and so on. A valuation function for ML takes in a sentence and a world as its arguments, and then returns a truth value as its value. So if new is a valuation function and w is a possible world, new sub w of script A is whatever truth value new maps script A and w to. If new sub w of script A equals f, then script A is false at world w on valuation new. If new sub w of script A equals t, then script A is true at world w on valuation new. These valuation functions are allowed to map any atomic sentence to any truth value at any world, but there are rules about which truth values more complex sentences get assigned at a world. Here are the rules for the connectives from TFL.
Math summary: these expressions define truth conditions for logical connectives within a valuation function. 1. The valuation of not A is true if and only if the valuation of A is false. 2. The valuation of A and B is true if and only if the valuation of A is true and the valuation of B is true. 3. The valuation of A or B is true if and only if the valuation of A is true or the valuation of B is true, or both. 4. The valuation of A implies B is true if and only if the valuation of A is false or the valuation of B is true, or both. 5. The valuation of A if and only if B is true if and only if the valuation of A is true and the valuation of B is true, or the valuation of A is false and the valuation of B is false.
So far, these rules should all look very familiar. Essentially, they all work exactly like the truth tables for TFL. The only difference is that these truth table rules have to be applied over and over again to one world at a time. But what are the rules for the new modal operators? And the most obvious idea would be to give rules like these.
Math summary: the first expression evaluates whether a necessity statement is true in a world. It checks if a statement is true in all accessible worlds. The second expression evaluates whether a possibility statement is true in a world. It checks if there exists at least one accessible world where the statement is true.
This is just the fancy formal way of writing out the idea that A is true at W just in case A is true at every world, and A is true at W just in case A is true at some world. However, while these rules are nice and simple, they turn out not to be quite as useful as we would like. As we mentioned, ML is meant to be a very flexible tool. It is meant to be a general framework for dealing with lots of different kinds of necessity. As a result, we want our semantic rules for and to be a bit less rigid. We can do this by introducing another new idea, accessibility relations. An accessibility relation, R, is a relation between possible worlds. Roughly to say that R W sub 1 W sub 2 in English, world W sub 1 accesses world W sub 2, is to say that W sub 2 is possible relative to W sub 1. In other words, by introducing accessibility relations, we open up the idea that a given world might be possible relative to some worlds but not others. This turns out to be a very fruitful idea when studying modal systems. We can now give the following semantic rules for box and diamond.
Math summary. The first expression defines the truth condition for a necessity modal operator applied to a proposition. It states that the necessity of a proposition being true in a world 1 is true, if and only if, for all worlds 2 that are accessible from world 1, the proposition is true in world 2. The second expression defines the truth condition for a possibility modal operator applied to a proposition. It states that the possibility of a proposition being true in world 1 is true, if and only if there exists a world 2 that is accessible from world 1, and the proposition is true in world 2.
Or in plain English, box A is true in world W sub 1 if and only if it is true in every world that is possible relative to W sub 1, and diamond A is true in world W sub 1 if and only if it is true in some world that is possible relative to W sub 1. So there we have it. An interpretation for ML consists of three things: a collection of possible worlds W, an accessibility relation R, and evaluation function V. The collection of possible worlds can really be a collection of anything you like. It really doesn't matter so long as W isn't empty. For many purposes, it is helpful just to take a collection of numbers to be your collection of worlds. And for now at least, R can be any relation between the worlds in W that you like. It could be a relation which every world in W bears to every world in W, or one which no world bears to any world or anything in between. And lastly, V can map any atomic sentence of ML to any truth value at any world. All that matters is that it follows the rules 7 when it comes to the more complex sentences. Let's look at an example. It is often helpful to present interpretations of ML as diagrams like this.
Image summary. The image is a state diagram. The diagram represents two states with transitions between them. The first state has a self loop and a transition from the second state. The first state is associated with a not B, while the second state is associated with not A and B. The diagram indicates the relationships and properties of the two states, showing how they relate to each other, and the conditions that hold true within each state. The diagram illustrates the connections and characteristics of the two states, indicating that the first state can transition back to itself, and the second state transitions to the first state. The diagram also reveals the truth assignments of A and B in each state, with A being true and B being false in the first state, and A being false and B being true in the second state.
Here is how to read the interpretation off from this diagram. It contains just two worlds, 1 and 2. The arrows between the worlds indicate the accessibility relation. So 1 and 2 both access 1, but neither 1 nor 2 accesses 2. The boxes at each world let us know which atomic sentences are true at each world. A is true at 1 but false at 2. B is false at 1 but true at 2. You may only write an atomic sentence or the negation of an atomic sentence into one of these boxes. We can figure out what truth values the more complex sentences get at each world from that. For example, on this interpretation, all of the following sentences are true at W sub 1.
Math summary. The expression represents a set of logical statements. The first statement is A and not B. The second statement is B implies A. The third statement is possibly A. The fourth statement is necessarily not B.
If you don't like thinking diagrammatically, then you can also present an interpretation like this. W's 12R, angle bracket 1, 1 angle bracket 2, 1 angle brackets.
Math summary. This assigns truth values to variables A and B in two different scenarios. In the first scenario, variable A is true and variable B is false. In the second scenario, variable A is false and variable B is true.
You will get the chance to cook up some interpretations of your own shortly when we start looking at counterinterpretations. 42.2 A Semantics for System K. We can now extend all of the semantic concepts of TFL to cover ML.
Code summary. The provided text defines several key concepts in modal logic. It explains modal validity, which occurs when a conclusion is true in all possible worlds given that the premises are true. It also defines modal truth, contradiction, and satisfiability, describing when a statement is true in every world, false in every world, or true in at least one world, respectively. These definitions provide a framework for evaluating the logical consistency and truth of modal statements.
From now on, we will drop the explicit modal qualifications since they can be taken as read. We can also extend our use of, however, we need to add subscripts again, just as we did with. So when we want to say that a sub 1, a sub 2 through a sub n therefore C is valid, we will write a sub 1, a sub 2 through a sub n models kappa omega. Let's get more of a feel for this semantics by presenting some counterinterpretations. Consider the following false claim.
Math summary. This expression asserts that not A implies not possibly A. Within the context of system K, it states that if not A is true, then it necessarily follows that it is not possible for it to be true.
In order to present a counterinterpretation to this claim, we need to cook up an interpretation which makes not a true at some world W, and not diamond a false at W. Here is one such interpretation, presented diagrammatically.
Image summary. This is a diagram. It illustrates a counterinterpretation for a claim. The diagram shows a transition from a state where a proposition A is false to a state where it is true. This indicates that while it might be false at one point, it becomes true later, suggesting a change in the truth value of it.
It is easy to see that this will work as a counterinterpretation for our claim. First, not A is true at world 1, and second, not diamond A is false at 1, A is true at 2, and 2 is accessible from 1. So there is some world in this interpretation where not A is true and not diamond A is false, so it is not the case that not A entails with a subscript of K, not diamond A. Why did we choose the subscript K? Well, it turns out that there is an important relationship between system K and the definition of validity we have just given. In particular, we have the following two results.
Math summary. The first statement expresses a soundness result. If a conclusion C can be proven from assumptions A1 through and using system K, then the conclusion C is semantically entailed by assumptions A1 through and with respect to system K. The second statement expresses a completeness result. If a conclusion C is semantically entailed by assumptions A1 through and with respect to system K, then the conclusion C can be proven from assumptions A1 through and using system K.
The first result is known as a soundness result, since it tells us that the rules of K are good, sound rules. If you can vindicate an argument by giving a proof for it using system K, then that argument really is valid. The second result is known as a completeness result, since it tells us that the rules of K are broad enough to capture all of the valid arguments. If an argument is valid, then it will be possible to offer a proof in K which vindicates it. Now, it is one thing to state these results, quite another to prove them. However, we will not try to prove them here, but the idea behind the proof of soundness will perhaps make clearer how strict subproofs work. In a strict subproof, we are not allowed to make use of any information from outside the strict subproof, except what we import into the strict subproof using E. If we've assumed or proved A by E, we can use I inside a strict subproof. And in K, that is the only way to import a formula into a strict subproof. So everything that can be proved inside a strict subproof must follow from formulas I, where outside the strict subproof we have A. Let's imagine that we are reasoning about what's true in a possible world in some interpretation. If we know that A is true in that possible world, we know that I is true in all accessible worlds. So everything proved inside a strict subproof is true in all accessible possible worlds. That is why I is a sound rule. 42.3 A semantics for system T. A few moments ago, we said that system K is sound and complete. Where does that leave the other modal systems we looked at, namely T, S4, and S5? Well, they are all unsound relative to the definition of validity we gave above. For example, all of these systems allow us to infer A from box A, even though box A does not model sub Ka. Does that mean that these systems are a waste of time? Not at all. These systems are only unsound relative to the definition of validity we gave above. Or to use symbols, they are unsound relative to sub K. So when we are dealing with these stronger modal systems, we just need to modify our definition of validity to fit. This is where accessibility relations come in really handy. When we introduced the idea of an accessibility relation, we said that it could be any relation between worlds that you like. You could have it relating every world to every world, no world to any world, or anything in between. That is how we were thinking of accessibility relations in our definition of sub K. But if we wanted, we could start putting some restrictions on the accessibility relation. In particular, we might insist that it has to be reflexive. Minus right triangle for all WRW. In English, every world accesses itself, or in terms of relative possibility, every world is possible relative to itself. If we imposed this restriction, we could introduce a new consequence relation, sub T, as follows. A sub 1, a sub 2 through a sub n models sub bold T. See if and only if there is no world in any interpretation which has a reflexive accessibility relation, at which a sub 1, a sub 2, through a sub n are all true and C is false, we have attached the T subscript to, because it turns out that system T is sound and complete relative to this new definition of validity.
Math summary: the first statement expresses that if a set of premises proves a conclusion in system T, then the set of premises semantically entails the conclusion in system T. The second statement expresses that if a set of premises semantically entails a conclusion in system T, then the set of premises proves the conclusion in system T.
As before, we will not try to prove these soundness and completeness results. However, it is relatively easy to see how insisting that the accessibility relation must be reflexive will vindicate the RT rule.
Math summary: this represents a logical inference rule. Given an input M, and given that box A is true, then it is true and RTM is also true.
To see this, just imagine trying to cook up a counterinterpretation to this claim. We would need to construct a world W at which A was true, but it was false. Now, if A is true at W, then it must be true at every world W accesses. But since the accessibility relation is reflexive, W accesses W, so it must be true at W, but now it must be true and false at W contradiction. 42.4 A semantics for S4. How else might we tweak our definition of validity? Well, we might also stipulate that the accessibility relation has to be transitive.
Math summary: this statement expresses the principle of transitivity for a relation. It states that for all elements labeled element 1, element 2, and element 3, if element 1 is related to element 2, and element 2 is related to element 3, then it follows that element 1 is related to element 3.
In English, if W sub 1 accesses W sub 2 and W sub 2 accesses W sub 3, then W sub 1 accesses W sub 3. Or in terms of relative possibility, if W sub 3 is possible relative to W sub 2 and W sub 2 is possible relative to W sub 1, then W sub 3 is possible relative to W sub 1. If we added this restriction on our accessibility relation, we could introduce a new consequence relation, models sub S4, as follows. A sub 1, a sub 2, through a sub n models with a subscript of S4. See if and only if there is no world in any interpretation which has a reflexive and transitive accessibility relation, at which a sub 1, a sub 2, through a sub n are all true and C is false, we have attached the S4 subscript to, because it turns out that system S4 is sound and complete relative to this new definition of validity.
Math summary: the first statement describes a condition. If a set of assumptions, specifically assumption 1, assumption 2, through assumption n, proves a conclusion C under a certain system S4, then that same set of assumptions implies that conclusion C under system S4. The second statement describes another condition. If a set of assumptions, specifically assumption 1, assumption 2, through assumption n, implies a conclusion C under system S4, then that same set of assumptions proves that conclusion C under system S4.
As before, we will not try to prove these soundness and completeness results. However, it is relatively easy to see how insisting that the accessibility relation must be transitive will vindicate the S4 rule.
Image summary: the image shows a diagrammatic representation of a logical rule. The diagram illustrates a rule labeled R4, which involves logical operators and variables. The diagram shows the relationship between different logical statements. The diagrammatic representation is used to explain a concept related to logical inference or deduction.
The idea behind strict subproofs, remember, is that they are ways to prove things that must be true in all accessible worlds. So the R4 rule means that whenever A is true, A must also be true in every accessible world. In other words, we must have a S4A. To see this, just imagine trying to cook up a counterinterpretation to this claim. A S4A. We would need to construct a world W sub 1 at which box A was true, but box A was false. Now, if box A is false at W sub 1, then W sub 1 must access some world W sub 2 at which box A is false. Equally, if box A is false at W sub 2, then W sub 2 must access some world W sub 3 at which it is false. We just said that W sub 1 accesses W sub 2, and W sub 2 accesses W sub 3. So since we are now insisting that the accessibility relation be transitive, W sub 1 must access W sub 3. And as box A is true at W sub 1 and W sub 3 is accessible from W sub 1, it follows that it must be true at W sub 3. So it is true and false at W sub 3. Contradiction. 42.5 A semantics for S5. Let's put one more restriction on the accessibility relation. This time, let's insist that it must also be symmetric.
Math summary. This statement asserts that for all World 1 and for all World 2, if World 1 has access to World 2, then World 2 has access to World 1. In essence, it describes a symmetric accessibility relation between possible worlds.
In English, if W sub 1 accesses W sub 2, then W sub 2 accesses W sub 1. Or in terms of relative possibility, if W sub 2 is possible relative to W sub 1, then W sub 1 is possible relative to W sub 2. Logicians call a relation that is reflexive, symmetric, and transitive an equivalence relation. We can now define a new consequence relation, sub S5, as follows. A sub 1, a sub 2, through a sub n models S5 see if and only if there is no world in any interpretation whose accessibility relation is an equivalence relation, at which a sub 1, a sub 2, through a sub n are all true and C is false. We have attached the S5 subscript to, because it turns out that system S5 is sound and complete relative to this new definition of validity.
Math summary. The first statement says, if a set of assumptions proves a conclusion in the system S5, then the set of assumptions semantically entails the conclusion in the system S5. The second statement says, if a set of assumptions semantically entails a conclusion in the system S5, then the set of assumptions proves the conclusion in the system S5.
As before, we will not try to prove these soundness and completeness results here. However, it is relatively easy to see how insisting that the accessibility relation must be an equivalence relation will vindicate the R5 rule.
Math summary. This expression represents a modal logic rule. It involves a matrix with 3 rows and 2 columns. The first column contains the negation of the necessity of A, the necessity of A, and the negation of the necessity of A. The second column contains the term R5M.
The rule says that if it is not necessary, that is, false in some accessible world, it is also not necessary in any accessible possible world. That is, we have not box A entails S5 box not box A. To see this, just imagine trying to cook up a counterinterpretation to this claim.
Math summary. This expression asserts a modal logic entailment. It states that if not necessarily A is true, then it implies that necessarily not necessarily A is also true, specifically within the S5 modal logic system.
We would need to construct a world, W sub 1, at which not box A was true, but box not box A was false. Now if not box A is true at W sub 1, then W sub 1 must access some world, W sub 2, at which it is false. Equally, if box not box A is false at W sub 1, then W sub 1 must access some world, W sub 3, at which not box script A is false. Since we are now insisting that the accessibility relation is an equivalence relation, and hence symmetric, we can infer that W sub 3 accesses W sub 1. Thus, W sub 3 accesses W sub 1 and W sub 1 accesses W sub 2. Again, since we are now insisting that the accessibility relation is an equivalence relation, and hence transitive, we can infer that W sub 3 accesses W sub 2. But earlier we said that not box script A is false at W sub 3, which implies that script A is true at every world which W sub 3 accesses. So script A is true and false at W sub 2. Contradiction? In the definition of sub S5, we stipulated that the accessibility relation must be an equivalence relation. But it turns out that there is another way of getting a notion of validity fit for S5. Rather than stipulating that the accessibility relation be an equivalence relation, we can instead stipulate that it be a universal relation.
Math summary. This expression states that for all possible worlds 1 and 2, World 1 has access to World 2.
In English, every world accesses every world, or in terms of relative possibility, every world is possible relative to every world. Using this restriction on the accessibility relation, we could have defined sub S5 like this. A sub 1, a sub 2 through a sub n models S5, see if and only if there is no world in any interpretation which has a universal accessibility relation, at which a sub 1, a sub 2 through a sub n are all true and C is false. If we define sub S5 like this, we would still get the same soundness and completeness results for S5. What does this tell us? Well, it means that if we are dealing with a notion of necessity according to which every world is possible relative to every world, then we should use S5. What is more, most philosophers assume that the notions of necessity that they are most concerned with, like logical necessity and metaphysical necessity, are of exactly this kind. So S5 is the modal system that most philosophers use most of the time. Practice exercises. A. Present counterinterpretations to the following false claims. 1. Not P models sub K not diamond P. Two box of open parenthesis P or Q, close parenthesis models sub K box of P or box of Q. 3 turnstile K not box open parenthesis A and not a close parenthesis. 4 a KA. B present counterinterpretations to the following false claims. 1 AS4A. 2 diamond A box open parenthesis diamond A implies B close parenthesis entails S4 box B. Z present counterinterpretations to the following false claims. 1 box of open parenthesis M implies O close parenthesis comma diamond M models sub T O. 2 box of models sub T box A. Further reading. Modal logic is a large subfield of logic. We have only scratched the surface. If you want to learn more about modal logic, here are some textbooks you might consult. Playbutton Hughes G.E. and Cresswell M.J. A New Introduction to Modal Logic, Oxford Routledge. Playbutton Priest G. An Introduction to Non-Classical Logic, 2nd ed., Cambridge, Cambridge University Press. Playbutton Garson J.W. 2013. Modal Logic for Philosophers, 2nd ed., Cambridge, Cambridge University Press. None of these authors formulate their modal proof systems in quite the way we did, but the closest formulation is given by Garson. Part 9. Meta-theory. Chapter 43. Normal forms. 43.1 Disjunctive normal form. Sometimes it is useful to consider sentences of a particularly simple form. For instance, we might consider sentences in which not sign only attaches to atomic sentences, or those which are combinations of atomic sentences and negated atomic sentences using only. A relatively general but still simple form is that where a sentence is a disjunction of conjunctions of atomic or negated atomic sentences. When such a sentence is constructed, we start with atomic sentences, then perhaps attach negations, then perhaps combine using, and finally perhaps combine using. Let's say that a sentence is in disjunctive normal form if it meets all of the following conditions. DNF1, no connectives occur in the sentence other than negations, conjunctions, and disjunctions. DNF2, every occurrence of negation has minimal scope, i.e. any not sign, is immediately followed by an atomic sentence. DNF3, no disjunction occurs within the scope of any conjunction. So here are some sentences in disjunctive normal form.
Math summary. The expression presents a list of logical statements. The first statement is A, the second statement is A and not B and C, the third statement is A and B or A, and not B, the fourth statement is A and B or A and B and C and not D, and not E, the fifth statement is A or C, and not P234 and P233 and Q or not B.
Note that we have here broken one of the maxims of this book and temporarily allowed ourselves to employ the relaxed bracketing conventions that allow conjunctions and disjunctions to be of arbitrary length. These conventions make it easier to see when a sentence is in disjunctive normal form. We will continue to help ourselves to these relaxed conventions without further comment. To further illustrate the idea of disjunctive normal form, we will introduce some more notation. We write plus or minus A to indicate that it is an atomic sentence which may or may not be prefaced with an occurrence of negation. Then a sentence in disjunctive normal form has the following shape.
Math summary. This expression represents a disjunction of conjunctions. It takes several groups of inputs. Each group consists of a series of terms that are combined using a conjunction operation. Each term in the conjunction may be either a positive or negative form of an input. The results of these conjunctions are then combined using a disjunction operation to produce a final output.
We now know what it is for a sentence to be in disjunctive normal form. The result that we are aiming at is disjunctive normal form theorem. For any sentence, there is a logically equivalent sentence in disjunctive normal form. Henceforth, we will abbreviate disjunctive normal form by DNF. 43.2 Proof of DNF theorem via truth tables. Our first proof of the DNF theorem employs truth tables. We will first illustrate the technique for finding an equivalent sentence in DNF and then turn this illustration into a rigorous proof. Let's suppose we have some sentence S which contains 3 atomic sentences A, B, and C. The very first thing to do is fill out a complete truth table for S. Maybe we end up with this. As it happens, section is true on 4 lines of its truth table, namely lines 1, 3, 7, and 8. Corresponding to each of those lines, we will write down 4 sentences whose only connectives are negations and conjunctions, where every negation has minimal scope.
Math summary. The first expression represents the logical conjunction of 3 Boolean variables a, b, and c. The second expression represents the logical conjunction of the gradient of a, the negation of b and c.
Which is true on line 1 and only then, which is true on line 3 and only then, which is true on line 7 and only then, which is true on line 8 and only then.
Math summary. The first expression is a logical expression that is true when it is false, b is false, and c is true. The second expression is a logical expression that is true when it is false, b is false, and c is false.
We now combine all of these conjunctions using v, like so.
Math summary. This expression represents a logical disjunction, meaning and or operation, of 4 separate logical conjunctions, meaning and operations. The first conjunction is a and b and c. The second conjunction is a and not b and c. The third conjunction is not a and not b and c. The fourth conjunction is not a and not b and not c. The entire expression evaluates to true if any one or more of these 4 conjunctions are true.
This gives us a sentence in DNF which is true on exactly those lines where one of the disjuncts is true, that is, it is true on and only on lines 1, 3, 7, and 8. So this sentence has exactly the same truth table as delta. So we have a sentence in DNF that is logically equivalent to delta, which is exactly what we wanted. Now, the strategy that we just adopted did not depend on the specifics of delta, it is perfectly general. Consequently, we can use it to obtain a simple proof of the DNF theorem. Pick any arbitrary sentence, script S, and let script a sub 1 through script a sub n be the atomic sentences that occur in script S to obtain a sentence in DNF that is logically equivalent section. We consider section S truth table. There are 2 cases to consider. One section symbol is false on every line of its truth table. Then, section symbol is a contradiction. In that case, the contradiction, open parenthesis script a sub 1 and not script a sub 1 close parenthesis, is in DNF and logically equivalent to section symbol. 2 section is true on at least one line of its truth table. For each line I of the truth table, let B sub I be a conjunction of the form.
Math summary. This expression forms a logical conjunction. It takes a series of input statements, each of which may or may not be negated. The expression combines these possibly negated statements using the logical and operation.
Where the following rules determine whether or not to include a negation in front of each atomic sentence. A sub m is a conjunct of b sub I if and only if a sub m is true on line I. Not a sub m is a conjunct of b sub I if and only if a sub m is false on line I. Given these rules, b sub I is true on and only on line I of the truth table, which considers all possible valuations of a sub 1 through a sub n, that is, S's truth table. Next, let I sub 1, I sub 2 through I sub m be the numbers of the lines of the truth table where script S is true. Now let script D be the sentence.
Math summary. This expression represents a logical disjunction, also known as an OR operation. It takes a series of terms, specifically b sub I1, b sub I2, and so on up to b sub IM, and combines them using the OR operation. The result is true if at least one of the terms is true.
Since delta is true on at least one line of its truth table, script D is indeed well defined. And in the limiting case where delta is true on exactly one line of its truth table, script D is just script b sub I sub 1 for some I sub 1. By construction, D is in DNF. Moreover, by construction, for each line I of the truth table, S is true on line I of the truth table if one of D's disjuncts, namely BI, is true on and only on line I. Hence, S and D have the same truth table and so are logically equivalent. These 2 cases are exhaustive, and either way, we have a sentence in DNF that is logically equivalent to S. So we have proved the DNF theorem. Before we say any more, though, we should immediately flag that we are hereby returning to the austere definition of a TFL sentence, according to which we can assume that any conjunction has exactly 2 conjuncts and any disjunction has exactly 2 disjuncts.
Table 1 summary. The truth table shows all possible combinations of truth values for 3 atomic sentences, and the resulting truth value for a sentence SS is true in a minority of the cases.
43.3 Conjunctive normal form. So far in this chapter, we have discussed disjunctive normal form. It may not come as a surprise to hear that there is also such a thing as conjunctive normal form, CNF. The definition of CNF is exactly analogous to the definition of DNF. So, a sentence is in CNF if it meets all of the following conditions. CNF 1. No connectives occur in the sentence other than negations, conjunctions, and disjunctions. CNF 2. Every occurrence of negation has minimal scope. CNF 3. No conjunction occurs within the scope of any disjunction. Generally then, a sentence in CNF looks like this.
Math summary. This expression represents a logical formula in conjunctive normal form. It is a conjunction of multiple clauses. Each clause is a disjunction of literals, where each literal is either an atomic proposition or its negation. The expression combines these clauses using logical AND operations,
where each sub k is an atomic sentence. We can now prove another normal form theorem. Conjunctive normal form theorem. For any sentence, there is a logically equivalent sentence in conjunctive normal form. Given a TFL sentence, delta, we begin by writing down the complete truth table for delta. If script S is true on every line of the truth table, then script S and left parenthesis script a sub 1 logical or not script a sub 1 right parenthesis are logically equivalent. If script S is false on at least one line of the truth table, then, for every line on the truth table where script S is false, write down a disjunction plus or minus script a sub 1 or dots or plus or minus script a sub n which is false on and only on that line. Let script C be the conjunction of all of these disjuncts. By construction, script C is in CNF and script S and script C are logically equivalent. Practice exercises. A. Consider the following sentences. 1. Left parenthesis A implies not B right parenthesis. 2. Not open parenthesis a double arrow B close parenthesis. 3. Not A or not A and B's. 4. Not of A implies B and implies C. 5. Not of open parenthesis A or B close parenthesis if and only if open parenthesis not C and not a close parenthesis implies not B close parenthesis. Left parenthesis not left parenthesis I and not B right parenthesis implies C right parenthesis and not left parenthesis A and D right parenthesis right parenthesis. For each sentence, find a logically equivalent sentence in DNF and one in CNF. Functional completeness. Of our connectives, not attaches to a single sentence and the others all combine exactly two sentences. We may also introduce the idea of an n-place connective. For example, we could consider a 3-place connective and stipulate that it is to have the following characteristic truth table.
Table summary. The truth table defines the behavior of a 3-place connective, where the connective is false in most cases, except when the first input is true and the second input is true while the third input is false, or when the first input is false and the second input is true while the third input is false.
Probably this new connective would not correspond with any natural English expression, at least not in the way that corresponds with and. But a question arises: if we wanted to employ a connective with this characteristic truth table, must we add a new connective to TFL? Or can we get by with the connectives we already have as we can for the connective neither nor, for instance? Let us make this question more precise. Say that some connectives are jointly functionally complete if, for any possible truth table, there is a sentence containing only those connectives with that truth table. The general point is, when we are armed with some jointly functionally complete connectives, no characteristic truth table lies beyond our grasp, and in fact, we are in luck. Functional completeness theorem. The connectives of TFL are jointly functionally complete. Indeed, the following pairs of connectives are jointly functionally complete. Given any truth table, we can use the method of proving the DNF theorem, or the CNF theorem, via truth tables from chapter 43 to write down a scheme which has the same truth table. For example, employing the truth table method for proving the DNF theorem, we find that the following scheme has the same characteristic truth table as A, B, C, above.
Math summary. This expression represents a logical disjunction, which means it combines 3 separate logical AND operations. The first AND operation takes input values A, B, and the negation of C. The second AND operation takes input values A, the negation of B, and C. The third AND operation takes the negation of A, input value B, and the negation of C. The result is true if at least one of these 3 AND operations is true.
It follows that the connectives of TFL are jointly functionally complete. we now prove each of the subsidiary results. Subsidiary result 7, functional completeness of not and square root. Observe that the scheme that we generate using the truth table method of proving the DNF theorem will only contain the connectives not and or. So it suffices to show that there is an equivalent scheme which contains only not and or. To demonstrate this, we simply consider that.
Math summary. This expression describes a logical equivalence. It states that the logical conjunction of two propositions, proposition A and proposition B, is logically equivalent to the negation of the logical disjunction of the negations of proposition A and proposition B.
Are logically equivalent. Subsidiary result 2, functional completeness of and, exactly as in subsidiary result 1, making use of the fact that.
Math summary. This expression evaluates two logical statements. The first statement is A or B. The second statement is not A and not B. The expression then performs a logical an operation between the results of these two statements.
Are logically equivalent. Subsidiary result 3, functional completeness of and, exactly as in subsidiary result 1, making use of these equivalences instead.
Math summary. The expression presents two pairs of logical statements and asserts a relationship between the statements within each pair. The first pair includes the logical OR of two inputs and a logical implication involving the negation of the first input, implying the second input. The second pair includes the logical AND of two inputs and the negation of a logical implication, where the first input implies the negation of the second input.
Alternatively, we could simply rely upon one of the other two subsidiary results and repeatedly invoke only one of these two equivalences. In short, there is never any need to add new connectives to TFL. Indeed, there is already some redundancy among the connectives we have. We could have made do with just two connectives if we had been feeling really austere. 44.1 Individually functionally complete connectives. In fact, some two-place connectives are individually functionally complete. These connectives are not standardly included in TFL since they are rather cumbersome to use. But their existence shows that, if we had wanted to, we could have defined a truth functional language that was functionally complete, which contained only a single primitive connective. The first such connective we will consider is up arrow, which has the following characteristic truth table.
Table summary. The table illustrates the truth table for the Sheffer stroke, where the result is false only when both inputs are true, and true otherwise, representing the negation of the conjunction operation.
This is often called the Sheffer stroke, after Henry Sheffer, who used it to show how to reduce the number of logical connectives in Russell and Whitehead's Principia Mathematica. In fact, Charles Sanders Peirce had anticipated Sheffer by about 30 years, but never published his results. It is quite common as well to call it NAND, since its characteristic truth table is the negation of the truth table for up arrow is functionally complete all by itself. The functional completeness theorem tells us that and are jointly functionally complete. So it suffices to show that, given any scheme which contains only those two connectives, we can rewrite it as a logically equivalent scheme which contains only up arrow. As in the proof of the subsidiary cases of the functional completeness theorem, then, we simply apply the following equivalences.
Math summary. The expression calculates logical equivalences using the NAND operator. First, it expresses the logical NOT of an input and the NAND of the input with itself. Second, it expresses the logical OR of two inputs and the NAND of the first input with itself and the NAND of the second input with itself.
To the subsidiary result 1. Similarly, we can consider the connective down arrow.
Table summary. The truth table defines a logical operation where the output is true only when both inputs are false. Otherwise, the output is false.
This is sometimes called the Peirce arrow. Peirce himself called it AMPHEC. More often, though, it is called NOR, since its characteristic truth table is the negation of V, that is, of neither nor. Down arrow is functionally complete all by itself. As in the previous result for up arrow, although invoking the equivalences.
Math summary. The expression represents logical equivalences. It states that the negation of a logical variable A is equivalent to a NOR A. It also states that the logical AND of variables A and B is equivalent to a NOR A, NOR B, NOR B.
And subsidiary result 2. 44.2 Failures of functional completeness. In fact, the only two-place connectives which are individually functionally complete are up arrow and down arrow. But how would we show this? More generally, how can we show that some connectives are not jointly functionally complete? The obvious thing to do is to try to find some truth table which we cannot express using just the given connectives, but there is a bit of an art to this. To make this concrete, let's consider the question of whether it is functionally complete all by itself. After a little reflection, it should be clear that it is not. In particular, it should be clear that any scheme which only contains disjunctions cannot have the same truth table as negation, that is.
Table summary. The table presents a simple truth table, where the value of a proposition and its negation are shown to be opposite.
The intuitive reason why this should be so is simple. The top line of the desired truth table needs to have the value false, but the top line of any truth table for a scheme which only contains will always be true. The same is true for to and left right arrow. V wedge right arrow and double arrow are not functionally complete by themselves. In fact, the following is true. The only two-place connectives that are functionally complete by themselves are up arrow and down arrow. This is of course harder to prove than for the primitive connectives. For instance, the exclusive or connective does not have a T in the first line of its characteristic truth table, and so the method used above no longer suffices to show that it cannot express all truth tables. It is also harder to show that, for example, left right arrow and together are not functionally complete. Chapter 45. Soundness. In this chapter, we relate TFL's semantics to its natural deduction proof system, as defined in Part 4. We will prove that the formal proof system is safe. You can only prove sentences from premises from which they actually follow. Intuitively, a formal proof system is sound if it does not allow you to prove any invalid arguments. This is obviously a highly desirable property. It tells us that our proof system will never lead us astray. Indeed, if our proof system were not sound, then we would not be able to trust our proofs. The aim of this chapter is to prove that our proof system is sound. Let's make the idea more precise. We'll abbreviate a list of sentences using the Greek letter gamma, gamma. A formal proof system is sound relative to given semantics if whenever there is a formal proof of I from assumptions among gamma, then gamma genuinely entails I given that semantics. Otherwise put, to prove that TFL's proof system is sound, we need to prove the following soundness theorem. For any sentences gamma and script C, if gamma proves script C, then gamma models script C to prove this. We will check each of the rules of TFL's proof system individually. We want to show that no application of those rules ever leads us astray. Since a proof just involves repeated application of those rules, this will show that no proof ever leads us astray, or at least that is the general idea. To begin with, we must make the idea of leading us astray more precise. Say that a line of a proof is shiny if the assumptions on which that line depends tautologically entail the sentence on that line. To illustrate the idea, consider the following.
Math summary. This logical proof starts with an initial statement. F implies G and H given F and G and H. It infers G and H from G and H. It extracts G finally. It concludes that F implies G, based on the initial assumption F and the derived statement G.
Line 1 is shiny if and only if F implies the quantity G and H models F implies the quantity G and H. You should be easily convinced that line 1 is indeed shiny. Similarly, line 4 is shiny if and only if F implies the quantity G and H. F models G again. It is easy to check that line 4 is shiny, as is every line in this TFL proof. We want to show that this is no coincidence. That is, we want to prove. Shininess lemma, every line of every TFL proof is shiny. Then we will know that we have never gone astray on any line of a proof. Indeed, given the shininess lemma, it will be easy to prove the soundness theorem. Proof: suppose gamma proves script C, then there is a TFL proof, with script C appearing on its last line whose only undischarged assumptions are among gamma. The shininess lemma tells us that every line on every TFL proof is shiny. So this last line is shiny, that is gamma models script CQED. It remains to prove the shininess lemma. To do this, we observe that every line of any TFL proof is obtained by applying some rule. So what we want to show is that no application of a rule of TFL's proof system will lead us astray. More precisely, say that a rule of inference is rule sound if for all TFL proofs. If we obtain a line on a TFL proof by applying that rule, and every earlier line in the TFL proof is shiny, then our new line is also shiny. What we need to show is that every rule in TFL's proof system is rule sound. We will do this in the next section, but having demonstrated the rule soundness of every rule, the shininess lemma will follow immediately. Proof: fix any line n on any TFL proof. The sentence written on line n must be obtained using a formal inference rule which is rule sound. This is to say that if every earlier line is shiny, then line n itself is shiny. Hence, by strong induction on the length of TFL proofs, every line of every TFL proof is shiny. QED note that this proof appeals to a principle of strong induction on the length of TFL proofs. This is the first time we have seen that principle, and you should pause to confirm that it is, indeed, justified. It remains to show that every rule is rule sound. This is not difficult, but it is time-consuming since we need to check each rule individually, and TFL's proof system has plenty of rules. To speed up the process marginally, we will introduce a convenient abbreviation. Delta I delta will abbreviate the assumptions, if any, on which line I depends in our TFL proof. Context will indicate which TFL proof we have in mind. Introducing an assumption is rule sound. If script A is introduced as an assumption on line n, then script A is among delta sub n, and so delta sub n models script A. Wedge introduction is rule sound. Proof: consider any application of wedge introduction in any TFL proof, that is, something like. To show that wedge I is rule sound, we assume that every line before line n is shiny, and we aim to show that line n is shiny, that is, that delta sub n models a wedge B. So let V be any valuation that makes all of delta sub n true. We first show that V makes it true. To prove this, note that all of delta sub I are among delta sub n by hypothesis. Line I is shiny. So any valuation that makes all of delta sub I true makes it true. Since V makes all of delta sub I true, it makes it true too. We can similarly see that V makes B true. So V makes it true and V makes B true. Consequently, V makes A and B true. So any valuation that makes all of the sentences among delta sub n true also makes A and B true. That is, line n is shiny. OED, all of the remaining lemmas establishing rule soundness will have, essentially, the same structure as this one did. And E is rule sound. Proof: assume that every line before line n on some TFL proof is shiny, and that E is used on line n, so the situation is.
Math summary: the expression describes a logical inference process. On line I, the system has the logical conjunction of A and B. On line n, the system has A and performs a logical AND operation with E and I.
Or perhaps with B in calligraphic font on line n instead, but similar reasoning will apply in that case. Let V be any valuation that makes all of delta sub n true. Note that all of delta sub I are among delta sub n by hypothesis. Line I is shiny. So any valuation that makes all of delta sub I true makes A in calligraphic font logical and B in calligraphic font true. So V makes A in calligraphic font logical and B in calligraphic font true, and hence makes A in calligraphic font true. So delta sub n models A in calligraphic font. QED, we leave this as an exercise. Proof: assume that every line before line n on some TFL proof is shiny, and that E is used on line n, so the situation is.
Code summary: the provided algorithm demonstrates a proof for the soundness of a logical rule, specifically the disjunction elimination rule. It takes as input a proof structure involving disjunction and conditional statements. The algorithm shows that if certain conditions are met, lines before a specific line are shiny, and disjunction elimination is used, then a valuation that makes the premises true also makes the conclusion true. The proof splits into cases based on which part of the disjunction is true, and shows that in either case, the conclusion holds.
Let V be any valuation that makes all of delta sub n true. Note that all of delta sub m are among delta sub n by hypothesis. Line m is shiny. So any valuation that makes delta sub n true makes A or B true. So in particular, V makes A or B true, and hence either V makes a true or V makes B true. We now reason through these two cases. Case 1, V makes a true. All of delta sub I are among delta sub n, with the possible exception of script A, since V makes all of delta sub n true and also makes script a true. V makes all of delta sub I true. Now by assumption, line J is shiny. So delta sub j models script C, but the sentences delta sub I are just the sentences delta sub j. So delta sub I models script C, so any valuation that makes all of delta sub I true makes script C true. But V is just such a valuation, so V makes script C true. Case 2, V makes B true. Reasoning in exactly the same way, considering lines K and L, V makes C true. Either way, V makes C true, so delta sub n models C QED proof. Assume that every line before line n on some TFL proof is shiny, and that not E is used on line n, so the situation is.
Code summary: the material presents a proof regarding the rule soundness of a logical inference rule. It starts with an assumption about lines in a proof being shiny, and uses this property to demonstrate that a contradiction arises if the rule is not sound. The proof concludes that the rule must be sound, as the assumption leads to a contradiction. A similar proof is sketched for another rule, with one proof being left as an exercise. Math summary. This represents a proof structure. Line I asserts statement A. Line J asserts the negation of statement A. Line N asserts a contradiction, derived by applying the negation elimination rule to lines I and J.
Note that all of delta sub I and all of delta sub J are among delta sub N by hypothesis. Lines I and J are shiny. So any valuation which makes all of delta sub N true would have to make both script A and not script A true. But no valuation can do that, so no valuation makes all of delta sub N true. So delta sub N models bottom vacuously. QED, we leave this as an exercise. Ballot box with check I is rule sound.
Code summary. The code block asserts that X is rule sound, but it does not provide a proof or further explanation. It indicates that the user should complete the proof as an exercise. Essentially, it states a claim without supporting evidence, delegating the justification to the reader.
Proof. Assume that every line before line N on some TFL proof is shiny, and that not I is used on line N, so the situation is.
Math summary. The expression describes a logical inference rule. On line I, we have statement A implying a contradiction. On line N, we have not A and not I minus J.
Let V be any valuation that makes all of delta sub N true. Note that all of delta sub N are among delta sub I with the possible exception of it itself. By hypothesis, line J is shiny, but no valuation can make the perpendicular symbol true, so no valuation can make all of delta sub J true. Since the sentences delta sub I are just the sentences delta sub J, no valuation can make all of delta sub I true. Since V makes all of delta sub N true, it must therefore make script A false and so make not script A true. So delta sub N models not script A QED IP implies I implies E if and only if I and if and only if E are all rule sound. We leave these as exercises. This establishes that all the basic rules of our proof system are rule sound. Finally, we show all of the derived rules of our proof system are rule sound. Proof. Suppose that we used a derived rule to obtain some sentence A on line N of some TFL proof and that every earlier line is shiny. Every use of a derived rule can be replaced at the cost of long-windedness with multiple uses of basic rules. That is to say, we could have used basic rules to write A on some line N plus K without introducing any further assumptions. So applying our individual results that all basic rules are rule sound several times, K plus 1 times in fact, we can see that line N plus K is shiny. Hence the derived rule is rule sound. QED, and that's that. We have shown that every rule, basic or otherwise, is rule sound, which is all that we require to establish the shininess lemma and hence the soundness theorem. But it might help to round off this chapter if we repeat my informal explanation of what we have done. A formal proof is just a sequence of arbitrary length of applications of rules. We have shown that any application of any rule will not lead you astray. It follows by induction that no formal proof will lead you astray. That is, our proof system is sound.
Table VI summary. The table states that a specific rule is sound, but the details are omitted as an exercise. Table VII summary. The table indicates that VE is rule sound.
Practice exercises. A. Complete the lemmas left as exercises in this chapter. That is, show that the following are rule sound. 1. For all I hint, this is similar to the case of an E. 2x hint, this is similar to the case of not E. 3 implies introduction, hint, this is similar to or elimination. 4 implies E. 5 IP, hint, this is similar to the case of not I. Appendix A. Symbolic notation. 1.1 Alternative nomenclature. Truth functional logic, TFL goes by other names. Sometimes it is called sentential logic because it deals fundamentally with sentences. Sometimes it is called propositional logic on the idea that it deals fundamentally with propositions. We have stuck with truth functional logic to emphasize the fact that it deals only with assignments of truth and falsity to sentences, and that its connectives are all truth functional. First-order logic, FOL, goes by other names. Sometimes it is called predicate logic because it allows us to apply predicates to objects. Sometimes it is called quantified logic because it makes use of quantifiers. Formulas. Some texts call formulas well-formed formulas. Since well-formed formula is such a long and cumbersome phrase, they then abbreviate this as WFF. This is both barbarous and unnecessary. Such texts do not countenance ill-formed formulas. We have stuck with formula. In section 6, we defined sentences of TFL. These are also sometimes called formulas or well-formed formulas, since in TFL, unlike FOL, there is no distinction between a formula and a sentence. Valuations. Some texts call valuations truth assignments or truth value assignments. N-place predicates. We have chosen to call predicates one place, two place, three place, etc. Other texts respectively call them monadic, dyadic, triadic, etc. Still other texts call them unary, binary, ternary, etc. Names. In FOL we have used E, B, C for names. Some texts call these constants. Other texts do not mark any difference between names and variables in the syntax. Those texts focus simply on whether the symbol occurs bound or unbound. Domains. Some texts describe a domain as a domain of discourse or a universe of discourse. 1.2 Alternative symbols. In the history of formal logic, different symbols have been used at different times and by different authors. Often, authors were forced to use notation that their printers could typeset. This appendix presents some common symbols so that you can recognize them if you encounter them in an article or in another book. Negation. Two commonly used symbols are the ho, not sign, and the swung dash or tilde. In some more advanced formal systems, it is necessary to distinguish between two kinds of negation. The distinction is sometimes represented by using both not sign and. Older texts sometimes indicate negation by a line over the formula being negated, for example, A, B. Some texts use x not equal to y to abbreviate not sign x equals y. Disjunction. The symbol V is typically used to symbolize inclusive disjunction. One etymology is from the Latin word vel, meaning or. Conjunction. Conjunction is often symbolized with the ampersand, and the ampersand is a decorative form of the Latin word et, which means and. Its etymology still lingers in certain fonts, particularly in italic fonts, thus an italic ampersand might appear as and. This symbol is commonly used in natural English writing, e.g. Smith & Sons, and so even though it is a natural choice, many logicians use a different symbol to avoid confusion between the object and metalanguage. As a symbol in a formal system, the ampersand is not the English word and. The most common choice now is which is a counterpart to the symbol used for disjunction. Sometimes a single dot is used. In some older texts, there is no symbol for conjunction at all. A and B is simply written ob. Material conditional. There are two common symbols for the material conditional, the arrow, right arrow, and the horseshoe, horseshoe. Material biconditional. The double-headed arrow, left-right arrow, is used in systems that use the arrow to represent the material conditional. Systems that use the horseshoe for the conditional typically use the triple bar, identical to, for the biconditional. Quantifiers. The universal quantifier is typically symbolized as a rotated A, and the existential quantifier as a rotated E. In some texts, there is no separate symbol for the universal quantifier. Instead, the variable is just written in parentheses in front of the formula that it binds. For example, they might write xpx, where we would write ForAllX px. These alternative typographies are summarized below.
Table summary. The table presents symbolic notations for various logical operations. Each operation has different symbols that can be used to represent it.
Polish notation. This section briefly discusses sentential logic and Polish notation, a system of notation introduced in the late 1920s by the Polish logician Jan Lukasiewicz. Lowercase letters are used as sentence letters. The capital letter N is used for negation. A is used for disjunction, K for conjunction, C for the conditional, E for the biconditional. A is for alternation, another name for logical disjunction. E is for equivalence. In Polish notation, a binary connective is written before the two sentences that it connects. For example, the sentence a B of TFL would be written cab in Polish notation. The sentences not A implies B and not open parenthesis A implies B close parenthesis are very different. The main logical operator of the first is the conditional, but the main connective of the second is negation. In TFL, we show this by putting parentheses around the conditional in the second sentence. In Polish notation, parentheses are never required. The leftmost connective is always the main connective. The first sentence would simply be written C and a B, and the second in C A B. This feature of Polish notation means that it is possible to evaluate sentences simply by working through the symbols from right to left. If you were constructing a truth table for NCAB, for example, you would first consider the truth values assigned to B, and then consider their conjunction, and then negate the result. The general rule for what to evaluate next in TFL is not nearly so simple. In TFL, the truth table for not A and B requires looking at A and B, then looking in the middle of the sentence at the conjunction, and then at the beginning of the sentence at the negation. Because the order of operations can be specified more mechanically in Polish notation, variants of Polish notation are used as the internal structure for many computer programming languages. Appendix B. Alternative proof systems. In formulating our natural deduction system, we treated certain rules of natural deduction as basic and others as derived. However, we could equally well have taken various different rules as basic or derived. We will illustrate this point by considering some alternative treatments of disjunction, negation, and the quantifiers. We will also explain why we have made the choices that we have. 2.1 Alternative disjunction elimination. Some systems take DS as their basic rule for disjunction elimination. Such systems can then treat the for all E rule as a derived rule, for they might offer the following proof scheme.
Math summary. This represents a logical proof or derivation within a formal system. It shows a series of steps, each deriving a new statement from previous ones. The proof begins with initial assumptions or premises, indicated by labels like M, I, and J. Each line represents a step in the proof, deriving a new statement based on inference rules applied to previous statements. The arrow notation indicates the application of a specific inference rule, referencing the line numbers of the statements used as input. The goal is to derive a conclusion by applying these rules sequentially.
So why did we choose to take for all E as basic rather than DS? Our reasoning is that DS involves the use of and the statement of the rule. It is in some sense cleaner for our disjunction elimination rule to avoid mentioning other connectives. 2.2 Alternative negation rules. Some systems take the following rule as their basic negation introduction rule.
Math summary. The expression shows three separate labels, M, n-1, and n, stacked vertically. The last label, n, is indented to the right.
And a corresponding version of the rule we called IP as their basic negation elimination rule.
Math summary. The expression represents a symbolic manipulation or transformation. It involves several components including an initial value m and a value n-1. These are arranged within a structure involving symbols a, b, and e star. The final result of the manipulation is e star times m-n.
Using these two rules, we could have avoided all use of the symbol altogether. The resulting system would have had fewer rules than ours. Another way to deal with negation is to use either lem or dne as a basic rule and introduce IP as a derived rule. Typically, in such a system the rules are given different names too. E.g., sometimes what we call not E is called perpendicular I, and what we call X is called perpendicular E. So why did we choose our rules for negation and contradiction? Our first reason is that adding the symbol to our natural deduction system makes proofs considerably easier to work with. For instance, in our system it's always clear what the conclusion of a subproof is. The sentence on the last line, for example in IP or not sign I, not sign asterisk and not sign E, subproofs have two conclusions, so you can't check at one glance if an application of them is correct. Our second reason is that a lot of fascinating philosophical discussion has focused on the acceptability or otherwise of indirect proof IP, equivalently excluded middle, that is lem or double negation elimination DNE, and explosion i.e. 10. By treating these as separate rules in the proof system, you will be in a better position to engage with that philosophical discussion. In particular, having invoked these rules explicitly, it would be much easier for us to know what a system which lacked these rules would look like. This discussion, and in fact the vast majority of mathematical study on applications of natural deduction proofs beyond introductory courses, makes reference to a different version of natural deduction. This version was invented by Gerhard Jensen in 1935, as refined by Dag Prowitz in 1965. Our set of basic rules coincides with theirs. In other words, the rules we use are those that are standard in philosophical and mathematical discussion of natural deduction proofs outside of introductory courses. 2.3 Alternative quantification rules. An alternative approach to the quantifiers is to take as basic the rules for all introduction and for all elimination from section 34, and also 2 CQ rule which allow us to move from for all x not a to not exists x a and vice versa. Taking only these rules as basic, we could have derived the exists introduction and exists elimination rules provided in section 34. To derive the exists introduction rule is fairly simple. Suppose it contains the name C and contains no instances of the variable x, and that we want to do the following.
Math summary. The expression describes a logical construct. The first line states that under condition M, a proposition A holds, where A contains constant C. The second line states that under condition K, there exists an X such that proposition A holds, where it contains variable X and constant C.
This is not yet permitted since in this new system we do not have the I rule. We can, however, offer the following.
Math summary. This expression represents a logical derivation or proof sequence. It starts with an assertion involving a variable c. Subsequent steps introduce negations, quantifiers, existential and universal, and logical rules like conjunctive quantification and universal elimination. The derivation aims to arrive at a contradiction, ultimately proving an existential statement through indirect proof. The steps involve negating the existence of a variable x, satisfying a condition, then deriving a contradiction from the assumption that the condition holds for c, and finally concluding that there must exist an x satisfying the condition.
To derive the exists E rule is rather more subtle. This is because the exists E rule has an important constraint, as indeed does the for all I rule, and we need to make sure that we are respecting it. So suppose we are in a situation where we want to do the following.
Math summary. This represents a logical derivation within a proof system. It starts at line M with the assertion that there exists an x such that a statement A involving x is true. From this, a subproof begins at line I, assuming that statement A is true for a specific instance C within the subproof. At line J, another statement B is derived. At line K, outside the subproof, statement B is shown to be true based on the previous steps.
Where C does not occur in any undischarged assumptions or in script B, or in there exists XA of ellipsis X ellipsis X ellipsis. Ordinarily, we would be allowed to use the there exists elimination rule, but we are not here assuming that we have access to this rule as a basic rule. Nevertheless, we could offer the following more complicated derivation.
Math summary. The expression represents a logical proof. It starts with an assumption that there exists an x such that a statement A is true. From this, it derives a statement B through a series of logical steps. These steps involve implication introduction, modus tollens, universal introduction, contraposition, negation elimination, and indirect proof. The final result of the proof is the statement B.
We are permitted to use for all on line K plus 3 because C does not occur in any undischarged assumptions, or in script B the entries on lines K plus 4 and K plus 1 contradict each other. Because C does not occur and there exists X script A, open parenthesis, ellipsis X ellipsis, close parenthesis. Armed with these derived rules, we could now go on to derive the two remaining CQ rules, exactly as in section 38. So why did we start with all of the quantifier rules as basic, and then derive the CO rules? Our first reason is that it seems more intuitive to treat the quantifiers as on a par with one another, giving them their own basic rules for introduction and elimination. Our second reason relates to the discussion of alternative negation rules. In the derivations of the rules of 3i and 3e that we have offered in this section, we invoked IP. But as we mentioned earlier, IP is a contentious rule. So if we want to move to a system which abandons IP, but which still allows us to use existential quantifiers, we will want to take the introduction and elimination rules for the quantifiers as basic, and take the CQ rules as derived. Indeed, in a system without IP, lem, and DNE, we will be unable to derive the CQ rule which moves from not for all x, A to there exists x not A. Appendix C. Quick reference. 3.1 Characteristic Truth Tables.
Table 3.1 Summary. The table presents characteristic truth tables for logical operations. The truth values for conjunction and disjunction are generally false and true respectively, except when both inputs are true or both are false. The implication is true in most cases, except when the first input is true and the second is false, while the biconditional is true when both inputs have the same truth value.
3.2 Symbolization. Sentential connectives. It is not the case that P not P either P or Q, P or Q. Neither P nor Q not P or Q, or not P and not Q. Both P and Q, P and Q. If P then Q, P implies Q. P only if Q, P implies Q. P if and only if Q, P if and only if Q. P unless Q, P or Q. Predicates. All Fs or Gs for all x. F of x implies g of x, some Fs or Gs there exists in x such that f of x and g of x not all Fs or Gs not for all x. F of x implies g of x, or there exists in x such that f of x and not g of x no Fs or Gs for all x. F of x implies not g of x, or not there exists in x such that f of x and g of x. Identity. Only C is g for all x, g of x if and only if x equals C. 3.3 Using identity to symbolize quantities. There are at least Fs. 1 There exists x such that f of x2 there exists x sub 1 there exists x sub 2 open parenthesis f of x sub 1 and f of x sub 2 and not x sub 1 equals x sub 2. Close parenthesis 3 There exists x sub 1 there exists x sub 2 there exists x sub 3 open parenthesis f of x sub 1 and f of x sub 2 and f of x sub 3. Not x sub 1 equals x sub 2 and not x sub 1 equals x sub 3. And not x sub 2 equals x sub 3 for there exists x sub 1. There exists x sub 2 there exists x sub 3 there exists x sub 4 open parenthesis f of x sub 1 and f of x sub 2 and f of x sub 3 and f of x sub 4 and
Math summary. The expression describes a logical formula. It asserts the existence of n variables, named x sub 1 through x sub n, that satisfy a condition f. This condition f applies to each of the n variables. Additionally, it stipulates that x sub 1 is not equal to x sub 2, and so on up to x sub n minus 1 not being equal to x sub n. The initial part of the expression specifies that x sub 1 is not equal to x sub 2, x sub 1 is not equal to x sub 3, x sub 1 is not equal to x sub 4, x sub 2 is not equal to x sub 3, x sub 2 is not equal to x sub 4, and x sub 3 is not equal to x sub 4.
There are at most fs. One way to say there are at most n fs is to put a negation sign in front of the symbolization for there are at least n plus 1 fs. Equivalently, we can offer 1 for all x sub 1 for all x sub 2, open bracket, open parenthesis f of x sub 1 and f of x sub 2 close parenthesis implies x sub 1 equals x sub 2. Close bracket 2 for all x sub 1 for all x sub 2 for all x sub 3 open bracket left parenthesis f of x sub 1 and f of x sub 2 and f of x sub 3 right parenthesis implies.
Math summary. This expression represents a logical OR operation. It checks if at least one pair of three input values, input value 1, input value 2, and input value 3 are equal to each other. The expression evaluates to true if input value 1 equals input value 2, or input value 1 equals input value 3, or input value 2 equals input value 3.
3 for all x sub 1 for all x sub 2 for all x sub 3 for all x sub 4 open bracket left parenthesis f of x sub 1 and f of x sub 2 and f of x sub 3 and f of x sub 4 right parenthesis close bracket implies.
Math summary. The expression describes conditions related to equality among variables. The first part states that at least one pair of variables x1, x2, x3, and x4 must be equal. The second part describes a universal quantification over n plus 1 variables x1 through xn plus 1. If a condition f holds for all these variables, then at least one pair of consecutive variables from x1 to xn plus 1 must be equal.
There are exactly fs. One way to say there are exactly n fs is to conjoin two of the symbolizations above and say there are at least n fs and there are at most n fs. The following equivalent formulas are shorter.
Math summary. The expression defines logical statements for 0, 1, 2, 3, and n for 0. It states that for all x, f of x is not true. For 1, there exists an x such that f of x is true, and for all y, if f of y is true, then x equals y. For 2, there exists an x1 and an x2 such that f of x1 and f of x2 are true. x1 does not equal x2, and for all y, if f of y is true, then y equals x1 or y equals x2. For 3, there exists an x1, x2, and x3 such that f of x1, f of x2, and f of x3 are true. x1 does not equal x2, x1 does not equal x3, x2 does not equal x3, and for all y, if f of y is true, then y equals x1 or y equals x2 or y equals x3. For n, there exist x1 through xn such that f of x1 through f of xn are true. x1 does not equal x2 through xn1 does not equal xn. And for all y, if f of y is true, then y equals x1 or through y equals xn.
3.4 Basic Deduction Rules for TFL. Reiteration negation.
Math summary. The first expression represents a reiteration rule. It states that given a statement A, one can reiterate or repeat that statement A. The second expression represents a negation introduction rule. It states that if assuming a statement A leads to a contradiction, then one can infer the negation of that statement A.
Conjunction.
Math summary. The first expression shows an introduction rule for conjunction. Given statement A on line M and statement B on line N, it derives the conjunction of A and B on a new line. Citing the introduction rule and lines M and N, the second expression shows a negation elimination rule. Given a derivation from the negation of A to a contradiction, it concludes the truth of A, citing the negation elimination rule and the lines of the derivation. The third expression shows an elimination rule for conjunction. Given a conjunction of A and B on line M, it derives on a new line, citing the elimination rule and line M.
Indirect proof.
Math summary: the expression presents deduction rules in a formal system. The first part shows a conjunction elimination rule, where from a statement A and B, and the statement B, one can infer A. The second part demonstrates an indirect proof, where assuming the negation of A leads to a contradiction, and then A is inferred. The last part shows an indirect proof, where assuming A is true.
Conditional.
Math summary: this represents a logical inference rule. It describes a process where, given a statement A and the negation of statement B, or given that A implies B, we can infer a new statement. The inference involves line numbers I and J, and it produces a result based on the implication I applied to those line numbers.
Explosion.
Math summary: the first expression represents a logical deduction rule. It states that given a statement A implies B, and statement A is true, then statement B can be inferred. This is denoted by an elimination rule E, which takes two inputs, M and N. The second expression represents a rule called explosion, where from a contradiction, denoted by the perpendicular symbol, any statement A can be inferred. This is denoted by X with input M.
Disjunction. Biconditional.
Math summary: the image presents several logical inference rules. The first rule introduces a disjunction. The second rule shows a biconditional introduction. The third rule introduces a disjunction. The fourth rule shows disjunction elimination. The fifth rule shows biconditional elimination. The sixth rule shows biconditional elimination.
3.5 Derived rules for TFL. Disjunctive syllogism.
Math summary: the expression represents a disjunctive syllogism. It starts with two premises, the disjunction of statement O or statement B, and the negation of statement A. From these, it derives that statement B must be true using the disjunctive syllogism rule. Similarly, given the disjunction of statement O or statement B, and the negation of statement B, it derives that statement A must be true using the disjunctive syllogism rule.
Excluded middle.
Math summary: this represents the excluded middle rule. It states that given two premises, the first with a proposition A and the negation of proposition B, and the second with the negation of proposition A and the negation of proposition B, then we can infer proposition B using the law of excluded middle applied to the first and second premises, as well as premises K and L.
De Morgan rules modus tollens.
Math summary: the first expression applies De Morgan's law. Given the negation of A or B, it outputs the negation of A and the negation of B. The second expression applies modus tollens. Given A implies B and the negation of B, it outputs the negation of
MTMN.
Math summary: this expression applies De Morgan's law. It starts with the negation of logical A and the negation of logical B, combined with a logical AND. It then transforms this into the negation of logical A or logical B. The transformation is labeled with DEM and the line number M.
Double negation elimination.
Math summary: the first expression applies De Morgan's law. It starts with the negation of A and B, then transforms it to the negation of A or the negation of B. The second expression applies double negation elimination. It starts with the double negation of A and simplifies it to A. The third expression applies De Morgan's law in reverse. It starts with the negation of A or the negation of B and transforms it to the negation of A and B.
3.6 Basic deduction rules for FOL. Universal elimination.
Math summary: this represents a universal elimination rule. Given a universally quantified statement that holds for all x, denoted as for all x A of x, it infers that the statement A holds for a specific instance C, denoted as A of C. This inference is labeled as universal elimination.
Existential introduction.
Math summary: the expression describes the existential introduction rule in logic. It states that if there exists an instance of a proposition involving a variable and a constant, then there exists some instance of that proposition. The expression includes indicators for the line number in a proof.
X must not occur in a C. Universal introduction.
Math summary: the expression represents a universal introduction rule in formal logic. Given a statement A that holds for a specific element C, it concludes that A holds for all elements X. The rule is valid under the condition that C does not appear in any undischarged assumptions.
Existential elimination: negative C must not occur in any undischarged assumption. X must not occur in A, which contains C and C.
Math summary: this represents a rule of inference called existential elimination. It states that if there exists an X such that a proposition A involving X is true, and if from involving a specific constant C, one can derive a proposition B, then one can infer B, provided that C does not occur free in the original existential statement or in any undischarged assumptions.
C must not occur in any undischarged assumption in there exists X, A of ellipsis X ellipsis X ellipsis, or in B identity introduction.
Math summary. The expression represents the identity introduction rule, which states that C equals C is equivalent to the value 1.
Identity elimination.
Math summary. This represents an identity elimination rule in logic. It states that if A equals B, and we have a statement A containing A in two locations, and another statement A where B replaces one of the A's, then this is equivalent to having A equals B, and a statement A with B in both locations, and another statement A where A replaces one of the B's. Both sides of the equivalence are labeled with EMN.
3.7 Derived rules for FOL.
Math summary. The expression describes logical inference rules. It states that from for all x, not A, and not exists x, A, we can infer M using a rule called CQ. Similarly, from exists x, not A, and not for all x, A, we can infer M using the CQ rule. The other expressions describe similar logical inferences using the CQ rule, involving negations of quantifiers and the existence or non-existence of x-satisfying condition, A.
Glossary. Antecedent: the sentence on the left side of a conditional. Argument: a connected series of sentences divided into premises and conclusion. Atomic sentence: an expression used to represent a basic sentence. A sentence letter in TFL or a predicate symbol followed by names in FOL. By conditional, the symbol left right arrow, used to represent words and phrases that function like the English phrase if and only if, or a sentence formed using this connective. Bound variable: an occurrence of a variable in a formula which is in the scope of a quantifier followed by the same variable. Complete truth table: a table that gives all the possible truth values for a sentence of TFL or sentences in TFL, with a line for every possible valuation of all sentence letters. Completeness: a property held by logical systems if and only if models implies proves. Conclusion: the last sentence in an argument. Conclusion indicator: a word or phrase, such as therefore, used to indicate that what follows is the conclusion of an argument. Conditional: the symbol to, used to represent words and phrases that function like the English phrase, if then, a sentence formed by using this symbol. Conjunct: a sentence joined to another by a conjunction. Conjunction: the symbol used to represent words and phrases that function like the English word and, or a sentence formed using that symbol. Conjunctive normal form, DNF, a sentence which is a conjunction of disjunctions of atomic sentences or negated atomic sentences. Connective: a logical operator in TFL used to combine sentence letters into larger sentences. Consequent: the sentence on the right side of a conditional. Contingent sentence: a sentence that is neither a necessary truth nor a necessary falsehood. A sentence that in some case is true and in some other case false. Contradiction of FOL: a sentence of FOL that is false in every interpretation. Contradiction of TFL: a sentence that has only FS in the column under the main logical operator of its complete truth table. A sentence that is false on every valuation. Disjunct: a sentence joined to another by a disjunction. Disjunction: the connective V, used to represent words and phrases that function like the English word or in its inclusive sense, or a sentence formed by using this connective. Disjunctive normal form, DNF, a sentence which is a disjunction of conjunctions of atomic sentences or negated atomic sentences. Domain: the collection of objects assumed for a symbolization in FOL, or that gives the range of the quantifiers in an interpretation. Empty predicate: a predicate that applies to no object in the domain. Equivalence in FOL, a property held by pairs of sentences of FOLs, if and only if the sentences have the same truth value in every interpretation. Equivalence in TFL, a property held by pairs of sentences if and only if the complete truth table for those sentences has identical columns under the two main logical operators, that is, if the sentences have the same truth value on every valuation. Existential quantifier: the symbol there exists of FOL used to symbolize existence. There exists x. F of x is true if at least one member of the domain is F. Formula, an expression of FOL built according to the inductive rules in section 26. 2. Free variable: an occurrence of a variable in a formula which is not a bound variable. Functional completeness: property of a collection of connectives, which holds if every possible truth table is the truth table of a sentence involving only those connectives. Interpretation: a specification of a domain together with the objects the names pick out and which objects the predicates are true of. Invalid: a property of arguments that holds when the conclusion is not a consequence of the premises, the opposite of valid. Joint possibility: a property possessed by some sentences when they are all true in a single case. Main connective: the last connective that you add when you assemble a sentence using the inductive definition. Metalanguage: the language logicians use to talk about the object language. In this textbook, the metalanguage is English, supplemented by certain symbols like metavariables and technical terms like valid. Metavariable is a variable in the meta-language that can represent any sentence in the object language. Name a symbol of FOL used to pick out an object of the domain. Necessary equivalence, a property held by a pair of sentences that in every case are either both true or both false. Necessary falsehood, a sentence that is false in every case. Necessary falsehood, a sentence. Necessary truth, a sentence that is true in every case. Negation, the symbol not sign, used to represent words and phrases that function like the English word not. Object language, a language that is constructed and studied by logicians. In this textbook, the object languages are TFL and FOL. Predicate, a symbol of FOL used to symbolize a property or relation. Premise, a sentence in an argument other than the conclusion. Premise indicator, a word or phrase such as because, used to indicate that what follows is the premise of an argument. Provable equivalence, a property held by pairs of statements if and only if there is a derivation which takes you from each one to the other one. Provable inconsistency, sentences are provably inconsistent if a contradiction can be derived from them. Satisfiability, in FOL, a property held by sentence of FOLs if and only if some interpretation makes all the sentences true. Satisfiability, in TFL, a property held by sentences if and only if the complete truth table for those sentences contains one line on which all the sentences are true, that is, if some valuation makes all the sentences true. Scope, the subformula of a sentence of TFL, or a formula of FOL for which the main connective is the operator. Sentence of FOL, a formula of FOL which has no bound variables. Sentence of TFL, a string of symbols in TFL that can be built up according to the inductive rules given on P51. Sentence, letter, and letter used to represent a basic sentence in TFL. Sound, a property of arguments that holds if the argument is valid and has all true premises. Soundness, a property held by logical systems if and only if not implies not. Substitution, instance, the result of replacing every free occurrence of a variable in a formula with a name. Symbolization, key, a list that shows which English sentences are represented by which sentence letters in TFL. Tautology, a sentence that has only TS in the column under the main logical operator of its complete truth table. A sentence that is true on every valuation. Term, either a name or a variable. Theorem, a sentence that can be proved without any premises. Truth value, one of the two logical values sentences can have, true and false. Truth, functional connective, an operator that builds larger sentences out of smaller ones and fixes the truth value of the resulting sentence based only on the truth value of the component sentences. Universal quantifier, the symbol for all of FOL used to symbolize generality. For all x, f of x is true if every member of the domain is f valid, a property of arguments where their conclusion is a consequence of the premises. Validity, a sentence of FOL that is true in every interpretation. Validity of arguments in FOL, a property held by arguments. An argument is valid if and only if no interpretation makes all premises true and the conclusion false. Validity of arguments in TFL, a property held by arguments if and only if the complete truth table for the argument contains no rows where the premises are all true and the conclusion false. That is, if no valuation makes all premises true and the conclusion false. Valuation and assignment of truth values to particular sentence letters. Variable, a symbol of FOL used following quantifiers and as placeholders in atomic formulas. Lowercase letters between S and Z. In the introduction to his volume Symbolic Logic, Charles Lutwidge Dodson advised, when you come to any passage you don't understand, read it again. If you still don't understand it, read it again. If you fail even after 3 readings, very likely your brain is getting a little tired. In that case, put the book away and take to other occupations, and next day when you come to it fresh, you will very likely find that it is quite easy. The same might be said for this volume, although readers are forgiven if they take a break for snacks after 2 readings. You have reached the end of the document.